Bottom boundary, layer dynamics above rough, vegetated beds. Abstract. Bottom boundary layer processes are key for sediment transport. To estimate bed shear stresses, wave friction factors are often used. Experimental data on wave friction factors are limited to sandy environments. Here, numerical simulations conducted with a 1D model show that for hydraulically rough beds with presence of vegetation, wave friction factors deviate from existing data. Keywords. 1. Introduction. The bottom boundary layer, BBL, is the near-bed region where flows are significantly influenced by friction arising from bed roughness. Flows in the BBL are decisive for bed shear stresses, which are responsible for sediment suspension and deposition. Engineering models for coastal morphological evolution are often based on estimates of bed shear stresses for determination of sediment transport. 1. 2. To determine the bed shear stress, empirical friction laws are typically applied. Here, a wave friction factor is introduced which relates the bed shear stress to the free stream velocity 3. Several experiments have been conducted for hydraulically smooth and rough beds beneath waves to determine 4.8. However, in the presence of vegetation, the hydrodynamics are altered, which affects the bed shear stresses 9.11. 12. Investigated the effects of rigid vegetation on BBL processes using a numerical model with a turbulence closure and nonlinear drag on the stems. The results showed that existing obtained for non-vegetated beds cannot be applied for laminar and turbulent, hydraulically smooth vegetated beds. In this case, a thinning of the BBL occurs which increases the bed shear stress. Here, the work by 12 is extended by including bottom roughness in his 1D model and exploring the importance of bottom roughness versus drag on the vegetation stems for infinite vegetation heights. 2 methods. KR 180 and KN is the roughness plus superscript indicating wall units. The model is run for sinusoidal free stream velocities above infinite vegetation heights of 0.35 m with near-bed vertical resolutions of 0.01 kn, a 115, and a total of 101 cells in the vertical resolution. In addition, a wave period of 10s is applied to match experimental data 5, and the temporal resolution is 0.06. Model simulations are performed for input numbers in the range 105 to 3106, corresponding to significant wave heights of 0.8, 4.3 m for the bottom roughness. Kn in the range 0.5 to 2.5 are applied which correspond to fine to coarse sand. These input parameters were chosen to represent the conditions found in exposed areas of eelgrass vegetation in Danish waters 16. The rigid vegetation is characterized by stem diameters of D00083 m and densities of N0, 185, 370, 739, 1479, stems M2. 3 results. As function of a 1 kn hollow, gray dots showing experimental data 4.8, and colored dots showing simulation results for different vegetation stem densities, N. As function of a 1 kn hollow, gray dots showing experimental data 4.8, and colored dots showing simulation results for different vegetation stem densities, N. As function of colored dots show simulation results for different stem densities, N. Open circles, squares, highlight simulations with a 1 kn 4370, 160. 4 discussion. The results showed that for rough, turbulent boundary layers, vegetation drag affects the dynamics through reduced velocities, thinning of the boundary layer not shown, and increased turbulence. The findings are in line with results for smooth, laminar and turbulent boundary layers 12. The results imply that existing expressions for wave friction factors based on experiments above non-vegetated beds cannot be successfully applied in the presence of vegetation. ALD 17 concluded in the same way that hydrodynamic conditions above the canopy were poorly correlated with in-canopy bed shear stresses and sediment suspension. While the flow-induced bed shear stress is reduced for vegetated beds, and its capacity for sediment suspension is reduced, the increased turbulence levels enhance sediment suspension. Several studies thus suggest that turbulence rather than mean flow is the key driver of sediment resuspension within canopies 10, 18, 19. The present results of turbulence levels for different flow and vegetation settings suggested that maximum turbulence levels occur for different stem densities depending on the flow conditions. Similar empirical results have been shown by Al. 20, while on the other hand Tang al. 18 showed a positive correlation between turbulence levels and stem densities. Hence, further studies of turbulence production within canopies are still needed at different scales. With respect to sediment suspension, it should also be taken into consideration that the velocity reduction within the canopy in some cases results in a transition from hydraulic rough to smooth beds. In the present study, 3 cases of small Kn plus 3036 for conditions changed classification to hydraulically smooth in the presence of dense vegetation, N1479, as Kn plus 30 not shown. In addition, the cases studied here were for of 0.8 to 4.3 m and Kn of 0.5 to 2.5 m. However, in many places, coastal vegetation grows in more sheltered areas of lower and finer bed materials. In these settings, the bed will also be hydraulic smooth. Even though findings for wave friction factors are similar for the two regimes 12, a smooth bed potentially suppresses sediment suspension due to the near-bed laminar flows, though stem-generated vortices and local flow features around the stems become important for the understanding of sediment transport and resuspension. 5. Conclusion. Wave friction factor, based on data from oscillatory wave boundary layers, cannot be used for hydraulically rough beds in presence of vegetation. The authors acknowledge funding from Innovation Fund Denmark, Contract 429800031B. DRCH and NGJ acknowledge DHI's research contract with the Danish Ministry of Higher Education and Science, Contract 525500005B. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 40, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Lowe, A.J. 2011, Deterministic Coastal Morphological and Sediment Transport Modeling, a Review and Discussion. Reviews of Geophysics 49-2. 2 Van Elsie, 2007, Unified View of Sediment Transport by Currents and Waves. II. Suspended Transport. ASCEJ Hydraulic, 133-6, 668-689. 3IG, 1967, Wave Boundary Layers and Friction Factors. Coast 110. 4 Ra, 194,664, Motion of Waves in Shallow Water. Interaction between waves and sand bottoms. Prakar Sochland A187, 115. 5 BL, Sumer BM, J 1989, Turbulent Oscillatory Boundary Layers at High Numbers. J Fluid Mech 206, 265, 297. 6 JW, 1975, Friction Factor Under Oscillatory Waves. J Waterways Port Coast Div ASCE, 101, 135, 144. 7 JFA, 1987, turbulent oscillatory flow over rough beds. J. Fluid Mech 182, 369-409. 8. Sumer BM, BL, J. 1987, turbulence in oscillatory boundary layers. In and advances in turbulence. 556, 567. Springer. 9. JCR, MA 2012. Wave and tidally driven flows in eelgrass beds and their effect on sediment suspension. Mar Progser 440, 82, 71-287. 10S, M. Maji, S. H. 2022, sediment suspension affected by submerged rigid vegetation under waves, currents and combined wave-current flows. Coast 173, 104082. 11. JC, Henderson SM, 2018, flows within marine vegetation canopy. In Advances in Coastal Hydraulics, Chapter 1. World Scientific. 12. NG, 2024, spatially averaged, vegetated, oscillatory boundary and shear layers. J. Fluid Mech 999, A33. 13. Y. Dr. ED, 2024, numerical simulations of flow inside a stone protection layer with a modified K turbulence model. Coast 1989, 104469. 14. OE, NG, Van AD, UD T, 2023, linear and nonlinear frequency domain modeling of oscillatory flow over submerged canopies. JR 615, 668-685. 15. Dr. S. Sterner J. 2013, RANS-based simulation of turbulent wave boundary layer and sheet flow sediment transport processes. Coast 73 151 166. 16. PA Al. 2019, habitat model of eelgrass in Danish coastal waters, development, validation and management perspectives. Frontmar 6 175. 17. NC, A. Low R. M. 2022, seagrass meadows reduce windwave-driven sediment resuspension in a sheltered environment. Frontmar 8 733542. 18. Tang C. Lei J. HM 2019, impact of vegetation-generated turbulence on the critical, nearbed, wave velocity for sediment resuspension. Water Res 55590-45917. 19. RO, Coco G. 2018, turbulence as the main driver of resuspension in oscillatory flow through vegetation. J. Rays Earth Surface 123, 891-904. 20. A. J. T. D. Solar M. X. 2014, experimental observations on sediment resuspension within submerged canopies under oscillatory flow. Shelf Rays 91-2231. Numerical modeling of nearshore wave transformation and overtopping with weakly dispersive wave models. Abstract. We investigate the performance of a numerical model based on fully nonlinear depth-averaged equations for simulating wave propagation, transformation, and overtopping over coastal structures. The model is based on the weakly dispersive green equations, solved with a high-order finite volume finite difference scheme. Wave breaking is modeled either by locally switching to the nonlinear shallow water equations or by adding a diffusive-like term to dissipate energy, with a turbulent viscosity computed from the turbulent kinetic energy. Contrary to the former approach, the latter allows to perform computations with fine meshes, which is necessary to compute wave run-up and overtopping accurately. The model is used to reproduce experiments of solitary and irregular wave propagation, breaking, run-up, and overtopping, with satisfactory results. Keywords. 1. Introduction. Numerical models are commonly used to assess wave propagation and transformation in the nearshore zone, as well as wave interaction with coastal structures. Weakly dispersive depth-averaged models, also called type BT models, are well suited for that type of application. They retain enough dispersive effects to model wave propagation in shallow and intermediate water depths, typical of coastal areas, at a reasonable computational cost. Two important physical phenomena that need to be accurately modeled are wave breaking and wave run-up or swash, plus potentially the overtopping of coastal structures. Several approaches can be followed to model wave breaking with such models, the two most common being to locally solve the nonlinear shallow water equations, NSWE, instead of the dispersive equations to model the breaking wave as a bore, the so-called hybrid approach, or to add a diffusive-like term to the momentum equation with the subsequent energy dissipation controlled by an eddy viscosity. In this work, a numerical model solving the enhanced green equations from 1 in 1 horizontal dimension, 1 HD, is presented and applied to reproduce several wave flume experiments involving wave breaking, run-up, and overtopping. Both mentioned wave-breaking closures are compared. 2. Numerical model. Is the free surface elevation, d the still water depth, h plus d the total water depth, g the acceleration of gravity, u the depth-averaged horizontal velocity, and q the momentum? Is the bottom friction term modeled with Manning's law and treated implicitly, and is a dispersive source term, obtained from the solution of the additional elliptic? 3. Which takes most of the computational effort? The expressions for the different terms in the elliptic equation can be found in 2. The left-hand sides of 1 and 2 are the NSWE, here solved with a high-order finite volume method. This offers the advantage of modeling easily and accurately the wet-dry transitions and the evolution of the shoreline. A third-order MUSCL reconstruction of the flow variables at cell interfaces is used, following 3, and the hydrostatic reconstruction from 4 is used to preserve the positivity of the water depth and the motionless steady states. The derivatives in the dispersive terms are computed with second-order cented finite difference formulas, leading to a system of equations from 3, solved with the Thomas algorithm to recover to accurately detect breaking onset, the values of, and depend on the case, and typically fall in the range 0.3, 0.6, and 20, 30, respectively. Then for this approach, no parameter needs to be calibrated, which is its main advantage, in addition to its simplicity. With this condition, we obtained converged and stable results with a Courant number C05. Wave generation and absorption are performed with relaxation zones. 3. Experimental validation. For all the simulations performed, a Courant number C05 is used, as well as a Manning friction coefficient N0012S/M13. 3.1. Shoaling, breaking and run-up of a solitary wave. Evolution of the solitary wave, amplitude along the slope in trial 43 of the experiments from 7 for the different breaking approaches. The position of maximum run-up in the experiments is represented by the orange line. Comparison of 2 snapshots of the free surface elevation in trial 43 of the experiments from 7. Left during the breaking phase. Right during the rundown phase. 3.2. Irregular waves overtopping a coastal dike with shallow foreshores. Setup of the experiments of 8, with the location and number of the wave probes. Total wave spectra and significant wave heights in the experiment, and the simulation for one case at wave gauges number 5 and 14. Computed and measured average overtopping discharge for the 18 cases simulated. For conclusion, we developed a numerical model solving the weakly dispersive ESGN equations with a finite volume finite difference method. Wave breaking is modeled either by neglecting dispersion or by including a diffusive-like term with an eddy viscosity modeled with the turbulent kinetic energy. Both methods perform well, although the second one appears to be more accurate and robust. The model is then applied to a complex case of random waves overtopping an impermeable sea dike, with intense breaking on the foreshore. This case highlights the robustness of the numerical scheme regarding wetting and drying. Furthermore, it shows that the breaking approach allows to accurately model the transformation of the wave spectra with little calibration. The average overtopping discharges are reproduced with acceptable accuracy. The authors thank the French ANRT for its financial support towards D Research Program through the CIFRE Grant 2022-1017. The authors would also like to thank Suzuki and Flanders Hydraulics, Belgium, for providing the data of the wave overtopping experiments from 8. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1P FD Marque F. M. 2011, A Splitting Approach for the Fully Nonlinear and Weakly Dispersive Green. J 23414791498. 2M AG M. 2023, Low Dispersion Finite Volume Element Discretization of the Enhanced Green Equations for Wave Propagation, Breaking, and on Unstructured Meshes. Ocean Model 182, 102157. 3 Van Leer B. H. 2021, Towards the Ultimate Understanding of MUSCL, Pitfalls in Achieving Third-Order Accuracy. J. 446, 110640. 4 Dong J. Lee D.F. 2020, A Reliable Second-Order Hydrostatic Reconstruction for Shallow Water Flows with the Friction Term and the Bed Source Term. J. Math 376, 112871. 5M. M. 2018, On Wave Breaking for Type Models. Ocean Model 123, 1639. 6M. M. 2009, Hybrid Finite Volume Finite Difference Scheme for 2DH Improved Equations. Coast 5656, 09620. 7 SC, TW, TC, YH 2008, On the Evolution and Run-Up of Breaking Solitary Waves on a Mild Sloping Beach. Coast 55129 75988. 8 Suzuki T. Al. 2017, Efficient and Robust Wave Overtopping Estimation for Impermeable Coastal Structures in Shallow Foreshores Using Swash. Coast 122-1, 8123. 9 JA, JE 1992, Estimating Incident and Reflected Wave Fields Using an Arbitrary Number of Wave Gauges. In Proceedings of 23rd International Conference on Coastal Engineering. 777, 789. Venice, Italy. Prototype Scale Experimental and Numerical Investigation on Wave Attenuation through Idealized Mangrove Forest. Abstract. Coastal vegetation is of great importance in attenuating coastal flooding and enhancing coastal disaster prevention. While numerous studies have examined wave attenuation by mangroves using rigid cylinder models, limited research has focused on the interactions between extreme waves and mangroves with complex root systems, such as those of species. Prototype-scale experimental and CFD numerical models were conducted to investigate the protective performance of the mangrove forest under tsunami-like wave conditions. The influence of wave and mangrove characteristics on wave attenuation coefficients was systematically analyzed. Results indicate that higher incident wave heights and water depths generally reduce wave attenuation coefficients, while high-density mangrove forests, HDM, significantly enhance wave attenuation coefficients compared to low-density configurations, LDM. To predict the wave attenuation coefficient, 5 dimensionless parameters, derived from mangrove and wave characteristics, were evaluated using artificial neural networks, ANN. The ANN model shows excellent predictive performance, R2098, for wave attenuation coefficients, identifying mangrove density and cross-shore width as the most dominant factors, contributing 47% and 30% to wave attenuation, respectively. These findings emphasize the critical role of the mangrove forest in coastal flood mitigation and provide valuable insights for coastal planning and disaster risk reduction strategies in vulnerable regions. Keywords. 1. Introduction. Coastal communities are increasingly vulnerable to inundation events driven by high surge levels and intensified waves, exacerbated by sea level rise associated with climate change. The frequency and severity of flooding in coastal regions highlight the urgent need for effective protective measures. While numerous studies have investigated green mitigation structures, such as mangrove forests, to reduce inundation impacts, uncertainties remain regarding their protective performance, particularly in wave attenuation. The complexity and variability of natural systems pose significant challenges to accurately predicting their effectiveness, contributing to the absence of standardized engineering guidelines for their widespread implementation. 1. Wave attenuation in mangroves has been extensively studied through laboratory experiments, e.g. 2. And numerical modeling, e.g. 3. Laboratory investigations often utilize artificially mangrove models, such as cylindrical arrays, to assess their effectiveness in attenuating regular, irregular, and transient waves. However, most previous studies, e.g. 4, have highlighted the critical influence of vegetation geometry, particularly the role of complex root systems, on wave damping. Moreover, these physical experiments were conducted on reduced scales, which may introduce significant scale effects, thereby affecting the accuracy of the results and their applicability to real-world conditions. Similarly, numerical studies have examined flow hydrodynamics around cylindrical arrays predominantly, neglecting the impact of mangrove root systems on wave attenuation. Yin al. 3, for instance, incorporated resistance and porosity sources to simulate mangrove trunks and root systems, but encountered difficulties in accurately capturing hydrodynamic patterns within realistic mangroves. These challenges underscore the need for advanced three-dimensional modeling approaches. This study addresses these gaps by conducting prototype-scale experiments and computational fluid dynamics (CFD) models to evaluate the protective performance of mangroves against long waves. Detailed investigations were conducted to analyze the hydrodynamic patterns around mangroves with complex proproot systems and to examine the influence of wave parameters and mangrove characteristics on wave attenuation coefficients. Furthermore, an artificial neural network (ANN) model was implemented to identify the key parameters governing wave attenuation coefficients, providing insights into their relative contributions. 2. Experimental and numerical models. 2.1. Prototype-scale physical model. Profile view of physical tests, indicating bathymetry, instrumentation, and mangroves. 2.2. Open foam-based numerical model. This study utilized OpenFoam, an open-source computational fluid dynamics (CFD) platform, to simulate the interaction between tsunami-like waves and an idealized mangrove forest. OpenFoam, built on a modular C++ library, applies the finite volume method, FVM, for spatial discretization. 5. In the OpenFoam framework, the flow solver, with the advantages of wave generation and active absorption techniques, was implemented, enabling precise replication of wave physics observed in laboratory experiments. To accurately capture turbulence effects, the flow solver was coupled with the KSSD closure scheme, which enhances the precision of simulations. Further descriptions of the numerical setup are available in Dang al. 6. Wave transformation in leading, middle, and trailing sections of baseline, HDM and LDM. Comparisons of measured and simulated elevations, velocities B, and pressures C. 3. Results and discussions. Effects of wave heights, A, water depth, B, and density, C, on attenuation coefficient. The study further explored the impact of dimensionless parameters, including relative wave height RA, relative horizontal extension of vegetation, RB, submerged ratio of vegetation, vegetation submerged volume fraction, and vegetation relative submerged projected area, AR, on the wave attenuation coefficient. To estimate the attenuation coefficients based on these parameters, artificial neural networks, ANNs, were implemented, which demonstrated a strong agreement between predicted and measured coefficients for both the training and testing datasets, yielding R2098 and 0.97, respectively, Fig. 5C and D. Furthermore, ANNs were used to evaluate the relative importance of each input parameter on wave attenuation coefficients. The results revealed the vegetation's submerged volume and relative mangrove lengths referred to mangrove density and width as dominant factors, contributing 47% and 30% to the transformation of wave attenuation coefficients. Fig. 5b. 4 conclusions. Structure of ANN model. A. Importance index of each input parameter. B. Comparisons of measured and predicted coefficients using the ANN model. CD. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Kelty K. T. Cox D. T. P. Mitchell W. 2022, Prototype Scale Physical Model of Wave Attenuation Through a Mangrove Forest of Moderate Cross-Shore Thickness, LeDAR-Based Characterization and Scaling for Engineering with Nature. Front Mar 8. 2T. Al. 2020, Physical Model Investigation of Mid-Scale Mangrove, Effects on Flow Hydrodynamics and Pressures and Loads in the Built Environment. Coast 162, 103791. 3 Yin Z, Li J, Y, H, Yin T, 2023. Solitary Wave Attenuation Characteristics of Mangroves and Multiparameter Prediction Model. Ocean 285 115372. 4M, JL, IJ 2019. Experimental Analysis of Wave Attenuation and Drag Forces in a Realistic Fringe Mangrove Forest. Adwater 130 11033. 5P. I. JL 2015. Three-dimensional numerical wave generation with moving boundaries. Coast 101 3547. 6 Dang H. Park H. Shin S. Ha T. Cox D. T. 2024. Numerical Modeling and Assessment of Flood Mitigation Structures in Idealized Coastal Communities. Open Foam Simulations for Hydrodynamics and Pressures on the Buildings. Ocean 307, 118147. 7 Ra, JT, PA 1984 Wave Diffraction Due to Areas of Energy Dissipation. J. Port Coast Ocean 110, 16779. Exploring Wave Generation, Mechanisms Through the Vortex Force Formalism. Abstract. The implementation of the vortex force formalism, equations in 2DH within the X-Beach numerical model, while equivalent to those based on the radiation stress formalism already implemented, provides the advantage that the effects of adiabatic wave transformation and dissipation on long wave generation can be separated. Model results reveal that the dissipation term, due to depth-induced breaking, generates free long waves propagating both shoreward and seaward, consistent with the theory of the varying mechanism proposed by Al. 1982. Further analysis is conducted on a synthetic fringing coral reef, with slopes of 1,1 and 125. The results demonstrate that both adiabatic and dissipative terms significantly impact long wave generation. However, the dissipation term is most influential on steep slopes, while the adiabatic terms becomes more dominant on milder slopes, in agreement with previous findings in the literature. Keywords. 1. Introduction. IG waves are long-period oceanic waves, with periods ranging from 20s to several minutes. They are particularly significant in nearshore areas, especially during storms, where they can greatly impact coastal erosion and flooding. See Burton al. 2018 for a full review. Understanding the generation and propagation of IG waves to the shore is therefore a crucial area of study. And Stewart, 1962, demonstrated through the radiation stress, RS, concept that wave groups generate bound long waves via second-order nonlinear difference interactions. On a flat bottom, these bound long waves are out of phase with the wave group. During their propagation to the shore, they are then progressively released as free waves due to the bathymetry variations. Al. 2021, and during wave breaking as a result of reduced wave, 2012. Another generation mechanism for IG waves was proposed by Al. 1982, who showed that the temporal variation of the forcing could generate free long waves. These free waves originate from the surf zone and propagate both shoreward and seaward. In recent years, numerical modeling has greatly enhanced our understanding of IG waves on complex bathymetries and of their impact on beach. Al. 2009 developed the X-beach model. It uses a wave action balance to propagate wave groups coupled with the nonlinear shallow water equations, NLSWE, to simulate long waves and wave-induced currents. This coupling between short and long waves utilizes the RS formalism, which incorporates a forcing term in the NLSWE to account for all physical effects related to short wave transformation. Although this method is efficient and widely validated, it does not distinguish between the effects of adiabatic wave transformation and dissipation on the generation of IG waves. The vortex force, VF, formalism equations, Smith, 2006, address this issue by clearly decomposing the conservative and dissipative effects. Although these equations have been used in the past to model rip current, Weir al. 2011, they have never been applied to IG waves. The implementation of these equations as an alternative to the already implemented RS formalism, therefore improves our understanding of IG waves generation and propagation. 2. The depth-averaged vortex force equations. 2.1 Vortex force equations. The three forcing terms from the short waves are placed on the right-hand side of 1. The first term is the wave dissipation term, including depth-induced wave breaking, dissipation by bottom friction and damping by vegetation, denoted as and. The second term on the right-hand side is the conservative Bernoulli head term, which acts as an adjustment in the mean pressure to accommodate for the presence of waves, Lane al. 2007. The last term is the vortex force, which is a reaction of the mean flow to wave refraction. The main difference between the RS and VF equations lies in the quantities considered. In the RS formalism, the equations solve for the total momentum, which includes both the velocity of the mean flow and the Stokes drift, whereas the VF equations focus solely on the velocity of the mean flow, velocity. Despite this difference in approach, Smith, 2006, demonstrates that the two sets of equations are mathematically equivalent in 2DH. 2.2 Flat bottom solution. The first term in the numerator of 4 originates from the wave mass source term on the right-hand side of the continuity equation. 2. The second term is related to the Bernoulli head, which is a finite depth contribution and vanishes in deep water. 2.3 Separation of the generation mechanisms. assuming that the dissipation term due to depth-induced breaking is related to the varying mechanism, and that the Bernoulli head and the wave mass source term from the continuity equation are associated with the generation of bound waves, it becomes possible to separate the generation mechanisms by activating or deactivating these terms and assessing their relative importance. We can then imagine three cases. All mechanisms. All the terms are included in the equations. Forcing only, the Bernoulli head and the wave mass source term are turned off, and bound wave only, the dissipation term is turned off. The goal of this work is to understand how each term in the VF equations relates to the generation mechanisms of IG waves. Specifically, we aim to verify whether the dissipation term induced by wave breaking accurately describes the varying mechanism described by Al. 1982, as suggested by Burton, 2015. For simplicity, this work focuses on simulations in 1D cross-shore. Under this hypothesis, the vortex force term vanishes. 3 results. An ideal test case for assessing which IG wave generation mechanism is predominant is a fringing coral reef. The typical bathymetry is characterized by a steep forereef slope, with typical slopes in natural environments approximately ranging from 1,1 to 125, as shown in Table 1 of Al. 2015, starting in the offshore region and transitioning to a shallow reef flat, which then leads to a sandy beach. In this type of environment, short waves are strongly dissipated by both wave breaking and bottom friction on the forereef slope and reef flat. Al. 2012 and Van Al. 2013 studied the reef in Western Australia, characterized by a forereef slope of 120. They were the first to show some evidence of forcing in coral reef environments, using field measurements and simulations. More recently, Al. 2019 carried out some laboratory experiments on coral reef platforms, as well as numerical experiments with NH, the phase-resolving version of, and showed how important the reef slope is to the generation of IG waves, concluding that for very steep slopes of 1/6 or less, forcing is dominating the signal, whereas bound waves become increasingly important as the slope gets milder. In this section, we consider an idealized situation, with a constant offshore depth of 21.5 m, followed by a forereef slope that varies between simulations, and then a reef flat at a depth of 1.5 m. We neglect bottom friction and consider a smooth reef to focus solely on the short wave dissipation by breaking. The coastline is not included, as our focus is on the generation mechanisms of incoming IG waves. An absorbing boundary condition is placed on the reef flat. Bichromatic waves are generated 3m, T112s, T115s at the offshore boundary. Figure 1 illustrates the IG wave surface elevation generated for two cases, a steep forereef slope of 1,1 and a milder one of 125. The generation mechanisms were separated using the method proposed in Sect. 2.2. The separation appears effective, as the patterns observed in the all mechanisms simulation exhibit characteristics of both the forcing-only and bound wave forcing-only simulations. However, this is not a strict superposition of the IG surface elevation from the two cases. Each mechanism modulates the water depth differently, thereby altering the propagation speed of both short and IG waves. The forcing-only case shows the propagation of free IG waves traveling both onshore and offshore from the breaking point, consistent with the theoretical model of Al. 1982. In the offshore region, the 125 slope primarily exhibits a progressive IG wave pattern, while the 1,1 slope shows a standing wave pattern. The separation of generation mechanisms reveals that this standing wave pattern is mainly caused by the superposition of outgoing waves from forcing and incoming bound waves. However, for the 1,1 slope, some reflection is also observed in the bound wave forcing-only case between breaking events. We hypothesize that the depth variation mechanism described by Al. 2021 releases free IG waves which are then partially reflected by the depth variation, Al. 2023. The amplitude of the waves generated by the forcing is higher for the 1-1 slope. This is an expected result, consistent with the findings of Al. 2019. For the steep slope case, the surf zone is only a few tens of meters long, whereas for the milder slope, it extends over an order of magnitude greater distance. This implies much higher breaking intensity for the steep slope, which likely serves as a proxy for more efficient IG wave generation. In this scenario, IG waves are generated almost at the same location, ensuring they remain in phase during their generation. In the case of bound wave forcing only, the amplitude of the waves present on the reef flat is higher for the milder slope case, which is a well-known result, see Al. 2020 and others, as the large spatial extent of the sloping area allows a more efficient energy transfer from the short to the long waves. Spacetime diagrams of the IG surface elevation for two forereef slopes, 125 left and 1 right. Columns show simulations for all mechanisms top, forcing center, and bound wave forcing bottom. The white lines indicate the boundaries of the sloping area. These results clearly demonstrate the complexity of the phase relationship between generated waves and released bound waves, disproving the assumption that forcing is strictly in phase with the wave group, as already shown by Al. 2018. For conclusion, this paper presented the implementation of the VF formalism in, and its application to an idealized fringing reef case. The separation of the forced waves and released, bound waves proved effective, offering a clearer understanding of the generation mechanisms of IG waves. Future work will focus on generalizing these findings across a wider range of parameters and exploring other types of bathymetries. This research was funded by the FWO Waves Project, 3E2 21057. Special thanks to Robert Call for his support in model development and helpful discussions. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: T. 2012. Dissipation of incident forced long waves in the surf zone. Implications for the concept of bound wave release at short wave breaking. Coastal 62, 76-285. Burton X. al. 2018. Waves, from driving mechanisms to impacts. Earth Rev 177, 774, 799. Burton X. 2015. Hydro Parla. La. S. al. 2018. Forcing Revisited, Phase Between Forcing and Response. J. Rays Oceans, 123, 1354-1363. S. al. 2021. Free and Forced Components of Shoaling Long Waves in the Absence of Short Wave Breaking. J. 515146-51487. S. al. 2023. Free Long Wave Transformation in the Nearshore Zone through Partial Reflections. J. 53-661-681. Lane E. al. 2007. Wave Current Interaction, a comparison of radiation stress and vortex force representations. J. 371122-1141. M.S. Stewart R.W., 1962, Radiation Stress and Mass Transport in Gravity Waves, with application to surf beats. J. Fluid Mech 134480-154. G. al. 2019. Physical and numerical modeling of wave generation and transformation on coral reef platforms. J. Rays Oceans, 124-1410-1433. A. Al. 2012. The Dynamics of Wave Transformation over a Fringing Reef. J. Rays 117, C11022. E. Al. 2015. The Influence of Coral Reefs and Climate Change on Wave-Driven Flooding of Tropical Coastlines. Rays 42640-76415. D. Al. 2009. Modeling Storm Impacts on Beaches, Dunes and Barrier Islands. Coastal 56, 1112, 1133, 1152. Smith J. A. 2006. Wave Current Interactions in Finite Depth. J. 367140, 31419. G. Al. 1982. Two-Dimensional Surf Beat. Long Wave Generation by a Time Varying. J. Rays Oceans 80, 7C1 492, 498. Van A. Al. 2013. Numerical Modeling of Low-Frequency Wave Dynamics over a Fringing Coral Reef. Coastal 73, 178, 190. Weirby Al. 2011. A Vortex Force Analysis of the Interaction of Rip Currents and Surface Gravity Waves. J. Rays 116, C0, 5001. Q. Al. 2020. Shoaling of Bound Waves on Plain Slopes for Bichromatic Wave Conditions. Coastal 158-1-03684. Challenges in Assessing Longshore Transport along the Gulf of Cadiz Coast. Insights from Analysis of Different Wave Data Sources. Abstract. Estimating coastal sediment budgets presents significant challenges due to the complex nature of coastline configurations and the often bimodal wave regime. This study investigates longshore sediment transport, LSD, along the Gulf of Cadiz by analyzing estimates obtained from various wave data sources and employing various approaches. The sensitivity of transport calculations to different wave data sources and approaches is evaluated, and the impact of easterly waves, or, is examined for the different approaches. The nearshore wave regime was simulated using the SWAN model, with offshore conditions from ERA 5 and the Faro buoy. Results were validated using observational data, and LSD was estimated using a deep water approximation of the CERC formula, extracting the net transport and the two components of the sediment transport, west-east and east-west. The results emphasize the critical importance of selecting appropriate forcing for applied models to simulate the nearshore wave regime and estimate sediment transport. Keywords. 1. Introduction. Accurate estimations of longshore sediment transport, LSD, are essential for understanding coastal dynamics and addressing issues like coastal erosion. LSD is primarily influenced by wave parameters, including wave direction, height, and period, which directly control sediment movement along the shoreline. Therefore, analyzing the sensitivity of sediment transport calculations to different wave data sources is important, as variations in wave data can lead to significant differences in transport estimates. The coast along the Gulf of Cadiz has experienced significant anthropogenic impacts over the past few decades, disturbing the natural sediment transport processes. Coastal infrastructure, dredging, and urbanization have disrupted sediment dynamics, affecting the region's coastal morphology, sediment distribution, and shoreline stability. 1. Some areas along this coast have been the objective of extensive studies, such as the Ria Formosa in southern Portugal. This region has experienced complex shoreline changes, with alternating erosion and accretion trends driven by both natural and human factors, with retreat rates as high as 8.9602 m/year 2. Similarly, the coast has shown shoreline retreat rates ranging from 10 to 20 m/year 3. Here, we can come back to the complexity of the coastline and bimodal wave regime. In this context, this study aims to explore different approaches to estimate the potential LSD derived from various wave data sources. For that, we focus on evaluating the sensitivity of LSD estimates to different wave data sources, and on assessing the impact of these variations to model accuracy. Additionally, we investigated the influence of easterly waves, or on sediment transport. 2 methods. 2.1 Wave datasets and propagation. Gulf of Cadiz showing the location of the 2 sectors, offshore buoy and wave data, point from the ERA 5 model used as boundary conditions, in green, and location of 2 ADCP moorings used for validation. Wave data from the ADCP measurements, and from SWAN simulations extracted at approximately 20 m ADCP location, were offshore using Snell's law. This procedure allowed the extension of the data to deeper water depths. Filtered approach settings. Sector. Location. Representative shoreline orientation. Wave direction filters. 1. 216, 0126, 0270, 02. Maria Cape. 145, 090, 0235, 022, potential longshore sediment transport. 3 Results and discussion. 3.1 Validation of wave propagation scheme. Summary of SWAN model performance compared with ADCP wave data. OBS observation data. Model boundary condition. Bias. RMSE. ROBS data. Boundary conditions. ADCP. ERA 5. 0.21. 2. 2268. 0.33. 4.08. 44.96. 0.72. 0.49. 0.29. Faro buoy. 001. 0.9. 486. 0.24. 3.75. 33.91. 0.78. 0.48. 0.53. ADCP. ERA 5. 0.33. 0.24. 3660. 0.42. 3.48. 55.76. 002. 0.33. 0.17. Faro buoy. 0.2. 0.45. 1658. 0.29. 3.59. 42.48. 0.51. 0.29. 0.44. 3.2 Potential longshore sediment transport. The results from the analysis of LSD in the 2 sectors show distinct patterns, which depends on both the wave data sources and approach, Table 3. Along the SW facing Sector 1, the net sediment transport is directed predominantly eastwards, independently of the forcing conditions. The west-east transport often exceeds the east-west, FBUOI1, FERA 51, and SERA 51, implying that this component of the transport dominates clearly. However, for SBUOI1 and OBS1, the transport values for both approaches are nearly equal with the net pointing towards the east. In contrast, Sector 2 exhibits lower values for net LSD, with some outputs showing predominance in the westward transport, e.g. FBOI2 and SERA 52. This sector is sheltered from higher energy waves approaching from the west, but is exposed to easterly waves, showing lower transport rates with higher variability. A previous study assessed the longshore sediment transport towards the Guadiana-Ebb tidal delta, using the CERC2 formula, finding an average rate of 1.9105 m3 year and a maximum rate of C5 105 m3 year, which closely align with the results of the OBS2, Table 3. The direction of longshore sediment transport along the coast has been reported as eastwards, varying from 50 to 300-105 m 3-year 9. Sediment transport computations, based on SBUOI2 and OBS2, suggest nearly similar transport in both directions. The results reflect the relative exposure of the coast to a bimodal wave climate, which is dominated by the WSW swell generated in the eastern Atlantic, with conditions short-period waves generated by SE Mediterranean winds, generally playing a secondary role 10-11. Longitudinal sediment transport for the sectors 1-2 Maria Cape, and different approaches and boundary conditions, including net transport and west-east, east-west components, 105 m 3-year. The rightmost column shows the relative contribution of easterly waves to transport. OBS observational data. Sector. Approach. Boundary condition. Code. WEEWNet. E%. 1. Filtered. Faro buoy. FBUI1. 30.21. 2.95. 27.26. 9. 1. Filtered. ERA 5. FERA 51. 21.23. 1.2. 20.02. 5. 1. Swan. Faro buoy. SBUI1. 15.21. 14.87. 0.33. 49. 1. Swan. ERA 5. SERA 51. 15.24. 1.54. 13.69. 9. 1. OBS. OBS1. 16.52. 15.42. 1.1. 48. 2. Filtered. Faro buoy. FBUI2. 0.14. 14.27. 14.12. 99. 2. Filtered. ERA 5. FERA 52. 2. Swan. Faro buoy. SBUI2. 0.87. 0.62. 0.25. 42. 2. Swan. ERA 5. SERA 52. 0.11. 0.53. 0.41. 82. 2. OBS. OBS2. 5.23. 304. 2.18. 37. Eastward sediment transport shows significant variability across different approaches and boundary conditions. For most approaches, eastward transport dominates, consistently exceeding 40%. In Sector 1, FBUOI2 and OBS2 show eastward transport values of 49% and 48%, respectively. However, there are instances, particularly in Sector 1, where eastward transport is less prominent, with values falling below 9%. In contrast, in Sector 2, eastward transport reaches up to 99% in FBUOI2. 4 conclusions. The results from the analysis of LSD show distinct patterns, which vary according to both the approach and wave data source in the boundary condition. The results emphasize the critical importance of selecting appropriate wave forcing for applied models to simulate the nearshore wave regime and estimate sediment transport. This work was funded by FCT Portuguese Foundation for Science and Technology, REF. 2023.03101, and is a contribution of Coastal Resilience, Remote Sensing Monitoring Project, funded by FCT Portuguese Foundation for Science and Technology Reference, 20220-5392 PTDC. org 1054499202205392 PTDC. The authors would like to thank Prof. CCMAR Dr. CIMA and Dr. IPMA for providing the ADCP data for validation. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1K M. O. A.R. Costas S. T. 2019. Impacts of Human Interventions on the Evolution of the Ria Formosa Barrier Island System, S. Portugal. Geomorphology 343, 129, 144. 2 Lira PC, SA, R. C. 2016. Coastline Evolution of Portuguese Low-Lying Sandy Coast in the Last 50 Years, an Integrated Approach. Earth. Data 8-1265-278. 3J, FJ del LG, A 2015, Las Playas del Min. 126-34-09-426. 4N, RC, LH 1999, a third-generation wave model for coastal regions. 1. Model description and validation. J. Rays, Oceans 104C4764976666 org 10, 102998, JC02622. 5 Roberts KJ, WJ, JJ, 2019, Ocean Mesh D1, MATLAB-based software for two-dimensional unstructured mesh generation in coastal ocean modeling. Model 1251-8471868. 6 Santos F. Lopes AGRL 2014, do Ode. Portuguese Littoral Working Group, Report P237, in Portuguese. 7E, A, O 2019, a method to estimate the longshore sediment transport at ebb tidal deltas based on their volumetric growth. Application to the Guadiana, Spain-Portugal border. Earth surf. Brook. Land. 4413-2-5572569. 8 AD, Murray Ob 2006, High-Angle Wave Instability and Emergent Shoreline Shapes. 1. Modeling of Sand Waves, Flying Spits and Capes. J. Rays, Earth Surf 111-119. 9 CDX 2015, La y en las playas con, del Costa, Las Los, Guadiana y Guadalquivir. Final. Madrid P72, CDEX, 224-105001. 10J, JJ, M, 2021, Analysis of Wave and Wind Energy in the Gulf Coast. In 14th European Wave and Tidal Energy Conference, 5-9 Sep 2021, 113. 11 TA, J, I del L, 2015, Variability in Storm Climate along the Gulf of Cadiz. The role of large-scale atmospheric forcing and implications to coastal hazards. Climate Dyne 45-24992-514. Process-based numerical modeling of total water levels, flooding, and morphology changes during hurricane impact at Florida Panhandle beaches. Abstract. Low-lying barrier islands around the Florida Panhandle in the United States are highly susceptible to storm-induced coastal flooding and erosion. Projected sea level rise (SLR) and storm intensity resulting from climate change will amplify these effects. Predicting these effects accurately will aid in improving decision-making capabilities for coastal communities and military installations near the coast. This study utilizes CSHORE, a very efficient 1D process-based cross-shore model, for assessing flooding and morphological change along barrier island beaches. The model was applied to 71 transects over 70 centering around base, TAFB, Florida, assessing total water level, TWL, flooding and morphological change during Hurricane 2018, and the spatial variability of these effects due to hurricane landfall location. Model validation, generally peak water levels compared to measured high water marks, HWM. However, most HWMs were within one standard deviation of the modeled statistical mean value. Preliminary results of this study showed significant variability of TWL at the shoreline along the 70 stretch of coast, from 0.83 m mean sea level, MSL, northwest of TAFB, where winds propagated offshore, to 3.38 m MSL southeast of TAFB, where winds propagated onshore. Future work includes validating the morphological change from CSHORE using Hurricane Michael forcing conditions, assessing the impact of profile spacing and offshore profile length on model accuracy, and investigating the impact of various SLR scenarios on TWL flooding for TAFB. Keywords. 1. Introduction. Beach areas, communities, infrastructure, and even military installations located in the Florida Panhandle, bordering the Gulf of Mexico, are vulnerable to flooding caused by storm-driven elevated water levels. Being able to accurately and efficiently predict total water level, TWL, and corresponding flooding caused by an event is essential for emergency management decision-making and longer-term mitigation planning. TWL is the combination of mean sea level MSL, tide, storm surge, and wave. The coastal area under investigation encompasses a series of disconnected barrier islands, marshland, and connected land bridges. Offshore, the water depth approaches 20 m, MSL2, from the shoreline to the northwest, widening to approximately 15 to the southeast, Fig. 1. The continental shelf is relatively flat, 100 m depth, and extends 220 from the shoreline. This research aims to assess whether CSHORE can accurately predict TWL flooding and changes produced by hurricane-level storms, and to compare how these effects differ compared to the storm landfall location. Study location map, including offshore depth contours around the wider TAFB and MB area. 2. Methodology. TWLs are assessed by CSHORE using Hurricane Michael 2018 forcing conditions along with a range of sea level rise SLR scenarios. The advantage of CSHORE lies in its computational efficiency and robustness. Compared with higher fidelity models like XBeach2, which can take hours if not days to run for the same size grids and model length, CSHORE can be a very efficient tool, allowing many simulations with different input conditions to be conducted over a relatively short amount of time. Hydrodynamic validation of CSHORE model runs was conducted using measured high water marks around MB, approximately 20 southeast of the base. Profile transects were taken every one, perpendicular to the shoreline, over approximately 70 around TAFB and MB Fig. 1. The 71 total transects are 10-15 long depending on location, with cross-shore spacings of 110 m used to determine how profile resolution affects TWL flooding and morphology change. Due to the lack of measured water level and wave height information for the area, hydrodynamic inputs into the model were sourced from advanced circulation, ADCIRC, model outputs run for Hurricane Michael at given points along the 20, 10, and 5 m offshore depth contours 3. 3 results. CSHORE computation results for MB during the peak water level produced by Hurricane Michael. The most recent validation results show that at the peak of the storm, CSHORE probabilistic mean water level values at locations normally located on the dry beach are 0.410 m below HWM measured around MB. However, these measurements generally fall within one standard deviation of the statistical mean, Fig. 2. There are several factors as to why modeled values are slightly. Firstly, the offshore bathymetry around MB is quite complex, including deep offshore sandbars and a dredged shipping channel, which may go beyond the 1D capabilities of CSHORE. Secondly, the measured HWMs were taken from seed lines inside buildings in the aftermath of Hurricane Michael, and may not be truly representative of a typical TWL at the peak of the storm. Lastly, the modeled water level is a statistical output of the average value over the 20 min, indicating that the TWL may have been higher for a shorter period, as indicated by the free surface standard deviation shown in Fig. 2, which will need to be looked at in more detail. CSHORE transects modeled along the wider TAFB area, white. The approximate hurricane track is visualized as the dotted green line. Colored dots represent input white-blue and output at the shoreline yellow-red TWLs. For future work, refinement of the MB models will be conducted by assessing the impact of changing profile spacing and offshore profile length on the TWL prediction. Morphology changes over the wider TAFB area will be validated using pre- and post-storm LIDAR-derived digital elevation models with modeled results. Including and excluding morphology changes within the CSHORE model will be assessed to see how this affects TWL flooding results. Once this refinement has been completed, the optimal model parameters will be reapplied on model runs over the wider TAFB area with different SLR scenarios to see how TWL changes along the shoreline and to assess the spatial distribution of flooding hazards relative to the point of hurricane impact and SLR. 5. Conclusion. This study investigates the ability of CSHORE, an efficient process-based 1D model, to predict TWL flooding around TAFB during hurricane events. Due to the computational efficiency of CSHORE, hydrodynamic and impacts along sandy beaches can be assessed in seconds to minutes, allowing high resolution of modeled cross-shore profiles over a wide area. Using Hurricane Michael, 2018, as input conditions, the model was applied along a 70 stretch of coastline, encompassing LB, TAFB, and MB. This efficiency allows many beach profiles to be modeled over the wide area, providing insight into the spatial variability of hydrodynamic and impacts resulting from hurricane-level storms. Model results were validated against measured HWMs at MB. The results showed reasonable agreement, with HWMs generally falling within one standard deviation of the modeled TWL statistical mean, highlighting important factors including complex nearshore bathymetry and potential limitations in measured data. The study revealed a high spatial variability in flooding along the coastline, with TWL at the shoreline varying significantly relative to the hurricane landfall point. Future work will focus on model refinement, including change and evaluating the impact of different SLR scenarios on TWL at TAFB. Funding source: DUDI ESDCP Award No. W912HQ22C0041. Comparative Assessment of Total Water Levels for Coastal Military Facility Readiness and Resilience Using Numerical Models. Pi, J. Of Delaware. Thank you to and Gupta ADCIRC Input, Casey and ADCIRC Input, and Van and Ellen, Initial X-Speech Input. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1N.T. 2022, Cross-Shore Numerical Model CSHORE 2022 for Coastal Sediments and Structures, Research Report No. CACR 2204. Center for Applied Coastal Research, University of Delaware, Newark, Delaware, p. 19716. 2VD Al. 2015, X-Beach Technical Reference, Release. Model Ref GUID 1141. 3MV, RA 2024, The Role of Advection in Storm Surge for Hurricane Michael, 2018. J. Rays Oceans 129 7E202, 4JC02, 1105 Org 10 1029202, 4JC02, 1105. 4 U.S. Geological Survey, USGS, Short-Term Network Data Portal. Water Floods FEV Accessed 2023. 5MD, PJ, TA 2003, Reduced Drag Coefficient for High Wind Speeds in Tropical Cyclones. Nature 422, 69292, 79283. Org 10 1038 Nature 0, 1481. Verification of the SFINCS model, applying GPS-measured flood marks from the storm surge, in southern Denmark. Abstract. Over the past century, individuals in Denmark have continuously settled closer to the sea, increasing the exposure to flooding tremendously. Paradoxically, the proximity to the sea, which over the decades caused property prices to skyrocket, has now transformed into a substantial risk. The Danish Coastal Authority, DCA, is responsible for national assessment of coastal flood risk under the EU Floods Directive. DCA is continuously seeking, fit-for-purpose, numerical models to ensure ongoing improvements of risk assessment. The last 2 years, DCA has tested the SFINCS, Superfast Eye of Coast S, Model 1, 2 against historical events. However, in October 2023, Denmark was hit by the devastating storm surge, which led to an indispensable comparison of in-flood mark measurements and available water level gauges against the performance of SFINCS. On average, throughout the model domain, in total 13 flood marks and 5 complete gauge, SFINCS predictions of maximum water levels lies within 5 RMSE6, compared to GPS flood marks and gauge water level measurements. This manuscript presents DCA's model verification results and describes future application of SFINCS in DCA. Keywords. 1. Introduction. Denmark boasts a diverse coastline stretching more than 7,300, featuring everything from straight high-energetic coasts to low-exposed fjords and estuaries through narrow channels and straits. The Danish Coastal Authority, DCA, is responsible for producing national maps of coastal flood risk. Therefore, the awareness of the availability of new numerical models is a crucial part, continuing improvements. The last 2 years, DCA has tested the SFINCS model against almost forgotten historical events. However, in October 2023, Denmark was hit by the storm surge of the century, which led to an indispensable comparison of real flood mark measurements against the performance of SFINCS. This paper presents Danish verification results of the October 2021-2023 storm surge and describes future application of SFINCS in DCA. First sect. 2. Method provides a description of DCA GPS flood marks and the model setup. Section 3, Model Results, primarily focuses on water level outcomes, although a demonstration of the predictive capability of flood extents will be presented at the conference. 2. Method. 2.1 GPS measured flood marks. Flood marks on houses along the coast bear witness to the devastating high water levels. Ideally, marks were elected inside construction buildings or sheds, which were not waterproof, but offered protection against weather. In some areas, several flood marks were found within the spatial resolution of the hydrodynamic model. Hence, an average value of flood level was estimated for the model to compare with. Every GPS value was measured, with the accuracy of 2-3 RTK signal. 2.2 Model Setup. The SFINCS model is set up to cover a coastal area of 100 x 100. The model runs on an equidistant rectilinear grid of spatial resolution of 100 m, with an underlying table of 5 meters. Tables are based on values from the high-resolution 0.40.4 m Danish Terrain Model DTM by the Danish Agency for Data Supply and Infrastructure 3, the coarser bathymetric model 50 m by the Danish Geodata Agency 4, and DCA's in-house National Map of Land cover polygons of Manning's roughness coefficients, n based on 5. A national DCA dataset of dike elements, x, y, z coordinates are implemented as weir lines for which the model will determine overflow based on its weir formulations. The model simulation ran on a single laptop with run times around 30 min for the storm duration of close to 4 days. The model is forced with measured 10 min interpolated water levels at input locations as seen in Fig. 2s dots. Spatial and time varying gridded wind data from the Danish Institute, DMI, operational DMI NEA weather prediction model is applied as wind forcing 6. The gridded wind data is accessible in temporal resolution of 1H and a spatial resolution of 2.2. Input of river runoff discharges in river and sea triangles in Fig. 2. River enable the model to determine the combined water levels in and river delta at the harbors. However, water level measurements in the rivers were only available in. Currently, waves and rain are not yet implemented, but is of highest priority and will be a part of the final model setup. The model simulation ran on a single laptop with run times around 30 min for the storm duration of close to 4 days. 3 model results. GPS location and values, black, are shown on the map of SFINCS maximum water level. Extracted model values, yellow, is held against GPS values and water level gauge stations, harbors. Modeled water levels are compared to water level gauge measurements. Evaluation of modeled water levels, water level gauges, and measured GPS flood marks. Time series. NSC. RMSEM. Harbors. 0.86. 0.15. River 1. 0.21. 0.43. River 2. 0.89. 0.14. Harbors. 0.992. 0.04. Harbors. 0.997. 0.03. Harbors. 0.97. 0.09. Harbors. 0.986. 0.06. Peak water levels. NRMSEM. Plus 17. 0.06. For discussion. The model resolution of 100 m clearly sets a limitation on the direct comparison to the measured GPS flood marks. More than one flood mark might be measured inside a model 100 m computational cell. Local orientation of streets affects the impact from local wind setup. Therefore, representative average values of flood mark measurements in this area are compared to the model result. The average flood mark value takes the location of the flood mark measured closest to the center of all flood marks in that area. Are reproduced with excellence at most of the harbors. However, harbor NSE 0.86, RMSE 0.15, and River 2, NSE 0.89, RMSE 0.14, are in general underestimated. In this model setup, rain was not added yet as a driver. However, the author is aware that area received a significant amount of rainfall during the 1822 of October 2023. Missing local rain can to some extent explain this underestimation. At River 1, modeled water levels are well predicted on the front slope of the, however, after the peak, the models significantly overestimate the water levels, leading to a poor model result, NSE -0.21, RMSE 0.43. River was burned into the model bathymetry, but poor resolution data of the geometry, depth and width was available. Further, flooding is found on the floodplain at River 1 see Fig. 2, and this might be an over-prediction. The floodwater leads back into the river again, after the peak, causing a delay in the decrease of water level in the river. In most of the harbors, the SFINCS model is able to mimic the dynamics of the storm surge and even complete the broken-in with NSE 0.986, RMSE 0.06. Based on the model verification findings, coupled with previous model investigations, have led to further developments in SFINCS use in DCA. 1. The SFINCS model has already been used under the implementation of the EU Floods Directive in Denmark 7. 2. Ongoing investigations of the SFINCS model as a fundamental part of a national dike assessment project where dike breach-related flooding will be evaluated. 8. And 3. The SFINCS model is highly capable of hind casting incomplete. This is something DCA will benefit from in their future extreme value analysis. 5. Conclusion. In conclusion, the SFINCS model delivers encouraging results. On average, maximum water level estimates close to 5 centimeters, RMSE 6, from GPS flood mark levels and water level gauge measurements. Finally, most of the measured are reproduced with excellence, best in harbor with NSE of 0.997 and RMSE 3. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References. 1. 2024, the SFINCS Model Documentation. Homepage and Software and Data Products Last Accessed 3, 2024. 2T. Van M. K. Van A. 2021. Modeling Compound Flooding in Coastal Systems Using a Computationally Efficient Reduced Physics Solver, including fluvial, pluvial, tidal, wind, and wave-driven processes. Coastal 163-18. Org 101016J2020103796. 3. Agency for Data Supply and Infrastructure, 2022. Homepage Data Om Danmark Data Danmarks, last accessed 2 June 2022. 4. Danish Geodata, 2022, Agency. Homepage Den last accessed 2 June 2022. 5K, R, B, Herdman L, L, Barnard PL 2021. Drivers of Extreme Water Levels in a Large, Urban, High-Energy Coastal Estuary. A Case Study of the San Francisco Bay. Coastal Engineering 170, P12. Org 101016J2021103984. 6. Danish Institute, 2025, Weather Model. Homepage Data Forecast Data, Weather Model HARMONI last accessed 6, 2025. 7. Danish Coastal, 2024, National FRA. 8. KS, AL 2024, developing a national model for calculating dike failures and related floods in Denmark. Paper presented at Rencontres Maritime RIM 2024, Con. Jets, circulation cells, and meanders. What controls flow patterns in bar channel systems? Abstract. Nearshore circulation, patterns driven by breaking waves, are controlled by the geometry of nearshore bathymetric features, including crescentic or channel-incised sandbars. In these systems, the circulation pattern can range from rip current jets with symmetric feeder currents, rip current jets pushed to one side of a channel, pairs or single circulation cells, and meandering or uniform alongshore currents. These complex circulation patterns impact sediment transport, morphological evolution, transport of biota and pollutants, and swimmer hazards. Although the forcing that drives alongshore currents and bathymetric rip currents is well known, further work is needed to understand what controls the spatial patterns, including cross-shore and alongshore positions of flow maxima and reversals, of jets, circulation cells, and meanders. Here, idealized numerical modeling of circulation and waves, COAWSD, coupling ROMS and SWAN, in channel-incised sandbar systems is used to investigate the circulation pattern response to the size and asymmetry of channels during a range of incident wave heights and directions. The model results and an analysis of wave-averaged momentum balances are used to develop a framework that classifies circulation patterns as a function of wave forcing and bathymetry. Keywords. 1. Introduction. Wave breaking on nearshore bathymetric features, including crescentic or channel-incised sandbars, results in spatially complex nearshore circulation patterns. 1, 2. Surf zone circulation patterns in these systems include alongshore flows that feed rip current jets that sometimes are centered on the channel and sometimes are shifted to one side of the channel. Bathymetric rip currents sometimes manifest as pairs of circulation cells or a single circulation cell, without a jet-like feature that extends farther offshore. Under some conditions, the circulation consists of meandering or nearly uniform alongshore currents, and features with strong cross-shore transport do not form despite the presence of a channel. These complex circulation patterns impact sediment transport and morphological evolution, for example causing migration or infilling of channels. 3. Additionally, the presence of a jet rather than circulation cell S, and the presence of converging alongshore flows rather than an alongshore current, impacts the transport of biota and pollutants. 4, 5, and swimmer hazards. 6, 7. Although the forcing that drives alongshore currents and bathymetric rip currents is well known. 1, 2, 8. Further work is needed to understand what defines thresholds between distinct spatial patterns, including rip current jets that are centered or shifted, double or single circulation cells, and meandering or uniform longshore flows. 2 methods. Here, idealized numerical modeling of circulation and waves, COAWSD, coupling ROMS and SWAN. 8, 9, in channel-incised sandbar systems is used to investigate the circulation pattern response to the geometry of bar channel systems during a range of incident wave heights and directions. 2 bar types are assessed, including a bar trough, with a pronounced bar and deeper trough region onshore of the bar, and a terrace with a nearly flat region. The depth and width of the channel incising the bar trough or terrace bathymetry are varied, spanning a range representative of natural conditions. Small, medium, and large asymmetries in the bar height are introduced. Wave heights are varied from small, where the onset of breaking barely occurs at the bar crest, to large, where breaking occurs offshore of the channel. Wave angles are varied from shore normal to highly oblique at breaking. The model results and an analysis of momentum balances are used to develop a framework that classifies circulation patterns as a function of wave forcing and bathymetry. 3 results and discussion. 3.1 Simulated circulation patterns. For a symmetric channel with shore normal waves, a symmetric rip current jet and feeder current system forms Fig. 1 as. For weakly oblique waves, Rip current jets are shifted in the direction of the breaking wave-driven alongshore current and exit the surf zone at an oblique angle Fig. 1b and c. For more strongly oblique waves, a meandering alongshore current forms, not shown, with minimal offshore flow in the channel rather than a rip current jet. When the channel bathymetry has a moderate asymmetry, a circulation cell forms on the side of the channel with the shallower bar for cases with shore normal waves, Fig. 1d, or waves with mildly oblique angles towards the shallower side of the channel, Fig. 1f. For waves with obliquity away from the shallow side of the channel, Fig. 1e, and for waves of any direction with a larger bathymetric asymmetry, Fig. 1g, h and I. The resulting circulation is a meandering alongshore current paired with a circulation cell in the channel. Color contours of bathymetry, scale below, and modeled circulation, pattern arrows point in flow direction flow with length proportional to speed versus alongshore, north N at top, and cross-shore beach on left coordinate for shore normal column 1, oblique from S column 2, or oblique from N column 3 wave conditions, and a bar channel bathymetry with symmetric bar, row 1, asymmetric bar with 0.2 m shallower bar crest on S side, row 2. An asymmetric bar with 0.4 m shallower bar crest on S side, row 3. Modeled circulation patterns include a symmetric jet with feeder currents, an asymmetric jet pushed to the NB or SC edge of the channel, a fixed circulation cell on the shallower side of the channel, D, F, and a meandering alongshore current, G, H, I. 3.2 Momentum balances. Dominant terms in these balances have been described in prior work 1, 2, 8, and many others. Here, spatial patterns of these balances are investigated, identifying variations as a function of the suite of circulation response types. In addition, several approaches are used to develop frameworks to aid interpretation of these complex momentum balances. 3.3 Frameworks. The circulation response in the model is interpreted as the result of a competition between several processes, summarized with velocity scales derived from momentum balances. First, the average wave setup gradients between the channel and sides define a rip current velocity scale that is related to the wave forcing and water depths in the channel and on the bar crest 2s. Second, a breaking wave-driven alongshore current velocity scale is a function of wave height and angle, beach slope, and a drag coefficient 2. Third, if there is an asymmetry in the bathymetry, a pressure gradient-driven current results that scales with the wave setup difference from one side of the channel to the other, adapted from 2. Modeled and observed flow patterns are explained reasonably by the relative size of the rip current velocity scale with the wave-forced and pressure gradient-driven alongshore flow scales. Further work is needed to understand how wave-forced and pressure gradient-driven alongshore flows may act together, or in opposition to enhance or suppress rip currents. The relative importance of and interactions between these processes also are explored. For example, leading order momentum balances suggest that comparing the topographic radius of curvature with centrifugally stable hydrodynamic radii may help to understand when a feeder current or alongshore current turns to form a jet rather than continuing alongshore. Further work is needed to determine if this approach defines thresholds between the identified circulation pattern types. Additional studies may investigate the interplay of wave forcing and bathymetry with other factors controlling circulation, including offshore bathymetry, wind forcing, and shelf currents and stratification. This analysis is supported by the U.S. National Science Foundation, NSF. Field observations were supported by NSF, a National Security Science and Engineering Faculty Fellowship, a Bush Fellowship, and the Office of Naval Research. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1B T. Brander R. 2016, Rip Current Types, Circulation and Hazard. Earth, Rev 163, 121. Org 101016J20, 1609008. 2M, S. B. Warner J.C., N. 2017, Rip Currents and Alongshore Flows in Single Channels Dredged in the Surf Zone. J. Rays, Oceans 122-537993816. Org 10100220, 16JC0 12222. 3DF, B. S. 2024, The Roles of Bathymetry and Waves in Rip Channel Dynamics. J. Rays Earth Surf 129-1115. Org 1010292023, JF007389. 4 Morgan S.G., Shanks Al. Mac J.H., AJHM, F. 2018, Planktonic Subsidies to Surf Zone and Intertidal Communities. Rev Marine 10-345-369. Org 10-1146 Marine 0, 108-160-60514. 5M, SJNM, J 2023, Exchange of Plankton, Pollutants and Particles Across the Nearshore Region, Annual Reviews of Marine. Science 15-1136. Org 10-1146 Marine 032122, 115057. 6 RJ Al, 2014, Evaluation of Swimmer-Based Rip Current Escape Strategies. Hazard 71-3, 182-11846. Org 10-1007, S110690, 13099791. 7B, R. Brander R. T. B. 2016, Modeling the Alongshore Variability of Optimum Rip Current Escape Strategies on a Multiple Rip-Channeled Beach. Hazards 80, 11663-686. Org 10-1007, S11069, 15-21013. 8N. G. Warner J. M. 2012, Implementation of the Vortex Force Formalism in the Coupled Ocean-Atmosphere Wave Sediment Transport, COAWSD Modeling System for Inner Shelf and Surf Zone Applications. Ocean Model 40, 76595. Org 10-1016J20, 1201003. 9 Warner J. B. He R. J. 2010, Development of a Coupled Ocean-Atmosphere Wave Sediment Transport, COAWSD Modeling System. Ocean Model 30, 5323244. Org 10-1016J20, 100-7010. Forced versus free analysis of waves across an offshore reef on the coast of Oregon. Abstract. On the Oregon coast, IG waves can be especially energetic and therefore are an important component of many nearshore processes. Herein, we present results from a field experiment conducted at Beach on the central Oregon coast. A main goal of the field experiment was to characterize the IG transformation across an alongshore rock reef that lies approximately 1.5 offshore, including the relative contributions of forced versus free IG components. The data analyzed herein are from the cross-shore array of bottom-mounted pressure sensors deployed during the experiment during the fall of 2022. Results demonstrate, somewhat surprisingly, that for all sensors, both the bound and free IG components are strongly correlated with the local swell energy. In addition, the theoretical bound IG from nonlinear interactions agrees well with the measured bound IG energy extracted through a analysis. The theory agrees less well at the offshore gauge on top of the rock reef, potentially pointing to the increased importance of either IG directionality or IG reflection at the reef. Keywords. 1. Introduction. IG, waves are generally defined as waves at frequencies between 0.004 and 0.04 that are mainly generated by nonlinear wave-wave interactions in the C and swell bands. Initially, these bound, Ig waves are coupled to the wave group structure in the C swell band, AL. 1994-1995. However, at some point later in there, they are released during the process of short-wave shoaling, breaking, and dissipation. Released Ig waves and other Ig that may be locally directly generated by additional linear forcing mechanisms occurring at Ig time scales are termed free Ig. On the Pacific Northwest coast of the U.S., the total Ig energy is known to contribute significantly to the total wave spectral energy, with their relative contribution to water surface variance increasing in the very near shore and affecting both the maximum and total water levels. Some previous work that is particularly relevant here includes Al. 2015, who collected a valuable data set of Ig observations from a cross-shore array located just north of our field site, CR Fig. 1's. Their work demonstrated the influence of Ig energy on enduring energetic sea states. However, in their field deployment, all the sensors were placed shoreward of the steep, shore-parallel reef. Hence, they could not draw any conclusions about the effect of the reef on either Ig or shortwave transformation. Additionally, the early work of and Stewart, 1962, documented the nonlinear wave coupling theory, allowing calculations of the expected bound Ig. Al. 1992 provided an analysis of the various dependencies of the coupling coefficients, and Al. 1994-1995 example analyses of the contribution of bound versus free Ig on another West Coast beach. Pressure and wave buoy locations during the field experiment. SM denotes smart mooring pressure sensors that were integrated with the spotter wave buoys. A portion of the alongshore rock reef is marked with a black line, complete alongshore extent not shown. 2. Field experiment. The most relevant sensors for the work presented herein are the cross-shore array of RBR pressure sensors, with the most offshore one located on top of the reef, as shown in Fig. 1. They were deployed for about a month, starting from the middle of September, and recorded the pressure continuously at 16. The smart moorings were pressure sensors integrated into individual spotter buoys, so far ocean, which sampled at 2 in 15 min bursts with a 50% duty cycle. We will concentrate on the RBR solo data in the present work due to the high sampling rate and long data records, continuous sampling, which better enables the analysis. 3 results. Time series of Ig wave height Hg measured by bottom-mounted pressure sensors, RBR Solo 2, Smart Mooring 3. The observed bound Ig energy is extracted from the pressure records using analysis, e.g. and 1985. Figure 3 compares the total Ig energy with the bound Ig component computed from the short wave spectrum using the and Stewart theory, predicted bound, and the bound Ig extracted from the analysis, observed bound, for each solo sensor. The time series demonstrate very good agreement between the predicted and observed bound Ig, with the exception of the most offshore sensor, which was located atop the rock reef. 2 things important to note here are that 1. The predicted Ig calculation assumes unidirectionality, shore normal, in the Ig spectrum, and 2. The offshore slope of the rock reef is very steep, 1.5, and may therefore be very reflective to Ig Fig. 1. Time series of the total, bound, and free Ig. Black lines, total Ig energy, blue lines, observed bound Ig calculated from, and red lines, bound Ig energy predicted by LHS theory. Top panel is sensor on top of the reef, lower panels are increasingly located shoreward, compared to Fig. 1. Correlations between the bound and free Ig energies, with the sea and swell energy. 4. Summary. The results so far shed some light on the relative contributions of bound versus free Ig at this field site. For the most part, the LHS theory accurately predicts the bound IG in comparison that measured with analysis. Both the bound and free IG components appear to be correlated with the incoming swell energy Fig4. The alongshore reef seems to be clearly influencing the IG observed at the reef top. Some future work includes attempting a bound IG calculation that incorporates direction information in the short wave band collected by the spotter buoys. A more comprehensive analysis of the energy, flux balance, and exchanges of energy between the short wave and IG band, in both directions, and evidence of IG dissipation. Finally, this work is intended to inform methodologies for forecasting the IG climate-based global wave model information, e.g. Al. 2014. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: F.A.J. 2014, A Numerical Model for Free Waves, Definition and Validation at Regional and Global Scales. Ocean Model 77, May 2032. S. R.T. 1985, Observations of Shoaling Surface Gravity Waves. J. Fluid Mech 161, 425-448. J.W., K.L., J.E., R.T. 2015, Observations of an Energy Flux on a Low-Slope Beach with High-Energy Long-Period Ocean Swell. Race 42, 2299339941. THC, S, RT 1994 Frequency, 0.005005 Motions on the Shelf. Part I, Forced Waves. J 24917927. THC, S, RT, WC 1995. Frequency, 0.005005 Motions on the Shelf. Part II, Free Waves. J 25106311079. MS, Stewart R.W., 1962. Radiation Stress and Mass Transport in Surface Gravity, Waves with Application to Surf Beats. J Fluid Mech 13480-154. M, RT, RJ 1992 Bound Waves. J Rays 97 11-11453, 11469. KG, F. Jones CT, A 2019, Performance Characteristics of Spotter, a newly developed real-time wave measurement buoy. J Ocean Tech 36, 11271141. Spatial clustering of sea level across the Dutch coast. Abstract. Extreme sea level events pose significant risks to coastal regions, with non-tidal residuals, NTRs, being a primary driver in low-lying areas like the Netherlands, where shallow seas amplify their impact. This study investigates the spatial patterns of NTRs along the Dutch coast, using time series clustering on historical NTR. The design of hydraulic boundary conditions divides the Netherlands into 3 coastal regions. To evaluate whether this division sufficiently captures regional variability, 3 clustering scenarios, K3, K4, and K5, were explored. The analysis identified K5 as the optimal configuration based on the Davies index. This result emphasized the importance of fine-scale approaches to understanding regional spatial variations in NTR dynamics. Regional bathymetry and tide surge interactions were explored as drivers of these spatial patterns. Southern stations near river systems and deeper waters displayed characteristics distinct from northern stations in the sea, which are influenced by shallow tidal flats. Analysis of the M2 tidal constituent and the timing of NTR maxima relative to high tides underscored the role of tidal dynamics in shaping spatial clusters. Future research will focus on integrating temporal patterns and environmental drivers into clustering methodologies, providing deeper insights for coastal risk management and adaptation strategies. Keywords. 1. Introduction. Extreme sea level events, once occurring once per century, are projected to become annual at over half of all tide gauge locations by the end of the 21st century. 1. This rise poses significant risks to the environment and socioeconomic infrastructure, increasing susceptibility to recurrent coastal floods. To address these challenges, a deeper understanding of extreme sea level events and their dynamics is needed for effective adaptation measures and coastal flood risk management. With its low-lying coastal areas, the Netherlands is particularly vulnerable to coastal flooding too. This underscores the need for detailed analysis of extreme sea level events, including their non-tidal residual (NTR) components. Such events can exhibit non-uniform temporal and spatial patterns, clustering in certain regions and periods, thereby intensifying flood risks. While basin-scale studies of extreme sea levels in the North Sea exist 4, there is a gap in recognizing and analyzing the joint spatial and temporal characteristics of NTRs. The design of hydraulic boundary conditions divides the Netherlands into 3 coastal regions. 5. This study investigates spatial patterns of measured historical NTR to evaluate whether this division sufficiently captures spatial variability. This can advance best practices in local modeling, improve our ability to predict future extreme sea levels, and enhance stakeholders' capacity for risk management and decision-making in coastal areas. 2. Materials and methods. 2.1 Data. A map of the Dutch coast, showing the location of the 16 GSLA-3 stations used in the study, and b. the duration of the sea level records with frequency periods. 2.2 Data preprocessing and event definition. The observed total sea level was searched for outliers linearly to remove long-term trends caused by sea level rise, and then split into 2 components, the tidal component and the non-tidal residual NTR. The former was derived using harmonic tidal analysis 8, and the latter was calculated by removing the predicted tidal signal from the observed total sea level. The NTR thus includes water level variations caused by factors and wave effects, as well as the nonlinear interactions between them. Since the tidal phase can be affected by depth changes due to the surge, and vice versa, the NTR also includes the nonlinear effect of tide-surge interaction. The data remained in its original frequency, and any gaps were not filled. Events were identified using the peak over threshold (POT) method on NTR, with a 70th percentile threshold per station. An event was defined from the first threshold exceeding moment to the last, ensuring a 3-day gap for independence between subsequent events. The relatively low threshold allowed us to include less severe scenarios and enabled us to extract the time series of storm development rather than focusing solely on peak sea level magnitudes. This approach resulted in a total of 45,843 events across stations. 2.3 Spatial time series clustering. To analyze spatial patterns, we defined NTR events across the entire study area by grouping occurrences within a 2-day window. This approach resulted in 3,140 events along the Dutch coast between 1980 and July 2017. However, due to data gaps in the GAT-8 tide gauge from 5/17, 26/8, and 29/31, 2014, several events from that year were excluded. Ultimately, 3,129 NTR events were used for clustering analysis. One-time series extraction. For each event, the start time was the earliest occurrence across the coast, and the end time was the latest. NTR time series spanning this interval were extracted for each station. Time series extraction. For each event, the start time was the earliest occurrence across the coast, and the end time was the latest. NTR time series, spanning this interval, were extracted for each station. 2. Each time series was normalized to a time index ranging from 0 to 1, based on its duration in hours. Each time series was normalized to a time index ranging from 0 to 1, based on its duration in hours. 3. Regridding. Time series were regridded using linear interpolation to a uniform grid of 536 regular time steps, using the event with the largest time step and duration as a reference. Regridding. Time series were regridded using linear interpolation to a uniform grid of 536 regular time steps, using the event with the largest time step and duration as a reference. 4. Standardization. Time series were standardized to have a mean of 0 and a standard deviation of 1. Standardization. Time series were standardized to have a mean of 0 and a standard deviation of 1. 5. Concatenation. All time series per station were combined into a single dataset with 536 time steps, 3129 events, resulting in 1,677,144 features. Concatenation. All time series per station were combined into a single dataset with 536 time steps, 3129 events, resulting in 1,677,144 features. 6. Dimensionality reduction. Applying PCA to the features to reduce data dimensionality, retaining 99% of the variance. This reduced the number of features from 1,677,144 to only 14. Dimensionality reduction. Applying PCA to the features to reduce data dimensionality, retaining 99% of the variance. This reduced the number of features from 1,677,144 to only 14. 7. K-medians clustering. Clustering of the PCA-reduced dataset using 3 different numbers of clusters, K3, 4, and 5. K-medians clustering. Clustering of the PCA-reduced dataset using 3 different numbers of clusters, K3, 4, and 5. To evaluate different cluster number options, we employed the Davies index. Moreover, we used the hypothesis test to determine if the empirical distribution functions of the clusters were statistically different. 3. Results and discussion. Spatial clustering results for a K3, B, K4, and C, K5, with different symbols and representing tide gauge stations within each cluster. 3.1. Bathymetry characteristics and tide surge interactions. The spatial differences of clusters were analyzed with a focus on bathymetry and tide surge interactions. Figure 3 illustrates the bathymetry within a 3.33, 0.03 degrees, radius per station, including mean bathymetry values and a broader regional perspective. While individual stations within clusters do not show many similarities, regional patterns are evident. Southern stations are located near river systems and closer to deep waters, whereas northern stations in the sea are situated in shallow waters and tidal flats. Stations such as and Den Helder show similarities to the nearby western sea stations. This showed that regional patterns have a greater influence than localized conditions. Left, a close-up view showing the location and bathymetry of the 16 tide gauge stations, with the indicated mean bathymetry, Z, of the area. Right, the Dutch coast divided into 3 regions based on the K3 clustering, with tide gauge symbols, and representing the clusters for K5. A timing of NTR events maximum relative to the nearest high water tide, B, M2 phase, and C, amplitude in the North Sea, as derived from the FES 2014 Global Tide Dataset, Liard al. 2016. For conclusion. This study analyzed the spatial patterns of elevated non-tidal residuals, NTR, along the Dutch coast. A time series clustering technique was employed on NTR time series for 3 scenarios, K3, 4, and 5. The optimal number of clusters was determined to be K5, highlighting the importance of finer-scale approaches for understanding regional extremes. Regional bathymetry and tide surge interactions emerged as important factors, shaping the observed NTR spatial patterns. For example, southern stations near river systems and deeper waters exhibited distinct characteristics compared to northern stations in the sea. While this study focused on spatial clustering, the integration of temporal patterns is essential for comprehensive coastal management. Thus, future work will explore joint patterns of sea level to inform more effective coastal management strategies. Additionally, future research should analyze other environmental drivers as well, such as wind and storm tracks. Drivers could also be incorporated into clustering methodologies to better capture the nuanced temporal patterns. This research was supported by the Dutch Research Council, NWO, OCNWM 21109, Chance, Climate Seahenge Impacts on Extreme Sea Levels in Coastal Waters, Project. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 IPCC 2021, Climate Change 2021, The Physical Science Basis. Contribution of Working Group I to the 6th Assessment Report of the Intergovernmental Panel on Climate Change. Cambridge University Press. 2W 2013 Coasts, the High-Risk Areas of the World. Hazard 66 1363 1382. 3CF, Van den Brink HW 2023. Update Van Extreme, N Wind Op Basis Van N. KNMI number, TR406. 4A, N, L. Al, 2018. Identification of extreme storm surges with high impact potential along the German North Sea coastline. Ocean Dine 6813 711382. 5J, Beckers J, C, 2011. A probabilistic model for the determination of hydraulic boundary conditions in a dynamic coastal system. Coastal Proc 1. 6 ID Al, 2021. GESLA version 3. A major update to the global higher frequency sea level dataset. Data J1032 93314. 7E R S J 2005. NHUN Report AGI 2005 GSMH 012. 8 Bowman W 2014 UTide Python package. 9M JAA S Morales O 2024 Storm surge from historical observations of sea level along the Dutch coast in the North Sea. Submitted. Coastal Dynamics 2025, Carlos. Advancing Compound Coastal Flood Modeling on Southern, a Hybrid Stochastic Approach. Abstract. Sea level rise and changing patterns of storminess associated with climate change are expected to increase the frequency and severity of compound coastal flooding events, posing significant challenges to coastal communities in enhancing preparedness and adaptation strategies. This work presents a hybrid stochastic approach for the probabilistic assessment of compound coastal flooding. The stochastic climate emulator Tesla is employed to generate synthetic time series of oceanographic and hydrologic conditions, incorporating oceanographic drivers such as sea level anomalies, tropical cyclones, storm surge, tides, wind waves, and precipitation. These time series are downscaled using a hybrid statistical numerical framework that integrates surrogate models of high-fidelity hydrodynamic simulators, e.g. Delft 3D, Swan Swash SFINCS. The framework is applied to to simulate flood exposure under present climate, as well as various sea level rise scenarios and climate projections. The framework is designed to support decision-making processes by facilitating the participatory development of dynamic adaptation pathways. By allowing for rapid evaluation of flood risks, the approach provides valuable insights for building resilient adaptation strategies for vulnerable coastal communities. Keywords. 1. Introduction. The low-lying coastal communities on islands in the Indo-Pacific region face unprecedented challenges due to projected sea level rise, SLR, and other impacts associated with climate change. These islands are particularly susceptible to compound coastal flooding driven by high water levels and heavy rainfall induced by a combination of oceanographic drivers such as sea level anomalies, i.e., those driven by the Southern Oscillation ENSO, tropical cyclones, TCs, storm surge, tides, and wind waves. Understanding the intricate interplay among these factors and accurately predicting extreme events are essential to reduce coastal community vulnerability and for exploration of the efficacy of dynamic adaptation pathways. Here, we utilize the stochastic climate emulator, Tesla 1, to generate realistic synthetic time series of oceanographic and hydrologic boundary conditions. These time series then serve as inputs for a sequence of surrogate models that integrate the combined impact of the typical climatology as well as extreme events such as TCs. 2 methods. 2.1 Stochastic Climate Emulator. This work extends the use of the time-varying emulator for short and long-term analysis, Tesla 1, to generate stochastic realizations of offshore total water levels and spatially varying precipitation events. Following a synoptic weather classification, the mean sea level pressure, MSLP, and sea level pressure gradient, SLPG, fields define a daily predictor for waves. These large-scale fields are defined based on the ESTELA method, 4 to capture the source and travel time of the wave energy reaching the area. For the prediction of the storm surge and precipitation, a local area surrounding the study site, 2x2, is used over the MSLP, SLPG, and 500 HPA height fields. The annual variability is captured by the ENSO and Madden-Julian oscillation modes, respectively. These predictor variables at both spatial scales, basin-wide and local, are statistically correlated and used to fit in logistic regression, ALR, of weather types. As a result, Tesla can provide thousands of simulations of hundreds of years of plausible chronicle conditions, i.e., offshore drivers of total water levels and precipitation that can drive compound coastal flooding. These synthetic time series are then downscaled using an efficient hybrid statistical numerical modeling framework. 2.2 Hybrid statistical numerical downscaling. Workflow for downscaling fluvial, pluvial, and driven processes from regional to local and high-resolution scale. The sequence of hybrid models used in this study simulates wave transformation at regional scale to high-resolution estimates of inland flooding. For the TC climatology, SHI-9, a surrogate model of SWAN-2 is used to obtain directional wave spectra estimates from TC tracks. The wind setup induced by the given TC track is computed with GreenSurge-6, a surrogate model of Delft 3D4 based on a summation of Green's functions of the wind forcing. The resulting storm surge is derived by combining the wind setup with pressure-induced sea level changes, computed using the inverse barometer effect. For the regular wave climate at local scale, the additive hybrid model, BinWaves 3, based on SWAN simulations, is used for downscaling the offshore wave spectra to the spatially varying nearshore conditions. Surf zone hydrodynamics are further downscaled along 1D cross-shore profiles across the shoreline using SWASH 8, based on the numerical model SWASH 10. To simulate local-scale hydrological impacts, precipitation patterns generated by Tesla are downscaled into runoff using runoff, a model that relies on a library of SFINCS5 simulations to explore every combination of the temporal and spatial characteristics of the storms. Finally, flood, a surrogate model of SFINCS, is used to compute high-resolution overland flow, capturing the combined effects of fluvial, pluvial, and wave-driven processes. 3. Application to Southern. The robust hybrid framework is demonstrated on Southern, USA Fig. 1.2, although it can be of great interest to any coastal community. The computationally efficient framework enables the stochastic simulation of synthetic time series under several SLR scenarios for multiple time horizons. Moreover, changes in the future probability of weather patterns are identified using Intergovernmental Panel on Climate Change AR6 Global Climate Model projections. As a result, the methodology makes it possible to assess current and future flooding exposure within minutes. Conceptual for linking a climate-based emulator with a sequence of hybrid models to produce synthetic time series of inland flooding. The authors acknowledge support from the U.S. Department of Defense's Multi-University Research Initiative Grant 2,033,958, N000-1423128862, and Environmental Science and Technology Certification Program, Grant 2,035,806, W912HQ 24C001. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Anderson D. A. L. J. A. F. J. P. 2019. Time-varying emulator for short and long-term analysis of coastal flood hazard potential. J. Rays. Oceans 124-12-920-99234. Org 10-10-2920-19 JC0 15312. 2. N. RC. LH. A third-generation wave model for coastal regions. 1. Model description and validation. J. Rays. 104C4, 7649-7666, 1999. Org 10-10-2998, JC0 2622. 3L FJ ADC R 2024. An additive hybrid method to downscale directional wave spectra to nearshore areas. Ocean Model 189-10-2346. Org 10-10-16 JOCMOD 202-410-2346. 4HL. Validation Document Delft 3D Flow, WL Delft Hydraulics Report X0356, 2007. Index Option Com and Task Doc Download and Guide 217. 5T Van M. K. Van A. Modeling compound flooding in coastal systems using a computationally efficient reduced physics solver, including fluvial, pluvial, tidal, wind, and wave-driven processes. Coastal 163, 103,796, 2021. ISSN 378-3839, Org 10-10-16J2020, 103796. 6B L S V F. Green Surge, an efficient additive model for predicting storm surge induced by tropical cyclones. Under review at Coastal Engineering, submitted. 7J FJ M Al 2014, ESDLA, a method for evaluating the source and travel time of the wave energy reaching a local area. Ocean Dyne 64, 118-11191. Org 101007, S102360, 1407407. 8A LB, FJ 2024 SWASH, a hybrid model for nearshore wave processes. Ocean 290, 1116419. Org 1010, 16J Oceanian G 2023, 116419. 9 Vaniso, LB.R, FJ 2024 S, a stop-motion hybrid model to predict tropical cyclone-induced waves. Ocean Model 188, 102341. Org 1010, 16J OCMOD 20241, 02341. 10M, Stelling G, Smit P, 2011 SWASH, an operational public domain code for simulating wave fields and rapidly varied flows in coastal waters. Coast 5810-992-1012. Org 1010, 16J COSTLNG 20-1105015. Analytical prediction of wave dissipation, coefficient in vegetation. Abstract. The predictions of wave attenuation from vegetation are associated with considerable uncertainty in practical engineering, because practitioners often must select dissipation coefficients from empirical datasets and extrapolate from small-scale tests. The present work proposes an analytically based method to evaluate the dissipation coefficient for spectral energy conservation models based on fixed hydrodynamic force coefficients, invariant of sea state and vegetation characteristics. The approach is applied to data from 2 experimental campaigns, with the results demonstrating considerable success and potential application for the proposed method. The method will enable practitioners to explore and apply an alternative and more robust approach compared to the conventional use of empirical datasets. Using fixed hydrodynamic force coefficients, whereby greater accuracy and reliability is achieved, will enable practitioners to more effectively and directly compare various layouts of natural and nature-based solutions using quantitative methods. Future work includes extension to an irregular wave formalism and application to field data. Keywords. 1. Introduction. The robust prediction of wave attenuation processes in submerged and emergent marine vegetations are of considerable importance for the quantification of natural and nature-based solutions, e.g., nature restoration, incorporating a reduction in flood risks. For spectral wave modeling in vegetation, the vegetation characteristics and a dissipation coefficient are required as input for spectral dissipation models for arbitrary spectra, e.g. Suzuki al. 2012 al. 2019. Here, the closure coefficient in the dissipation model is termed the dissipation coefficient, contrary to normal terminology in the literature. This is to distinguish it from the hydrodynamic drag coefficient, CD, that is considered a material property for the stem, to be introduced below. The value of, as used in modeling, constitutes a significant factor of uncertainty. Most empirical works recall that previous works term this a drag coefficient, as a function of this number, or the Carpenter, KC number, so becomes a function of the hydrodynamic loading. The work by and Smith, 2014, indicated that also the stem length to water depth ratio must somehow be accounted for to reduce scatter in the data. Finally, empirical works have shown that follows different for different vegetation densities when plotted against KC, al. 2014. A further complication is that depends on the fitting function, e.g., using either al. 1984 or and 2004 for the fitting, though those values of may not be transferable to dissipation models for arbitrary spectra, see analysis in al. 2019. Finally, is measured as a global attenuation parameter across the length of the canopy, while local values are needed for general-purpose spectral wave models. The non-transferability of its non-locality, its sea state dependence, and its scatter due to vegetation characteristics make it extremely challenging for a practitioner to assign suitable values of InDesign studies. The present work will propose a novel approach in which the user specifies hydrodynamic force coefficient, drag, and inertia, and the model evaluates the appropriate as a function of sea state, water depth, and stem characteristics. The present work is restricted to a derivation for regular waves, while ongoing research extends the theoretical approach to arbitrary sea states. 2. Model formulation. 2.1 Wave transformation model. 2.2 Closure for dissipation by vegetation. The benefit of the proposed reformulation is that a practitioner can assign material properties, hydrodynamic drag coefficients, and vegetation characteristics whereafter U3 is evaluated instead of inputting the variability in as a function of the spectral wave solution across space, sea states, and simulation period. This new approach results in an increased robustness and reduced sensitivity to subjective assessments by the practitioner as long as U3 can be evaluated on the fly. Here, it is proposed to evaluate U3 using the linearized wave theories by 2016 and in fall 2022 for submerged and emergent vegetation, respectively. The theories predict the in-canopy velocity profile, so 2 and 3 can be evaluated analytically for regular waves. The theory requires that both CD and the inertia coefficient be given, since inertia also results in an in-canopy velocity reduction, CEG. Low ALD. 2005. The present approach can be extended to conditions with vegetation flexibility through the effective length concept. However, the cases available with regular wave conditions were such that the stems were either rigid, or the hydrodynamic conditions so mild that flexible strips behaved rigidly. Flexibility will be considered in a future extension to irregular wave conditions and application to field cases. The velocity profiles with and without vegetation for a submerged canopy. Wave periods of 4s left and 7s right. U is the ratio of blue to red lines inside the canopy. The proposed model. 3. Allows for an on-the-fly evaluation of needed by the wave transformation model, with the dissipation by vegetation as in 1's. 3 results. Predictive capabilities are evaluated for 2 experimental campaigns, as reported in SECS 3.1 and 3.2. Details of the experimental campaigns are below, but first it is stressed that a constant set of hydrodynamic force coefficients of CD20 and 0.5 was applied for all simulations, a total of 62 regular wave cases. 3.1 Validation against and fall 2022. Comparison of experiments and numerical wave attenuation for the and fall 2022 experimental campaign. Top panel T15S, bottom panel T17S32 validation against AL. 2011. ALD. 2011 reported on a laboratory campaign with wave attenuation through flexible strips of vegetation. The individual strips had a length of 0.1 m, a width of 3 and a thickness of 0.7. The canopy was placed on a horizontal plateau. It was 9 m long, and it consisted of 40,000 strips M2. A total of 20 different wave conditions, periods from 1.25s to 2.5s, and wave heights from 0.05 m to 0.13 m, for each of the 3 water depths of 0.3 m, 0.5 m, and 0.8 m was simulated. The wave attenuation for 4 wave conditions in 2 water depths was depicted in AL. 2011. The wave attenuation across the canopy is reproduced and depicted in Fig. 3. While some scatter is seen, the wave attenuation for all 8 cases was accurately captured at the end of the canopy. The wave height was measured at the front of the canopy, at 2 locations within the canopy, and at the end of the canopy. The experimental data was applied to evaluate by assuming an exponential wave height decay. An identical data processing procedure was applied to the numerical results, and the predicted values of are provided in the legend in Fig. 3, which shows that ranges from 0.15 to 0.46, a factor of 3. For the 8 cases. This is a helpful illustration of the challenge faced by practitioners to assign realistic values of during model setup. Comparison of the experimental wave attenuation markers and the numerical predictions for a single set of hydrodynamic force coefficients. Predicted stated in the legend. Comparison of numerical predictions for an experimental data. Predictor by Al. 2013, as provided in the text. The accuracy of the predictions in Fig. 4 suggests the considerable strength of the present approach, because it allows to extrapolate from small-scale laboratory experiments to field conditions. It is a common approach to propose prediction formulas for as a power to Kc for small values of Kc at laboratory scale, hence the extrapolation to large Kc, i.e. field conditions, is associated with considerable uncertainty. This uncertainty is mitigated by the analytical approach too. 4 conclusions. A novel approach was proposed to predict, based on local hydrodynamic conditions and vegetation characteristics, which significantly increases the robustness of wave attenuation modeling in vegetation. The robustness is improved by an on-the-fly evaluation of the interaction between waves and vegetation, such that a practitioner may simply specify constant hydrodynamic force coefficients, material properties, instead of a variable dissipation coefficient, solution dependent. This is an important step to improved robustness in engineering design of natural and nature-based solutions. The lead author is thankful for funding from DHI's research contract with the Danish Ministry of Higher Education and Science, contract 52550005B. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: Anderson M.E., Smith J.M., 2014, Wave Attenuation by Flexible, Idealized Salt Marsh Vegetation. Coast 838292. R.A., J.T., P.A., Wave Diffraction Due to Areas of Energy Dissipation. J. Waterway, Port, Coastal, and Ocean Engineering ASCE 110-1, 6779, 1984. NG 2016, Wave Averaged Properties in a Submerged Canopy, Energy Density, Energy Flux, Radiation Stresses, and Stokes Drift. Coast 1175769. NG Fall BC, Vanna DA 2019, A Frequency Distributed Dissipation Model for Canopies. Coast 15135-146. NG Fall BC 2022, Wave Averaged Properties for Non-Breaking Waves in a Canopy, Viscous Boundary Layer and Vertical Shear Stress Distribution. Coast 174-104117. Low RJ JR, SG 2005, Oscillatory Flow Through Submerged Canopies, 1. Velocity Structure. J-Rays 110, C10016. FJ, IJ 2004, An Empirical Model to Estimate the Propagation of Random Breaking and Waves over Vegetation Fields. Coast 51-103-118. ONG, Van AD, UD T, 2023, Linear and Nonlinear Frequency Domain Modeling of Oscillatory Flow over Submerged Canopies. J-Ray 615668-685. Y. Ren D.G., Wu W., 2014. Experimental Investigation of Wave Attenuation Through Model and Live Vegetation. J. Port Coast Ocean, 1404040-14019. JF v. Memo CD, 2011, Wave Attenuation Due to Meadows. J. Rays 4945-03514. Suzuki T. M. Berger B. MC. S. 2012. Wave Dissipation by Vegetation with Layer Schematization in Swan. Coast 596471. Nearshore Wave-Induced Current in the Laboratory. Abstract. The study of nearshore wave-induced currents, which play a critical role in marine transport, has motivated numerous laboratory experiments, and yet, the understanding of cross-shore wave-induced currents under controlled laboratory conditions remains incomplete. For the first time, 3D particle tracking is applied in a laboratory flume to measure wave-induced currents in front of a slope under 5 different regular wave conditions. The wave-induced velocity profiles evolve over time, reaching a quasi-equilibrium after approximately 1 hour. In most cases, the observed profiles do not align with the theoretical Stokes or conduction solutions. The surface drift is consistently smaller than theoretically predicted, and in some cases even negative, indicating the presence of a strong mean return current in the upper portion of the water column. The observed patterns cannot be explained solely by the relative water depth and wave steepness Ka, leading to the hypothesis that convection processes contribute to these discrepancies. Further investigation of visually observed coherent convective structures, such as vortex trains, will be undertaken. Keywords. 1. Introduction. In the nearshore zone, extending from the shoreline to a few offshore, waves propagating at the ocean's surface generate currents that play an important role in marine transport. Modeling marine transport in this area is essential for environmental sciences, but it necessitates a thorough understanding of wave-induced currents throughout the water column. Most existing models have been calibrated using laboratory flume experiments, which aim to investigate the relationship between wave forcing conditions and the resulting current profiles in both deep and intermediate water depths, in front of and over a slope. Despite over 40 research studies on this topic, no clear conclusions can be drawn, and the understanding of cross-shore wave-induced currents in laboratory conditions, in front of and over a slope, remains incomplete. The mean velocity UE profile varies significantly across studies. We can distinguish 3 types of a depth uniform profile 1, a sheared profile 2, and an anti-Stokes profile, i.e. the velocity equals in magnitude, but opposite in direction to the Stokes drift 3. These discrepancies remain unexplained, leading to the development of empirical models that are limited to representing specific conditions tied to particular laboratory experimental setups. A comprehensive literature review of existing experiments does not reveal any new relationships or explanations beyond those already published. However, one potential source of the observed discrepancies can be identified in the measurement methods used. In the shoaling zone, only 5 out of 23 studies recorded velocity, with 4 of these employing visual techniques, e.g. dye, which are nowadays considered relatively imprecise, given the developments in measurement technology. In studies that measured velocity, accurate quantification of flow has only been performed using point probe measurement techniques, such as laser, LDV. As a result, a complete velocity profile is effectively an artificial representation, constructed over time, unless perfect reproducibility is assumed and measurements are taken at the exact same time over multiple repetitions, which is rarely the case. However, with the advancement of new measurement technologies over recent decades, these limitations can be mitigated, significantly enhancing our ability to track particle trajectories accurately and investigate Stokes drift and mean current profiles for. In this study, a laboratory experiment is conducted in which, for the first time, 3D particle tracking, PTV, is applied to investigate wave-induced currents near the shoaling zone. The goal is to compare wave-induced current profile under different hydrodynamic forcing to compare with literature and theoretical solutions. 2. Methodology. Experimental setup. The measurement volume is 50 x 30 x 15, length, height, depth. Optical access was provided via the glass sidewalls and a bottom glass window positioned 1 meter offshore of the beach toe. Fluid velocity measurements were obtained using a 3D particle tracking (PTV) system from La Vision, which comprises a mini shaker apparatus, a box containing 4 fixed-angle cameras capturing images at 100, 2 LED light boxes, and the Shake the Box data processing system. The 3D PTV technique involves illuminating a fluid volume seeded with neutrally buoyant particles and tracking these particles in space and time throughout the measurement volume. Additionally, an overhead camera was positioned 3.3 m above the still water level to track form plastic spheres floating on the surface. Wave conditions and theoretical Stokes drift, USD at the surface, Z0. H is the wave height, T the wave period, Ka the wave steepness, the relative water depth, the number and Re the wave number. The water depth H0 35 m for all conditions. Wave HM TS Ka Vert Re 0S W1 0.1 1.8 0.1 0.71 22 12,500 3.3 W2 0.13 1.4 0.18 0.96 16 22,300 7.3 W3 0.06 1.2 0.1 1.18 5 5,000 2 W4 0.07 1.4 0.09 0.96 8 6,500 2.1 W5 0.04 0.85 0.11 2.02 1.1 711 1.8 Note that the mean velocity, UL, where the means wave averaged, of a fluid parcel is the sum of the Stokes drift, USD, and the mean velocity, UE, of the fluid measured at a fixed spatial location 5. 3 results. 3.1 Profile evolution over time. Mean velocity measurements through the water column for W4 at T5, 10, 15, 30, 60, and 120 min after the beginning of wave generation. The legend is shown in Fig. 3. Figure 2 illustrates the evolution of the velocity profile over time for W4, reaching near equilibrium after 30 min. While the measured velocity profile closely aligns with the conduction solution at 15 min, it stabilizes at a profile not represented by either theoretical solution. A similar pattern is observed for other wave conditions, with quasi-equilibrium always reached after 60 min. A similar amount of time to reach such quasi-equilibrium was reported by N7 and al. 8 for similar laboratory scales with a beach slope of 110 and 120, respectively. The surface drift deviates significantly from theory at equilibrium, initially approximating the Stokes solution at T5 min, but decreasing over time, sometimes becoming negative. Since the Stokes solution is the sum of the Stokes drift and a negative depth uniform mean return current to ensure a zero depth integrated volume flux, the smaller surface drift suggests a sheared mean return current with maximum magnitude in the upper part of the water column. Only in deeper water W5 exhibits a surface drift matching the Stokes solution, though the rest of the profile differs notably. Fig. 3. 3.2 Profile as a function of n-Ka. Figure 3 compares the profiles at equilibrium for all wave conditions. Comparing wave conditions with similar Ka 0.1, but different W1, W3, W4 and W5, the conduction solution seems to align with measurements for W1, while neither solution describes measurements for the other wave conditions. This is in contradiction with the literature, from which it can be concluded that the velocity profile tends towards the Stokes solution for 1.8 and towards the conduction solution for 0.71878. It nonetheless seems that the profiles become less and less sheared as increases. For wave conditions W4 and W2, which have the same but different Ka, both profiles are similarly sheared, albeit with different magnitudes. They both experience a strong mean return current in the upper layer, which significantly reduces the surface drift compared to the Stokes drift, Table 1. We have not considered a large enough number of Ka values to draw general conclusions. Nonetheless, Al. 9 and N7 found that for both small wave steepness Ka and relative water depth conditions, the profile gradually changes into a shape where a backflow occurs at the surface. Although a similar trend is observed here, the differences cannot be explained by the influence of the n-Ka alone. Thus, we expect that other processes not accounted for in the Stokes and conduction solution must be involved. Mean velocity profile at T120 min for all wave conditions. W1, W3, W4 and W5 have a similar wave steepness Ka 0.1 Table 1. W2 and W4 have the same 0.96. For conclusion. For the first time, 3D particle tracking, PTV, was employed to acquire high-resolution wave-induced current velocity profiles in front of a slope in a laboratory setup. This direct measurement technique allows for unprecedented spatial and temporal resolution flow measurements, circumventing the technical limitations inherent in methods such as laser, LDV. The time required for the velocity profile to reach a quasi-equilibrium state was observed to be 60 min at the experimental scale. Although the equilibrium time has been documented in several studies, it is often overlooked, resulting in the publication of unstable profiles that may contribute to discrepancies in the existing literature. It is critical for laboratory data used in model calibration to be obtained after the equilibrium has reached, as most numerical models generate equilibrium profiles 10. With the exception of W1, which aligns with the conduction solution at equilibrium, none of the measured profiles correspond to either of the Stokes or conduction theoretical solutions. Note that the conduction solution is theoretically not applicable for steep waves, while the Stokes solution is only valid for deep water, where a bottom boundary layer is absent. The three distinct types of the mean return profile were observed at various points during the experiment, suggesting their occurrence may not laboratory dependent. However, contrary to the findings reported in the literature, no straightforward relationship with n-Ka could be established over the range of conditions tested. This indicates that other factors, including processes such as convection, must be considered. Coherent vortex structures, visually observed during the experiment and similar to those described by Al. 11, which are a function of the parameters Ka and beach slope, could contribute to some of the observed differences. Further analysis will be conducted to explore these interactions. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Gru J. 2016. Experimental particle paths and drift velocity in steep waves at finite water depth. J. Fluid 810. 2 Dyke PPG, Barstow SF 1981, Wave-Induced Mass Transport, Theory and Experiment. J. Rays 19-289-106. 3 SG, EA, HM, J. Ties L 2007, Laboratory Observations of Mean Flows Under Surface Gravity Waves. J. Fluid Mech 573, 130-1147. 4 Van Den T.S., C. R. A. Taylor Ph. 2019, Experimental Study of Particle Trajectories Below Deepwater Surface Gravity Wave Groups. J. Fluid Mech 879, 168-186. 5D. M. 1978, An Exact Theory of Nonlinear Waves on a Mean Flow. J. Fluid 89, 609-646, 12. 6 SM 1953, Mass Transport in Water Waves. Philtrans Roy Soch London, A 245-903, 76-11-7618. 7 RCH, JDC, 1957, An Experimental Investigation of Drift Profiles in a Closed Channel. Proc VI Conf on Coastal Chap 10 171, 193. 8 CC, PLF Carter TG, 1972, Mass Transport in Water Waves. Report No. 146, Massachusetts Institute of Technology. 9U, JPT, T, 1974, Mass Transport in Gravity Waves on a Sloping Bottom. Proceedings of the International Conference in Coastal Engineering. 10 BE, Dr. 2018, on the overproduction of turbulence beneath surface waves in averaged Stokes models. J. Fluid Mech 853, 419-460. 11N, K, Y 1994, The Offshore Vortex Train. J. Fluid Mech 276, 113-124. Evaluation of clustering techniques for revealing dependence between wind speed and surge height. Abstract. Extreme storms over the North Sea drive coastal flood risk in the Netherlands, causing high waves and extreme sea levels. Designing flood defenses requires accurate statistical extrapolation of hydraulic load conditions with return periods of 1,000 years or more. This is a challenging task, given limited observational data. This study uses a large, simulated dataset, 9000 years, to explore the statistical dependence between extreme wind speed U and surge height S storms were clustered using several techniques. Self-organizing maps, SOM, effectively captured physical relationships, such as the influence of wind direction and tidal offset on storm dynamics. However, variability in statistical dependence between U and S for different clusters was better represented using manual clusters. Copula models were fitted to the cluster data, with the BB8 copula outperforming others. This study illustrates the potential of machine learning to identify patterns in large datasets, while emphasizing the relevance of manual clustering approaches for revealing nuanced statistical dependencies critical to flood risk assessment. Keywords. 1. Introduction. Extreme storms above the North Sea are the main driver of coastal flood risk in the Netherlands, resulting in high waves and extreme sea levels due to storm surge. To mitigate this risk, flood defenses are designed to sustain extreme hydraulic load conditions, defined in terms of water levels and wave heights with return periods of 1,000 years or more. 1. Although observations span approximately 100 years, the derivation of these design conditions relies on statistical extrapolation, introducing uncertainties due to limited data length relative to the target return periods, data inhomogeneities, and missing storm observations too. Recent advances in numerical weather prediction have enabled reanalysis and datasets to emerge as a standard alternative to observational data 3. However, 1,000-year and beyond return period estimates using probabilistic models fitted with approximately 75 years of reanalysis might still introduce uncertainty when natural variability is large 3. Along improved atmospheric reanalysis 4, short, mid, and recently long-range forecasting have been made available, such as the Seasonal Forecast System, SEAS-5, by the European Centre for Medium-Range Weather Forecasts, ECMWF-5. Recently, the Royal Dutch Institute, KNMI, has produced a large dataset of simulated sea levels, using the DCSM model with wind data from SEAS-5-6. Effectively, approximately 9,000 years of simulated weather and storm surge are now available, allowing the derivation of higher precision estimates for the return levels of extreme wind speed and sea levels. Moreover, this large dataset enables us to study other storm characteristics and mutual correlations in more detail. The aim of this research is to study the statistical dependence between extreme wind speed and surge height, using the large dataset by KNMI and applying copula models. The outcomes are comprehensive dependency structures, conditioned to environmental, causal, and consequential aspects of storms, which is achieved by clustering storms, which is important for modeling hydraulic loads in the design of coastal infrastructure. 2 Data and methods. The dataset by KNMI, 6, contains simulated sea level time series from the 5 Model 7, forced with wind fields from SEAS-5-5. The so-called Dutch Continental Shelf Model, DCSM, is a numerical model that solves the two-dimensional shallow water equations, which is also used for operational forecasting along the Dutch coast. The 5 model is run with the 6 hourly mean sea level pressure and wind stress from each SEAS-5 ensemble member as input, resulting in sea levels in the North Sea with a 10 min resolution 7. To prevent mutual dependence among ensemble members, the first month of each ensemble is excluded. From a statistical perspective, each ensemble member from SEAS-5 represents a possible climate scenario, enabling their combination into a single, extensive dataset equivalent to approximately 9,000 years of data. In past years, KNMI has performed numerous validations of the dataset, using various DCSM versions and observational data. More details can be found in 6.8. 2.1 Storm Selection and The first step is to select extreme events from the dataset of simulated wind and sea levels. For this study, 6 locations along the Dutch coast were selected. Sea level time series were extracted from the closest 5 output grid cell, and wind data from nearby SEAS-5 grid cells, as shown in Fig. 1s. Since wind speed is one of the main drivers of extreme sea levels, storms are selected using a peaks-over threshold based on wind speed. The threshold is defined conditional on the wind direction during the peak wind speed, such that 9,000 storms were selected for each of the 16 wind directions, per location. This roughly corresponds to storm events with a return period of 1 year, given the wind direction. Map of locations, an example of storm event B, including definitions of features. 2.2 Clustering. The next step is to cluster the selected 9,000 storm events to identify different storm types. 3-vector quantization methods, the self-organizing maps, SOM-9, the K-means algorithm, KMA, based on storm features and KMA based on the full-time evolutions 10, were compared with a manual clustering based on storm features. This manuscript focuses on results from SOM. The SOM algorithm was performed on a hexagonal lattice, and the initialization vector is determined using the maximum dissimilarity algorithm, MDA 11. The 9 storm features, as defined in Fig. 1, were normalized and weighted based on expert judgment. An evaluation of the inter- and cluster variability revealed that 196 clusters were a suitable choice. The SOM identifies neurons. Each neuron holds adjacent data we define as clusters. 2.3 Statistical dependence. For each cluster, the statistical dependence between U and S is evaluated. First, the pairs are translated to uniform space using the empirical cumulative distribution function, CDF. Then the following copula models are fitted to the data: the student, Clayton, Frank, Joe, BB1, BB6, BB7, and BB8 copula. The goodness of fit is evaluated using the criterion SM12. 3 results. Resulting feature values for each nodes in a 14x14 grid from the SOM algorithm for. Each plot represents one of the 9 features, and the color indicates the feature value. Pair plots in the standard normal space for 8 example nodes from the SOM results for. This correlation coefficient is indicated in each corner. Performance of various copula models fitted to the data corresponding to 8 example nodes. Expressed by SM, the squares indicate the copula model that best fits the data. For discussion, conclusions, and future work. Figures 3 and 4 show no clear link between specific cluster characteristics and the statistical dependence between U and S. In contrast, manual clustering reveals more variability, with some clusters showing strong upper tail dependence, 0.6, and others weak dependence, alongside clearer differences in copula model performance. However, only 8 clusters were evaluated from the SOM algorithm. To fully assess the capability of SOM to capture variations in statistical dependence, the semi-correlations should be evaluated for all 196 clusters to identify potential patterns and relationships with specific features. This study demonstrates how machine learning techniques, such as self-organizing maps, SOM, can potentially contribute to effectively identifying patterns in large datasets, revealing key physical relationships in storm dynamics. At the same time, the findings highlight the ability of manual clustering approaches for capturing nuanced statistical dependencies. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 SN, T, 2015, Developments in Levee Reliability and Flood Risk Analysis in the Netherlands. Geotechnical Safety and Risk v. 5060. iOS Press. 2 ID Al, 2023, GESLA version 3. A major update to the global higher frequency sea level dataset. Geoscience Data Journal 10.3, 293 314. 3P Thorpe A. G. 2015. The Quiet Revolution of Numerical Weather Prediction. Nature 525, 4755. 4H Al. 2020. The Era 5 Global Reanalysis. QJ R. Soch. 146 730 1999 2049. 5 ECMWF, SEAS 5 User Guide 2021. 6 CF, Van den Brink HW 2024, An Appraisal of the Value of Simulated Weather Data for Quantifying Coastal Flood Hazard in the Netherlands. Preprint. 7H, H. M. 1995, The Dutch Continental Shelf Model. Coast Stud 9 425 467. 8 Van den Brink HW 2020, Het van ECMWF, Het van Extreme. KNMI. 9T 2001, Self-Organizing Maps. Springer Series in Information Sciences. 30. 10 SB, 1982, least squares quantization in PCM. IEE Trans, Theory 28-129-137. 11 Camus P. F.J. Medina R. A.S., 2011, Analysis of Clustering and Selection Algorithms for the Study of Multivariate Wave Climate. Coast 58-6-453-462. 12 C. B. D. 2009, Goodness of Fit Tests for Copulas, a Review and a Power Study. Insurance Math, 44-199-213. Parallel Computing, Using Multi-Block Grids, for Hydrodynamic and Transport Simulation in Coastal Areas. Abstract. The curvilinear hydrodynamic 3D with vertical sigma coordinate, CH3DS, model developed by Sheng, 1986, is routinely applied in 3D hydrodynamic and water quality modeling studies at the Engineering Research and Development Center, ERDC, Mississippi. Recent model improvements include the spatially and temporally varying wind and wave radiation stress gradient forcing. The practical applications of the original single-block version of CH3DS, which include the aforementioned model improvements, have been limited to small computational domains and short simulation time periods, due to long computational processing time as well as large memory requirements. Critical to elimination of these restrictions was the implementation of a multi-block grid generation and message passing interface, MPI, by and Chapman, 2009. The advantages of the multi-block grid parallel version of CH3DS include the flexibility of site-specific horizontal and vertical grid resolution assigned to each grid block, reduced memory and computational time requirements, allowing larger computational domains and longer simulation time periods. The hydrodynamic modeling of Deer Island, Biloxi Bay, and adjacent Mississippi Sound for Deer Island, ecological restoration, was used for demonstrating the advantages of the parallel computing using multi-block grid technique in this study. A comparison of multi-block grid predictions of water levels, salinity temperature time series is presented. CPU wall clock times of multi-block grid on several HPC computer systems are presented. Keywords. 1. Introduction. Computational domain grid from previous studies. 2. Multi-block grid generation and MPI. Horizontal grid resolution at Deer Island and Biloxi Bay using the single-block grid from previous studies. High grid resolution for the Deer Island study. 40-block grid Deer Island computational domain. 3. Model validation results. Water levels comparison at NOAA station. Temperature comparison at Shellbank USGS station. Salinity comparison at Shellbank USGS station. 4. Conclusion. It has been shown that the multi-block grid and MPI techniques can be used for conducting hydrodynamic and transport modeling in coastal areas such as navigation channels and inlets. Also demonstrated were the advantages of the multi-block grid technique used in this study over the multi-block grid, generating from single-block grid of previous studies. High grid resolution can be generated in the areas of interest without affecting those elsewhere. Future research should focus on the combination of multi-block grid and inset grid techniques in the application of ecosystem restoration or navigation channel modifications. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References. Sheng Y.P., 1986. A three-dimensional mathematical model of coastal, estuarine, and lake currents using boundary-fitted grid. Report No. 585, ARAP Group of Titan Systems, Princeton, NJ. PV, Chapman RS 2009. Application of multi-block grid and techniques in hydrodynamic modeling. DoD High Performance Computing Modernization Program. User Group Conference, HPCMP UGC 2009. Sans CA. Bunchby, E. SC, E. Chapman R. 2018. Three-dimensional hydrodynamic, water quality, and sediment transport modeling of Mobile Bay. Letter report prepared for the U.S. Army District, Mobile, Al. Ra J.J., NW 1992, ADCIRC, an advanced three-dimensional circulation model for shelves, coasts, and estuaries. Technical report DRP 92-6, U.S. Army Engineer Research and Development Center, Vicksburg, MS. Dingwai VP, SC, E. 2024, three-dimensional hydrodynamic modeling of Deer Island, Biloxi Bay, and adjacent Mississippi Sound for Deer Island ecological restoration, U.S. Army ERDC, Coastal and Hydraulics Laboratory, Vicksburg, Mississippi, July. Under review. Model forcing, with parametric versus realistic wave spectrum. Abstract. The accuracy of nearshore hydrodynamic model predictions depends on the quality of the forcing applied at the offshore boundary. Waves are represented statistically in phase-averaged models, while they are represented individually in phase-resolving models. Since X-Beach SurfBeat fully resolves waves, the frequency distribution of the forcing wave spectra affects the computation of the forced waves at the offshore boundary. We ran X-Beach SurfBeat simulations with two types of forcing: parametric forcing, where a JONSWAP spectra is reconstructed internally, and spectral forcing, which the observed full directional spectra. For unimodal wave conditions, both the JONSWAP reconstruction and spectral forcing produced results that closely matched wave observations. However, under bimodal wave conditions, the parametric forcing, JONSWAP, was less accurate compared to spectral forcing. In regions influenced by multiple wave climates, spectral forcing provides a more accurate representation of nearshore hydrodynamic processes. Keywords. 1. Introduction. IG waves, with periods ranging from 20s to 3 minutes, significantly contribute to coastal inundation and erosion. Their impact becomes even more pronounced in the context of climate change, which is driving global sea level rise and an increase in the frequency and intensity of storms. Understanding and accurately modeling IG waves is therefore essential to predict coastal hazards and develop sustainable adaptation strategies. A key feature of the X-Beach Hydrodynamic Model 1, in SurfBeat mode, is its capability to resolve IG motions, making it an effective operational tool for predicting nearshore processes within the surf and swash zones. The reliability of nearshore predictions with X-Beach depends heavily on the quality of the input data, particularly the accuracy of the bathymetry and of the wave forcing at the offshore boundary. Here we study how the choice of boundary conditions, parametric or spectral, affects IG energy predictions. 2 methods. We ran X-Beach in SurfBeat mode, forced with observations from a wave and current profiler, AWAC, located near the offshore boundary of the domain, using 2 types of spectral boundary conditions. One is parametric, where the input consists of bulk wave parameters, including significant wave height, peak period, peak direction, and directional spreading, which X-Beach uses to construct a JONSWAP spectrum. The other one is a general type spectral forcing, where the measured spectra are used as input. We chose to study 2 beaches, where nearshore observations were available, Secret Harbor, and both in the southwest of Western Australia Fig. 1 as. In summer, the region experiences a diverse range of wave conditions influenced by local sea breezes and distant swell sources, while in winter, strong long swells originating from the Southern Ocean dominate the wave climate. 1. Secret Harbor is 50 south of Perth. It is sheltered by a long submerged reef located approximately 5 offshore, which acts as a natural barrier, reducing the swell intensity near the beach. Further south is exposed to consistent swell, particularly large in winter due to strong low-pressure systems from the Southern Ocean. Beach is a 1.5 long pocket beach, fronted by limestone reefs, partially exposed at low tide. The AWAC was deployed in approximately 18 m depth. The domain chosen is 1900 m long and 1800 m in the crossshore direction, and the depth at the offshore boundary exceeds 20 m. A location of model domains. B. Domain and bathymetry. C. Secret Harbor domain and bathymetry. 3. Results and discussion. Time series of A and B, short wave height, M0 and C and D, wave height HIG from observations and XBeach runs, at the AWAC locations for A and C, Secret Harbor and B and D, and scatter plots of modeled wave height HIG, XB versus observed wave height HIG, OBS, at Secret Harbor, with parametric and realistic spectral forcing conditions. Scatter plots of the modeled IG wave height versus observed wave height for the Secret Harbor run, Fig. 2G shows a better correlation when using a realistic spectral forcing, correlation coefficient, R053, rather than a JONSWAP spectral forcing, R072. Wave height HIG versus short wave height M0, peak period, coded, from modeling at Secret Harbor, with parametric and spectral forcing. 4. Discussion. In XBeach, bound waves are forced at the offshore boundary to prevent the generation of spurious free long waves, resulting from the radiation stress gradients caused by shortwave groups. The bound waves are generated from the interactions between pairs of primary waves. The amplitude of each individual bound wave is calculated following Theory 5. The interaction coefficient, function of the shortwave frequencies and direction differences, is calculated following Al. 6 and Van Al. 7. The total bound, long wave amplitude is therefore dependent on the shape of the shortwave spectrum. Interactions between low-frequency shortwaves, i.e., swell, lead to larger bound waves than high-frequency shortwaves, i.e., WinC 4. Shortwave and bound long-wave spectra, calculated from real blue and JONSWAP spectra in 2 bimodal cases. A. Swell slightly dominant, M0059M, 112S, B. WinC slightly dominant, M0062M, 42S. Note, real spectra have been smoothed for display. This study highlights the importance of forcing nearshore models with an adequate spectral representation of the offshore wave spectra. In the present study, we used a model resolving IG waves only. Therefore, the improvement using realistic spectral forcing only affects the accuracy of IG wave simulation. We expect that it would be important as well when using fully wave-resolving models, such as XBeach, hydrostatic, or SWASH. 5. Conclusion. Forcing with realistic wave spectrum, rather than bulk wave parameters, significantly improves the estimation of IG wave energy in cases when the wave conditions are multimodal. However, it does not make any difference for short wave height, in the present case where we used a spectral averaged model for short waves. Our results highlight the importance of using full directional spectra to force nearshore hydrodynamic models, and more generally, the importance of retaining spectral information from global regional models or observations, with the possibility of performing spectral reconstruction. This is important for and hybrid downscaling, where bulk parameters are generally used to build the training dataset. This research was funded by the Partnership, a collaboration between the Australian Department of Defence, Bureau of Meteorology and CSIRO, and by the University of Western Australia. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 40. which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1S, G, 2015, Sandbar Straightening Under Wind, Sea, and Swell Forcing. Mar 368, 2541. 2S, Al 2021, Free and Forced Components of Shoaling Long Waves in the Absence of Short Wave Breaking. J. 3S, G, 2013, Response to Variable Wave Forcing in the Near Shore. J. Rays Oceans, 11870957106. 4M, RT, RJ 1992 Bound Waves. J. Rays Oceans. 5K, 1962, On the Nonlinear Energy Transfer in a Gravity Wave Spectrum Part 1. General Theory J. Fluid Mech 12 480 1500. 6 THC, S, RT 1994 Frequency, 0.005005, Motions on the Shelf. Part I, Forced Waves. J. 917, 927. 7 Van A, A.J., I 2003, Numerical Modeling of Wave Response During Delilah. J. Rays Oceans. Fast Modeling of Wave-Driven Flooding for Sandy and Coral Reef-Lined Coasts. Abstract. Coastal communities worldwide face flooding threats from tides, surge, rain, and rivers, yet wave-driven impacts are often inadequately considered in large-scale assessments due to high computational costs. The SFINCS model enables the efficient computation of wave-driven flooding, but until now, it required boundary conditions from expensive models like XBeach. Here we overcome this problem and apply and validate a method to efficiently derive nearshore wave conditions using the fast wave spectral model SnapWave. These nearshore conditions are then used to drive dynamic waves in SFINCS. The method is validated using a laboratory case of a sandy beach and a field case from Philippines affected by Typhoon 2013. This is a first application on a coral reef-lined coast, which is beyond the application area of the methodology to determine wave transfer. The results indicate that SFINCS can model overland wave heights and flooding extent with reasonable accuracy compared to XBeach, but with a significantly reduced computation time. From over 3 hours to just 20s overall, the SFINCS SnapWave IG methodology demonstrates promise for large-scale applications in coastal hazard studies. Keywords. 1. Introduction. Coastal communities worldwide are under threat of flooding due to multiple drivers of tide, surge, rivers, rain, and waves. 1. However, for coastal flooding assessments at regional to continental scales, waves are often not, or only by approximation, accounted for due to the high computational expense needed. While the physics of wave-driven flooding is already included in the SFINCS Model 2, boundary conditions to drive SFINCS were still needed from a computationally expensive numerical model like XBeach 3, 4, or from 1D-based, Meta Models 5, that do not fully account for alongshore varying 2D effects. To be able to include dynamic wave and overtopping in a 2D fast flooding model, we need to also derive nearshore IG wave conditions in a computationally efficient way. Such a method has been introduced in AL. 2024-6. In this work, we apply and validate such a method to efficiently compute wave boundary conditions and compute resulting wave-induced flooding, and 2. Methodology. Side view of a coastal, with overview of the coupled SFINCS SnapWave IG model, including indication of how incident and wave processes are resolved. 3 results. 3.1 Laboratory Cases GLOBEX. The first case is from the GLOBEX Lab Experiments 10, consisting of a mildly sloping sandy beach profile with a 180 slope. Wave conditions for the considered test A3 are 0,1 and 225 s, representative for real-world conditions of 2m and 10 s previously. These tests were used to verify the performance of the IG wave transformation methodology, using the observed incident wave heights as input 6. In the current application, we model the incident wave heights using SnapWave, so that a full comparison with the entire set of observations of wave-induced setup, as well as incident, and IG wave heights can be made. Observed and modeled incident and wave heights top, water level middle and bed level elevation bottom, for laboratory GLOBEX A3 test. 3.2 Field Case, Coral Reef Coast. The second case pushes the application area of the methodology to the steeper coral reef-lined coast of the Philippines. Their typhoon, 2013, caused significant flooding and casualties 11. This case was modeled in the SFINCS Introduction Paper 2, where it was shown that it could be modeled efficiently with sufficient accuracy as compared to the results obtained with an advanced 2-layer X-beach non-hydrostatic model. However, in that study, the wave input was still derived from water level time series at the end of the coral reef flat from the computationally demanding 2D X-beach model, thereby effectively adding computational time too. In the current case, the full wave transformation from offshore to coral reef flat to overland flooding is modeled by SFINCS with the coupled SnapWave IG solver. The model starts in about 45 m offshore water depth, and the IG is placed just offshore of the reef edge, at about 3 m water depth. The simulation is limited to 30 min, since this already takes more than 3h to model by X-beach. Comparing the modeled maximum water depth between 1. Original simulation of SFINCS forced by 2D X-beach, and 2. Simulation of SFINCS IG, show a similar flood extent and depth Fig. 3. For this case, the inland flood extent is mostly limited by the terrain, which becomes steeper after the coastal floodplain behind the coral reef. In further comparison to the X-beach model results, 2 locations at the beach and at a house that is washed away 11, and a perpendicular are considered Fig. 4. Comparison of maximum modeled water depth between SFINCS forced by X-beach left and SFINCS with coupled SnapWave IG solver right. 4 Conclusions. Comparison of maximum, mean and instantaneous modeled water levels between X-beach blue, SFINCS forced by X-beach green, and SFINCS with coupled SnapWave IG solver orange, for both the upper time series at the beach middle and time series at destroyed house lower. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1ME, Irish JL, Frey I, F, Edge BL 2011, Global Warming and Hurricanes, the Potential Impact of Hurricane Intensification and Sea Level Rise on Coastal Flooding. Change 104, 575-597. Org 10 1007 S10 5840099790. 2T Van M. K. Van A. 2021. Modeling Compound Flooding in Coastal Systems Using a Computationally Efficient Reduced Physics Solver, including fluvial, pluvial, tidal, wind, and wave-driven processes. Coast 163, 103796. Org 10 1016J2020103796. 3D, AL 2009, Modeling Storm Impacts on Beaches, Dunes and Barrier Islands. Coastal 56, 1133-1152. Org 10 1016J2009-08006. 4C, K, CD, BG, Beck MW, 2024. Improved efficient physics-based computational modeling of regional wave-driven coastal flooding for reef-lined coastlines. Ocean Model 189, 102358. Org 10 1016J2024102358. 5 Call R, C, F, SG, R, 2024. Rapid simulation of wave on morphologically diverse, reef-lined coasts with the Beware 2 broad-range estimator of wave attack in reef environments, meta-process model. Hazards Earth, 2435973625. Org 10 51942435972024. 6 TWB, Van M, Van A, JCJH, S 2024. Estimating nearshore wave conditions at large spatial scales. Frontmar, 1113555095. Org 103389202413555095. 7J, Call R, R, Van A, D, 2023. Modeling wave group-scale hydrodynamics on orthogonal unstructured meshes. Environ Model, 162, 105655. Org 10 1016J20231056555. 8 Van M, D, Van A 2023. Wave effects in a rapid compound flood model. Dame IN, USA. 9 TWB, Van A, Van M, RGA, JCJH 2024. The Importance of Waves in Large-Scale Coastal Compound Flooding. A Case Study of Hurricane Florence, 2018. 10G, AL 2013. Wave Dynamics on a Gently Sloping Laboratory Beach. Coastal Dynamics. 11V, Bricker JD, 2015. Destructive tsunami-like wave generated by surf beat over a coral reef during typhoon. 67854. Org 10 10388854. Wave height estimation methods for non-breaking waves using video images. Abstract. Optical monitoring systems have become essential tools for measuring hydrodynamic parameters in the shoreface zone. They offer continuous data collection over large spatial areas, making them highly valuable in coastal research. However, accurately estimating wave heights from optical imagery remains a challenge due to the complexities of wave interactions, variations in camera configurations, and environmental conditions. This study evaluates two methodologies for estimating wave heights in the non-breaking zone using UAV footage, building on the limitations of previous techniques. The methods automatically detect waves using image processing techniques, initially measured in pixels. These pixel-based measurements are then converted to real-world coordinates, meters, through geometric transformations. A central focus was the variability of wave height estimates across different regions of interest, ROIs of the image. The findings emphasize the critical role of optimal camera placement in enhancing measurement accuracy. This analysis contributes to advancing optical monitoring techniques, improving hydrodynamic parameter estimation, and better understanding dynamic coastal environments. Keywords. 1. Introduction. The derivation of wave heights from video imagery in the nearshore zone relies on the significant alteration in optical properties, as the imaging mechanism captures surface reflections. 1. Wave heights have been estimated by stereographic configurations in non-breaking zones. 2, 3. A method that is practically infeasible in open sea conditions. In breaking zones, time-stack images from a single camera have been employed. 4. But this approach lacks consistency in the shoaling zone, where breaking waves and the characteristic white foam are absent. Wave dynamics and environmental conditions, among other variables, are largely uncontrollable in natural settings and impact wave height measurements. In contrast, camera configurations such as tilt, rotation, and height can be adjusted to align with the user's intent. Unmanned aerial vehicles, UAVs, offer a notable advantage in this context, allowing for the adjustment and optimization of all camera parameters on flight surveys over fixed cameras. Although geometric correction techniques aim to standardize measurements throughout the image, it is essential to assess the region of interest, ROI, where the results are most accurate and uniform. This study evaluates how variations in ROI in an image affect the estimation of wave heights by comparing two methods. 2. Study area and video settings. A study area and B, segmented 9 regions of interest ROI, defined in the center of the image. Aerial imaging for this study was conducted using the DJI-2 Pro, equipped with a L1D20C camera featuring a 1-inch CMOS sensor. This sensor enhances light capture and significantly improves image quality, particularly in comparison to most commercial drones, enabling high-resolution imaging even in varied lighting conditions. As this is the initial phase of developing a robust wave height estimation technique from images in the shoaling zone, a 2-min video was recorded in 4K resolution, 3842/160 pixels, at 30 frames per second, generating a total of 3,600 frames. This frame rate facilitated a detailed visual inspection of the extracted frames during image processing and feature extraction, allowing for the evaluation of different segmentation techniques while minimizing computational costs. The drone was operated at a consistent altitude of 49.8 m above sea level, with the camera set at a tilt angle of 65 degrees. This configuration was chosen to optimize the field of view and enhance the capture of fine details necessary for the study. 3. Wave heights estimation methods. A. Undetected waves height in braking zone. B. Detected wave height white features in non-braking zone. A. Geometric rectification of method 1, reproduced and modified from 4. B. Geometric rectification of method 2. C. Extracted wave height high in pixels. Here was determined by calculating the average height of the highest 1/3 of the estimated waves of each image. 4. Results and discussions. In this section, we present the analysis of wave features in the braking zones, focusing on ROIs 6 to 9. Since the extracted features are based on the inverted segmented foreground, the surf foam influenced the accuracy of the measurements, highlighting the method's inefficiency in braking zones as shown in Fig. 1s. Hence, ROIs 1 to 5 were excluded from further analysis. Estimated significant wave heights and their respective absolute difference in the selected ROI. Image height position pixels. Significant wave height m. ROIs. Method 1. Method 2. Differences. 6. 801,000. 0.93. 1.07. 0.15. 7. 600 800. 0.93. 1.06. 0.13. 8. 400 600. 0.55. 0.56. 0.01. 9. 200 400. 1.47. 1.7. 0.23. Time series of the computed wave heights from method 1 red and 2 blue at the analyzed ROI. The x-axis represents the largest wave extracted from each frame at a rate of 1 frame per second. 5. Conclusion. Understanding the impact of camera orientation on feature detection enables practitioners to optimize their systems for more accurate wave parameter measurements. Ensuring the camera is oriented to clearly capture key objects is essential, as this reduces the need for costly reinstallations of fixed cameras or repeated UAV surveys. The methods outlined in this study show consistent results across all extracted ROI in the non-breaking zones. To achieve ideal accuracy, study areas should be centered within the image. While values for methods 1 and 2 show slight variation across the ROI, further validation using additional hydrodynamic sensors is recommended to enhance the method's reliability. Thanks to FCT-MCTES for the financial support to CESAM, UIDP 500172020 plus UIDB 500172020 plus LA/P00942020 through national funds. Content produced within the scope of the Agenda Nexus, Verde Digital Paratransportes, financed by the Portuguese Recovery and Resilience Plan, PRR, with no C64511208300000059, Investment Project No. 53. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1R Al, 2012, New Breaking Wave Height Direct Estimator from Video Imagery. Coast 61 142 48. 2U, Mendes D. R. 2020, Breaking Wave Height Estimation from Images, 2 Methods for Coastal Video Monitoring Systems. Remote Sensing 12.2. 3A 2006, Measurements of Short Water Waves Using Stereo-Matched Image Sequences. Coast 531210 131032. 4J S. M. 2020, Extracting Nearshore Wave Properties from Video, a New Method for Coastal Estuaries. Estuarine, Coastal and Shelf Science 246. 5S. Hill DF, MA, MJF 2011, Remote Sensing of Surf Zone Waves Using Stereo Imaging. Coast 58 3239 250. Dynamics of Waves Across the Southern Reef Barrier of Mayotte, Indian Ocean. Abstract. Due to climate change, tropical islands are being increasingly exposed to coastal hazards. Under energetic incident swells, IG waves can have a key contribution to extreme water levels and flooding, but their dynamics at Barrier Reef remains little studied. In this context, this study analyzes IG wave generation mechanisms and transformations across a barrier reef to the southwest of Mayotte, Indian Ocean, combining a new comprehensive field dataset with phase-resolving wave modeling. This analysis reveals that IG waves are mostly forced and suffer a substantial dissipation by bottom friction, particularly at low tide. Numerical experiments with reduced bottom friction representing a degraded coral reef suggest that IG waves would grow by about 20% across the reef at high tide. This study highlights the key role of coral reefs to dissipate IG waves and hence limit extreme water levels and subsequent coastal hazards. Keywords. 1. Introduction. Tropical islands are currently facing an increase in coastal hazards due to the combination of global sea level rise, natural subsidence, the possible intensification of cyclonic activity, and the degradation of coral reefs. In tropical volcanic islands, the absence of continental shelves usually causes extreme water levels and subsequent flooding to be controlled by the effects of atmospheric pressure gradients and short wave dissipation, which drives a wave setup. In addition to these processes controlling still water levels, Energetic swells can induce large waves, hereafter IG. See 1 for a review, which correspond to long waves associated with the presence of groups in the incident short waves and can drive intermittent flooding. Yet, over the last decades, this phenomenon has mostly been studied at sandy beaches, and the analysis of the processes controlling IG wave generation and transformations across coral reef lagoon environments has been limited to a few studies, mostly focusing on fringing reefs, e.g. 2-3. In this context, this study investigates the generation of IG waves and their transformations and dissipation across a complex coral reef lagoon system to the southwest of Mayotte, in the Indian Ocean. 2 Study site. A. Location of Mayotte archipelago in the Mozambique Channel. 2. Bathymetric map and location of the studied area in Mayotte. And C. Zoom in on the instrumented across the reef barrier with location of the 10 pressure transducers used in this study. This studied barrier reef is about 1 wide, with a reef slope combining a very steep lower part, 1/8, below 10 m and a moderately steep upper part, 120 from 10 m up to the reef crest Fig. 1c. The reef flat is gently sloping, with a mean slope of the order of 11000. The first 200 m of the barrier reef are characterized by a strong roughness due to the combination of a spur and grooves patterns, and a high density of corymbose and branch coral. The remaining part of the reef is much smoother and corresponds to coral skeletons and patches of sediments. Applying a 1D frequency-integrated wave energy model over pairs of adjacent sensors from the same dataset as in the present study. 4. This volume, estimated roughness lengths Ks ranging from over 1 m at rough part of the reef and 0.01 m at the smooth part. 3. Data and methods. 3.1 Field data. A comprehensive field campaign was organized from late August 2023 to November 2023 across the Barrier Reef Lagoon System to the southwest of Mayotte, Fig. 1. During this field campaign, 10 pressure transducers were deployed across the barrier reef, and several current profilers were deployed around this Fig. 1c. Bottom pressure was converted to surface elevation using linear wave theory, and the frequency cutoff between short and IG waves was adaptive and defined as half the peak frequency of the short waves. 3.2 Numerical modeling. In order to complement data analysis and better understand IG wave generation and propagation across the barrier reef, the phase resolving model SWASH 5 was implemented over the studied reef barrier. The modeled domain extends over 1200 m in the crossreef direction and 400 m in the alongreef direction, and is centered on the instrumented Fig. 1. The realistic bathymetry starts by 25 m water depth and follows a 150 to 200 m wide plateau after the numerical wavemaker. The horizontal grid has a spatial resolution of 2 m in the crossreef direction and 5 m in the alongreef direction. 2 layers are used in the vertical, which allows for small dispersion errors up to frequencies of 0.3 for the considered water depths 5. Based on roughness length estimates of 4 at the instrumented, the bottom friction coefficient seed was set to 0.02 at the rough part of the reef and 0.005 elsewhere, which also matches the values used by 6 at an Australian fringing reef, 2022. Along the southwest open boundary, SWASH is forced with directional wave spectra computed from a global application of the WaveWatch III model, as described in 7. In order to account for the water depth inconsistency between the closest grid point in WaveWatch III and the open boundary of SWASH, a linear shoaling is applied to these directional spectra. 4 results. 4.1 Short and IG waves variations during the field campaign. Observed mean water depth A and M0B at PT1, IG wave height across the reef C, and correlation between the IG waves and the wave energy envelope D. Times T1 corresponds to the high tide during the energetic event considered for numerical modeling. 4.2 Evolution of short and IG waves across the reef under storm conditions. Observed circles and modeled solid lines 0A, 02B, bathymetric profile and location of the PTs C, and modeled blue and observed black spectra at PT1D, PT5E and PT8F, at high tide on the 1909-2023 T1 on Fig. 2. Modeling results reveals firstly that, during high tide and energetic conditions, short waves grow due to shoaling over the reef slope and start to break just before PT1, after which they smoothly decrease across the reef barrier, Fig. 3a. This behavior is overall well captured by swash, although wave height is underestimated after PT7. The mean wave period 02 decreases by a factor of 2 across the Fig. 3b, due to the development of higher harmonics Fig. 3d to 3f. These energy transfers are well captured by swash, although energy over 0.2 is strongly underestimated after PT7 Fig. 3f, which will be discussed later. IG waves continuously grow until PT3, after which they reach a plateau at M0 IG0 25 m. The spectra in the IG band are rather flat, with the maximum of energy found between 0.007 and 0.02, and these patterns are also well reproduced by swash. 5. Discussion and conclusions. 5.1. Predictive skills and limitations of the model. The spatial patterns of both short and IG waves are overall well reproduced by the model, although short wave heights remain underestimated after PT7. As energy is transferred towards higher harmonics through triad interactions, see sect. 4.2. A finer spatial resolution may be required to better capture the resulting shorter waves. Next, the wave boundary conditions may suffer inaccuracies as wave modeling in this part of the Indian Ocean is particularly challenging due to the presence of the current at the entrance of the Mozambique Channel, e.g. 8. Yet, IG waves are accurately reproduced by swash, so that modeling results can be used with confidence to further analyze their dynamics. 5.2. Importance of IG waves dissipation by bottom friction. The fate of coral reefs in a context of global change is a major concern worldwide, e.g. 9. In order to evaluate the importance of coral reef for IG wave dissipation, SWASH was launched with a uniform friction coefficient set at 0.005, which corresponds to a reef covered by coral skeletons and patches of sediments. This simulation shows that IG waves are increased by about 20% across the reef barrier, compared to the present-day situation, where the first 200 m of the reef are characterized by a high roughness. IG waves crossing the reef barrier propagate through the lagoon as free waves and reach the coast of the main island, where they can contribute to extreme sea levels and subsequent coastal hazards. This study demonstrates the key role coral reefs in dissipating IG waves and stresses the importance of protecting these environments to mitigate the impacts of ongoing global changes. This research is funded by the France 2030 PPR Ocean and Climate Project FUTURISKS, ANR 22 POCE 0002. Permanent pressure data are collected to the southwest of Mayotte in the scope of the National Observation Service, DYNALIT, part of the Research Infrastructure ILICO. The developing teams of the codes WaveWatch III and SWASH are warmly acknowledged for making their source code available. Finally, and provided help during the field campaign of 2023. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Burton X. A. Van A. Coco G. Al. 2018, Waves, From Driving Mechanisms to Impacts. Earth, Rev. 177, 774, 799. 2A. Low R. G. Van A. Morsi, 2012, The Dynamics of Wave Transformation Over a Fringing Reef. J. Rays 117, C11022. Org 10 102920 12 JC00 8310. 3W, E, F, SG 2022, Water Level Modulation of Wave Transformation, Setup and Overlaw Saline Fringing Reef. J. Rays, Oceans 127-7, Article 7. Org 10 10292022 JC0 18570. 4M Al, 2025. Frictional Dissipation of Incident Waves Over a Spatially Varying Rough Barrier Reef in Mayotte, Indian Ocean. Proceedings of the Coastal Dynamics Conference, Portugal. 5M, Stelling G., Smit P., 2011 SWASH, an operational public domain code for simulating wave fields and rapidly varied flows in coastal waters. Coast 5810-992-1012. Org 10 10 16 J20 1105015. 6 DP, Al 2021, A Numerical Study of Wave-Driven Mean Flows and Setup Dynamics at a Coral Reef Lagoon System. J. Rays Oceans 126, E202 0JC0 16811. Org 10 10 292020, JC0 16811. 7A, Al 2024, A New Global High-Resolution Wave Model for the Tropical Ocean. 126. Org 10 519420 242610. 8G, F 2021, Surface Currents and Significant Wave Height Gradients, Matching Numerical Models and High-Resolution Altimeter Wave Heights in the Current Region. J. Rays, Oceans 126, E202 0JC0 16564. Org 10 10 292020, JC0 16564. 9 Walker A.S., C.A. Van R. 2024, Past disturbances and local conditions influence the recovery rates of coral reefs. Glob change, 31E17112. Wave-induced velocities in rigid suspended canopies. Abstract. Many aquaculture farms, such as those cultivating seaweeds and mussels, create suspended canopies in coastal waters that can serve as nature-based coastal protection measures. These canopies are typically off-bottom and heterogeneous, with line spacings significantly larger than lateral element spacing. Existing wave attenuation and canopy flow models assume benthic, homogeneous canopies and may yield inaccurate predictions for suspended, heterogeneous canopies. Understanding wave-induced velocities in such suspended canopies is critical for improving wave attenuation predictions and developing canopy flow models. This study aims to advance the understanding of wave-induced velocities in suspended canopies. Laboratory experiments were conducted to examine horizontal and vertical velocities in suspended cylinder arrays under waves. Results show that canopies only minimally influence vertical velocities, but significantly affect horizontal velocities. The horizontal orbital velocity attenuates within and below the canopy and overshoots above it. Denser canopy configurations and longer wave periods generally enhance these effects. Additionally, two horizontal mean current regimes around the canopy interfaces are observed, one with shoreward streaming around the canopy top and seaward streaming around the canopy bottom, and another without these effects. The hydrodynamic conditions that distinguish these regimes are identified for different canopy configurations. These findings provide insights that could improve the prediction of wave attenuation caused by suspended aquaculture farms and their design. Keywords. 1. Introduction. Nature-based, green, coastal protection measures, such as coastal vegetation fields, have received increasing attention for their cost-effectiveness and ecological services compared to traditional infrastructure like one. In addition to benthic vegetation, e.g., seagrass, suspended aquaculture farms that cultivate seaweeds and mussels can also function as coastal protection too. These farms create off-bottom, suspended canopies in the water column, providing greater wave attenuation potential and significantly altering local hydrodynamic patterns compared to benthic canopies. Understanding wave-induced velocities in suspended canopies is essential for estimating their wave attenuation capacity and optimizing farm productivity. 3.5. While wave-induced velocities in benthic canopies have been extensively studied, e.g. 6.7, research on suspended canopies remains limited. 8.9. Moreover, previously established canopy flow models often assume homogeneous canopies, whereas suspended aquaculture canopies are typically heterogeneous, by line spacings significantly larger than the lateral element spacing 10. It has been demonstrated that shoreward streaming around the canopy top and seaward streaming around the canopy bottom are expected under waves 8. However, the canopy configurations and wave conditions that generate these mean currents remain unclear, despite their important role in nutrient transport. To deepen the understanding of wave-induced velocities in suspended canopies, we experimentally quantify orbital and mean velocities in arrays of off-bottom rigid cylinders under waves. This paper is as follows. Sect. 2 describes the experimental setup. Sect. 3 presents the data and preliminary analyses, and Sect. 4 concludes the study. 2. Experimental setup. Experiments were conducted in the Aberdeen University Random Wave Flume AURWF, which is 20 m long, 0.45 m wide, and 0.7 m deep. Regular waves were generated by a bottom-hinged wave paddle equipped with active wave absorption. The suspended canopy is represented by an array of PVC cylinders, each 0.3 m long, 1 diameter, positioned 0.2 m below the still water level, and supported by individual frames. See Fig. 1. The cylinders were supported by 2 horizontal steel rods, 5 min diameter, located at Z03 m and 0.4 m, respectively, with both rods connected to the sides of each frame. Sketch of the experimental setup, side view, not to scale. The dashed vertical line indicates the LDA measurement profile, while the green shaded area represents the suspended canopy. Denotes the canopy length. Summary of experimental conditions. Canopy M NM2 HM TS A01 4.3 2 222 0.17 1.21416 B01 2.15 2 444 0.17 1.21416 C02 4.3 4 111 0.17 1.21416 D02 2.15 4 222 0.17 1.21416 E060810 4.3 1.82430 372822 0.17 1.21416 F081012 2.15 2.43036 564437 0.17 1.21416 LDA measurement locations represented by X symbols plan view, not to scale, the number of cylinders is counted from the lower line. Horizontal and vertical velocities were measured using a two-component laser anemometry, LDA system. Data were acquired from 10 above to 10 below the canopy, with a vertical resolution of 1 near the upper and lower canopy interfaces, and 2 elsewhere. The LDA sampling frequency ranged from 50 to 150, depending on the velocity magnitudes, with measurements taken at each point for at least 200 wave periods. For all velocity measurements, the free surface elevation was simultaneously recorded using a collocated twin-wire resistant type wave gauge, in addition to one reference gauge placed around 3 m in front of the canopy, sampling frequency 256. For canopies A, B, C, and D, 4 vertical profiles were measured in the middle of the canopy, see Fig. 2, which were averaged to obtain the representative velocity profile. For canopies E and F, 1 vertical profile was measured at the center of the canopy. To provide reference velocity profiles, measurements were repeated without cylinders, but with the supporting frames in place, for canopies A, B, C, and D, and in the empty flume for canopies E and F, the measured data were phase-averaged and processed following a procedure similar to that outlined in 6. 3 results. 3.1 Vertical profiles. Figure 3 shows example vertical profiles of wave-induced velocities for canopy C and wave conditions, with H0 17m and T14s the root mean squared, horizontal orbital velocity, and the horizontal mean velocity, are significantly altered due to the canopy. Fig. 3 overshoots above the canopy, but attenuates within and below the canopy. Fig. 3c shows clear shoreward streaming around the canopy top and seaward streaming around the canopy bottom, which is consistent with previous studies 7-9. In contrast to the horizontal velocities, the vertical orbital velocity is largely unaffected by the canopy, and the mean vertical velocity is near zero throughout the depth. Vertical profiles of A. Horizontal wave orbital velocity, B. Vertical wave orbital velocity, C. Mean horizontal velocity, and D. Mean vertical velocity for canopy C, with H 0.17m and T 1.4s. The shaded area denotes the position of the suspended canopy. The dashed lines represent reference vertical profiles measured without cylinders, but with the supporting frames in place, while the dotted solid lines indicate vertical profiles measured with cylinders. 3.2 Depth-averaged horizontal orbital velocity. To examine the canopy effect on horizontal orbital velocity, we define where was obtained by measuring velocity profiles using frames without cylinders. Figure 4 shows depth-averaged over 3 vertical sections of the profile, above, within, and below the canopy, plotted against for canopies A, B, C, and D. T2 is the horizontal wave orbital excursion length at 0.2 m below the still water level, i.e. at the top of the canopy, calculated using linear wave theory. For the canopy section, 0.5 m Z02 m ranges from 0.82 to 0.9 Fig. 4b, with higher values observed for sparser canopies and lower. Although is close to 1, its impact on wave attenuation prediction may be relatively large because the wave decay coefficient used in common wave attenuation models is typically proportional to 3, CEG. 10 and 3. Depth averaged indicates depth averaging versus, for canopies A, B, C, and D, A below the canopy bottom, B at the canopy section, and C above the canopy top. 3.3 Mean currents around the canopy interfaces. Vertical profiles of horizontal mean current induced by canopies, at E with 430 and B, F with 215, represented by ref, where ref was obtained from measurements without any frames or cylinders in the wave flume. Marker indicate the magnitude of, as shown in the bar. For conclusion, this paper describes the experimental setup and data obtained from detailed laboratory experiments on wave-induced velocities in rigid suspended canopies. Results show that horizontal orbital velocity attenuation within and below the canopy increases with higher. Two horizontal mean current regimes around the canopy interfaces are identified, with critical values distinguishing these regimes. This paper provides benchmark results for future experiments using flexible mimics to model suspended aquaculture canopies realistically. The results can also help validate wave attenuation models and develop canopy flow models for suspended canopies. Further investigation, including wave-induced turbulent velocities in suspended canopies, is. This work has been funded under the NERC Scottish Universities Partnership for Environmental Research, Super, Doctoral Training Partnership, Grant Reference Number NES00-73421. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1S P. T.J. Herman P.M.T. H.J. 2013, Ecosystem-Based Coastal Defense in the Face of Global Change. Nature 504, 7478-7983. 2L. K. QP. DW. D. 2020, Aquaculture Farms as Nature-Based Coastal Protection, Random Wave Attenuation by Suspended and Submerged Canopies. Coast 161, 03737. 3Lay J. H. 2019, Wave Damping by Flexible Vegetation, Connecting Individual Blade Dynamics to the Meadow Scale. Coast 147, 138, 148. 4 Stevens C. Plu D. N. D. 2008, The Physics of Open Water Shellfish Aquaculture. 38 3145 160. 5CL Harrison P.J. K. CS 2014, Seaweed Ecology and Physiology, 2nd. Cambridge University Press. 6 Low R.J. Jr. S.G. 2005, Oscillatory Flow Through Submerged Canopies, 1. Velocity Structure. J. Rays Oceans 110C, 10016. 7M. M. 2017, The Wave-Driven Current in Coastal Canopies. J. Rays Oceans 122 53660 3674. 8H. X. QP 2019, Wave-Driven Flow Induced by Suspended and Submerged Canopies. Adwater 123 16172. 9 Tang X. P. YH. Y. PLF 2023, Turbulence Kinetic Energy Inside Suspended Vegetation Domain Under Periodic Water Waves. J. Port Coast Ocean 149 3040 23004. 10L. Lay J. K. DW 2021, Wave Attenuation by Suspended Canopies with Cultivated Kelp. Coast 168 103947. Beach Nourishment in a High-Energy U.S. West Coast Environment. Abstract. Dredged sediment from engineered inlets can be used to nourish coastlines adjacent to these inlets, serving as a beneficial alternative to offshore disposal. Effective strategies for beneficial use of dredged sediment, however, rely on understanding of local sediment transport. A beach nourishment project utilizing dredged sand was carried out at a highly energetic beach north of the Columbia River mouth, Washington, USA. Within 2 weeks of placement, during a moderately energetic period, a large part of the beach nourishment had eroded. To predict local hydro and there, a X-beach model was used. validated with field observations of nearshore hydrodynamics and morphology. It showed that while the subaerial nourishment eroded rapidly, it is likely that the sediment is deposited around the inner bar and is still available to the morphological system of beach. Additionally, model simulations suggest the nourishment provided a buffer against erosion of the local dune system during its presence. Keywords. 1. Introduction. Beach nourishments are widely used to combat coastal erosion along sandy shorelines worldwide. 1. 2. Sediment is placed on the beach to increase beach width and provide protection against shoreline erosion and coastal flooding. Erosion can be especially acute along coastlines adjacent to engineered inlets, as jetties modify sediment transport pathways, and engineered inlets can act as a greater sink for alongshore sediment transport than natural inlets. Regular maintenance dredging is often required to keep engineered inlets navigable, and dredged sediment can be used for nourishment as an alternative to offshore disposal. However, effective strategies to beneficially use dredged sediment to reduce erosion impacts rely on understanding the local transport pathways and timescales of erosion and dispersal of beach nourishments. A beach nourishment project that utilized dredged sediment was carried out at Beach, Washington, a highly energetic beach north of the Columbia River mouth, Fig. 1. This beach is located within the Columbia River Littoral Cell, CRLC, where the sandy beaches have a broad surf zone and multiple sandbars. 3, and the morphology displays significant variability due to seasonal changes in environmental conditions. 4. The 3 Long Beach is located between the North Jetty and North Head, Fig. 1b, and was formed because of the construction of the North Jetty, constructed 1913-1917. 5. The shoreline of beach has been retreating since 1950, most likely due to insufficient sediment supply from the depleted ebb tidal delta of the Columbia River. 5. Besides being a recreational location, the beach also acts as protection for the North Jetty infrastructure. 6. Location of beach, the beach nourishment, oceanographic instruments, tripods, and a bathymetric survey of 220-92010, colored area in B, and X-Beach model domain blue polygon in A. 2. Methodology. 2.1 Field observations. Hydrodynamic and monitoring was performed to investigate the behavior of the nourishment. A total of 21 topographic and 7 bathymetric surveys were conducted between July 2010, before the start of the placement, and November 2011. 6, with survey S06 occurring immediately post-construction and S07 conducted 2 weeks later. Offshore waves and currents were measured at a tripod in a water depth of 17 m near shore. Waves and currents were measured at 2 stations, located around MLLW, Fig. 1. 2.2 Model setup. A large-scale, 2-way coupled Delft 3D4 and Swan model of the Columbia River mouth was used to simulate water levels, currents, and waves in the area. The model consisted of a structured grid covering an area of approximately 260 long by 210 wide, with a horizontal resolution varying between about 90 m inside the Columbia River inlet to about 8,000 m at the seaward extents of the model grid. 10 vertical sigma layers were included to simulate 3D effects. The oceanic boundaries were forced with astronomic tidal constituents that were adjusted with measured time series of non-tidal residual water levels recorded at 2 tide gauges in nearby inlets. The model bathymetry, referenced to the NAVD 88 vertical datum, was constructed from a variety of recent sources collected between 2004 and 2027. Wind and wave forcing were included based on time-varying, spatially uniform conditions measured at offshore NDBC, wave buoy 46,029-8. Depth-induced braking, nonlinear triad interactions, bottom friction, wind growth, and white capping processes were included in the wave model. To predict local hydro, and at beach, a smaller-scale X-Beach model was set up, using the Halloween version of X-Beach 9, and running in wave-averaged mode. The model domain ranged from the river mouth to north of North Head, ensuring that the area of interest was sufficiently far away from the model boundaries and using a curvilinear grid Fig. 1. The model bathymetry was constructed based on the post-construction survey, S06, supplemented with other sources. To limit the cross-shore domain size, the bathymetry was cut off at 11 m and artificially extended to 30 m with a slope of 1/100, such that the offshore boundary was located in sufficiently deep water to accurately compute the bound waves. The model bathymetry in the inlet was artificially filled up to prevent numerical instabilities. The X-Beach model was forced with water levels and two-dimensional wave spectra from the large-scale coupled Delft 3D model, extracted at the X-Beach offshore boundary. The morphological response was calibrated by varying the calibration factor for time-averaged flow due to wave asymmetry, as value, steering the onshore sediment transport component by changing the effect of the wave asymmetry in the computation of the sediment advection velocity. The coastal area was divided into blocks in a longshore and cross-shore direction. The volume changes within based on bathymetric and topographic survey data were used for calibration, resulting in an AS value of 0.15. 3. Model validation. Water levels predicted by the Delft 3D model were compared against observed values at NOAA station 9,439,040 inside the Columbia River between August 4 and November 15, 2010, with a root mean square error, RMSE, error of 0.14 m or 3% when normalized by the range of observed values. Normalized RMSE errors in modeled wave heights and peak wave periods were 8% and 15% of the measured range in values, respectively, compared to observations acquired during two instrumented tripod deployments, total of 68 days. Hydrodynamic validation at Station 1, C. Water levels, incident band significant wave height, and wave height. Morphological validation at two transects, D, E, and map showing locations of the transects, F. 4. Impact of beach nourishment. Erosion rates of the subaerial nourishment berm in relation to hydrodynamic conditions were examined during the 2-week model. The nourishment berm, 1, eroded gradually during this period, with peaks in erosion rates occurring when significant wave heights above 3 m coincided with high tide, Fig. 3 a sea, and band swash likely overtopped the berm, not shown here. These events transport sediment seaward and reduce the berm height, Fig. 2d. Erosion of the beach berm outside of the nourishment area occurred, too, with smaller erosion volumes. The erosion of the berm coincided with a transition from quiescent summer conditions to the more energetic conditions during fall that typifies the strong seasonal cycle in the area. The model simulations show that the eroded sediment from the nourishment area was transported predominantly in cross-shore direction and was deposited around the inner bar system between 3 m and 1 m. Fig. 2d, in agreement with findings from 6. The nearshore deposition of nourishment sand indicates that it is still within the morphologically active zone and could be transported up the beach again under mild conditions. Time series of volume change of the nourishment berm in relation to offshore hydrodynamic conditions, B, C. Dune erosion volumes over the entire simulation with and without nourishment present, D, where the shaded area indicates the nourishment area, including bed level change at two transects, EF. 5. Conclusions. A pilot placement of dredged sediment was conducted at beach. A distinct nourishment berm, placed on the beach, eroded during a 2-week period of moderately energetic conditions following placement. Using a combination of field observations and numerical modeling, it was shown that while the subaerial nourishment eroded rapidly, it is likely that the sediment is deposited around the inner bar and is still available to the morphological system of beach. Additionally, model simulations suggest the nourishment provided a temporary buffer against erosion of the dune system locally. This material is based upon work supported by the U.S. Army Corps of Engineers Portland District, U.S. Geological Survey Coastal and Marine Hazards and Resources Program, USGS USA Grant Cooperative Agreement No. G24 AC000136, and the Strategic Software Development Program, I1000694. Any use of trade, firm, or product names is for descriptive purposes only and does not imply endorsement by the U.S. government. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Dean R.G., 2002 Beach Nourishment, Theory and Practice. World Scientific, River Edge, NJ p. 399. 2. Ham L. M. H. A. R. MJF 2002, A Summary of European Experience with Shore Nourishment. Coast 47 237 264. 3p. GM. G. B. 2005, Seasonal to Along a High-Energy Dissipative Littoral Cell. J. Coastal Rays 21 553 578. 4p. DJR. G. Van M. 2009, Seasonal Scale Morphological Evolution, Field Observations and Numerical Modeling. Coast 56 1153 1172. 5 GM. P. MC. D. G. 2010, Historical Evolution of the Columbia River Littoral Cell. Mar 273 96 126. 6 Stevens A. G. P. GM 2012, Southwest Washington Littoral Drift Restoration, Beach and Nearshore Monitoring. U.S. Geological Survey Open File Report 2012, 1175, 67. Org 103 13320 121175. 7 Stevens A. HR, Elias PL, GR, PR, SG, JM, GM 2023, Monitoring and Modeling Dispersal of a Submerged Nearshore Berm at the Mouth of the Columbia River, USA. Coast 180 1104285. 8 National Data Buoy Center. Station History Station 46029. Accessed 8 2025. 9 2023, X-Beach Manual, Release X-Beach 1246057 Halloween. Sensitivity of Storm Surge Modeling to the Representation of Atmospheric Forcing, the Case Study of Hurricane. Abstract. In early September 2017, hurricane made landfall in St. Martin and generated major storm surges. The present study reveals the strong sensitivity of such storm surge modeling to the choice of atmospheric forcing. Several simulations are performed with the coastal and regional ocean community model under various atmospheric forcings, either a typical global reanalysis or a parametric vortex with 2 tested resolutions, 0.25 and 0.08. The best results are obtained with the higher resolution parametric vortex forcing, leading to a maximum storm surge of 1.83 m in agreement with observations. By contrast, using a global reanalysis forcing that strongly underestimates the hurricane intensity only captures 16% of the observed surge. Limitations associated to using a parametric forcing are finally unveiled, with an overestimated negative surge as the hurricane is leaving the island, most likely attributed to missing local vortex asymmetries and topographic effects on the wind field. A small time lag between the modeled and observed surges also likely results from uncertainties in the exact position of the cyclone. Keywords: 1. Introduction. Storm surges induced by tropical cyclones, TCs, are among the most costly and deadly natural disasters. 1. These surges are positive sea level anomalies, driven by atmospheric pressure gradients, wind stress, and wave-induced setup, combined with astronomical tides. Storm surge modeling is highly dependent on the representation of the TC atmospheric conditions. 2, 3, notably TC intensity, duration of intensification, size, landfall angle, forward speed. 4, 6, and the spatial and temporal resolutions. 7. Available atmospheric reanalysis data have a relatively coarse resolution and tend to underestimate the TC intensity. Another alternative is to build a TC parametric representation fitted to available data, which are the best track reference dataset, providing TC maximum intensity and track based on all available observations. Such representations, however, cannot represent the fine-scale asymmetries of the cyclone. More realistic cyclonic wind fields can be obtained with high-resolution atmospheric models, but they are more complex to implement and computationally expensive. In September 2017, TC struck the north of the Caribbean Sea as a Category 5 hurricane FIG. 2.1, causing significant storm surges, particularly in the northern Caribbean arc and Florida. 8. The tide gauge on the island of St. Martin recorded a surge of 2 m, and Al. 9, based on field surveys, estimated that the local surge reached up to 3 m. The present study aims to investigate the sensitivity of a storm surge modeling system to the representation of atmospheric conditions at St. Martin, where made landfall. This analysis will help improve the understanding and accurate modeling of TC-induced storm surges, which is crucial for better characterizing this hazard and developing more effective adaptation strategies. 2 methods. 2.1, Ocean Model Configuration. Numerical simulations of the storm surge induced by hurricane are carried out with the Coastal and Regional Ocean Sea Model, version 2, CROCO, Org Records 11036115. It is a free-surface oceanic model running on structured mesh, with a split explicit time-stepping scheme and terrain-following coordinates. In this study, CROCO is configured to solve the three-dimensional incompressible primitive equations under the hydrostatic and approximations. We use the model's two-way nesting capabilities, provided by the grid refinement in Fortran AGRIF Package 10, to refine the resolution around the region of interest. A 3-resolution domain covers the northern Caribbean arc, followed by 2 successive zooms around the island of St. Martin, resulting in nested domains with 600 m and 120 m resolution, respectively, Fig. 2.1. Regional bathymetric digital elevation models with 0.00511 and 0.001 resolution, Org 1017183, MNT ANTN 100M, HOMONIM WGS 84, are used, with the former applied to the 3 grid, and the latter to the 2 finer resolution domains. All 3 domains have 32 vertically stretched levels, with default stretching parameters, 7, 2, 200 m, that provide enhanced resolution near the surface and the bottom. The model is run with its default for regional simulations, forced by momentum and heat bulk fluxes, varying atmospheric pressure, see sect. 2.2. The lateral boundary and initial conditions are derived from the daily mean of the global ocean reanalysis provided by the EU Marine Service information, with a horizontal resolution of 112 and 50 vertical levels, Org 1048670, MWA 00021. Our simulations include tidal forcing derived from Oregon State University's TPXO 7 global ocean tide models. Simulation outputs are given at a 10 min frequency. 2.2 Atmospheric forcing. Ocean model configuration. The boundaries of each domain are shown as dashed lines. The cyclone track is represented in black, with the color of the dot indicating the wind intensity. The green cross indicates the position of the tide gauge on St. Martin Island. 2.3 Tide gauge data. Storm surge simulations are validated against 1 min observations from the tide gauge located at St. Martin, minus 63.085 E, 18.083 N, Org 10-17183, REFMAR 159. The raw data are first processed with an interquartile range filter to remove outliers, followed by the application of a filter with a 10 min cutoff frequency to reduce noise and match the model output frequency. 3 results. Time series of wind intensities, atmospheric pressure top panel, and free surface anomalies bottom panel during hurricane at St. Martin for the tide gauge observations and the 3 simulations at the model closest point to the tide gauge. Modeled and observed free surface anomalies are calculated relative to pre-surge mean sea level. Examining the modeled storm surges generated under these different atmospheric forcings, Fig. 2.2, bottom panel, shows that the best agreement with the observed maximum surge amplitude is achieved with WI008, showing a bias of only +5, followed by WI025, with a bias of -29. In contrast, the maximum surge modeled under ERA 5 forcing is significantly underestimated, consistently with its wind speed underestimation, resulting in a bias of -1.5 m and a maximum surge reaching only 16% of the observed peak value. The temporal lag between the peak surge in the observations and that modeled with WI008 and WI025 is most likely associated with the uncertainty of a few kilometers in the exact position of the cyclone in the hourly interpolated best track data. The highest correlations between the simulations and the observations are obtained with a +30 min lag applied to the simulations, resulting in correlations of 0.92 and 0.96 for WI025 and WI008, respectively. Modeled free surface anomalies for WI008 on 609 at 10H left and 12H right for the 600m and 120m resolution domains. Black arrows indicate wind direction. Their norm is proportional to wind intensity. Dashed lines show contours. For discussion and conclusion. This study demonstrates that intensity and spatial resolution are critical factors in modeling localized storm surge events, such as that generated by TC in St. Martin. Using ERA 5 winds, which are poorly resolved and significantly underestimated, results in a major underestimation of the storm surge, with the maximum value reaching only 16% of the observed peak. Using parametric forcing with similar parameters but varying resolutions, we observe local wind intensity differences of up to 15 ms1 and changes in the maximum storm surge amplitude of 34, highlighting the importance of choosing an appropriate resolution. The finer resolution, 0.08, parametric forcing accurately represents the surge peak with a bias of +5 compared to the observations. However, this forcing has some limitations, as it does not represent local wind effects, such as the influence of topography on the cyclonic vortex. It is also worth noting that the ERA 5 surface pressure field was used for all atmospheric forcing, with an atmospheric pressure of 975 at St. Martin, while being underestimated, minimum TC central pressure of 914, reported by ACS during landfall on the island, suggesting that the inverse barometric effect is also underestimated in our simulations. If this missing effect was taken into account, we would expect the slight overestimation of the surge modeled with the WI008 forcing to be further accentuated. However, the validity of using a local maximum wind, as provided by ACS, in a parametric formulation based on an azimuthal profile, is questionable, as this approach can lead to an overestimation of the wind's 14. The resolution of the oceanic grid also plays an important role in surge modeling. We ran 2 additional simulations, one with an additional refinement of 40m resolution, and one limited to the 600m nest only. The first converges with the 120 m grid results, showing a 1.49 m surge at the tide gauge location, while the second reaches 1.05 m only. The resolution of 120 m thus appears satisfying to accurately represent the effects of wind and atmospheric pressure on the surge. However, wave effects on the surge were not considered and would require a higher resolution grid to be accurately represented. Overall, regardless of the forcing used, storm surge modeling is constrained by inherent uncertainties in the position of the TC. Even with state-of-the-art reference data on TC position, such as the ACS dataset, the TC position is typically available only every 3H and must be interpolated between these two positions, bringing some uncertainty. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Needham H.F. Al. 2015, A Review of Tropical Cyclone-Generated Storm Surges, Global Data Sources, Observations, and Impacts. Rev 53-2, 545-591. 2. N. Al. 2018, Recent Progress in Storm Surge Forecasting. Cyclone Rays Rev 7-128, 139. 3. N. Al. 2012, On Hurricane Parametric Wind and Applications in Storm Surge Modeling. J. Race 117 D9. 4. M. Al. 2022, Impact of Highest Maximum Sustained Wind Speed and its Duration on Storm Surges and Hydrodynamics along Krishna-Godavari Coast. Dyn 59, 310571078. 5. Irish J.L. Al. 2008, The Influence of Storm Size on Hurricane Surge. J. 38 92003213. 6. A.N. Al. 2020, Impact of Tropical Cyclone Landfall Angle on Storm Surge along the Mid-Atlantic Bight. J. Rays 125-4. 7. M. Al. 2024, Storm Surge Modeling Along European Coastlines, The Effect of the Temporal Resolution of the Atmospheric Forcing. Ocean Model 192, 102432. 8. So S. Al. 2019, Storm Surge from Hurricane along the Florida Peninsula. Coast Shelf 229 106402. 9. T. Al. 2019, Coastal Processes and Influence on Damage to Urban Structures During Hurricane Martin and French West Indies. J. Marine 77215. 10. L. Al. 2012, Two-Way Nesting in Split Explicit Ocean Models, Algorithms, Implementation, and Validation. Ocean Model 49, 5121. 11. Regional 500 m Bathymetric Digital Elevation Model of the Antilles Zone for Hydrodynamic Modeling, Project. SHOM and External Organizations, 2017. 12. S. Al. 2024, Unveiling the Global Influence of Tropical Cyclones on Extreme Waves Approaching Coastal Areas. NatureCom 15 16593. 13. H.E. Al. 2006, Parametric Representation of the Primary Hurricane Vortex. Part II, A New Family of Sectionally Continuous Profiles. Monthly Weather Rev 134, 1102-1120. 14. Avinas, Al. 2023, Re-examining the Estimation of Tropical Cyclone Radius of Maximum Wind from Outer Size with an Extensive Synthetic Aperture Radar Dataset. Monthly Weather Review 151-12, 3169-3-189. Equilibrium pocket beach design by combining shoreline S and X beach. Abstract. In designing pocket beaches enclosed by hard structures, the equilibrium shoreline position and the morphological response to storm conditions are key aspects. In this paper, a generic methodology is presented that can be used to design pocket beaches based on equilibrium profiles and assess the performance on storm retreat, long-term losses, and assessment of suitable ecological habitats. The proposed methodology is an iterative process composed of three main steps. 1. Determining the equilibrium shoreline. 2. Storm impact modeling. 3. Assessment of the beach performance and ecological evaluation. The equilibrium shoreline positions are modeled with a calibrated shoreline S model. The storm response of the pocket beach is computed with an X beach model validated on hydrodynamics, waves, currents, and morphological changes. Based on the assessment of the pocket beach performance, using shoreline retreat and sediment losses as the main parameters, the design of the structures and shoreline is then altered iteratively. The methodology presented in this study has been developed during a 10 years rehabilitation project of the Romanian coast. During this project, the phased construction sequence enabled continuous improvement of the methodology and the implemented numerical models using field measurements. Keywords. 1. Introduction. More than half of the world's coastline, 51%, features headland bay morphology, commonly referred to as pocket beaches. 1. These beaches are typically situated between two headlands or coastal structures. Man-made pocket beaches are frequently found on coastlines without natural sand supply. 2. The design of these pocket beaches involves a comprehensive understanding of coastal dynamics and sediment transport processes to achieve a stable equilibrium profile. Key considerations in pocket beach design include determining the equilibrium profile in both cross-shore and longshore directions, assessing the beach response to storm events, and subsequently evaluating the long-term beach stability. Sediment transport patterns in pocket beaches could lead to loss of material, which should be minimized to avoid the need for additional maintenance works. In this study, a generic methodology is presented that extends the approach of AL. 3. That was previously used to design pocket beaches in Romania. The presented methodology in this study can be used to design pocket beaches based on equilibrium profiles and assess the performance on storm retreat, long-term losses, and assessment of suitable ecological habitats. Location of the site, Romania. Also shown, locations of the design beach cell areas, red, project sites purple, green, field campaign sites magenta, sensor positions inset, and satellite image of the site source, Google Earth. 2. Methodology. Showing the proposed methodology for pocket beach design. 3. Results. 3.1. Equilibrium shoreline. Based on the position of the coastal structures, the equilibrium shoreline position was determined using shoreline S5, taking into account the wave sheltering effect of the structures. The shoreline S model was calibrated, providing an optimal set of diffraction parameters, which was needed to accurately reproduce shoreline behavior of a recently constructed pocket beach close by. 6. Next to the equilibrium shoreline shape, the seasonal variation of the coastline around the equilibrium was evaluated. The equilibrium cross-shore profile is essential for predicting how the beach will respond to wave action and sediment transport. This profile was determined using a fitted Dean profile on bathymetry measurements at existing sandy beaches in the project region. Finally, these equilibrium concepts were combined into a 3D model that was merged with the surrounding bathymetry and structures. At the study site, the bed level is composed of alternating smooth sandy beds and rough rocky features. To incorporate this rugosity in the model, a smoothing algorithm was applied using a moving average separating the smooth bed from the rough elements. The bed friction layer was constructed from this rugosity by conversion to a spatially varying Manning field using Strickler's formula. Including seabed irregularity this way, grid size dependencies and steep bathymetry, gradient, related modeling errors were resolved. 3.2 Storm Impact Modeling. To assess the performance of the design beaches during storm impact, X-beach simulations were conducted for the zones depicted in Fig. 1. Boundary conditions for the storm impact modeling were obtained from a calibrated SWAN model, providing wave input for various combinations of return periods, 100-year, and storm directions, 30-120 N. Based on the equilibrium pocket beach design, X-beach models 7 were set up to assess the storm impact and beach performance, see Fig. 3. The model setup process was largely automatized using data and beach designs in QGIS, combined with the open-source X-beach Python toolbox, COM toolbox. X-beach models developed in this study consisted of seaward slope extensions, 135, and lateral extensions of at minimum 1000 m to limit boundary effects. The cross-shore resolution of the models ranges from 18 m offshore to 2 m at the coastline, whereas the alongshore resolution ranges from 20 m to a minimum of 5 m at the coastal structures. To allow for wave transmission in the model, shore parallel sections of the coastal structures were artificially submerged. On these sections, the flow and wave roughness in the model was locally enhanced to prevent unrealistic currents. 5 field campaigns were undertaken to collect bathymetric surveys and measurements of waves and currents. These measurements were used to calibrate and validate the X-beach model settings. Wave measurements were done to 1. Assess the wave propagation across rocky outcrops compared to smooth sandy beds, and 2. Assess wave transmission through coastal structures. X-beach reproduces the short and wave swell, averaging RMSEIG 009 m and RMSESW 023 m over the all sensors during the November 2023 storm. Statistical measures, RMSE of the modeled short HM0SW and HM0IG, wave heights for the survey during the November 2023 storm. Locations indicated in Fig. 1. Parameter RMSE. Sensor 14M sensor, 55M sensor, 35MG sensor, 35MLS sensor, 35MLM sensor. Average HM0 SWM 0.07, 0.34, 0.24, 0.39, 0.04, 0.23, HM0 IgM 0.06, 0.08, 0.11, 0.06, 0.11, 0.09. 3.3 Beach performance. The X-beach model results were post-processed to determine the beach performance in terms of shoreline retreat and sediment losses caused by storm events, see Fig. 3. For each beach cell, requirements were for the maximum allowable retreat and sediment losses. Based on a large set of extreme conditions, a probabilistic approach was used to estimate the long-term losses from the pocket beaches. These results of this beach performance was used to alter the beach design, coastal structures, or to determine maintenance requirements and buffer volumes. Based on bathymetric measurements performed over a period of 5 years in this project, validation of the X-beach model showed reasonable predictions of sediment losses over this period 7. Example of the designed pocket beaches at Jupiter-Neptune presented as X-beach model input left, and the resulting sedimentation erosion pattern during a design storm. For discussion and conclusion. The methodology to design pocket beaches proposed in this paper has been applied along the Romanian Black Sea coast, where semi-protected pocket beaches were designed and constructed. An example of this result is presented in error. Reference source not found, which shows the designed pocket beaches at Jupiter-Neptune along with the morphological response computed by XBeach during design conditions. The presented method has been applied to design and construct pocket beaches along the microtidal Black Sea. While the method may also be suitable for areas with larger tidal ranges, further research is necessary to explore potential adjustments to account for larger tidal ranges. Additionally, long-term monitoring is required to validate the behavior of these beach cells over longer periods of time and assess maintenance requirements. This study presents a generic approach to designing and assessing pocket beaches, relying on equilibrium beach profiles and their response to storms, refined through multiple design iterations and field measurements. 3 main steps were found to be necessary for the design of pocket beaches at the field site of this study. 1. Determining the equilibrium shoreline. 2. Storm impact modeling. 3. Assessment of the beach performance and ecological evaluation. By including the equilibrium beach design with shoreline S and validating the XBeach model, this design approach is an improvement on the method by Al. 3. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Short AD, G. 1999, Embayed and Structurally Controlled Beaches. In Handbook of Beach and Shoreface, 232-49. 2 JM, J. 1988, Design of Pocket Beaches. The Spanish Case. In Coastal Engineering, 1411-1425. 3C, Pater P. H. J. 2018, Coastline Rehabilitation Application of Advanced Models and Practical Solutions to Develop a Sustainable Low-Maintenance Coastal Defense Scheme. In Coasts, Marine Structures and Breakwaters 2017, Realizing the Potential. ICE Publishing, 859-868. 4D, A. Van AP, JVT Call R. J. 2009, Modeling Storm Impacts on Beaches, Dunes and Barrier Islands. Coast 56, 1112-1133-1152. 5D, B. A. M. J. 2020, Efficient Modeling of Complex Sandy Coastal Evolution at Monthly to Century Time Scales. Frontmar, 7535. 6L, Brandenburg PGF, 2025, Equilibrium Beach Planform Assessment with the Shorelines Model. Thomas South Case Study, Romania Manuscript submitted for publication. 7WP, Van CWT, Brandenburg PGF, E. 2025, Long-Term Pocket Beach Morphology at the Romanian Coast, Field Measurements and Numerical Modeling. Manuscript submitted for publication. Eco-Dune Response to Beach Nourishment along the Northern Outer Banks Coast, North Carolina, USA. Abstract. It is recognized that beach nourishment can enhance sediment available for aeolian transport and dune growth in windy coastal settings. Additionally, recently constructed dunes often differ from naturally developed dunes in their plant communities and composition, which can alter the style of dune growth through interactions. However, directly quantifying the influence of beach nourishment and management activities on dune behavior is challenging due to the complexity of coastal sediment transport dynamics and a lack of field data at appropriate temporal scales. Here, we assess morphological and ecological changes to 3 beach dune systems in Duck, NC, USA at high temporal frequency over 1 year following a beach nourishment. We found that the average crest and toe elevations of the dunes at all sites increased. However, One of the dunes experienced net volume loss despite the addition of sand to the dune and adjacent beach. Importantly, we found that patterns and magnitudes of local deflation and accretion observed across these sites are correlated to bidirectional, positive feedbacks between vegetation and sedimentation. Keywords. 1. Introduction. Beach and dune nourishment are common mitigation strategies used to counteract some of the effects of erosion and sea level rise, thus improving annual to decadal scale coastal resilience. 1. The ability of dunes to grow and/or recover from storm impacts is linked to sediment availability and vegetation-sediment interactions, both of which are altered following nourishment of the adjacent beach. Past research suggests that sediment added to beaches can serve as an additional source of sand available for dune growth through Eolian processes too. Dune growth may be further enhanced through interactions in which dune grasses physically trap sediments and alter local nearbed wind fields, shear stress, leading to altered deposition patterns. These processes can vary depending on the species, density, and location of dune grasses across the dune face 3. However, the direct influence of beach nourishment and dune management on dune behavior, through increased sediment availability and subsequent dune processes, remains poorly constrained. Aerial imagery of the study area in North Carolina, and a Rose diagram B of wind speed measured between March 2023 and May 2024 from the U.S. Army Corps of Engineers Field Research Facility, FRF, Pier Mill Catalog. Dune study sites are at Ocean Pines C, Snow Geese D, and the FRF. 2. Study area and background. The Outer Banks of North Carolina, USA experience periodic dune erosion from extratropical and tropical storms 4. In response, 420,500 m3 of sand from an offshore borrow source was emplaced onto a 2.7 stretch of beach in Duck in May 2023. We studied morphological dune change following the beach nourishment at 3 sites, Fig. 1. 2 sites, Ocean Pines Op. Fig. 1C, Snow Geese SG. Fig. 1D, were located within the nourishment zone. The dune at SG was artificially widened using bulldozers, adding 76 m3m of sediment to the dune, and sand fences were emplaced on the dune crest and upper Stoss slope. Sand fences were also installed on the Op lower Stoss slope. Tillers were planted in August 2023 on the upper Stoss slope, SG, lower Stoss slope Op, and dune toe Op to supplement existing vegetation. Our final study site was located 350 m south of the nourishment bounds within the U.S. Army Corps of Engineers Field Research Facility, FRF. Fig. 1E, this site was unmanaged. Locally, tides are semi-diurnal with a range of 1 m winds, prevail most often from the north-northeast and south-southeast quadrant. Fig. 1B. Wind speeds are generally lowest between June and August, and highest in January through March. 3 methods. 3.1 Topographic surveys and change calculations. We established 5 cross-shore profiles at each site to monitor topographic changes of the beach and dune. Fig. 1CE. We collected topographic surveys along each once in March 2023 before the nourishment, bi-weekly from May to August 2023, and monthly thereafter, 19 profile sets total. Surveys were collected using a real-time kinematics GPS and extended 4 m landward of the dune crest to the position of the waterline at the time of the survey. From each profile, we extracted the cross-shore locations and elevations of the dune crest elevation maxima of a given profile and dune toe, using the maximum curvature approach 5. From these, we identified cross-shore positions of deflation and/or accretion, including dune toe trajectories, and calculated dune volume changes. Dune volume was defined as the integrated area between the dune toe and the most landward position of the, representing the volume change per unit longshore distance, m3m, between surveys. Changes in morphology metrics are reported as net averages plus or minus the standard deviation. 3.2 Vegetation surveys. Vegetation surveys were conducted in March 2023, July 2023, March 2024, and May 2024 using 0.25 m2 survey plots along each at the dune crest, Stoss slope, and toe Fig. 1 CE. For each plot we community composition, species richness, and vegetative cover, estimated as a visual percentage of surface area. We used simple linear regressions to assess relationships between elevation change, calculated July 2023, May 2024, and vegetative cover and species richness at each site. 4 results. 4.1 Dune profile change. Over the course of the study, dunes at OP and FRF experienced net volume increases of 19.352 m3m and 7.749 m3m, respectively. However, the SG dune lost some of the initial volume, 147 m3m, between May 2023, immediately post-nourishment, and May 2024, with the maximum loss of 12.7 m3m among all SG transects. Dune topographic surveys immediately following the nourishment, May 2023, and 1 year post-nourishment, May 2024, at the Field Research Facility, FRF, Snow Geese SG and Ocean Pines OP sites. Vegetation. 4.2 Vegetation. Vegetation metrics varied between sites, dune positions, and temporally, Fig. 3. The OP dune had established vegetation across the dune profile prior to nourishment. The FRF dune was consistently well vegetated, whereas the SG dune toe and lower Stoss slope were regularly bare. Species richness, a scalar metric where higher values indicate more diversity, ranged across the OP crest, 0.2, Stoss slope, 0.5, and toe 0.3. SG dune crest 0.3, Stoss slope 0.2, and toe 0.1. And FRF dune crest 2.6, Stoss slope 0.5, and toe 0.1. The highest maximum vegetative cover for the dune crest, Stoss slope, and toe positions occurred at the FRF crest, 94%, FRF slope 99%, and OP toe 63%. Fig. 3. The dune at SG had low vegetative cover at the Stoss slope, range, 0.50%, and toe, range, 0.3%. Between the two growing seasons, the average vegetative cover increased at the OP crest, 0.8%, and toe 1.7%. SG crest 6.6% and Stoss slope 22.8%, and FRF dune crest 8.9%, Stoss slope 43.3%, and toe 5%. Average vegetative cover decreased on the OP Stoss slope, 1.2%, and did not change at the SG dune toe. Variations in average total percent vegetative cover, measured in 0.25 m2 plots. Bars indicate minimum and maximum vegetative cover. 5 Discussion. Dune growth is often observed following beach nourishments, e.g. 6. We found that the dune crest and toe elevations increased at all of our sites, though the increase in crest height was negligible at OP. Following beach dune nourishment at SG, the dune experienced net erosion. At OP, where only the beach was nourished, the dune accreted. Dune growth at OP exceeded that at FRF by 11 m3m. The difference in the magnitude of dune accretion between OP and FRF could indicate that the beach nourishment has a strong effect on aeolian transport rates, allowing for accelerated dune growth adjacent to the nourished beach during an otherwise generally period. Alternatively, the growth at FRF relative to the erosion of SG may suggest that, as observed at neighboring beaches 7, distal dunes can be positively influenced by nourishment through delivery of reworked sand to the beach. The spatial variability in the net effects of beach nourishment on dune volume and morphology may be explained, in part, by feedbacks. It is well known that vegetation-sedimentation interactions can drive morphological changes in dunes under natural conditions 8. Our work provides evidence of positive feedbacks between sedimentation and vegetation following beach nourishment. Notably, the lower stoss slope of the SG dune was deflated by over 0.5 m following dune replenishment, Fig. 2, likely due to sediment compaction 9, and wind-driven erosion. The lack of vegetative cover on the stoss slope contributed to net dune erosion, as indicated by the simple linear regression results, in two likely ways. 1. Without the stabilizing presence of vegetation, finer sediments were winnowed from the stoss slope. And 2. Without the added surface roughness provided by above-ground vegetation, sediment trapping and deposition were diminished. Like previous studies 10, our results also suggest that the specific planting scheme plays a primary role in the spatial distribution of sediment deposition. The cross-shore deposition at SG and OP was predominantly at the locations of sand fence installations and vegetation plantings, Fig. 2. The sand fences, planted vegetation, and consequent incipient dune growth on the lower stoss slope at OP likely inhibited sediment transport further landward into the dune, resulting in the relatively static morphology landward of the incipient dune. In addition to the observed relationship between vegetative cover and sedimentation, we found vegetative cover generally increased following beach nourishment, even at unplanted sites, Fig. 3. These bidirectional, positive feedbacks underscore the role of processes on dune behavior following beach nourishments. 6 conclusions. This study demonstrates the highly interconnected nature of vegetation, sedimentation, and management decisions in dune dynamics. By quantifying spatial changes in dune morphology and ecology at 3 beach and dune systems over a 1-year period, following a beach nourishment in Duck, NC, USA. The 2 sites within the nourishment bounds had opposing responses to the nourishment during the study period, with the OP site experiencing substantial growth and the SG site losing volume. We found the net erosion of SG to be significantly explained by vegetative cover, or lack thereof, on the dune. Ultimately, our results suggest that strategic vegetation plantings can be leveraged by managers to amplify the benefits of beach nourishment through effective trapping of aeolian sediment, facilitating dune growth, and/or reversing dune erosion. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 MA, BC, B, AP, TA 2021. Beach nourishment has complex implications for the future of sandy shores. Rev Earth Environ 2, 17084. 2 HL, Kana T, SB, R 2018 Beachfill equilibration and dune growth at 2 large-scale nourishment sites. Ocean Dine 689119111206. 3.0 Moore LJ, 2013. Vegetation controls on the maximum size of coastal dunes. Proc Acad 11043, 17217172222. 4 MP, N, Adams PN, 2023. Total water level controls on the trajectory of dune toe retreat. Geomorphology 438 108826. 5 HF, AH, Ra, Howd PA 2007. A simple model for the spatially variable coastal response to hurricanes. Mar 230, 814120. 6A, G, KF, D, Jackson NL 2009. Beach nourishment and fordune restoration. Practices and constraints along the Venetian shoreline, Italy. J Coast Res 56280, 7291. 7A Al, 2018. Evolution of a beach nourishment project using dredged sand from Navigation Channel, Dunkirk, northern France. J. Coast, 22 457 474. 8 Ra Al, 2015, Going with the Flow or Against the Grain. The promise of vegetation for protecting beaches, dunes, and barrier islands from erosion. Front Environ 1342, 03210. 9 SG, PA, GMD 2020, Controls on Dune Scarping. Prague, Earth Environ 4469, 23947. 10 SS, N, Davis A, White A, CJ, JC, 2024, Exploring Ecological, Morphological, and Environmental Controls on Coastal Foredune Evolution at Annual Scales using a Process-Based Model. Sustainability 16-83460. Methodology for the design and implementation of nature-assisted beach recovery techniques. Abstract. Dry beach width varies according to the incoming marine dynamics. Winter storms erode beaches, which then recover during summer as calm marine conditions produce accretion. A wide dry beach is essential to provide protection against erosion and flooding due to winter storms and sufficient space for tourism and leisure activities. Hardening marine climate due to climate change effects prevents the full recovery of beaches during summer. Nature-assisted beach enhancement, NABE, techniques are useful tools to boost beach resilience and achieve wider dry beaches. Here we focus on plowing and 3 options of scraping, depending on the location of the borrow and filing areas, which have proven to be effective solutions. This study proposes the first methodology to assist in decision-making and the design of NABE actions. The methodology is divided into 3 main steps. 1. Selection of the most appropriate technique employing a decision tree. 2. Description of the operational system that decides whether to apply a NABE technique on a particular date or not. And 3. The design of NABE actions. This methodology not only takes into account beach sustainability, but also considers goals, such as beach widening for touristic purposes. This is the first time that the tourism perspective is considered in the development of guidelines for the application of NABE techniques. Furthermore, it is also the first time that plowing is proposed as a coastal management tool. Keywords. 1. Introduction. Beaches erode under the action of winter storms and accrete during mild summer wave conditions. Accretion is a slow process that takes months, but there are nature-based solutions that enhance beach recovery. 1. These techniques become increasingly necessary to fight against climate change effects, as the beach nowadays is commonly unable to recover naturally all the sand lost during the winter. This loss of sand and dry beach width increases the risk of erosion, flooding, and insufficient space for leisure activities. NABE techniques. Left plowing. Right scraping. This paper includes the general methodology in SECT 2, which is composed of 3 main steps, SECS 2.1, 2.2, 2.3, and a summary of the conclusions in SECT 3. 2. Methodology. The methodology Fig. 2 SECS 2.1 to 2.3 for the application of plowing or scraping techniques is divided into 3 main steps. 1. Selection of the most appropriate technique employing a decision tree. 2. Description of the operational system that decides whether to apply a NABE technique on a particular date or not. And 3. The design of NABE actions. Each of the steps requires basic data on the specific location in which the NABE technique wants to be applied. These data comprehend knowledge of the beach, sediment characteristics, wave and tides historical time series and forecast for the following days, and historical data of the spring-autumn beach variation. The knowledge required to manage these data and achieve the goal is given in the following. Methodology for the application of NABE techniques. 2.1 Step 1. Selecting the most appropriate NABE technique using a decision tree. The selection of the most appropriate NABE technique should be made with the support of the decision tree of Fig. 3. This decision tree also indicates if NABE techniques are adequate for the study area or not. This methodology is only applicable to fine sand beaches without environmental restrictions in the area and the presence of seasonal variability on the beach, with natural accretion that can be enhanced. Decision makers should have basic knowledge of the beach under study to be able to answer the questions included in the nodes of the decision tree. Once the technique has been selected, the decision maker should continue in Step 2 of the methodology. 2.2 Step 2. Deciding which days are appropriate for applying a NABE technique. NABE techniques should be applied in spring when calm marine conditions are expected. Nevertheless, sometimes an unexpected spring storm can hit the coast under study. To prevent its impact on scraped or beaches, the setup of an operational system that determines if fair weather conditions are foreseeable is required. Besides, when applying NABE, we should consider its ecological impact. The intertidal area is a habitat for, and also a foraging, nesting, and breeding location for avifauna and turtles. 5. Assess the impact of beach scraping on, and did not find a detectable effect on biodiversity. Furthermore, the correct management of the beach can provide new habitats, such as a healthy and stable beach and dune. Nevertheless, some authors propose timing the actions to avoid turtle nesting periods or effects on migratory species. Both aspects are site-specific and must be considered during NABE design. Decision tree to choose the best NABE option for a beach. 2.3 Step 3. Designing NABE actions. A. Design of plowing. Plowing is performed during the low tide hours. Astronomical tides can be forecasted easily, and the schedule of the daily low tides is accessible. In the case of tides, the one that occurs during the daylight should be chosen to ensure the safety of the operations. Additionally, the hours with less affluence of people on the beach are preferable. These criteria allow the generation of a schedule of the hours of daily minimal tidal level during spring. The plowing actions and scraping can be performed from 2 hours before to 2 hours after the minimum tidal level occurrence. The requirements of machinery can be computed based on machinery performance, the availability of 4 hours working window, and the extent of the beach. Besides, it is important to adhere to the following recommendations when implementing plowing. 1. The trajectory of the tractor should be parallel to the low tide shoreline. This means that ridges and furrows are created parallel to the shoreline as well. 2. It is preferable to generate the ridge on the landward side of the furrow. 3. There should be enough rows of plowing to cover the maximum width of the intertidal area, from the low tide shoreline to the high tide shoreline marks. Do not the dry beach area. And 4. The maximum depth of the furrows should be 0.3 m. Design of plowing. Plowing is performed during the low tide hours. Astronomical tides can be forecasted easily, and the schedule of the daily low tides is accessible. In the case of tides, the one that occurs during the daylight should be chosen to ensure the safety of the operations. Additionally, the hours with less affluence of people on the beach are preferable. These criteria allow the generation of a schedule of the hours of daily minimal tidal level during spring. The plowing actions and scraping can be performed from 2 hours before to 2 hours after the minimum tidal level occurrence. The requirements of machinery can be computed based on machinery performance, the availability of 4 hours working window, and the extent of the beach. Besides, it is important to adhere to the following recommendations when implementing plowing. 1. The trajectory of the tractor should be parallel to the low tide shoreline. This means that ridges and furrows are created parallel to the shoreline as well. 2. It is preferable to generate the ridge on the landward side of the furrow. 3. There should be enough rows of plowing to cover the maximum width of the intertidal area, from the low tide shoreline to the high tide shoreline marks. Do not the dry beach area. And 4. The maximum depth of the furrows should be 0.3 m. Design of scraping. The maximum mobilized volume should be less than the naturally, no NABE actions applied, accreted volume during the summer season. The volume of accretion depends on the beach under study and the incoming marine dynamics, and its calculation requires data on the evolution of the beach in previous summer seasons, from spring to autumn. The valid data for this purpose are topographic field surveys of the dry beach and intertidal area, or shoreline position, from field data, satellite or aerial images of spring and autumn of the same year. Besides, it is important to adhere to the following recommendations when implementing scraping. 1. The maximum depth of the borrow area should be 0.3 m, and 2. Scraping can be performed on various days during spring. The sum of all the scraped volumes should not exceed the maximum scraping volume described above. A minimum lag of time of 15 days between scraping operations is recommended. Note that the placement of the borrow area depends on the variant of the scraping technique. L to B and L to BF take the sand from the low intertidal area, and therefore, the borrow area should approach the low tide limit as much as possible. On the contrary, U to D take the sand from the upper intertidal area, and therefore, the borrow area should start from the high tide limit towards the sea. Design of scraping. The maximum mobilized volume should be less than the naturally, no NABE actions applied, accreted volume during the summer season. The volume of accretion depends on the beach under study and the incoming marine dynamics, and its calculation requires data on the evolution of the beach in previous summer seasons, from spring to autumn. The valid data for this purpose are topographic field surveys of the dry beach and intertidal area, or shoreline position, from field data, satellite or aerial images of spring and autumn of the same year. Besides, it is important to adhere to the following recommendations when implementing scraping. 1. The maximum depth of the borrow area should be 0.3 m, and 2. Scraping can be performed on various days during spring. The sum of all the scraped volumes should not exceed the maximum scraping volume described above. A minimum lag of time of 15 days between scraping operations is recommended. Note that the placement of the borrow area depends on the variant of the scraping technique. L to B and L to BF take the sand from the low intertidal area, and therefore, the borrow area should approach the low tide limit as much as possible. On the contrary, U to D take the sand from the upper intertidal area, and therefore, the borrow area should start from the high tide limit towards the sea. See design of L to BF scraping option. The faster dry beach widening is achieved by the L to BF variant of scraping. In this case, the borrow area is located in the low intertidal area, and the sand is placed on the beachfront, extending the dry beach towards the sea. The design of the filling area is fundamental for the success of the actions. The naturally formed summer berm presents a crest elevation that matches the total water level exceeded 1% of the time, TWL 1%, where TWL astronomic tide plus storm surge plus wave R2. Placing the sand in a higher position will lead to less dry beach gain, and placing it in a lower position can cause the retreat of the machinery-created high-tide shoreline by wave overtopping the berm crest. Therefore, the artificially created berm of L to BF technique should try to mimic this natural berm crest level. Note that TWL 1% and the berm crest level is a dynamic variable that evolves monthly. As a consequence, we propose a mean value, TWL 1%, as a first proxy for the berm crest level, computed as the average of the TWL 1% values during the summer months, from May to October. Design of L to BF scraping option. The faster dry beach widening is achieved by the L to BF variant of scraping. In this case, the borrow area is located in the low intertidal area, and the sand is placed on the beachfront, extending the dry beach towards the sea. The design of the filling area is fundamental for the success of the actions. The naturally formed summer berm presents a crest elevation that matches the total water level exceeded 1% of the time, TWL 1%, where TWL astronomic tide plus storm surge plus wave R2. Placing the sand in a higher position will lead to less dry beach gain, and placing it in a lower position can cause the retreat of the machinery-created high-tide shoreline by wave overtopping the berm crest. Therefore, the artificially created berm of L/BF technique should try to mimic this natural berm crest level. Note that TWL 1% and the berm crest level is a dynamic variable that evolves monthly. As a consequence, we propose a mean value, TWL 1%, as a first proxy for the berm crest level, computed as the average of the TWL 1% values during the summer months, from May to October. 3 conclusions. NABE techniques, such as plowing and scraping, are designed to enhance sand accretion by taking advantage of natural processes, reducing the reliance on human interventions. Additionally, both techniques are applied using land-based means, making them cost-effective and easy to apply with widely used machinery for crops and civil works, and scrappers respectively. The NABE techniques proposed here are suitable for their application during spring on sandy beaches that present seasonal variability and do not have environmental restrictions. These techniques alone cannot solve persistent erosion problems, which require a thorough analysis of underlying causes and remedial actions. The presented methodology aims to support decision-makers in implementing NABE techniques effectively while considering beach sustainability and touristic objectives. The data required for decision-making and the design of actions is easily accessible, and the calculations are simple. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1E C P I M Medina R. 2024. Laboratory Evaluation of the Effectiveness of Nature-Assisted Beach Enhancement Techniques. Coast 188-104428. 2P 1983 Beach Scraping. Coast 7 167-173. 3J Al. 2019. Accelerating Beach Recovery by Plowing the Intertidal Bar, a field experiment along the northern Spanish coast. J Coast Res 35973. 4E O I M Medina R. C. 2024. Onshore Sediment Transport Enhancement and Evolution of Laboratory Experiments of Beach Plowing. Coast 192-104523. 5 Smith SDA, Harrison M.A., J. B. 2011. Assessing the Impacts of Beach Scraping on the of New Brighton Beach, Northern NSW. In Australian Coastal Society. 20th New South Wales Coastal Conference, Tweed Heads, NSW, 113-2011. 6 Dean R.G., 1973. Heuristic Models of Sand Transport in the Surf Zone. In Proceedings of Conference Engineering Dynamic Surface, Zone 208-214, 1973. 7 J.T. Al., 2010. Beach Scraping as a Coastal Management Option. In 19th NSW Coastal Conference, 120. Testing a coupled shoreline and beach dune model for a predictive digital twin of a hybrid dune dike system. Abstract. In recent years, predictive digital twins, PDT, have emerged as a potential tool to monitor and predict the behavior of dynamic systems, including nature-based solutions in natural coastal systems. Here, we test the potential of using a simple, coupled shoreline and beach dune model as a base for a PDT. The models exchange sediment flux balance information at each time step and recalculate shoreline positions and beach dune profiles accordingly. We test the concept in 2 cases: a schematized shoreline, and a case study in an existing hybrid dune-dike system. Results show that the model is sufficiently robust for consideration as a basis for the PDT. Expected alongshore patterns, such as increased dune growth for larger beach widths, emerged in the schematized test, whereas most of the trends found in the real case could also be simulated. The information exchange of sediment fluxes across beach compartments allows different models to operate at different timescales simultaneously. Of specific sediment fluxes between beach dune compartments may be done directly, considering sufficient information and a proper description of the process already exists. Further steps include the development of a more robust framework for model and data integration, and the inclusion of different existing or new coastal models. Keywords. 1. Introduction. The use of nature-based solutions for coastal protection is increasing across the globe. 1. It ensures that desired protection levels are met while reducing the relative environmental impact that usually comes with traditional interventions. While several benefits exist, nature-based solutions are complex and consequently hard to forecast given their associated natural dynamics. Digital twins, DT, emerged as a potential tool that uses process-based and data-driven models to predict system behavior based on near real-time data integration, providing stakeholders with insights into the system's potential use and reliability. Here, we evaluate and test the potential of using a coupled shoreline and beach dune model as a base for a PDT of a hybrid dune-dike nature-based solution. We apply the coupled model to a schematic case and a case study in the Netherlands, where a hybrid dune-dike system already exists. 2. A predictive digital twin, PDT for coastal systems. 2.1 Structure Overview. For our case, a PDT is a digital copy of a physical system based on models and data-driven methods, where regularly updated information from its real counterpart is used as a boundary condition for testing and forecasting. Fig. 1. A core PDT aspect is the connection with its physical counterpart, which feeds the virtual system and ensures the PDT adapts accordingly. For a hybrid dune-dike system, the virtual twin needs to reproduce not only immediate changes, but also forecast the decadal evolution of the system. Unlike traditional DTs, where feedback is immediate, the interaction between real and virtual counterparts in hybrid dune-dike PDT occurs on the timescale of interventions, such as nourishments, Fig. 1. Thus, the PDT must predict far into the future to evaluate the likelihood of failure and estimate the remaining intervention lifetime. To test the applicability of such a concept, we chose two models that work at decadal scales: the shoreline evolution model Shoreline S2 and the process-based beach dune model CS Model 3. The main reasons for these choices include their maturity in the scientific community, the relatively low computational effort, the capability to solve the system dynamics at the appropriate timescales, and the flexibility for relatively direct integration using sediment fluxes. The Shoreline S Model 2 is a vector-based coastline model designed to predict shoreline evolution over time scales of years to centuries. Coastlines are schematized by movable grid nodes, which allows not only erosion and accretion of the shoreline, but also the development of different coastline patterns, such as spits and islands, at a low computational cost. The model is based on sediment conservation and updates the coastline based on wave-driven alongshore transport gradients, while considering an active profile that extends from the depth of closure up to the foredune crest. The CS Model 3 is a semi-empirical, supply-driven numerical model designed to simulate the cross-shore beach and dune evolution at decadal to centennial time scales. Beach dune evolution is solved through a combination of profile schematization and sediment balance between different beach dune compartments, i.e. beach, dune, bar, making it appropriate for coupling with a model such as Shoreline S. It includes dune erosion, aeolian transport, sea level rise, and beach bar exchange, though the last is not included in the current study. The beach profile shape is updated every time step through equations that are functions of the sediment volume, available within each profile compartment. Diagram of the foreseen PDT, showing the interaction loop between the virtual and real systems, highlighting the role of the evaluation criteria in defining the feedback between the virtual counterpart and the real system. The red arrow emphasizes the role of the PDT when testing operational actions when evaluation criteria are not met. The current study focuses on the shoreline S plus CS model integration. Photo from 2.2 test cases. We employ 2 test cases, a schematic case for a proof of concept and a real-life case to explore the specific applicability. For the schematic case, we use a straight shoreline with a fore-dune height of 5 m alongshore, a shoreline direction of 300 on, and a constant wave boundary of 1.5 m approaching from 270 n. We run tests with different wind velocities, 5, 7, and 15 ms1. All from 270 n for some cases. We enforce a storm for 2 days. With a significant wave height of 5 m and direction of 270 n, a satellite image from the area. The elevation map of the area, highlighting 0 and 3 m contours used as the base for the modeling input. See final shoreline and location used in the coupled model. 3 results and discussion. Results show that while the main expected patterns were solved within the proof of concept, and consequently, in a potential PDT, additional functionalities may be needed for complex scenarios. The schematic case shows the expected behavior for both shoreline displacement and dune growth Fig. 3. Dune growth in the accreting north is around 60% larger than in the erosive southern area when considering a no-storm condition with very high wind speeds. By adding a storm, the southern area presents dune erosion in the order of 15 m3 m1, whereas the northern portion still has dune growth due to the increased beach width and potential dune supply in the order of 10 m3 m1. For the test case, the model accurately captured the alongshore spread of sand toward the extremes due to the shoreline bulbous shape, as well as the order of magnitude observed in the measurements. However, it did not simulate the shoreline displacement at the northern part of the beach Fig. 4. Predicting accretion of 10-20 m instead of the observed shoreline erosive trend of about 10 m results from the schematic simulation. An example of profile development after the simulation with a storm and constant wind of 15 ms1, highlighting the alongshore difference in dune height due to increased supply. B. Comparison between the initial and final shoreline, highlighting the accretion and erosion of the northern and southern sectors, respectively. See alongshore distribution of the change in position and fore-dune volume. For dune growth, the model captured most of the overall spatial variability, but overestimated their magnitude Fig. 4. Observed dune growth in the area was generally lower than in the adjacent coastlines, with higher values to the north, median difference of 15 m3 m1 between, and the northern stretch. For the simulations, the median difference is about 10 m3 m1, though the model dune volume across the entire coastline by 15 m3 m1. 4. Conclusion and next steps. Comparison between observed green and predicted yellow dune volume change, A, and shoreline displacement, B, after a 1-year simulation. Left to right represents SN open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References. 1 H.J. Van M. S.G.J. M.B. Baptist M.J. 2015. Sustainable Hydraulic Engineering Through Building with Nature. J. Hydroenviron, Res 9 159, 171. 2D. B. A. M. J. 2020. Efficient Modeling of Complex Sandy Coastal Evolution at Monthly to Century Time Scales. Frontmar 7535. 3C. M. H. 2019. Simulating Beach and Dune Evolution at Decadal to Centennial Scale Under Rising Sea Levels. PLOS 1144E02-15651. 4W Al. 2019 1. Marine Research Rapport, C00219. 5 Kroon A. M. S. S. 2022. Subaqueous and subaerial beach changes after implementation of a mega-nourishment in front of a sea dike. JMSC. MDPIAG, P. 1152. Org 103390-100-81152. Prediction of a longshore transport of cobbles on open-coast composite beaches and dynamic cobble berm revetments. Abstract. Composite beaches, which consist of a sandy foreshore and steep cobble berm, are a natural analog to dynamic revetments, a potential engineered option for nature-based erosion mitigation. Information about a longshore transport is critical for predicting the performance of these structures. However, the different drivers of a longshore sediment transport on composite beaches are not fully understood, and predictive capability for a longshore cobble transport is currently lacking. Here, we tracked 300 cobbles for the winter season on 2 different composite beaches and a dynamic cobble berm revetment. The average total alongshore transport distance increased as the number of hours waves interacted with the cobble berm increased. There was also an elevation above which the cobble transport distance was no longer significant. Additionally, in contrast to some previous studies, we found no relationship between either mass or sphericity and transport distance of the cobble. Results indicate that accounting for wave interaction time with the cobble berm is critical for predictions of a longshore transport of cobble on composite beaches. Keywords. 1. Introduction. Composite beaches are composed of a gently sloping sandy foreshore and a steep cobble berm that evolves over time under wave impact. The cobbles move and roll during impact and dissipate wave energy. However, the relative importance of the different drivers of a longshore transport of cobbles on composite beaches are not well understood. Composite beaches have been noted to be a relatively stable beach type 1, and in the Pacific Northwest of the United States, PNW, they are a natural analog to dynamic cobble berm revetments, which are a possible option for nature-based erosion mitigation. 1. Understanding the controlling factors of the alongshore transport rate of cobble is critically important for determining the resilience of composite beaches and for developing maintenance requirements for dynamic cobble berm revetments. Studies of composite beaches have suggested that cobble shape and size are predictors of transport distance. However, results have not been consistent between sites. In some studies 2-4, cobble mass and transport distance were correlated. In others, a correlation between cobble shape and transport distance were observed 3-4. However, another study in a similar environment 5 saw no relationship between either cobble mass or shape and transport distance. The sand elevation relative to the cobble berm has also been noted to be extremely important in controlling alongshore transport. Most transport happens later in the winter season as the sand lowers and waves interact more with the cobble berm too. Predictive equations for alongshore transport are available for both sand and gravel beaches 6-8. The predictive equations are based on a range of factors, including wave steepness, beach slope, grain size, and wave angle. However, no alongshore transport equations are available for composite beaches, which have a distinct cross-shore boundary in sediment composition. The objective of this study is to present field observations of alongshore cobble transport, wave, and wave direction on 2 natural composite beaches, and a dynamic cobble berm revetment to elucidate potential relationships that may be viable as predictors of alongshore cobble transport rates. 2 methods. To observe alongshore cobble movement, we adopted the procedures of two, who used radio frequency identification technology, RFID, to track the transport of cobbles. We collected and tagged cobbles from 2 natural composite beaches in Oregon, Arch Cape and Falcon Cove, and a dynamic cobble berm revetment in Westport, Washington with RFID tags. The cobbles ranged in size and represented the grain size distribution measured at the sites. We replaced half of the cobbles collected from each site in October 2023, Arch Cape and Falcon Cove, and December 2023, Westport, and replaced the remaining cobbles at all sites in January 2024. Throughout the 2023-2024 winter season, the cobble berm was searched 1-2 times per month with a handheld RFID antenna, and cobble locations were recorded with an RTK GPS system. During RFID tracking, cross-shore profiles were collected, and the location of the cobble toe across the entire RFID search area was recorded. For analysis, the alongshore displacement for each cobble was calculated between each survey. For each individual cobble, both the total displacement and the maximum displacement were calculated. The total displacement was based on the alongshore distance between the cobble's initial and final locations, and the maximum displacement is the maximum alongshore distance traveled between any 2 surveys. Wave data from offshore buoys and tide data from nearby tide stations was used to calculate the total water level, TWL, following 9, using the average slope of the cobble berm and the beach. Using the probability distribution of TWLs at each site, the elevations of the average, 2%, 1%, 0.1%, and maximum TWL were calculated. 3 results. Satellite images of beaches at A. Arch Cape, B. Falcon Cove, and C. Westport. Dots represent cobble detection locations, and lines represent the location of the cobble toe. Colors correspond to survey dates. Total alongshore displacement of each cobble from its starting position on each survey date dots, and average total alongshore displacement, solid dashed line. Cumulative hours of above the cobble toe, since cobble placement are displayed on the right y-axis, blue solid dashed line. Total alongshore displacement based on cobble starting elevation, purple-yellow dots. TWL elevations are indicated with dashed lines. For discussion. Our observations highlight a relationship between TWL and cobble transport distance. This result is intuitive. However, it cannot be predicted by existing equations for alongshore transport developed for fully sand or fully gravel beaches, which assume cross-shore uniform sediment characteristics. These results indicate that a time component describing how often the waves are interacting with the cobble berm is critical for any predictive tool for alongshore transport. Maximum alongshore displacement between any 2 surveys plotted against cobble mass, a C and sphericity D, F. The highest maximum alongshore displacement in each 0.5 size bin is plotted as a filled circle. The best fit line to all data is plotted in red. 5 conclusions. In this study, we used radio frequency identification, RFID, tags to track cobbles over a 6-month period on 2 natural composite beaches and an engineered dynamic revetment. We observed significant northward alongshore transport at the 2 natural composite beaches and negligible alongshore transport on the dynamic revetment due to its higher toe elevation. The alongshore transport distances increased as the cumulative hours of above the cobble toe increased. The upper elevation limit of transport was approximately the 0.1% elevation of the TWL for the natural composite beaches. On average, we did not observe a correlation between mass or sphericity and cobble transport distance. However, the highest maximum alongshore displacements were associated with smaller cobbles. Future work will aim to propose a predictive equation for cobble transport rates on composite beaches and dynamic cobble berm revetments. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 JC, R. Hart R. 2005, Dynamic Revetments for Coastal Erosion in Oregon. 2 JC, Hart R. JV 2006, The Use of Passive Integrated Transponder PIT Tags to Trace Cobble Transport in a Mixed Sand and Gravel Beach on the High-Energy Oregon Coast, USA. MAR 232, 6386. Org 101016J20060 7005. 3 Young AP, H. M.S., M.E. 2023, Cobble Tracking Observations at Pines State Beach, CA, USA. J. Ray's Earth Surf. Org 1010292023, JF00 7199. 4 E. D. P. A. 2015, Short-Term Displacements of Marked Pebbles in the Swash Zone, Focus on Particle Shape and Size. MAR 367, 143, 158. Org 101016J20 1506006. 5 p.m., GM, CE, HM, D. 2021. And performance of a dynamic cobble berm revetment during a spring tidal cycle in North Cove, Washington State, USA. Coast 167, 103898. Org 101016J20 21103 6 JW 1991, A Longshore Sediment Transport Rate. J. Port Coast Ocean 117 624 640. Org 101061 ASCE 0 733950X 1991 117 6624. 7 Van E. A.J., Mason T. 2000, A Review and Assessment of Longshore Sediment Transport Equations for Coarse-Grained Beaches. Coast 42 43 275. Org 101016S037838839 000000314. 8 Van Lc. 2014, A Simple General Expression for Longshore Transport of Sand, Gravel and Shingle. Coast 902339. Org 101016J20 1404008. 9 MP Wilson G. Bond H. D.C. Predicting Wave on Composite Beaches. Coastal Engineering 199 104743, 2025. Org 101016J202 51044743. Sand Nourishments, Review of Research and Introduction of the Source Project. Abstract. Sand nourishments have become a popular management option to mitigate coastal retreat for sites with abundant sand supplies. Off-site sand is placed on the dry beach or underwater at typical water depths, up to 10 m. This nearshore zone has a high bed level variability and contains a cascade of morphological features. This makes the understanding and forecasting of nourishment and impacts challenging. The emerging climate change effects, sea level rise in particular, call for significant progress on this topic in due time. This paper presents an overview of field, laboratory, and modeling studies on nourishment. 4 key knowledge gaps were identified. First, the spreading of nourished sand through the coastal zone is poorly understood and has not been. Second, it is unclear how design variables such as size, placement location, and grain size affect the nourishment lifetime, spreading, and impact. Third, the cumulative effect of repeated nourishments on the coastal system is unknown. Fourth, models are not capable to reliably predict the morphological development and impact of nourishments. To tackle these knowledge gaps, we have launched the Source Research Project. Keywords. 1. Introduction. Over time, sand nourishments have become a popular management option to mitigate coastal retreat for sites with abundant, offshore, sand supplies. With nourishments, off-site sand is added to the coastal system to replenish sediment budget deficits. A distinction can be made between nourishments, where sand is directly placed where it is needed, and nourishments that aim for an indirect effect. In the latter case, sand is supposed to be transported to the area of interest utilizing natural transport pathways. The most common direct type of nourishments is beach nourishment, where sand is placed on the above-water beach, or just below mean sea level. Beach nourishments have been regularly carried out worldwide since the early 1900s. The first shoreface nourishment was implemented in the USA in 1935-1. Since the late 1990s, shoreface nourishments are common practice in the Netherlands. Shoreface nourishments are typically placed in 410 m water depths, which simplifies the construction and reduces costs and disturbances on the beach. Projected accelerated sea level rise requires rethinking of the nourishment strategy, e.g., whether or not volumes can be simply upscaled. At the same time, there is an increasing need to know in more detail how nourished sand spreads and affects the coastal functions and values, such as flood protection, nature, and recreation. This requires a sound understanding and reliable modeling of the impact and evolution of nourishments, shoreface nourishments in particular. This paper presents an overview of advances in research and introduces the Source Research Project targeted at addressing the identified knowledge gaps. 2. Review of research on shoreface nourishments. 2.1 Introduction. With nourishments becoming more and more commonplace, there is a wealth of field data. The last decades, the insights obtained on morphological behavior and driving processes have been complemented by laboratory experiments, conducted in controlled settings, and numerical modeling. More particularly, we have combined data from 40 historical nourishment projects in the Netherlands and USA between 1935 and 2009. Furthermore, we have made an overview of 10 shoreface nourishment laboratory experiments. Finally, we have categorized 13 numerical modeling studies from the period 2004-2024. In total, the review included around 100 coastal nourishment studies. 2.2 Example result: active and stable nourishments. Activity of historical shoreface nourishments in relation to empirical depth of closure, Ducey equations. As these are not based on the same parameters, the outer Ducey was calculated as shallower than the inner Ducey for 6 projects. Modified from 3 and 4 with ASCE permission. 2.3 Knowledge gaps. 1. Spreading of nourished sand is poorly understood, in particular the sediment exchange between the subaqueous and subaerial parts of the beach. Spreading of nourished sand is poorly understood, in particular the sediment exchange between the subaqueous and subaerial parts of the beach. 2. It is unclear how design variables such as size, placement location, and grain size affect the lifetime, spreading, and impact of shoreface nourishments. It is unclear how design variables such as size, placement location, and grain size affect the lifetime, spreading, and impact of shoreface nourishments. 3. The cumulative effect of repeated shoreface nourishments, scale, 110 years on the coastal system as a whole, 100 plus, 50 plus years is unknown. The cumulative effect of repeated shoreface nourishments, scale, 110 years on the coastal system as a whole, 100 plus, 50 plus years is unknown. 4. Models cannot reliably predict the nourishment development and impact. Models cannot reliably predict the nourishment development and impact. 3. Source project. Illustration of the source research project, including 4 work packages, WP. Our living labs will comprise 2 sand nourishments along the Dutch coast. The first living lab concerns an innovative shoreface nourishment planned for in 2025, which will consist of 6 elements with systematic variation in nourishment grain size, height, volume, and cross-shore position. The other living lab concerns the thinking process and conceptual design of beach nourishments primarily devoted to support the recreational function of the beach. These living lab nourishments will be co-designed, monitored, and evaluated together with 25 partners from international government organizations, research institutes, nature organizations, and industry. This is key for the intended societal impact. Co-created multifunctional sand nourishment strategies for resilient dynamic coastal flood defenses with high socioeconomic and natural values. This work is part of the research program Source, Sand End Strategies for Sustainable Coastal Ecosystems, funded by the Dutch Research Council, NWO, project number NWA 151822133. Furthermore, we would like to acknowledge internal research funding, the U.S. Army Corps of Engineers, funding through Coastal Inlets Research Program, CIRP, and Innovations in Sediment Management Strategic Focus Area, and the NWO Project 17595, CSCAPE, Sandy Strategies for Sustainable Coastal Climate Change Adaptation. Finally, acknowledges financial support from the European Research Council, ERC, under the European Union Horizon 2020 Research and Innovation Program, Grant Agreement No. 101,163,534. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Hall J.V., W.J. 1950, Test of Nourishment of the Shore by Offshore Deposition of Sand. Long Branch, New Jersey. Technical Memo No. 17. USACE, Washington, D.C., USA. 2 R.J. 1981. A Profile Zonation for Seasonal Sand Beaches from Wave Climate. Coast 4253-277. 3 Hands E.B. M.C. 1991. Mound Migration in Deeper Water and Methods of Categorizing Active and Stable Depth. Proceedings Coastal Sediments Conference, Seattle, Washington, USA. 1985-1991. Forfall, BC, K.E., A.M., Dr. 2021. Evaluation Techniques for the Beneficial Use of Dredged Sediment Placed in the Near Shore. JWPCE 147.5. Dredged Sediment Placement, Impacts to Salt Marsh Channel Metabolism. Abstract. Since the start of the 20th century, over half of global coastal wetlands have been lost, driven largely by coastal development and anthropogenic sea level rise. Key to designing effective marsh restoration projects to prevent further degradation is minimizing short-term ecosystem impacts. One important habitat restoration method currently in use is the placement of dredged sediment on the marsh platform to build marsh elevation. In 2019, the 7 Mile Island Innovation Laboratory, SMIL, was established as a testbed to advance marsh restoration techniques using sediment dredged from the New Jersey waterway. Since then, a number of sediment placements have occurred at the SMIL, but the spatial and temporal extent to which these placements affect the surrounding channel is unknown. We monitored a side-cast sediment placement for its biogeochemical impacts to the surrounding water column, and calculated metabolic rates before, during, and after placement to assess ecosystem impacts and function. We find that the sediment placement does drive short-term enhanced net, which persists beyond the signal of enhanced water column turbidity, but that this signal is comparable in both duration and magnitude to that driven by a seasonal tropical storm, suggesting that this type of ecosystem restoration strategy may be a promising solution with minimal long-term ecosystem effects. Keywords. 1. Introduction. Tidal salt marshes and wetlands provide a variety of ecosystem services that coastal communities and natural wildlife depend on, including blue carbon storage, permanent and transient habitat for many species, and protection from storm surges. 1. Because of their proximity to coastlines, salt marshes are also inherently susceptible to human interference, both directly from overuse and development, and indirectly due to anthropogenic sea level rise, SLR, which threatens to inundate their carbon reservoirs too. To combat marsh conversion to open water in the face of anthropogenic SLR, a variety of ecosystem restoration strategies are being used to prevent, stop, or reverse their degradation, including the placement of dredged sediment on the marsh platform. 3. The practice of beneficial use of dredged material, BUDM, has been authorized for use in the United States since 1986 and has been successfully applied across the Atlantic, Gulf, and Pacific coastlines to increase elevation. 4. Though effective at this, the spatial and temporal extent to which these BUDM placements affect the local ecosystem is currently poorly known. Previously, Fall Al. 2021, 5. Observed that elevated water column turbidity during a 2020 sediment placement returned to baseline after a few hours, indicating that resuspended sediment fell out of the water column within that time frame, and suggested that the total effect may end by that time too. However, biogeochemical changes can take longer to return back to baseline, and physical alterations may establish a new baseline that is different from the original. Here, we present water column and ecosystem metabolism rates before, during, and after a BUDM placement, providing functional indicators for a more holistic understanding of the system's recovery rate. 6. We find that sediment placement impacts ecosystem metabolism longer than turbidity remains elevated, but the ecosystem impact is comparable in magnitude to that driven by seasonal storms. We deployed instruments continuously collecting data from August 23 to October 19, 2023, capturing the period before, during, and after the placement. 7. This sidecast placement took place between September 2021, before ending somewhat abruptly due to an incoming tropical storm. It differed from previous BUDM techniques employed at SMIIL in that the sediment was actively dredged and immediately thrown by an arm off the side of the boat to various neighboring areas. We observed multiple times during the placement where sediment hit the logging instrumentation. 2 methods. 2.1 Measurements and data quality. We deployed 6 in Aquatrol 600 series sondes in a 0.252 area along the waterway channel measuring conductivity, temperature, dissolved oxygen, dew, pH, pressure, and turbidity every 10. Sondes were deployed 100 feet from the middle of the waterway to avoid boater interference. All sondes were maintained and calibrated using manufacturer-recommended methods. After collection, data were quality controlled using a gross range test, spike test, stuck value test, and moving mean filter, based on quality assurance quality control of real-time oceanographic data recommendations, QARTOD, and best practices adapted from AL. 2023, 8. Discrete bottle samples were collected for laboratory chemical analysis of dissolved oxygen to validate sensor measurements. Triplicate dew samples were collected into 125 ml volume calibrated flasks at initial deployment, during the dredging period and final recovery, following standard Winkler protocols, and titrated within a week. 9. Measurements of wind speed, temperature, and atmospheric pressure were downloaded from Climate Data Store using the hourly ERA 5 reanalysis products. 2.2 Dial Oxygen Method. Net ecosystem metabolism, NEM, is increasingly being used as a measure of aquatic system health. 10. High-resolution dissolved dew measurements can be used to determine NEM, which is the difference between organic matter fixed by gross primary production, GPP, and that remineralized by ecosystem respiration, ER 11. This approach is based on a water column oxygen mass balance budget, where the change in dew in over time is due to biological processes, photosynthesis and respiration, air-sea gas exchange, and horizontal tidal advection. Because of the shallow nature of this area, we assume that the water column is well mixed. 3 Results and discussion. 3.1 Baseline and seasonal context. Of temperature, dissolved oxygen dew, and pH were characterized by large diurnal fluctuations, with dew concentrations frequently exceeding supersaturation during the day, and pH ranging from 7.6 to 8.3 Fig. 1A, B, and C. Temperatures were relatively consistent among the 6 zones, ranging from 13.9 to 30.6 throughout the period, indicating that they were all measuring the same local water mass. As late summer turned to fall, changes in oxygen solubility reflected falling temperatures, with oxygen slightly undersaturated during late summer, but closer to equilibrium or slightly supersaturated in fall. Turbidity increased significantly from summer into late fall at 2 zones, zones 4 and 6, but the system was consistently clear from turbidity over the monitoring period. 50 NTU, Fig. 1D. For each of the zones monitoring the sediment placement site, the 12H moving mean of A. Temperature, B. Dissolved oxygen concentration, with equilibrium dissolved oxygen concentration, black shown for reference, C. pH, D. Turbidity, and E. Daily, 24H, moving mean net ecosystem metabolism, NEM. 3.2 Impact of BUDM sediment placement. During the sediment placement period, black box Fig. 1, we observed an increase in turbidity, as expected due to the increase in sediment in the water column. We also observed a disruption of the diurnal cycles in dew and pH, together with a decrease in oxygen saturation and increase in pH, both consistent with net respiration. NEM calculated at all 6 sites showed enhanced net during the sediment placement period, minus 78.6188302 M2D1, followed by a short autotrophic period, 11.2307502 M2D1. The enhanced net is likely driven by the dredged sediments, supplying a temporary source of additional organic matter, enhancing in respiration, with the subsequent autotrophic period perhaps due to an influx of readily available nutrients remaining once the sediment has settled out. Tropical storm blue box Fig. 1 crossed through SMIL immediately after the sediment placement period. This provides the opportunity to compare the ecosystem impact of the BUDM sediment placement with the perturbation driven by the storm. The effect on turbidity, dew, pH, and NEM was similar to that of the sediment placement, driving enhanced turbidity and a relatively strong but short-lived heterotrophic signal. Tropical storm resulted in over 4 days, 6102 M2D1. Although it complicates interpretation of potential long-term effects of the sediment placement, the storm's occurrence during our study period serendipitously demonstrated that the short-term ecosystem impacts of the BUDM sediment placement were comparable in magnitude and duration to those driven by this tropical storm. 4 Conclusions. This study contributes important information about the impacts of dredged sediment placements on salt marsh channel ecosystem metabolism. As a ready-to-be-utilized nature-based ecosystem restoration solution, using dredged sediment to help elevate the marsh platform will likely be used in the future to help marshes keep pace with sea level rise. We found that the dredged sediment placement did temporarily alter ecosystem metabolism, driving strong short-term net The signal subsided within 24H, though did last longer than the signal of elevated turbidity, the direct effect of the additional sediment in the water column. The serendipitous occurrence of tropical storm, shortly after the sediment placement period, enabled the study to show that the impact of the dredged sediment placement on salt marsh channel ecosystem metabolism was comparable in magnitude to the perturbation driven by the storm. Storms similar to are a relatively common natural occurrence in this region during the fall, although storm impacts are also being by anthropogenic climate change, indicating that this ecosystem is resilient to metabolic perturbations of this duration and magnitude. These results provide a promising reassurance that this BUDM sediment placement had only limited and short-term effects on the local salt marsh channel ecosystem, although further research is needed to more comprehensively quantify the biogeochemical and metabolic effects of BUDM sediment placement in a wider range of ecosystems and using differing sediment placement techniques. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 EB, Hacker SD, Kennedy C, U, AC, BR 2011, The Value of Estuarine and Coastal Ecosystem Services. 81-169-193. 2 KB, BR, MD 2009, Centuries of Human-Driven Change in Salt Marsh Ecosystems. Revmar, 11117-141. 3 KB Al 2022. Laying it on thick. Ecosystem effects of sediment placement on an island salt marsh. Front Environ 10. 4 DJ, P. Will RJ 2004. Beneficial use of dredged material for habitat creation, enhancement, and restoration in New York, New Jersey Harbor. J. Environ Manage 73, 13952. 5 Falke, D. Tyler Z. Welp T. 2021. Field measurement and monitoring of hydrodynamic and suspended sediment with the 7 Mile Innovation Laboratory, New Jersey. ERDC, CHL Technical Report 21-9. 6 MKA, Islam MA Does J, AR 2022, Salt Marsh Restoration, an overview of techniques and success indicators. Environ, Raise 2911, 15347, 15363. 7 USACE Philadelphia District, 2023, Army Corps issues advisory regarding upcoming maintenance, dredging along NJ Waterway. Philadelphia District and Marine Design Center. 8H, AL 2022, OOI Biogeochemical Sensor Data, Best Practices and User Guide, version 100. Ocean Observatories, Initiative, Biogeochemical Sensor Data Working Group. 9C, 2010, Determination of Dissolved Oxygen in Seawater by Winkler Titration using the technique. Repository.org. 10 Beck MW, JD, MC 2015, Improving Estimates of Ecosystem Metabolism by Reducing Effects of Tidal Advection on Dissolved Oxygen Time Series. Methods 1312, 731, 745. 11 HT, 1956, Primary Production in Flowing Waters. 12102-117. 12 Ks, Hunt PG, 2006, New Unified Equation for Wind-Driven Surficial Oxygen Transfer into Stationary Water Bodies. Trans ASAB 495, 1615-1622. 13 He, LI 1992, Oxygen Solubility in Seawater, Better Fitting Equations. 376130711312. ZA WJ 2004, Carbon Dioxide Degassing and Inorganic Carbon Export from a Marsh-Dominated Estuary, the River, a Marsh Co-2 Pump. 4923, 41354. How Development of Recreation, Embryo Dune Habitat, and Flood Safety Interact at Evolving Nature-Based Sandy Interventions. Abstract. Socioeconomic pressures on coastal zones demand innovative solutions for balancing human needs and natural dynamics. This study investigates how recreation, embryo dune habitat development, and flood safety interact within nature-based, multifunctional sandy anthropogenic shores, SAS, focusing on two Dutch case studies, the transient sand motor and the permanent dunes. Utilizing qualitative and quantitative methods, including interviews, surveys, sensors, and advanced modeling tools, agent-based models, and the cellular automata model BVEG, we explore socio-biophysical dynamics and long-term landscape evolution. Results show that recreational activities influence vegetation establishment, affecting embryo dune formation and thus habitat size. While high recreational pressure restricts embryo dune formation, this enhances fordune growth, strengthening their functionality as flood defense. However, with restricted embryo dune development, ecological value is compromised. Our findings highlight the need for design strategies that balance these competing objectives. Further recreational use scenario analyses for different SAS designs, including morphological design and spatial design of facilities, could uncover whether it is also possible to achieve synergy among recreation, flood safety, and ecological value of SAS. Keywords. 1. Introduction. Socioeconomic pressures on coastal zones are rising worldwide, leaving increasingly less room for natural coastal change without affecting human activities and infrastructure. The challenge is to find ways for social and natural systems to coexist, co-develop, and create synergies. Recent multifunctional, nature-based interventions on the sandy Dutch coast, such as the dunes FIG 1 and the sand motor, offer great potential in this respect. Constructed by mega-nourishment, these sandy interventions aim at providing flood safety on a decadal scale, meanwhile improving spatial quality, 1, by supporting the development of ecological and recreational values. Surprisingly, studies evaluating these innovative solutions paid little attention to how the social and natural systems interact in these strongly modified and designed coastal landscapes, to which we refer as sandy anthropogenic shores, SAS, and whether these interactions strengthen or weaken the primary functions of the nature-based intervention throughout the decadal scale lifetime of the intervention. Example of a multifunctional SAS in the Netherlands with various recreational facilities. Southern end of the dunes, 8 years after construction. Note interrupted embryo dune formation, near beach entrance, and recreational facilities. Yellow dotted line, approximate pre-intervention dune foot, white dotted lines, newly formed embryo dune areas. Coordinate red location marker, 5242-4926N, 438-1692 photo, Hollands. 2 methods. The general approach of the Rayashore project was based on the systems approach schematized in Fig. 2. To better understand the socio-biophysical dynamics of sandy anthropogenic shores and the implications for the functionality of SAS as nature-based solution, we selected 2 SAS cases. The sand motor is an example of a transient SAS, as the initially peninsula-shaped mega-nourishment is, by design, intended to return to a straight shoreline over time, while feeding sand to the neighboring beaches and fordunes that function as flood defense. Al. 2013. The Dunes SAS is an example of a permanent SAS that has to remain in place, as the constructed beach dune topography is the primary flood defense. A comprehensive understanding of the interactions in the coupled socio-biophysical SAS system was achieved by using both qualitative and quantitative research methods. These included interviews with institutional stakeholders, AL. 2023, beach visitor surveys and extended questionnaires filled out by beach visitors, AL. 2024, as well as sensors at beach entrances to measure the number of visitors. These methods were combined with field experiments to assess recreation impact on establishment and growth of dune-building grasses, Van Al. Impress and modeling exercises. Schematic overview of the approach followed in the Ray-Ashore project to link the studied socio-biophysical systems interactions to development of functionality of SAS over time. To explore the long-term 2050-year beach dune evolution of SAS including effects of recreation, the cellular automata model BVEG was first enhanced by improving the conceptualization of aeolian transport AL 2023 and incorporating aspects specific to nourished beaches, such as beach surface armoring, cliff formation, and alongshore varying shoreline evolution, AL. 2024, In addition, effects of recreation on vegetation development through trampling and car driving were added, AL. 2024b, where the ABM model focused on the vegetation establishment phase on the initially SAS, including effects of sand burial by aeolian deposition. The extended BVEG model focused on the biogeomorphological developments of a SAS, including not only aeolian processes, but also hydrodynamic processes. The vegetation dynamics and beach visitor were included in a more way compared to the ABM, and added car traffic as a mode of human activity. The simulated routes of car and foot traffic were dynamic, adapting in response to the evolving topography as new dunes were forming. With this extended BVEG model, various initial design characteristics and various scenarios for visitor numbers and beach pavilion density were explored. To evaluate the development of functionality of the mega-nourishment landscape over its lifetime under various scenarios for recreational pressure, we co-created with practitioners a set of indicators for representing development of embryo dune habitat and flood safety from the extended biomorphological model output, Fig. 2. Right-hand element. 3. Results and outlook. The wide beaches created by large-scale sandy interventions are attractive to, and provide space for, a wide range of recreational activities. The associated car and foot traffic at the beach affects new vegetation development on the initially bare beaches, and on the long term, was found to modify and dissect patterns of new dune development, illustrated in Fig. 1. The recreation-related traffic enters the SAS at various beach access points, from where foot and car traffic spreads to various points of attraction, including facilities like e.g. beach pavilions, small beach huts, as well as geomorphological features like the waterline and the human-made lagoon e.g. For kite surfing, model simulations showed that traffic influenced the vegetation development patterns, and accordingly, the size of the uninterrupted embryo dune habitat area, consistent with observed developments over years. This was observed for both case study areas. The magnitude of these impacts in the long-term, 2050 year, was explored through model simulations with the extended BVEG model, varying locations of beach access points, the number of visitors, as well as the initial design of the sandy intervention itself. Initial findings reveal that on wide, elevated SAS beaches, pioneer vegetation establishment and associated embryo dune formation is a quite persistent phenomenon. However, intense recreational activity does limit the formation and size of embryo dunes. This restriction, however, enables the original fordune row, that acts as flood defense, to continue growing as wind-blown sand is then not caught in embryo dunes, thereby strengthening long-term flood protection. Yet this synergy between recreation and flood safety comes at the expense of ecological value. Our findings highlight the need for design strategies that balance these competing objectives. Further scenario exploration using different recreational uses and SAS designs, morphological design and spatial design of facilities, could uncover whether it is also possible to achieve synergy among recreation, flood safety, and ecological value of SAS. The Ray-Ashore project is funded by the NWOENW Top Sector Program, Living Labs in the Dutch Delta, Contract No. 17,599, with in-kind support from Holland's HKV, Bureau Strand N, and H+N+S. We further wish to thank all stakeholder workshop participants, the anonymous beach visitors for filling out our questionnaires, and students and colleagues from HZ University of Applied Sciences for collaborations in conducting the beach visitor surveys. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: PWM, MF, AA, KM 2023. A participatory modeling approach to cognitive mapping of the socio-environmental system of sandy anthropogenic shores in the Netherlands. Ocean Coast Manage 243, 106739. PWM, KM, AA, MF 2023b. Using agent-based modeling to explore human impact on sandy beaches in the Netherlands. In Book of Abstract Encyclades 2023, Delft, the Netherlands. WebOrg BOA 2023624, using agent-based modeling to explore human impact on sandy beaches in the Netherlands. Al. 2024, Balancing Recreation and Flood Safety for Integrated Coastal Management, Understanding Beach Visitors' Types of Attitude and in Sandy Anthropogenic Shores. Ocean Coast Manage 25810-7407. M.S.S. 2023, Beyond Landscape Experience, a systematic literature review on the concept of spatial quality in flood risk management. RevWater 10.5. MJF Al. 2013, A New Alternative to Saving Our Beaches from Sea Level Rise, The Sand Engine. J Coast Race 295100-11008. KM 2023, Conceptualizing Aeolian Sediment Transport in a Cellular Automata Model to Simulate the Biogeomorphological Evolution of Beach Dune Systems. J. Marine, 11-71278. KM 2024, A Exploring the Biogeomorphological Evolution of Mega-Nourishments with a Cellular Automata Model. Geomorphology 463, 109371. Al. 2024, B. Exploring the Long-Term Impact of Beach Entrances on Dune Development. In Book of Abstract ICCE 2024, Rome, Italy. J. 2012, What is Spatial Quality and Why is it Important to the Design Process? Sensors and Systems. SCOM What is Spatial Quality and Why is it Important to the Design Process? Last accessed, 14/2025. Van S.J., J.M., MJPM, J. Recreation Impact on the Early Establishment of Dune Building Grasses, and on the Beach. J. Coast. 15/2025. Org 10-1007-S11185202-50-110-155 in press. Spatial quality is a concept used in spatial planning and design and applies to created and managed environments, including buildings, infrastructure, and landscapes. Environments will have higher spatial quality as functioning increases, use rises, and a variety of needs for people and are met. 2012. There is ambiguousness in the concept of spatial quality, where we follow the Dutch school of thought in relation to flood risk management. Here, needs for people and include a landscape that supports the existence of human and non-human life forms, recognizing ecological quality as one of the dimensions of spatial quality, next-to-use quality, experiential quality and long-term quality. Al. 2023. Understanding and preserving the dynamic coast of in the Dutch Delta is a matter of scales. Abstract. The 1953 storm surge disaster was a pivotal event for the coast, as it triggered the Delta Flood Protection Plan. The estuary were completely closed, and a semi-open storm surge barrier was placed in the eastern Scheldt. As a result, the large-scale redistribution of the ebb delta deposits triggered the migration of channels and shoals, and that had a major impact on the adjacent barrier island coasts. The coast of required extensive coastal maintenance efforts that included construction of groins and pile dikes, nourishments, but also pilot projects in the form of channel relocation and dune restoration. These well-documented interventions form an extensive research database that can be used to better understand coastal management strategies and the impact on coastal over a wide variety of time and spatial scales. Keywords. 1. Introduction. Left panel, location of the coast and ebb tidal delta of the Eastern Scheldt based on 2022 measurements. Upper panel, an overview of the and location of the barriers built as part of the Delta Flood Protection Plan. 2. Change of the ebb tidal delta. The response of the ebb tidal delta to the storm surge barrier is illustrated through selected bathymetries, and the changes, Fig. 2. All maps show similar channel shoal patterns. The open closure dam impact the tidal currents and propagation, but these currents are sufficient to retain the typical channel shoal patterns of the estuary. This response is very different to the adjustment of the adjacent and deltas, wherein the estuaries were completely closed off. With the absence of tidal inlet velocities, waves dominate and sediments are transported landward. Large-scale sediment redistribution resulted in the infill of the channels and landward shoal migration. 8. The oldest map, 1960, shows 3 main channels, van and with a west-east orientation in the mouth. These channels are separated by an elongate shoal area, on which part of the barrier was built. The channel forms the outflow of the onto the ebb tidal delta and is oriented west-east near the barrier, but eventually curves northward and splits the main shoal area in a seaward and a landward part. The shoal forms a major part of the ebb tidal delta. The storm surge barrier was completed in 1986, but its construction and the other dams constructed in the Delta Flood Protection Plan already had a pronounced effect on the of the ebb tidal delta between 1960 and 1986. The tidal prism temporary increased during construction and significantly reduced by approximately 30% after completion of the barrier 4. The volume of the ebb tidal delta increased by 90 million m3. This increase is not directly the response to the construction of the storm surge barrier, but was attributed to the increased tidal prism due to construction of dams in the landward part of the estuary and the closing of the adjacent Delta 7. Most relevant changes for the coast are the deepening of the channel and northward migration and expansion of the shoal, resulting in erosion of the shoal's southern margin and deposition on the seaward side. Major changes were also observed on the shoal as construction of the barrier closed off channels, which resulted in extensive sedimentation. 2 main aspects govern the development of the barrier and estuary after completion of the barrier. Firstly, sediment exchange between the ebb tidal delta and estuary was blocked. Even though flow can still enter and leave the estuary through the open barrier, the elevated foundation and connecting sills between the barrier elements and the extensive, deep scour pits that developed on either side of the barrier completely block sediment exchanges. Secondly, tidal prisms, and therefore tidal currents on the ebb tidal delta, significantly reduced. With decreased tidal currents and no sediment supply from the estuary, waves initiated erosion of the delta margin. As the alongshore North Sea tidal currents did not change, the eroded sediments were transported northward, following the dominant flood tidal currents. Net erosion, 40 million m3, dominates the changes after completion of the closure dam, 1986-2010. Most erosion takes place on the shoal that shows a general trend of lowering, while the in-channel deepen and further extend northward. A third channel, the former but now abandoned main ebb channel to the estuary, Gat, curved southward onto the shoal. Part of this rotation results from the shoal, Van Het, that forms the flood shoal of the tidal channel. This shoal is pushed northward as the channel extends, and thereby constrains the flow in the Gat channel. The erosion of the shoal decreased the wave dissipation, leading to a sustained wave attack on the coast 9. Left panels, bathymetry of the ebb tidal delta and coast for the years 1960, 1986, 2010 and 2022. Right panels, sedimentation erosion between 1962-022 in m. Top, sedimentation erosion rates for the periods 1961-986, 1986-010, and 2010-022 in m. 3 coastline of groins and pile dikes. For a long time, the coastal policy in the Netherlands was, no land shall be lost to the sea and hard structures, e.g. groins, pile dams, were used to counteract coastal erosion. 6.3. Along the northern coastline of groins, were built over a 6 stretch of coastline between 1834 and 1880, 1. To protect the beaches and dunes from landward migration of Gat Channel. As a result of groin construction, erosion rates reduced from 0.718 m-year to 0.02 m-year. 7 groins were also placed in the southwestern part of the coast between 1826 and 1861, close to the present-day location of the storm surge barrier. These groins resulted in a transition from an erosive state, m-year of prior to 1861, to accretion of 0.5 m-year after construction. In between these stone groins, additional wooden pile dikes were constructed. An important lesson learned is that these wooden pile constructions are not successful in retarding channel migration, as the piles just topple over and disappear in the advancing channel. Channel relocation. After construction of the dam and the storm surge barrier, the coastline was severely impacted, and coastal erosion mostly intensified as the large-scale morphology changed. The pre-existing hard structures may not be in the correct location in relation to the changed, which results in extensive maintenance efforts of the structures and severe coastline erosion. Frequent nourishments are essential to maintain both the coastlines and groins. 3. Experiments to counteract erosion due to landward migration of the channel were undertaken in 1987 and 1991, following the completion of the storm surge barrier. The channel was relocated stepwise to a former offshore position in 1987 between 13.215.3 and in 1991 11.213.5. Both experiments dredged the seaward part of the channel 2 and 2.7 mm. M3, which consequently shifted the channel wall 5,100 m offshore. The dredged material was placed landward on the shore face, beaches, and in the dunes. ALD 2015 concluded that the channel relocation accelerated the morphological adjustment to the changes introduced by the completion of the storm surge barrier. The landward migration of the channel stopped, and coastal erosion reduced. 1. Nourishments. The shift from coastal protection from hard structures to soft interventions results from a change in coastal policy. Since 1990, a new coastal policy called dynamic preservation was enacted. 5. The 1990 coastline is primarily maintained with sand nourishments as principal source. Despite the success of channel relocation, coastal erosion along the section of the coast was temporarily reduced, but not completely eliminated. Extensive nourishments were and are still needed to ensure coastal safety. Over 15 million m3 of sand was placed on, since 1990. Most of the nourished volume was placed on the western and southwestern beaches, 11 million m3. And a small part, 1 million m3, was directly added to the adjacent dunes. These nourishments have been successful in maintaining the coastline, but need to reoccur frequently, and are expensive. Coastal nourishments not only meet mandatory coastal safety standards, but can also be used to achieve additional economic, recreational, and ecological benefits. A major problem in the Dutch coastal dunes is nitrogen pollution that often results in increased, dense grass and sedge covers, and significantly decreased plant species diversity. As a pilot experiment, an alternative nourishment strategy was applied along an area of low coastal safety risk between 2016-2020. A regular nourishment was skipped to allow increased activity, beach and dune erosion, allowing more dune dynamics and aeolian sand spray into the dunes to counteract nitrogen pollution issues. This experiment was successful, as within a few years, the plant diversity in the enriched dunes recovers. 4 concluding remarks. The convex-shaped coastline is dominated by erosion as a result of waves and the contracting tide around the island tip. This erosion is enlarged by the landward migration and growth of the tidal channel that forms an efficient conveyor for a longshore sediment transport. This erosion was historically reduced or halted through the construction of groins and pile dikes. The construction of the Eastern Scheldt storm surge barrier significantly impacted the ebb tidal delta dynamics, resulting in growth of the channel and lowering of the shoal. The impact of the tidal channel on coastal erosion was successfully reduced through channel relocation. Nourishments are still needed, as the shoal reduced in height and wave-driven erosion likely increased. A pilot experiment showed that temporarily suspending nourishments in an area where coastal safety is not directly at risk can have a beneficial effect on dune ecology as more beach and dune dynamics occur and aeolian sand spray into the dunes increases. Human interventions are often implemented in response to disasters, but the timing for the execution of different level interventions can be a key for understanding the interaction and impact on different scale levels. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 JHM 1998, Seaward Coastal Defense, Limitations and Possibilities. J. Coast, 471-78. 2 Elias EPL, Van AJF, Lazar M., 2016. The contiguous ebb tidal deltas in the SW Netherlands. Large-scale morphological changes and sediment budget 1965-2013. Impacts of large-scale engineering. NJGN 127. 3 Lazar M., Elias EPL, Van AJF, 2017. Coastal Maintenance and Management of the Contiguous Ebb Tidal Deltas in the SW Netherlands. NST. Proceedings of Coastal Dynamics 2017, Coastal Dynamics 2017, 1261-1272. 4 Louders T. Van den Berg J.H., 1998. Geomorphological Changes of the Tidal System During and After Implementation of the Delta Project. J. Coast Race 141134-1151. 5 Ministry of Transport and Public Works, 1990. A New Coastal Defense Policy for the Netherlands. Public Works Department, Tidal Waters Division, The Hague P. 103. 6 H.J. Van H. 1989, N. Van Hun. Min. V. and W. N. S. 7 Van den Berg J.H. 1984, Morphological changes of the ebb tidal delta of the Eastern Scheldt during recent decades. 63.3, 63.375. 8 Van AJF, Elias EPL 2021, Half a Century of Morphological Change in the and Ebb Tidal Deltas, SW Netherlands Impacts of Large-Scale Engineering 1964-2015. Marine Geology 432, p16. 9T, Elias EPL Van AJF 2015, Relocating Channel. A Tale of Two Developments. In P. Ede, Proceedings of the Coastal Sediments 2015, p13. 10 Watson I, CW 1992, Technical Summary of the Complete Delta Works, including the Eastern Scheldt. J. Coast Res 1056. Large-scale beneficial use of dredged materials at the project, emerging landscapes and new habitats. Abstract. The capital dredging of 17 million tons of seabed material for the tunnel project, an 18-long immersed tunnel project connecting Germany and Denmark, was completed in the autumn of 2023. The major dredging project included from the very start planning for beneficial use of all the dredged seabed material. The vast majority of this has been deposited behind a 7-long breakwater along the Danish coast, creating a 400 m wide land reclamation. Ambitious plans for creating new coastal landscapes, working with nature within this land reclamation, is part of the project. Already now, certain elements of these coastal landscapes have been constructed, and new nature and habitats are emerging as part of the land reclamation. This paper will provide a status for the construction and development of these emerging coastal landscapes and new habitats. An overview and the underlying ideas and assessments on how the project is planned to create coastal landscapes, making use of the dredged material, will be presented. In addition, plans to create artificial reefs in Danish as well as German waters as part of the project will be explained. Keywords. 1. Introduction. Ambitious planning for beaches, coastal cliffs, wetlands, and meadows. The project is the world's longest immersed tunnel and the largest infrastructure project in Denmark. From the beginning of the planning for the tunnel project, beneficial use of the originally estimated 19 million m3 of seabed material from the capital dredging was a central element. 1. The overall project plan for the tunnel project to utilize the dredged material in a beneficial way by creating a large land reclamation was planned out between the project owner, the technical team, RAT, the landscape architects, and the environmental team with specialists in hydraulics, coastal morphology, water quality, and marine habitats, DHI. The concept for the land reclamation includes ambitious plans for creating new coastal landscapes, Fig. 1. Beaches, an eroding coastal cliff, coastal wetlands and meadows, in a new land reclamation utilizing the dredged seabed material. Such landscapes are original to the local environment at the project site, and nature types which to a large degree were lost in the area by the diking and draining of the low-lying hinterland following the fatal storm in the area in 1872. Beaches and access to the coast, planned as part of the new land reclamation, further replace and significantly improve pre-construction conditions at the site for the present-day local community and tourists. Lastly, new coastal elements must work to have net positive impacts to the local nature. Original project plan for new coastal landscapes by use of the approximately 19 m3 of dredged seabed material from the immersed tunnel project. 1. Western Beach 2. Cliff 3. Modified from 1. Copyright A.S. Aerial footages of the emerging land reclamation from May-June 2024, from east, left, and west, right. Copyright A.S. 2 status for emerging coastal landscapes during construction. The backbone of these new nature areas, the land reclamation, has now been constructed. Fig. 1. Lower figures. Construction of the outer perimeter was initiated in summer 2021, and dredging for the tunnel trench was completed in the autumn of 2023. Importantly, the land reclamation was planned as a streamlined structure, not influencing the overall water exchange between the Baltic Sea and the Kattegat North Sea. The nature elements of the outer perimeter were conceptually planned to develop by and with the natural hydrodynamics and morphological processes as nature-based solutions. In the western end, a beach is developing as planned since established in June 2021, Fig. 2 Upper figures. Some initial adaptation of the beach orientation to the local wave climate has occurred. With an annual net longshore sediment transport of 30,000 m 3 year towards the east, the beach naturally accumulates sediment and widens over time, with an orientation of the beach facing the equilibrium orientation for a net zero longshore transport according to the prevailing waves. The breakwater at the western extent of the land reclamation acts as a terminal structure for the beach. The beach will provide recreational opportunities for the local communities and tourists in the area, with a hotel in the immediate hinterland. In the eastern end of the land reclamation, a 6 m high coastal cliff has been constructed in autumn 2023, Fig. 2 Lower figures, using glacial seabed material from dredging of the tunnel trench. The cliff will naturally erode over time when exposed to waves. Initially, a containment bund protects the cliff from erosion and wave-cut notching by waves, while the cliff material will compact over the coming years. For the same reason, the cliff area will for some years be closed for the public. The containment bund will be lowered in some years to allow wave exposure of the cliff. The length of the presently constructed cliff is around 1,000 m long. In the first plans, a larger part, about 1,500 m, of the perimeter to the east was in cliff. However, with a newer decision by the Danish government from 2023 to preserve the tunnel element production site and work harbor for coming infrastructure projects, Sund, and 2023, beyond the construction of the fixed link, this plan is delayed. Eroded sediments from the constructed cliff will gradually supply sediment to the downstream coast in a similar manner as erosion from natural cliffs in the area contributes to the sediment budget along the coasts of the western Baltic. With the length of the cliff significantly shorter than originally planned, the effect of the cliff to work as a mitigating measure against project-facilitated erosion east of the land reclamation will be much less than the initial estimate, corresponding to 20-25% of the annual erosion volume. The inner parts of the land reclamation are still in process of being filled with seabed material, and as such still an active part of the construction for the tunnel project. Additional beaches in the western part of the land reclamation are still to be designed in further details and not yet constructed. Initial studies to support and investigate the original ideas of recreating a coastal lagoon landscape to facilitate exposed as well as more protected beaches and lagoon channels for water sports have been carried out considering not only beach lagoon form, stability and quality, but also sufficient water exchange to avoid stagnant water, and in the open channels to the ferry harbor considering ship wave-induced currents. Upper figures, Western Beach established and opened to the public in June 2021. Lower figures, erosion cliff constructed in the eastern end of the land reclamation in spring-summer 2023. Copyright AS3 breakwaters and new reefs facilitating hard substrate habitats. Since the planning and approval process of the fixed link in 2008-2014, worldwide focus on nature-based solutions and enhancement of biodiversity has increased enormously. The large-scale tunnel project represents a possibility to not only embed such initiatives in the project, where possible, but also through monitoring and modeling of habitats to gain knowledge for future projects. 3.1 Breakwater Habitats. The 7 of breakwaters bordering the land reclamation provide natural stones as the basis for emerging hard substrate-affiliated habitats in water depths down to about 6-8 m, This type of habitat has significantly diminished in the region over the last centuries due to stone fishing for construction of ports and other coastal structures. Monitoring to follow the development of the emerging habitats at the breakwaters and at the seabed in front of these will be carried out over the coming years, and the first results are presented at the conference. By applying state-of-the-art technology, such as eDNA sampling in conjunction with traditional biological monitoring, genetic traces of the animals living in the area of the can be identified, and the changes in the presence of species composition over time will be studied. The monitoring is done to study how fast the new coastal habitat and its role within the local food chain and local ecosystem develops, and to which degree it can replace habitats originally in the area of the land reclamation. Modeling is carried out to map connections between various habitat types, soft and hard bottom habitats, in the area to understand the ecological footprint. Baseline investigations at the new breakwaters took place in autumn 2024, where monitoring was carried out along a 700 m at mid-depth of the breakwater, water depth of 4 m. Biological samples were collected along with video transects and eDNA samples to describe the newly established hard substrate habitat. Initial results show that the dominating species is the opportunistic species. During pre-construction conditions, the habitat-forming red algae species was dominating the area. Analysis is currently to undertake a comprehensive biodiversity assessment to be followed in the coming years. 3.2 New reefs. Investigations to establish new stone reefs are ongoing in German, as well as Danish waters. A 42.5 ha stone reef at Saga's Bank, southeast of the island of in water depths of 10-15 m, is planned as part of the compensation agreement in the approval process of the tunnel project to benefit marine flora and fauna. The tender process for construction of the reef is in planning with the project owner. Snapshot of modeled wave transformation over early-stage investigations of potential new reefs east of the land reclamation. Bed contours are indicated in numerical modeling of waves, Fig. 3. Currents and shoreline development is carried out as part of the investigations for the new multi-purpose reefs to support the conceptual design of the reefs in terms of desired morphological impacts of protecting the coast, to support assessments of undesired effects of general sedimentation in areas of habitat type 1170 reef, and to investigate effects in the direction east of the reef. Negative coastline impacts, erosion, sedimentation, to protected coastal habitat types in a nearby 2000 area cannot be allowed, and hence a comprehensive study is carried out to identify and test the need for mitigation measures. Model results of currents and waves together with criteria for habitat types are used to assess the suitability of different types of vegetation, e.g. eelgrass and fauna habitats, mussel beds, ascidians, fish nurseries, in the sheltered area behind the reef, see Fig. 3 for different reef designs. The intended result is the creation of a so-called mosaic nature, with a multitude of targeted types of flora and fauna habitats forming in and around the reef. To further gain knowledge for future projects on the biodiversity effects of the artificial reef, different construction materials are planned to be used: marine glacial stones, quarry rock, and potentially concrete blocks. Following construction of the reefs, the monitoring mentioned above will in the future be extended to the multi-purpose reef to investigate and document the biodiversity enhancement of the reef, and to investigate sensitivity of biodiversity to different construction materials. 4 conclusions. Creating new land reclamations from dredged material from large-scale infrastructure projects can represent an opportunity for the local community and the environment. A large emerging coastal landscape is as part of the Fixed Link project with apparent benefits for the local community and with emerging habitats. Experience from the work reveals the opportunities, but also that careful and holistic planning of the land reclamation for a successful engineering design is essential. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 40, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1AS Fixed Link Coast to Coast, 2013 Environmental Impact Assessment. In Danish. Sundend, p. 1.655. 2JG Al, 2017, Restoration of a Boulder Reef in Temperate Waters, Strategy, Methodology, and Lessons Learnt. 102, 468-482. Org 1010-16J20, 1702058. 3 Sund, 2023. Vid. In Danish. p. 284. On wave energy dissipation along a seagrass field. Abstract. This study investigates the role of P in wave energy dissipation and attenuation under varying wave conditions and vegetation characteristics. A series of numerical simulations were conducted, considering different wave conditions and combinations of vegetation parameters, including leaf height, shoot density, stem diameter, and drag coefficient. The study compared scenarios with and without vegetation, and analyzed the impact of each vegetation parameter. The results confirm that P significantly increases dissipation and reduces wave height, particularly for low-medium wave conditions. The effectiveness of wave attenuation is enhanced with larger vegetation parameters, while reductions in these parameters lead to a significant decrease in dissipation capacity. These findings highlight the importance of restoring and preserving pea meadows for effective coastal protection. The study also suggests that the model used may reach saturation for high and long wave conditions, indicating the need for further research. Future work should focus on validating the model under extreme long waves and incorporating a broader range of vegetation characteristics. Keywords. 1. Introduction. Coastal regions face significant climate change impacts, including sea level rise and extreme wave events, leading to coastal erosion, flooding, and damages to infrastructures and coastal ecosystems. Nature-based solutions, such as preserving seagrass meadows, are key methods to develop coastal adaptation strategies to climate change. Seagrass meadows reduce wave energy, modifying near-bed flows, stabilizing sediment 1, 2, mitigating coastal impacts, and enhancing resilience against climate change. Their effectiveness depends on factors like canopy width, length, and density 3, 4. This is the case of an endemic Mediterranean seagrass species that supports marine biodiversity 5, stabilizes coastal ecosystems, and attenuates wave energy, reducing erosion and storm damage. Nearshore involve complex interactions, including wave propagation, sediment transport, and energy dissipation processes like bottom friction and wave breaking. Therefore, vegetation significantly impacts energy dissipation. The widely accepted, by and 2004-6, used in numerical models allow to account for its effects on simulation near shore. This formulation, incorporating vegetation characteristics as calibration parameters, enhances the study and design of nature-based solutions, marking a crucial step forward in developing effective coastal protection strategies. This study aims to explore the numerical behavior of this formula, considering this role in wave energy dissipation, addressing gaps in understanding in process-based models. Using numerical simulations, we investigate the sensitivity of and 2004-6 formulation to variations in wave conditions and seagrass characteristics, enhancing insights into their application and limitations. 2. Data and methods. 2.1 Study site. The study focuses on a semi-enclosed sandy beach located on the northeastern coast of Majorca Island, Balearic Islands, Western Mediterranean Sea. Spanning 1.7 with a dry beach width of 1550 m, the beach features dynamic transverse and crescentic bars, influenced by carbonate sands. The sandy seabed of hosts an endemic meadow at depths ranging from 5 to 35 m, along with rock reefs and beach is part of an ongoing beach monitoring Program 7, initiated in 2011, through which long-term data is collected. The program has also facilitated several experiments and research, including studies on the effects of pea meadows on wave propagation. 8. 9. 2.2 Numerical modeling. To analyze the role of wave forcing and seagrass meadow characteristics on wave energy dissipation and subsequent wave propagation processes, the open-source XBeach model has been employed. 9. This model simulates wave transformation processes, wave-induced currents, sediment transport, and bottom changes, and accounts for wave energy dissipation due to vegetation effects through the 2004 Formula 6. Simulations are based on the cross-shore hydrodynamics, corresponding to the central profile of Fig. 1a, which aligns with the experiment conducted by Infantes al. 2012. 9. The model has been calibrated using this experiment benchmark case, in which P characteristics were set to I stem height 0.4, stem diameter 0.0264 m, stem density per square meter N615 stems M2, and a seed 0.4. A total of 1,008 simulations have been performed, encompassing wave conditions with significant wave heights, ranging from 0 to 6 m and wave peak periods, ranging from 2 to 14 s. Additionally, variations in seagrass parameters, representing a 20% reduction and increase of parameters relative to the benchmark simulation, have been explored. For comparative purposes, simulations excluding vegetation effects have also been conducted. 3. Wave energy dissipation and P meadow characteristics. 3.1 Wave conditions and the role of vegetation on wave energy dissipation. To analyze how wave energy dissipation due to vegetation affects wave height evolution along the seagrass meadow, we examined the wave height ratio immediately downstream of the meadow for the benchmark case with respect to no vegetation, effects case under various forcing conditions, Fig. 3.1b. A cross-shore beach profile considered for simulations. Green line stands for the position of the P meadow. B. Wave height ratio with and without, considering vegetation, effects immediately after the seagrass meadow for different wave conditions. Interestingly, wave height reduction decreases on increasing wave period immediately at the end of the meadow, and remains almost constant regardless of the wave height. This behavior seems to indicate a saturation of an 2004 formula that may be related to the ability of P to act as a low-pass filter, dissipating higher frequency components more effectively. 12, 13. However, lack of experimental data for long waves makes it difficult to discern whether these results are a numerical artifice related to the use limitations of the or represent a real effect of seagrass meadows on wave energy dissipation. On analyzing the wave height reduction further onshore and out of the meadow, x 350 m, the reduction decreases as the result of an accelerated shoaling process observed as waves exit the meadow, here not shown. Furthermore, reduction decreases significantly with increasing wave energy, ranging from 5 to 30%, similar to previous experimental observations 3-10. It is worth noting that in the present study, the maximum submerged ratio was D013, lower than in previous experiments which was 0.5. Both submerged ratio and seagrass parameters may strongly influence vegetation dissipation. 3.2 Relevance of P parameters on wave energy dissipation due to vegetation. Ratio of variation of along the meadow for changes on P parameters respect to the benchmark case considering different wave conditions. Left panels stand for reduction of parameters, and right panels for increased values. The energy dissipation ratio due to vegetation, accumulated at the end of the meadow, varies with wave conditions when parameters are individually reduced, ranging from 0.4 to 0. In all three scenarios, the ratio is higher, indicating less energy dissipation under low and moderate waves. For extreme conditions and longer waves, the ratios approach 0, indicating no significant changes compared to the benchmark case. Among all parameters, is the most sensitive to variations and exhibits the highest changes. When parameters are increased, the results also show irregular distributions across different wave conditions, with variations ranging from 0 to 0.5 compared to the benchmark case. Unlike the reduced parameters, increasing the parameters leads to greater dissipation at the end of the meadow under long and highly energetic wave conditions, with being the most effective parameter. Examining parameter variations in terms of changes in at the end of the meadow, compared to the benchmark case, reveals that parameters reduction results in changes ranging from 5% to 30%, whereas increases yield smaller changes, between 5% and 10%. This indicates that for the same degree of parameter variation, reducing parameters has a greater impact on wave evolution than increasing them. This underscores that the decrease in the characteristics of P itself, in terms of leaf length, stem diameter and density, significantly diminishes its ability to attenuate wave energy, compared to the increase in these characteristics. It highlights the importance of maintaining healthy pea meadows and the severe consequences if seagrass conditions deteriorate. These findings emphasize the need of continuous restoration, planting efforts, and careful management of existing meadows. 4 conclusions. In this work, we address the effects of accounting for seagrass on wave energy dissipation, analyzing the of and 2004 in a process-based model, and examining the role of wave conditions and pea meadow characteristics on the formula behavior. Accounting for effects via the and 2004 model introduces an additional dissipation term, efficiently reducing wave height in low to medium wave energy conditions. In this sense, considering nature-based solutions and/or seagrass meadow restoration can be an effective coastal protection measure, especially in very shallow waters without high wave energy levels. Results point that, in 2004, formula saturates for long waves periods, disregarding wave heights, which enhances the possible link with the ability of the plant to act as a low-pass filter. However, the role of the wave period remains misunderstood. Further research is needed to assess model behavior immediately after the meadow, and particularly under high energy and long wave conditions, to better understand the coupling of different dissipation terms. Regarding the relevance of the vegetation parameters it has been observed that at low-medium energy wave levels, increasing vegetation characteristic parameters leads to higher dissipation levels. In contrast, reducing the characteristics parameters of P significantly decreases the capability of the meadow to attenuate wave height, 1 order of magnitude greater compared to the variations resulting from increasing the parameters. This relevant finding means that restoring P is important, but to ensure the continued well-being of the existing meadows is of even greater importance. The lack of full-scale laboratory and field experiments addressing wave energy dissipation due to vegetation that embraces both wave energy conditions and, especially, high energy and/or long wave conditions, vegetation characteristics and submerged ratios, makes it difficult to assess the limits of use of the and 2004. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1N M. A. 2011, Effects of Seagrass Meadows on Storm Waves. J. Coastal Rays. 373, 377. 2N. A. Low R. M. 2022, Seagrass Meadows Reduce Wind Wave-Driven Sediment Resuspension in a Sheltered Environment. Frontmar 87333542. 3J. Solar M. T. X. C. 2017, Impact of Created Canopy Gaps on Wave Attenuation in a Seagrass Meadow. Mar Progser 569, 103-116. 4 Sierra JP, V. X. M. C. EJ 2023, Potential of Transplanted Seagrass Meadows on Wave Attenuation in a Fetch-Limited Environment. J. Marine, 11-6-1186. 5R. Cullen LC, 2014, Biodiversity, Ecosystem Services, and the Conservation of Seagrass Meadows. Coast, 1995. 6F. I. 2004, An Empirical Model to Estimate the Propagation of Random Breaking and Waves over Vegetation Fields. Coast, 5121-3118. 7 Mora A. F. L. J. AT 2023, Years of Data at a Microtidal Urban Beach, Western Mediterranean Sea. Scientific Data 1013-1. 8 Infantes E. J. A. B. A 2009, Wave Energy and the Upper Depth Limit Distribution. Botanica Marina, 419-427. 9 Infantes E. A. G. J. M. H. 2012, Effect of a Seagrass Meadow on Wave Propagation. Mar Progser 456-6372. 10D. Al 2009, Modeling Storm Impacts on Beaches, Dunes and Barrier Islands. Coastal 56, 1133-1152. 11P. Al 2010, Wave Propagation over Large-Scale Experiments. In 7th HYDRLAB III Joint Transnational Access User Meeting. 5760. 12 Low RJ, Falter JL, JR, SG, MJ 2007, Spectral Wave Flow Attenuation Within Submerged Canopies, Implications for Wave Energy Dissipation. J. Rays Oceans, 112C5. 13 Bradley K. Hauser C. 2009, Relative Velocity of Seagrass Blades, Implications for Wave Attenuation in Low-Energy Environments. J. Rays Earthsurf, 114 F1 F0, 1004. Long-term modeling of coastal protection, measures on the Belgian coast. Abstract. The Belgian coast protects a densely populated hinterland and supports recreation, yet it faces localized erosion challenges. While coastal safety is not currently at risk, the area, located east of the port of Ostend, has experienced accelerated erosion since the port's expansion between 2008 and 2011. This study evaluates two nourishment strategies, a mega-nourishment and a foreshore nourishment, using the TELEMAC-based coast hydro model. Results show that foreshore nourishments effectively redistribute sediment toward the coast, enhancing beach elevation along the nourished stretch and slightly to the east. In contrast, mega-nourishments provide localized benefits, but result in greater sediment loss offshore and a larger erosional area. These findings highlight that foreshore nourishment is a more effective strategy for addressing nearshore erosion providing better long-term protection with the same sand volume. Keywords. 1. Introduction. The Belgian coast, with a total length of approximately 65, is an area of high importance protecting the densely populated hinterland, as well as providing recreation. It consists of sandy beaches, which are often fronted by a sea dike at coastal towns or by dunes, and is interrupted by 4 ports, Ostend and The area is influenced by strong tides, with a tidal amplitude up to 4 m at spring tide, and a net northeasterly directed longshore current. The offshore normal wave climate is described by an average significant wave height of 1 m and a typical wave period of 6s1. The area, located between the port of Ostend to the west and to the east, is suffering from long-term erosion, which has accelerated since the expansion of the port between 2008 and 2011. Corrected for nourishments, coastal erosion rates since the 90s below the low water line were reported to vary between 4 m3 m year on the west side of the project area to about m3 m year on the east side of the project area. Notably, rates obtained since 2010 show values as high as -55 m3 m year in the project area too. Although this erosion does not pose a threat for coastal safety at present, solutions are sought where coastal safety, recreation, and ecology are considered. Beach nourishments are frequently carried out at the Belgian coast, most commonly on the dry beach, to maintain beach width. However, other nourishment methods or strategies to maintain the beaches may be economically desirable. This paper presents an investigation of nourishment strategies for a long-term eroding area in Belgium using historical observations and numerical modeling. Firstly, long-term topographic and bathymetric measurements are used to understand the and volume changes in the area. Thereafter, two alternatives are studied for the project area using coast, a hydro model of the entire Belgian coast 3. 1. A mega nourishment, consisting of 3 mm3 sand, inspired by the sand engine in the Netherlands 4, and 2. A foreshore sand nourishment of 3 mm3. 2. Morphological evolution. Subaerial and intertidal beach topographic (LIDAR) measurements are available from 2005 onward, whereas foreshore measurements, single beam, are available since 2007. These have been used to evaluate morphological evolution and volumetric changes in the project area, which spans between coastal secs. 122 and 150 Fig. 1. Bathymetry at project site. Combination of beach LIDAR and foreshore single beam measurements. 2022. Seabed difference map from LIDAR and foreshore soundings between 2007 and 2022. Blue colors indicate erosion, red colors indicate accretion. In the period 2007-2022, the beach, defined from the dune toe to the low water line, shows a volume increase of 1.45 mm3, Fig. 3, largely due to the effect beach nourishments, which is the only type of nourishment executed in this period. Nourishments are especially used for coastal protection after the implementation of the Master Plan Coastal Safety in 2011. The total nourishment volume applied in the project area between 2007 and 2022 is 2.33 mm3. Overview of cumulative net volume changes in the beach, foreshore, and total volume, both corrected and not corrected for nourishments, benchmarked to 2007 in the area, coastal secs. 122-150, with nourishment volumes also shown. 3. Numerical model. 2 nourishment strategies, i.e. a mega nourishment and a foreshore nourishment, each with a volume of 3 mm3, were implemented in the project area Fig. 4. The numerical study was performed using the Coast Model 3. Coast is an unstructured model of the full Belgian coast, and the Scheldt estuary based on the finite element software, using the sediment transport model, Gaia, in combination with the full spectral TOMAWAC wave model. The physical processes that are considered in the hydrodynamic model are tides, using a representative tide, and wave-driven currents. In the spectral wave model, the full wave spectrum was calculated, taking into account wave propagation, including refraction, wave-current interaction, quadruplet interactions, wind input, whitecapping, bottom friction, and depth-induced braking. A representative wave climate was used, which was obtained using brute simulations of 10 years of wave conditions. Initial bathymetry of left foreshore nourishment Right, mega-nourishment. 4 results. The simulation results have been assessed to verify the effectiveness of the two nourishment strategies by comparing the loss and gain of sand volume from the nourishments and the morphological impact on the surrounding areas to the reference scenario where no nourishment is applied. The difference bathymetry maps after 10 years between the scenario and reference calculations show higher elevations in the scenario in red and lower elevations in blue, Fig. 5. Higher elevations may be due to higher initial elevations because of the nourishment, which has not completely eroded away after 10 years. Alternatively, if the bathymetry was the same at the initial conditions, outside the nourished areas, higher areas represent areas with either less erosion or more deposition in this area in the scenario than in the reference situation. The results show that the foreshore nourishment erodes, with sediment in the model redistributing toward the coast and feeding the beach, as well as slightly offshore. This leads to a higher elevation of the beach in the model, with the nourishment compared to the reference case without the nourishment. This process effectively protects the approximately 6 coastal stretch where nourishment was implemented, while also benefiting an area to the east. In addition, a large part of the nourishment volume still remains in place after 10 years. Nevertheless, some decrease in the bathymetry is visible further east, meaning that there may be local negative impacts. Difference bathymetry after 10 years, scenario and reference calculations. Top, foreshore nourishment. Bottom, mega-nourishment. 5 conclusions. The area of coastal sex 122-150 shows significant erosion over the past decades, which has accelerated since the expansion of the Port of Ostend in 2008-2011. A volume change analysis for the past 15 years shows a net erosion of more than 3 mm3, volume corrected for nourishments. 2 long-term nourishment strategies using the same sand volume have been tested in the TLEMAC-based model coast. 1. A mega-nourishment. 2. A foreshore nourishment. While mega-nourishments have demonstrated advantages in other locations and offer significant potential for aeolian transport compared to foreshore nourishments, this research suggests that the foreshore nourishment may be the most efficient nourishment strategy under the local conditions at. Results indicate that mega-nourishments lead to more sediment spread seaward and larger erosional area as compared to foreshore nourishments after 10 years. This research was performed as part of the study, carried out by IMDC on behalf of Division Coast of the Flemish government. The authors acknowledge the Flemish government and Department of Public Works for providing the funding and data to support this study. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1T, SK, K 2008, The Wave Climate in the Belgian Coastal Zone. In Littoral 2008. Proceedings 9th International Conference, 25-28, 2008, Venice, Italy. 1.8. 2RT Dan S. 2022, Trends. Van Tot 2019, in Dutch. 18.1.42.1. WL. 3G, B, L, E, A 2019 Coast, an integrated numerical model for the simulation of the Belgian coast. In Geophysical Research Abstracts. 21. Fort MAL. Initial spreading of a mega-feeder nourishment Observations of the Sand Engine Pilot Project. Coast 111, 2338, 2016. 5 a.m. 2008. Influences sur la plage bars, Nord la France in French. Supple issues, 52-3, 145, 166. 6e, wa, l, a, g, b, 2021. Implementation of cross-shore processes in Gaia. In 2020 Proceedings of the TLEMAC User Conference, 138. Of sand ridges on the shelf, modeling effects of waves, wind, and tide. Abstract. Shoreface-connected sand ridges, and tidal sand ridges, are large-scale rhythmic found on many sandy continental shelves. Previous studies have not addressed the combined impact of waves, wind, and tides on the evolution of these ridges. Furthermore, they were unable to simulate with wave topography feedbacks. The objectives of this study are to 1. Simulate in the presence of these feedbacks, and 2. To quantify the combined impact of waves, wind, and tide on the evolution of shelf ridges. To this end, a shelf model, Delft 3D plus SWAN, is used in a setting representative of the Belgian shelf. The model successfully simulates, in the presence of wave topography feedbacks, producing ridges with characteristics consistent with observations. Regarding 2, a mix of 2 types of ridges develops on the shelf, which resemble the and observed on the Belgian shelf. However, a notable difference is that observed are located further offshore than modeled ridges. Keywords. 1. Introduction. A bathymetric map of the Belgian shelf, showing and B. Top view of the rectangular model domain, with dimensions, where the X and Y represent the cross and alongshore directions, respectively. The model, comprising a coupled Delft 3D SWAN modeling system, is driven by waves, wind, and tides. For an explanation of the symbols, see the main text. Studies so far, see the reviews by 4 and 5, have focused either on, thereby assuming weak tidal conditions, tidal range 1m, or on, disregarding wave and wind effects. The combined impact of waves, wind, and tides on the long-term evolution of shelf ridges remains unquantified. Regarding, those studies faced 2 additional limitations. First, they neglected the effects of evolving ridges on wave characteristics, hereafter referred to as wave topography feedbacks. This choice was made because including these feedbacks led to the formation of unrealistic ridges that grew and migrated too fast, likely due to the absence of directional spreading of waves in the models used in those studies. Second, the shelf bottom slopes in those studies were less steep than those observed. Using more realistic slopes resulted in numerical instabilities. The objectives of this study, which is part of a research project of the Flemish government, called MOZES, are twofold. The first is to simulate, under realistic shelf slopes, and in the presence of wave topography feedbacks. The second is to investigate the impact of the combined waves, wind, and tide on the long-term evolution of shelf ridges. To this end, the coupled Delft 3D plus SWAN numerical model, hereafter referred to as shelf model, is applied in a setting representative of the Belgian shelf. Since the spectral wave model SWAN accounts for directional spreading, the shelf model is expected to address the first objective successfully. Section 2 describes the shelf model and the methodology used to achieve the objectives. Further details about the model can be found in 6. Section 3 presents the results and discussion, followed by the conclusions in Sect. 4. 2. Material and methods. 2.1 Shelf model. The shelf model assumes a rectangular shelf with dimensions, where the X and Y represent the cross and alongshore directions, respectively, Fig. 1b. Water level and currents, which are described by the nonlinear depth-averaged shallow water equations, are computed with the Delft 3D model 7. Sediment transport, assumed to be non-cohesive and characterized by a spatially uniform D50, is calculated according to the formulations of 8. These formulations include both and suspended load transport under the joint action of waves and currents. The time evolution of bed level, defined with respect to MSL, is determined by the net exchange of sediment between the water column and the bed, as well as the spatial gradients in the sediment transport vector. The wave propagation on the shelf is simulated with the SWAN model by solving the spectral wave action balance 9. Nonlinear wave-wave interactions and wave growth by wind are neglected. The model is forced with waves, wind and tide. Waves with a significant wave height 0, peak period 0, wave direction 0, with respect to the negative x-axis, positive counterclockwise, are prescribed at the seaward x and lateral y0 boundaries Fig. 1b. Wind with velocity and direction w is imposed uniformly across the shelf domain. Tidal constituents M2 and M4 are imposed at the seaward and lateral boundaries. 2.2 Methodology. Parameter configuration. Dimensions of the model domain, bathymetry, waves, wind and tide are based on field data of the Belgian coast, using the A and Flemish hydrography data portals, accessible at BN. Unless otherwise, all model parameters have their default values, as indicated in the Delft 3D and SWAN manuals. The model domain covers a total area 5075. The bathymetric map depicted in Fig. 1a is used to derive a representative bathymetry for the Belgian shelf, which is assumed alongshore uniform Fig. 2a. A sandy seabed with D5200 is assumed. Stormy waves 035m, 011s, 070 and stormy winds 21 W90O in the negative y-axis are considered, which are assumed to remain constant during the model simulations. At the southern boundary, y, the M2 and M4 tidal components have amplitudes 2167m and 401m, with phases of 273 and 494. At the northern boundary, y0, the amplitudes remain the same, but the phases are 296 and 4187. This prescribed tidal forcing simulates a tidal wave moving in the negative y direction. A uniform grid resolution of 250 m is applied, with a time step of 2 min. To reduce computation time, a morphological amplification factor of 400 is used. This is justified because the timescale is much longer, order of decades and centuries, than the hydrodynamic timescale, order of hours to days. A snapshots of the simulated bed level in the only waveswind experiment at times t0, and t3500b. A zoom-in at t3500 is displayed in panel CD, average height of the ridges and their migration speed versus time. Figure 2 shows snapshots of the simulated bed level at times t0 and t3500 in the case that only waves and wind are considered, only waveswind experiment. The randomly imposed bottom perturbations on the initial bathymetry panel evolve into large-scale, elongated, and oblique ridges on the shelf, which resemble. These ridges originate close to the shore face and gradually extend offshore. Eventually as in Fig. 2, but for the waveswind tide experiment. 3 Conclusions. The model successfully simulates, under wave topography feedbacks, and a realistic shelf bottom slope, producing ridges with characteristics consistent with observations. In the presence of waves, wind, and tide, a mix of two types of ridges emerges on the shelf, which resemble the and observed on the Belgian shelf. A key discrepancy is the relative location of on the shelf. Observed occur offshore, while modeled are situated more shoreward. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. And the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Dyer Kr., David A., 1999, Huntley, The Origin, Classification and Modeling of Sandbanks and Ridges. Shelf Raise 1910 12851330. J.R. Labache, R.G., E. 1997, Measuring Shoreline Change on Fire Island. Maritimes 39 11334. 3T, A. Al, K. 2022, Understanding Coastal Resilience of the Belgian West Coast. Water 1413. 4F, A. Swart He. N. R. D. 2015, Understanding Coastal Patterns from Depth-Averaged Sediment Concentration. Rev 53. 5 Swart He. Yuan B. 2019 Dynamics of Offshore Tidal Sand Ridges, a Review. Environ Fluid Mech 104771. 6A, Swart He, J.M., T, A. D. 2024, Presence and position of sand ridges on the shelf strongly impact decadal evolution of adjacent shorelines, a model study. J. Rays, Earth Surface 129. 7 Lesser Gr., J.A., Van J.A.T.M., Stelling G.S. 2004, Development and Validation of a Three-Dimensional Morphological Model. Coast 518883-915. 8 Van L.C., 1993, Principles of Sediment Transport in Rivers, Estuaries and Coastal Seas. Aqua Publications, The Netherlands. 9 LH, 2007, Waves in Oceanic and Coastal Waters. Cambridge University Press. 10 Al. 2025, MOZES, Research on the Morphological Interaction between the Sea Bottom and the Belgian Coastline, Working Year 3. Version 0.1. FHR Reports, 200793. Flanders Hydraulics Research, Antwerp. 3D Wave-Averaged Hydro Modeling of Sandbar Migration during the Duck 94 experiment with CROCO. Abstract. Sandbar migration, driven by complex interactions with nearshore hydrodynamics, remains a challenge for coastal modelers despite its critical role in dissipating incident wave energy. This manuscript aims at showing the ability of the 3D model CROCO, in its phase-averaged mode, to predict the cross-shore sandbar migration of a natural beach by solely depending on the wave conditions. The model benefits from the recently implemented and adapted SANTOSS formulation to compute sediment transport induced by shoaling wave asymmetry. Simulations are validated using datasets from the Duck 94 campaign, which capture the hydrodynamics and morphological changes of a barred beach in Duck, NC, USA. The model accurately reproduces observed onshore and offshore sandbar migration by varying only the wave forcing conditions. Same model parameters are used for both cases, achieving skill scores, BSS, of 0.69 and 0.74 respectively. Future work will extend the model alongshore to include 3D processes in the sediment transport, enabling the simulation of sandbar migration in both cross-shore and alongshore dimensions. Keywords. 1. Introduction. Sandbars play a crucial role in nearshore coastal processes by significantly reducing the energy of incoming waves breaking on the coast. However, existing models have shown moderate skill at simulating onshore and offshore migrations of sandbars at hours to days 1. The Coastal and Regional Ocean Sea, CROCO Model 2, has recently been enhanced with a new nearshore sediment transport model based on the SANTOSS Formulation 3. This formulation has been implemented in CROCO with some adaptation for the distinction between the wave-related transport, adapted SANTOSS, and current-related suspended load transport avoids conflicts and redundancy in the sediment budget computation. When compared to the erosion and accretion cases of flume experiments, CROCO showed its ability of predicting the offshore-onshore migration of a sandbar under storm post-storm conditions using the same configuration. These numerical simulations constitute a premiere in the prediction of the onshore and offshore migration of a sandbar using the same set of parameters. The model should now be applied to the morphological evolution of natural beaches to validate the good observed in the laboratory for the cross-shore migration of sandbars. As a first step, this manuscript aims to reproduce the onshore and offshore migration of the sandbar observed in the Duck 94 Campaign 5. The first section describes, briefly, the model formulation, followed by the presentation of the Duck 94 campaign and its associated measurement datasets in SECT. 3. Then these datasets are used in SECT. 4. To evaluate the resulting hydro simulations of the model. 2. Model formulation. The 3D model CROCO is used here in its phase-averaged mode to simulate hydrodynamics, waves, sediment transport, and morphological changes. The hydrodynamics are solved based on the vortex force formalism, allowing to divide the wave-averaged current equations and the non-conservative wave effects induced by waves. The WKB spectrum peak wave refraction model provides the necessary wave forcing, including the effect of currents on the waves. Sediment transport is split into two parts. The suspended load transport is solved with an advection diffusion equation using and Stokes drift velocities. The transport is solved with the recently developed adaptation of the SANTOSS Formulation 3, where the wave-averaged current contribution is removed, as its effect is already accounted for in the suspended load Model 4. Morphological changes induced by the sediment transport are solved using the formula. More details on the model formulation can be found in 2 and 4. 3. Duck 94 experiment. The Duck 94 in measurement campaign was carried out from August to November 1994, during which waves, currents, and bathymetry were measured on a daily basis along transects perpendicular to the beach of the Field Research Facility, FRF, in Duck, North Carolina, USA. During this measurement campaign, Duck Beach presented an alongshore uniform topobathymetry by the presence of an alongshore linear sandbar through system around 250 m distance in the FRF crossshore coordinates 5. Multiple datasets from the Duck 94 campaign are used to 1. Validate the 3D wave-induced hydrodynamic circulation of the model, and 2. Compare the surveyed bathymetries from the model predictions. On 12 October 1994, a storm event generated relatively energetic wave conditions of significant wave height 22 m, breaking around the sandbar and inducing intense currents. Cross-shore and alongshore vertical velocity profiles were measured at 7 locations during 1-hour-long runs using 7 electromagnetic current meters, EMCs, mounted on a mobile sled at fixed height from 0.41 m to 2.57 m above the seabed 6. The water level measured by the FRF tide gauge varied from -0.2 to 0.7, NAVD 88 m over the duration of the 7 runs. The transformation of the incident waves, due to the changing bathymetry, as it moves towards the beach was measured by a cross-shore array of 13 pressure sensors, yielding a comprehensive measurement of the wave height spanning the nearshore zone 7, as well as a 8 m depth pressure transducer array providing offshore bulk wave parameters. Bathymetry was surveyed on 12 October using the CRAB. The October 12 dataset is used to calibrate CROCO's ability to model wave-induced 3D hydrodynamic circulation on a barred beach under energetic conditions, such as those generated by storms, see SECT. 4.1. At the end of September 1994, the sandbar migrated towards the shore during a 6-day period of low-energy waves with a mean of 0.65 m, accretive case, followed by an offshore migration of the sandbar over a 4-day period due to the passage of a storm event, erosive case. This storm generated energetic wave conditions reaching a of 2.3 m and a relatively short period of 6.2 s, similar to the 12 October storm event. These three surveys, carried out over a short period of the order of a few days, and combined with the offshore wave conditions measured by the 8M depth pressure transducer array, provide a unique dataset for understanding and modeling the migration of a sandbar under various wave conditions, ranging from calm waves, 1M, to strong conditions, 2M. See sect. 4.2. 4 Model Simulations. 4.1 Hydrodynamic Simulations. This simulation aims at reproducing the hydrodynamic conditions of the 12 October of the Duck 94 campaign. The model is set up for 3D simulations along a crossshore of 900 m long, assuming alongshore uniformity. A periodic condition is imposed in the alongshore direction. The numerical domain is defined by an uniform horizontal grid with a resolution of 2M and 30 layers are used for the terrain following vertical coordinates over depths ranging from 0 to 8.5 m bathymetry. Variable wave conditions at the offshore limit and tide-induced water level variations, detected on October 12, force the simulation. A constant wind stress representative of the 12 October atmospheric conditions is also applied on the water surface. A model data comparison of the simulated significant wave height compared with data from 7. Bathymetry surveyed on 12 October is displayed in model data comparison of a cross-shore and B. Alongshore current velocities against observations from 8. Observation data are represented by the black circles. The vertical axes indicate the measurement locations. 4.2 Simulations. The CROCO configurations for both cases are identical. Only the initial bathymetry, the simulation time, and the wave conditions differ from one case to another. The numerical domain defines a 900 m long crossshore profile with horizontal resolution of 3 m and a vertical grid of 15 layers over depths ranging from 0 to 8.5 m, instead of 2 m horizontal resolution with 30 vertical level for the hydrodynamic simulations. The decreased resolution was chosen to guarantee stability in the model following the introduction of a moving bathymetry. Model data comparison of the predicted bathymetry for the accretive case, O, and the erosive case, B. Respective contributions of each sediment transport model, together with the total sediment transport contribution, are given for the accretive case and the erosive case in C and D, respectively. The critical bed shear stress, which controls the initiation of sand erosion in the suspended load model, is estimated at 0.173 nm2 from an empirical formulation that only depends on D50 and sediment density. A morphological factor of 16 is applied, significantly reducing the simulation time. In both cases, the migration of the bar is predicted in the right direction, respectively onshore directed for the accretive case, BSS 069, and offshore directed for the erosive case, BSS 074. Although there is underestimation of sediment transport in both cases, these results demonstrate the ability of CROCO to manage the balance between the transport model and the suspended load model with respect to the wave conditions. See Fig. 2. The calm wave conditions in the accretive case transport exceeding suspended load transport, illustrating the observed onshore sandbar migration driven by the asymmetry of shoaling waves under these conditions. In presence of more energetic wave conditions, such as in the erosive case, the model predicts a strong undertow current generated by the breaking waves over the sandbar, therefore inducing a greater suspended load transport compared to the transport. The simulation results in an abrupt offshore directed sandbar migration, in line with the in surveys. 5. Conclusion. In this manuscript, the 3D model CROCO-2 is used in its phase-averaged mode to perform hydrosimulations of a natural beach. The model includes a recently implemented model, adapted from SANTOSS 3.4, that computes the onshore directed sediment transport induced by the asymmetry of shoaling waves, while a suspended load model computes the offshore directed transport. Thanks to comparisons with multiple measurements from the Duck 94 campaign 517, the model demonstrates its ability to simulate the 3D nearshore circulation and the incident wave transformation over the barred beach of Duck, NC, USA. In the next step, morphological simulations for accretive and erosive cases, varying only forcing conditions, all model parameters being identical, successfully predicted shoreward sandbar migration for the accretive case and seaward migration for the erosive case. These predictions align with surveys from the Duck 94 campaign, yielding a BSS of 0.69 and 0.74, respectively. These encouraging results call for further investigations to provide, for the first time, a cross-shore prediction of onshore-offshore sandbar migration under storm and post-storm conditions using a single simulation. After this first step, the model should be extended to the alongshore dimension to help analyze the 3D nearshore circulation involved in sandbar formation migration. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Anderson D. A.S. N. K.L. Johnson B. P. 2023. The Impact of Inherited Morphology on Sandbar Migration During Mild Wave Seasons. Race 50, E2022, GL101219. 2P. R. R. Y. Williams J.C. A. 2015, on Rip Current Modeling. Ocean Model 963648. 3 Van A. D. A. Al. 2013. Practical Sand Transport Formula for Non-Breaking Waves and Currents. Coast 762642. 4H. J. C. P. 2023. Adaptation of the SANTOSS Transport Formula for 3D Nearshore Models. Application to Cross-Shore Sandbar Migration. Ocean Model 180-1102-138. 5 EL. S. RT 1998. Observations of Sandbar Evolution on a Natural Beach. J. Rays Oceans 103C232 033215. 6 AFG. Thornton EB. TC. TP 2000. Undertow over a barred beach. J. Rays Oceans 105C71699917010. 7S. RT. B. THC. EL 1997. Spectral Evolution of Shoaling and Breaking Waves on a Barred Beach. J. Rays Oceans 102C71579715805. Assessing satellite-derived waterlines in beaches with complex intertidal morphology. Abstract. Available tools for satellite-derived waterline (SDW) detection have been extensively validated in environments. However, detection of the water-land interface in beaches is still a challenge due to the complexity of the intertidal morphology together with intense hydrodynamic conditions. There is a need for further understanding of the environmental conditions that cause SDW, and how this knowledge can be used to flag erroneous SDWs automatically. The aim of this study is to assess the capacity of SDW detection in 2 environments with complex beach morphology using currently available methods. Here, we correlate issues to hydrodynamic factor such as wave, storm surge, and tide conditions at the instant of the image acquisition. The results indicate that the main oceanographic factors affecting SDW detection are tidal level and phase, flood ebb. Accurate detections are typically observed at higher tidal levels during the flooding phase, which is related to the fact that during the flooding phase, the sand in the water-sand interface is dry, and soil moisture does not affect the waterline detection. In the study area, no SDW detection was done during higher tidal levels, which could pose an issue for detecting accurate SDWs during high tides. Other factors such as SDW sinuosity, usually associated with the detection of complex intertidal bar shapes, correlated to erroneous SDW, for which it can be used as an additional parameter to flag SDW. Keywords. 1. Introduction. In recent years, satellite-derived waterlines, SDWs, have increasingly emerged as a key data source for analyzing the historical evolution of beach morphology, a fact that can be attributed to the global coverage, large time series, up to decades, and high frequency provided by recent satellite missions. Furthermore, public missions now allow for low-cost monitoring. Many tools were developed with the aim of automatically detecting the shoreline position in coastal environments, e.g. 1.3. Enabling the characterization of the shoreline evolution in several temporal and spatial scales. 4. While existing tools for SDW detection from optical satellite images have been extensively tested and validated in environments, their application in beaches poses significant challenges. The large intertidal zones with substantial cross and longshore morphological variability, together with the occurrence of intense hydrodynamic conditions, waves, tides, and surge, make the extraction of SDWs a complex process, often resulting in errors in detecting the water-land interface. 5. Thus, in beaches, extraction algorithms may often detect other interfaces instead of the waterlines. See Fig. 2. Given the vast amount of SDWs that can be derived from satellite images, identifying erroneous detections within the SDW time series presents a significant challenge in data processing. 6. Nevertheless, for the moment there is a need for further understanding of the environmental conditions that lead to SDW in environments, and how this knowledge can be applied to automatically flag erroneous SDWs. The aim of this study is to assess the capacity of SDW detection in environments with complex beach morphology using currently available methods. In order to do so, those SDWs that do not represent the waterline are identified and correlated to local hydrodynamics to understand the physical conditions that lead to erroneous detections. 2 methods. 2.1 Study site. Location of study sites: Salinas and El Puntal beaches on the northern coast of Spain. 2.2 Data. The SDWs were extracted from images captured by Sentinel-2 satellite missions. The SDW extraction was done with the SHOREX Tool 2, covering the period from 2015 to 2024, 144 SDWs for Salinas and 141 SDWs for El Puntal. The hydrodynamic factors considered were wave and storm surge data from numerical modeling and tide data from the nearest tide gauges, all of them obtained from the State Harbor Monitoring System, EASE. 2.3 Assessment of SDWs. The assessment was done through the following steps. I. Detection of the SDW using SHOREX. Definition of cross-shore transects equally spaced, every 50 m, along the beaches. Verification of the shoreline indicator. See indicators in Fig. 2. Identified as SDW in each transects by an operator who contrasts the SDWs over the respective satellite images. For each SDW, estimation of the percent of transects in which the SDW was correctly identified as the waterline. Correlation between this value and the respective hydrodynamic conditions at the moment of the image acquisition, as well as the characteristics of the SDW vector. For this last step, the following variables were considered. Significant wave height. Significant wave height. Peak wave period. Peak wave period. Astronomic tidal level. Astronomic tidal level. Storm surge level. Storm surge level. Tidal phase Boolean, 0 if ebb and 1 if flood tide. Tidal phase Boolean, 0 if ebb and 1 if flood tide. Tidal level plus tidal phase. The tidal level was categorized using ordinal encoding into discrete ranges based on quartiles. Minimum to P 25% 0, P 25% P 50% 1, P 50% P 75% 2, and P 75% maximum 3. The tidal phase was classified as either ebb 0 or flood 1. These variables were then combined to compute a single average value. Tidal level plus tidal phase. The tidal level was categorized using ordinal encoding into discrete ranges based on quartiles. Minimum to P 25% 0, P 25% P 50% 1, P 50% P 75% 2, and P 75% maximum 3. The tidal phase was classified as either ebb 0 or flood 1. These variables were then combined to compute a single average value. Vertex count refers to the number of points, vertices, that define the shape of a SDW line vector. Vertex count refers to the number of points, vertices, that define the shape of a SDW line vector. Sinuosity, a measure of how far from a straight line the SDW vector is. Estimates are done as sinuosity. Sinuosity, a measure of how far from a straight line the SDW vector is. Estimates are done as sinuosity. Different shoreline indicators, obtained by applying typical SDW detection algorithms in the beach El Puntal. 3 results. The results of the correlation analysis indicate that the main environmental factors affecting SDW detection in these beaches are the tidal level and the phase, flood ebb, see Fig. 3. Good detections were positively correlated to higher tidal levels during the flooding phase, with a correlation of 0.56. This may be related to the fact that during the flooding phase, the sand in the water-sand interface is drier, and the soil moisture does not affect the waterline detection. Inverse and weaker correlation was observed with wave parameters 0.15.4 and 0.28.4, indicating that large waves and periods tend to result in lower accuracy in waterline detection. Wave oscillations lead to water saturation of the sand along the swash zone, and some errors may arise if the image is taken during the rundown phase of energetic wave conditions. The correlation with storm surge wasn't significant, p-value 0.005. Correlation coefficient between each environmental variable and the percent of transects per SDW in which the waterline was correctly identified. Tidal phase is a Boolean variable that refers to the moment of the tide, ebb 0, flood 1, and the variable tidal level plus phase is derived as the average of an encoded tidal level, categorized into quartiles, 0 to 3 for each 25th percentile, and the Boolean tidal phase. Time series of astronomical tide, at El Puntal purple line. The yellow dots represent the time of each satellite image used in the analysis. Note that no dots are presented in water levels higher than 4 m. Finally, we also examined the correlation with SDW vector characteristics, including the vertex count and SDW sinuosity. A line vector consists of a sequence of connected straight-line segments, where each segment begins and ends at a vertex. The total vertex count reflects the complexity or detail of the line, with higher counts indicating more intricate shapes. This analysis revealed a positive correlation between the vertex count and the SDW, with a coefficient of 0.51, see Fig. 3. Conversely, high sinuosity, which is associated with the detection of complex intertidal bar shapes, showed an inverse correlation of -0.51 with erroneous SDWs, see Fig. 3. Both characteristics can serve as additional parameters to identify and flag potential SDW. 4 conclusions. This study presented new insights on the capacity of currently available SDW extraction tools to detect the waterline in beaches. According to the results presented here, accurate detections are typically observed at higher tidal levels during the flooding phase, which is related to the fact that during the flooding phase the sand in the water-sand interface is dry, minimizing the influence of soil moisture on waterline detection. These results highlight the importance of adapting the currently available waterline-shoreline detection and interpretation methods to beaches in order to detect morphological changes from SDWs in such complex environments. The next steps of the study will include exploring new approaches to improve shoreline detection in beaches, expanding the study to a wide range of beaches to develop methodologies tailored to specific hydrodynamic and conditions, developing an automatic method to flag erroneous waterline detection. This study forms part of the Thinkin and was supported by with funding from European Union Next Generation EU, PRTR C17I1, and the contract CIAPOS 2023394 funded by the European Social Fund Plus. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1K, Splinter KD, MD, JA, Turner IL, 2019. A Google Earth Engine-enabled Python toolkit to extract shorelines from publicly available satellite imagery. Environ Model, 122, 104528. 2E, JM, Pardo JE, J.C., L. 2020. An efficient protocol for accurate and massive shoreline definition from mid-resolution satellite imagery. Coast, 161, 03732. 3LP, IE, Lyra R, RLS Martins VG, AHF 2021, Coastal Analyst System from Space Imagery Engine CASSIE, Shoreline Management Module. Model 141.0, 5033. 4K, M, Splinter KD, JA, Turner IL, 2019. Subannual to multi-decadal shoreline variability from publicly available satellite imagery. Coast, 151, 6174. 5K AL, 2023. Benchmarking satellite-derived shoreline mapping algorithms. Earth Environ 4345. 6P, MS, Medina R, Beck AL, MA 2024, on the use of satellite information to detect coastal change. Demonstration case on the coast of Spain. Coast, 171, 104519. Microplastic pathways in the Arctic, integrating the hydrodynamic model with advanced ray tracing particle tracking. Abstract. Microplastic pollution in the Arctic represents a critical environmental challenge, driven by the region's intricate hydrodynamics and rapidly evolving climatic conditions. This study integrates high-resolution TELEMAC 3D, TOMAWAC, and 3D models to analyze source receptor pathways and identify accumulation zones for microplastics. The modeling framework incorporates wind, wave dynamics, and other processes influencing particle transport. Hydrodynamic validation was conducted via a combination of in- and remote sensing datasets. Results highlight potential accumulation areas and underscore the necessity of accounting for diverse transport mechanisms to accurately predict microplastic movement and deposition in Arctic waters. Keywords. 1. Introduction. Increasing microplastic pollution marine environments presents a significant ecological concern, driven by both local sources and long-range transport mechanisms. These particles, with characteristic diameters below 5 min greater than 1, are capable of producing toxic effects in a wide variety of organisms and are an important emerging contaminant one. While this trend is occurring throughout global water bodies, the Arctic Ocean, as an environment already under stress from climate change and falling sea ice concentrations, is both a uniquely vulnerable and highly complex site too. The Arctic's unique hydrodynamic, wave, and salinity conditions influence the dispersion and fate of microplastic particles, yet the processes governing their pathways remain insufficiently understood. And recent reviews have highlighted the importance of better understanding these transport pathways. 3. Particular emphasis has been placed on determining the relative impacts on transport from tidal currents, wind-driven currents, wave action, and buoyancy processes. 4-5. This is particularly important in the Canadian Arctic archipelago, where multiple ocean currents interface with complex shorelines, compounded by a limited amount of validation data. While Arctic microplastic concentrations have been measured in a number of recent investigations, 6. Relatively few investigations have attempted to apply numerical modeling to develop a more comprehensive understanding of transport pathways, which has been repeatedly cited as a vital research area. 5. A global NEMO Model 7, with a focus on the Fram Strait, was used to understand the impact of Arctic sea ice microplastic concentrations and identified concentration trend aligning with some observational data. 6. The impact of wave action has also been investigated in the surf zone, finding that it can be an important factor in transport. 8. To effectively understand microplastic source receptor pathways, it is therefore important to account for these processes. This study aims to address these knowledge gaps by applying the TELEMAC 3D hydrodynamic, TOMAWAC spectral wave, and 3D 9-10 particle tracking model (PTM). This combination of state-of-the-art tools provides a comprehensive approach to modeling microplastic transport by including a full range of processes. The integration of TELEMAC 3D with wave action and ray tracing particle tracking marks an advancement in simulating microplastic dynamics in the unique Arctic environment. 1.1 Grid and Study Area. Overview of Model Domain and Bathymetry. 1.2 Numerical Setup. The hydrodynamic modeling of the study was conducted with the TELEMAC 3D9 P013 suite, which employs a finite element approach on an unstructured mesh to solve Stokes equations. This widely applied 14 model is noted for its accuracy and excellent properties in high-performance computing environments. The three-dimensional, hydrostatic implementation of the model was used with a K-turbulence closure model in conjunction with the TOMAWAC spectral wave model 13. The mode boundary conditions for water levels and velocities were imposed using TPXO10 tidal constituents 15 and spectral waves from ERA 516, along with river discharges 17, and wind forcing derived from ERA 516. Particle tracking modeling was performed using 3D 9-10, a high-performance particle tracking model for simulating various particle types, with a focus on microplastics, using a parallelized ray tracing algorithm that handles ray reflection and refraction to track particle locations across three-dimensional unstructured grids. 3D incorporates numerical corrections for round-off errors, water surface discontinuities, and includes partially reflective boundary conditions, along with the ability to simulate microplastic beaching and washout in shallow or dry areas. 10. 2 Results. Water level validation at 4 selected sites shown in Fig. 1. Observed a C, E.G. and modeled B, DFH velocity at 4 Barrow Strait sites. Fig. 1. Model and satellite icons. Significant wave heights on 2019-09-18, 1949 UTC. 3 particle accumulation patterns. A normalized particle concentration at the conclusion of a 3-week simulation during September 2018. B. Difference in final normalized concentration, with and without wave action. 4. Conclusions. The Arctic is a complex environment where the understanding the microplastic transport remains a critical challenge for effective response and monitoring programs. To address this, a high-resolution TELEMAC 3D hydrodynamic, TOMAWAC wave, and 3D PTM models were applied in the Canadian Arctic. After validation, results showed that this approach provides a useful tool to identify potential particle accumulation zones and also highlighted the importance of accounting for all relevant processes, including wind-driven currents, wave action, and salinity gradients. Future work should focus on including the impacts of ice cover, as well as the processes of particle settling and resuspension, which are essential for capturing vertical transport dynamics. Long-term simulations will also provide valuable information for assessing seasonal and variability, while expanding observational datasets, particularly near Arctic communities, will improve model calibration and support informed decision-making for plastic pollution mitigation. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References. 1D P. A. N. M. Singaske al. 2021. The Impact of Microplastics on Marine Environment. A Review. Environ 16100552. 2T. R. P. E.V. A. S. al. 2023. Floating Microplastic Inventories in the Southern Sea. Arctic Ocean Front Mar 1012888301. 3JF S. M. M. Boole L. F. al. 2023. Future Monitoring of Litter and Microplastics in the Arctic Challenges, Opportunities, and Strategies. 9209-226. 4M, AAM 2022, Modeling of Marine Microplastics Fate and Transport, The State of the Science. J. Mar 10481. 5BD, J. A. L. N. J. Al. 2017. Using numerical model simulations to improve the understanding of microplastic distribution and pathways in the marine environment. Front Mar Internet. 6PS, S. E. A. S. S. A. Al. 2021. Pervasive distribution of polyester in the Arctic Ocean is driven by Atlantic inputs. 12106. 7 As, Morales M.A. 2021. Modeling the Accumulation and Transport of Microplastics by Sea Ice. J. Rays Oceans 126, E202, 0JC016826. 8S, DH, 2024, Short-Term Buoyant Microplastic Transport Patterns Driven by Wave Evolution, Braking, and Orbital Motion in Coast. Marble 201, 116248. 9A, A. Murphy E., 2022. A numerical framework for modeling fate and transport of microplastics in inland and coastal waters. Marble 184 114119. 10M AARS P 2025. A high-performance ray tracing particle tracking model for the simulation of microplastics in inland and coastal aquatic environments. 307 109423. 11 Roberts KJ WJ, JJ, 2019, Ocean Mesh D1, MATLAB-based software for two-dimensional unstructured mesh generation in coastal ocean modeling. Model 12 184768. 12 NOAA NCEI. ETOPO, 2022, 15 arcsecond global relief model. Cent Environ. 13 WA, 2020. Ongoing developments in TELEMAC and TOMAWAC at IMDC. Online Proc PAP, 2020 TELEMACMACRET User Conf, 2020. P 11521. 14I, Murphy E., Church I, A., Cornet A., 2019. Three-dimensional modeling of hydrodynamics and circulation in the St. John River Estuary, Canada. 15 Egbert G.D., SY 2002, Efficient Inverse Modeling of Barotropic Ocean Tides. J. Atmospheric Ocean Technol 19-183-2-04. 16 Bell B., H. A. P. P. A. Al. 2021, The Era 5 Global Reanalysis, Preliminary Extension to 1950. QJ R. Soch, 14741864227. 17 Natural Resources Canada, 2012, The Atlas of Canada, Rivers Internet. 18 Environment Canada, 2023, Historical Hydrometric Data Map Search Internet. 19 Morin K., Juniper K., S. D. I. M. Al. 2022, Canada's Internet Connected Ocean. Front Mar Internet. 20 S. R. 2008, Ice and Ocean Mooring Data Statistics from Barrow Strait, Central Section of NW Passage in Canadian Arctic Archipelago. J. Offshore Polar. 18. 21 EUMETSAT4. SRAL Level 2 Altimetry, Global Sentinel-3 Reprocessed. Monitoring the mean high water shoreline along the Cap Ferret Sand Spit, SW France, using the satellite-derived wet-dry sand line. Abstract. Building long shoreline position databases is critical to improve knowledge on past coastal dynamics and predict future changes. Several satellites acquiring recurrent optical images over land and coastal areas have been commissioned since the 1980s. This has allowed the implementation of various satellite imagery-based shoreline detection algorithms for sandy coasts, which rely on the waterline delineation. However, the detection accuracy decreases with increasing tidal range at sites exhibiting a non-uniform intertidal profile slope. This generally forces to exclude satellite images acquired near low tide at and coasts. This communication explores the ability of the wet sand-dry sand line extracted from satellite images to reproduce the mean high water shoreline along the scale Cap Ferret Sand Spit, SW France. The results show that satellite-derived wet-dry line provides a consistent proxy of the mean high water shoreline, with almost no influence of low water levels at image acquisition time. However, the use of satellite-derived waterline to retrieve the MHW shoreline should still be preferred for images acquired at high water levels. Keywords. 1. Introduction. With the commissioning of satellite constellations, providing free-access high-resolution images in the recent years, e.g. Landsat 8-9, Sentinel-2, there have been a growing effort within the coastal science community to implement robust and accurate methods to monitor shoreline changes from Earth observation products, e.g. 1.3. Most of these methods rely on delineating the interface between water and land surfaces, usually referred to as the instantaneous waterline. In environments, this satellite-derived instantaneous waterline matches well with shoreline proxies, e.g. Mean sea level, upper swash limit, used to study shoreline changes on timescales from days to decades, e.g. 3. In and environments, between low and high tides, the cross-shore position of the waterline can easily vary by tens to hundreds of meters, depending on the tide range and intertidal beach morphology and slope. Because the satellite images are taken at different tide states from one image to another, the satellite-derived instantaneous waterline cannot be used as a consistent proxy of the shoreline to address coastal changes in such tidal environments. To face this limitation, tidal correction algorithms have been developed to estimate the contribution of the tide to the waterline horizontal shift and to generate tidal-corrected waterlines having more consistency in time, e.g. 3.4. Tidal correction algorithms assume that the beach slope is constant. However, in and environments, beaches usually present a convex profile within the intertidal zone, with sometimes bars and rips emerging at low tide. Consequently, tidal correction algorithms can sometimes fail at compensating the tidal effect, especially for waterline derived from satellites' images taken near low tide 5. Another strategy to face this limitation consists in creating composite waterlines from a set of subsequent satellite-derived instantaneous waterlines taken over a rolling period long enough to cancel sea level variation effects, e.g. 2. However, such rolling period are typically of 1 year, which prevents from addressing shoreline changes occurring on timescales from days to seasons. For these reasons, it is necessary to investigate other approaches to extract the shoreline position from satellite imagery that suits 2 and environment 6. This communication explores how the boundary between the wet sand and the dry sand visible in satellite images can reflect the position of the mean high water (MWH) shoreline along the to Cap Ferret sand spit (SW France Fig. 1 as). For that purpose, MHW shorelines extracted from several LiDAR surveys are compared to wet-dry lines extracted from satellite images taken at dates close to those of the LiDAR surveys. A comparison with non-corrected satellite-derived waterlines is also provided. 2 Data and methods. 2.1 Topographic surveys and shorelines. 6 MWH shorelines were extracted from 6 LiDAR surveys acquired over the Cap Ferret sand spit by the Coastal Observatory of the Nouvelle Aquitaine region SW France between 2014 and 2021-7. Along the open coast of Cap Ferret sand spit, the MHW elevation is approximately 1.9 m NGF IGN 69, official French vertical datum, which corresponds to an elevation of about 1.5 m above mean sea level 4. 2.2 Satellite images. A B location map of the Cap Ferret sand spit and the study area orange rectangle. C Sentinel-2 image acquired on the 11-10-20-17, zoomed over the study area. White dashed lines denote some of the transects used to extract the wet-dry line from satellite images. The green curve indicates the baseline defining the origin. 2.3 Image classification. Satellite images were classified into 8 classes using a supervised classification algorithm based on a multi-layer perceptron neuronal network and inspired from the approach given in 3. To enable extraction of both the waterlines and wet-dry lines, the following classes were used: deep water, shallow water, wave foam, very wet sand, slightly wet sand, dry sand, vegetated dunes, others urbanized areas and dense vegetation. Distinct classifiers were trained and applied separately for Sentinel-2 and Landsat 8 images. For both classifiers, the training was based on pixel labeling over 12 images. Post-processing was applied to clean classified images. This includes light smoothing of class boundaries and removal of every isolated small patches of a class located within wider patch of a different class. 2.4 Wet-dry lines and water lines. The wet-dry line was defined as the boundary between pixel areas of marine and wet classes, deep water, shallow water, wave foam, very wet sand, slightly wet sand, and pixel areas of dry classes, dry sand, vegetated dunes, others. Extraction was made from each classified images at pixel scale, using a set of cross-shore transects that discretizes the coast in the longshore direction, within a longshore spacing of 10 m along the origin baseline, Fig. 1c. In case multiple wet-dry boundaries are found along the most offshore wet-dry boundary, among those not located seaward of any pixels belonging to the very wet sand and marine classes was kept. Following this rule ensures that we do not select a wet-dry boundary that could be located on a dried sandbar detached from the upper dry beach. Waterlines were extracted from each satellite images using the method given in 3. For each satellite images, This requires the computation of the optimal threshold in modified normalized water index, MNDWI, values that best distinguishes pixels belonging to the water classes from pixels belonging to sand classes. Then, for each satellite image, the water lines were delineated using a contouring method applied to the image-derived MNDWI raster based on the corresponding threshold. In the comparison with the MHW shorelines shown later, the most in-shore intersection between the waterlines and the cross-shore transects mentioned above was kept. Taking the most in-shore intersection minimizes the distance between the waterline and the MHW shoreline. 3 results. Comparison between satellite-derived wet-dry lines, red curves, satellite-derived waterlines, orange curves, and LiDAR-derived MHW shorelines, black curves for 6 matchups. A Landsat 8 image of 1710-2014. B, C, D, E, F Sentinel-2 images of 3110-2016, 1110-2017, 1610-2018, 90122020, and 1010-2020, respectively. The green curve indicates the baseline defining the origin. Visually, the wet-dry lines follow pretty well the MHW shorelines for all dates and capture the shoreline undulations that are sometimes present along the sand spit, e.g. Fig. 2C and D. The waterlines show similar abilities, except when extracted from the image acquired on 3110-2016 near low tide, Fig. 2B. Waterlines extracted from that image are clearly influenced by the presence of emerging ridge runnel systems. Even with a water level correction, it can be anticipated that for such low water levels, satellite-derived waterlines cannot be used to derive accurately the MHW shoreline and its alongshore variability. Global skills of the satellite-derived waterline and wet-dry line at reproducing the MWH shoreline. Shoreline proxy. Bias. RMSE. R2. Waterline. 26.7. 38.8. 0.75. Wet-dry line. 6.7. 20. 0.87. Skills of the satellite-derived waterline and wet-dry line at reproducing the MWH shoreline per matchup. Satellite image date. Shoreline proxy. Bias. RMSE. R2. 1710-2014. Waterline. 7.9. 13.8. 0.96. Wet-dry line. 27.5. 30.5. 0.94. 3110-2016. Waterline. 69.8. 78.4. 0.39. Wet-dry line. 4.4. 21.5. 0.8. 1110-2017. Waterline. 27.4. 33.2. 0.84. Wet-dry line. 14.1. 18.8. 0.94. 1610-2018. Waterline. 6.7. 9.5. 0.98. Wet-dry line. 12.1. 15.1. 0.97. 90122020. Waterline. 29. 25.4. 0.98. Wet-dry line. 5.8. 16.4. 0.97. 1010-2020. Waterline. 27.7. 29.4. 0.96. Wet-dry line. 3.6. 12.7. 0.94. For some specific matchups, for which satellite images were acquired with high water levels, the non-corrected waterline reproduces better the MHW shoreline than what the wet-dry line can do. Table 2, 10.2014 and 10.2018. For the 10.2014 matchup, the water level including tide and wave was slightly higher than the MHW elevation. This causes the wet-dry mark on the beach to be at elevations well higher than the MHW elevation, and explains why the skills obtained with the wet-dry line are poor. 4 conclusions. Our results suggest that the use of the wet-dry line as a proxy of the MHW shoreline at Cap Ferret sand spit could provide better results with more consistency. It allows using more safely satellite images acquired near low tide with no need of post-processing and visual controls, which are required when the waterline is used. However, for satellites image acquired at high water levels, e.g., higher than the MHW elevation, it seems preferable to use the waterline to derive the MHW shoreline. We anticipate that the accuracy of state-of-the-art satellite-based shoreline detection algorithms could be significantly increased for coasts if the wet-dry line is also taking into account. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Pardo J. L.A., J. 2012. Automatic extraction of shorelines from Landsat TM and ETM plus multitemporal images with precision. Remote Sens Environ 123, 111. 2AG RFG S 2018, The State of the World's Beaches. Rep 816641. 3K, MD, Splinter KD, JA, Turner IL, 2019. Subannual to Multi-Decadal Shoreline Variability from Publicly Available Satellite Imagery. Coast 151, 6174. 4B Al, 2021. Satellite-Derived Shoreline Detection at a High-Energy Beach. Geomorphology 383, 107707. 5AT, G, Stokes K. D. B, 2023. Satellite-based shoreline detection along high-energy coasts and influence of beach state. MAR 462, 107082. 6K Al, 2023. Benchmarking satellite-derived shoreline mapping algorithms. Earth Environ 4 1345. 7A Al, 2022. Decadal beach dune profile monitoring along a 230 high-energy sandy coast. Aquitaine, Southwest France. 139, 102645. Field measurement of seagrass coastal protection. Services in a fetch-limited, non-tidal sea. Abstract. Seagrass meadows are recognized for their coastal protection services in terms of reducing the wave level and limiting coastal erosion. This study aims to quantify these services for a dense seagrass meadow located in a non-tidal, fetch-limited sea. A year-long field campaign was conducted to collect data on wave statistics along the cross-shore direction of the seagrass meadow, bathymetry, and seagrass meadow characteristics. The seagrass meadow, composed of Zostera marina, extends from approximately 6 m to 2.3 m depth and is followed by a multi-bar, gently mild sloping foreshore, 1/100. A 1DX beach model was used to assess the wave transformation across the cross-shore profile and the dune erosion during a selected storm event, both with and without the seagrass meadow represented in the model. Maximum wave attenuation by the seagrass meadow reached 5%. However, this effect was diminished by depth-induced wave breaking. Consequently, the presence of the seagrass did not result in notable difference in wave levels or dune erosion when the seagrass meadow was excluded from the simulations. Keywords. 1. Introduction. Coastal hazards pose significant challenges to communities worldwide, highlighting the need for effective coastal protection. Seagrass meadows are claimed to provide coastal protection services by attenuating wave energy 1 and stabilizing sediment 2. Laboratory experiments further support these findings, demonstrating that seagrass can significantly reduce wave energy while also influencing the cross-shore redistribution of sediment. For instance, seagrass has been shown to shift bar positions and decrease subaerial beach erosion 3, 4. In the recently concluded EU Life project Life Coast Adapt, a seagrass meadow was planted to explore its protective potential. However, as the meadow is still in its early stages of establishment, it remains too young to evaluate comprehensively. Therefore, to investigate the potential of seagrass meadows as a coastal protection measure, a field campaign was initiated to study the coastal protection services provided by a mature seagrass meadow under similar conditions to the planted meadow. This study, conducted in a non-tidal, fetch-limited environment, involved year-long monitoring of wave dynamics, bathymetry, and seagrass meadow properties. The research question focused on the ability of the established seagrass meadow to reduce dune erosion and total water levels during storm events. 2. Methodology. In the region of the study site, the lower cross-shore profile is predominantly covered by seagrass meadows, or, except under conditions of excessive wave energy. This prevented the possibility of identifying two sites with comparable wave conditions and bathymetry, one with and one without seagrass. Consequently, the impact of seagrass meadows was analyzed using a calibrated numerical model, X-Beach 5, which is capable of simulating wave dissipation by seagrass. The model was calibrated with field data collected during the campaign, and the effect of the seagrass meadow was assessed by excluding vegetation parameters in the calibrated model setup. 2.1 Field data collection. Wave data were collected using 6 3-wave pressure sensors deployed along a perpendicular to the shoreline Fig. 1. 5 sensors AE were positioned within the seagrass meadow at depths below the mean sea level of A, 6.9 m B, 5.4 m C, 4.6 m D, 3.6 m and E, 2.3 m. An additional sensor, F, was placed offshore of the first sandbar at 1.1 m depth. The sensors sampled pressure data at 8 in bursts of 17 min, every 30 min. The measurement periods spanned December 2022 to June 2023 and August 2023 to December 2023. Offshore wave conditions were monitored using an WaveDroid buoy, which recorded wave height, period, and direction in 30 min bursts. Wave statistics were calculated using OceanLYZ6 to account for the pressure attenuation in the water column above the sensor. The bathymetry along the was surveyed using a combination of RTK-GNSS and an autonomous surface vehicle, USV, equipped with RTK-GNSS and a single echobeam sonar. RTK-GNSS was used to measure depths from land to 0.5 m, while the USV extended the profile to 9 m depth. Bathymetric surveys were conducted bi-monthly throughout the field campaign. The characteristics of the seagrass meadow were assessed through underwater video surveys. Discrete sampling of seagrass shoots was carried out in May 2023 and May 2024, and used to calibrate video analyses. Seagrass inventories conducted in 2020 provided additional data on seagrass coverage 7. 2.2 Numerical Model Setup. A 1D X-Beach model was used to analyze the coastal protection services of the seagrass meadow. The impact of the seagrass meadow was assessed by running the X-Beach model with and without the vegetation module. Comparisons were made for a selected storm event based on maximum total water levels from Wave Data 8 and observed water levels from 1976 to the present. The numerical model XBeach was selected for this study due to its ability to simulate both complex hydrodynamic and morphological processes, including wave dissipation by submerged aquatic vegetation. A 1D model configuration was implemented based on surveys conducted during the field campaign. A 1M resolution was applied along the crossshore, which was oriented in a west-east direction. Offshore wave boundary conditions were defined using data from the most seaward pressure sensor. The wave conditions were described using a JONSWAP spectrum, with directional data derived from the wave buoy. Vegetation parameters required as input by XBeach are plant height, leaf width, and plant density, which were derived from the field observations. The drag coefficient of the vegetation was calibrated using wave measurements over the seagrass meadow. Additionally, the calibration of parameters unrelated to vegetation was based on sensor F Fig. 1. As no vegetation was present between the sensors at E and F, dune erosion was defined as the volumetric difference above the dune toe elevation between the initial and final profiles in the simulation. The dune toe elevation was determined from field surveys and set to 1.2 m. Total water levels were calculated by extracting the water level and wave height at a nearshore location, x 735 m in Fig. 2 in the model. Wave was estimated using 9 for a riprap revetment, with slope and surface roughness parameters derived from an adjacent revetment. Offshore still water levels were obtained from SMHI's station 2228, located 20 north of the study site. 3 Study site. The study was conducted at lat. 55.96, 12.75, a small coastal settlement on the southwestern coast of Sweden, which was designated as one of the pilot sites in the EU LIFE project Life Coast Adapt. The study site is situated along a strait connecting the Baltic Sea to the North Sea. This area experiences minimal astronomical tidal variation, with amplitudes of less than 10. However, tides have been observed to reach up to 1.68 m above mean sea level, as recorded at the SMHI station 2228. The historical wave climate for the study site was derived from a regional SWAN model, which provided hourly wave data from 1959 to 2023-8. Preliminary total water levels were reconstructed by combining these wave data with observed water levels, neglecting dissipation processes, to identify the most severe historical storm at the site. The highest total water level occurred during a storm event in 2011, which was subsequently selected as the reference storm scenario. For this event, the significant wave height ranged between 0.3 to 1.7 m, peak period between 2.3 to 4.6 s, wave directions during the highest waves 271 w, and water levels from 0.2 to 1.6 m above mean sea level. During extreme storm events, damage is caused by dune erosion and wave. The coast at the study site is characterized by a sandy, mild-sloped upper cross-shore profile with a series of 4 to 5 sandbars. D50 are approximately 0.21. The depth of closure, defined following 10, is approximately 2.5 m, with a bottom slope of 1/100 up to this depth. An aerial photograph of the study site showing the wave buoy yellow dot, wave pressure sensors red dots, bathymetry, black line, and seagrass meadows delimited by green lines. B. Wave rose from buoy measurements. C. Orientation map with the case study area, red rectangle. D. Overview of with the study area, yellow dot. 4 Results. Wave attenuation as waves propagate towards the shore is influenced by multiple dissipation processes, including wave breaking, bottom interaction, and influence of vegetation. The total wave dissipation was estimated by calculating the ratio of wave heights measured by the wave buoy and sensors AF. The median wave attenuation was at sensor A, 0.99, sensor B, 0.94 sensor C, 0.94 sensor D, 0.9 sensor E, 0.9 and sensor F, 0.78. However, the attenuation represents not only dissipation due to vegetation, but also the combined effects of all wave dissipation processes. Analysis of the wave measurements show that wave dissipation increases as water depth decreases, with the largest reductions observed at the shallowest sensor F. This is primarily attributed to depth-induced wave breaking. Using the numerical model, the contribution of the seagrass meadow to wave dissipation was isolated. Figure 2b illustrates wave height profiles along the simulated, for scenarios including and excluding vegetation. The model indicates that the seagrass meadow influenced wave heights primarily at depths between 4.3 and 0.5 m, with a maximum reduction of 5% during the simulated storm event. Above 0.5 m depth-induced wave breaking became the dominant wave dissipation process. Model simulations indicated that during the selected storm event, dune erosion resulted in a volumetric loss of 4.1 m3m, and this erosion increased by 5% when excluding the seagrass. This suggests that the presence of the seagrass meadow has a very limited impact on dune erosion during storms at the study site. An example output from one of the calibration simulations, B. Simulation results from X Beach for the time step with the highest wave conditions during the selected storm event. It can be concluded that the seagrass meadow at the study site has negligible influence on wave conditions once depth-induced wave breaking begins. This is attributed to the depth of the seagrass meadow relative to the typical wave periods and the dominance of depth-induced breaking on the shallow foreshore. Consequently, the seagrass meadow provides very limited coastal protection service at the study site. This study indicates that seagrass meadows are not a viable coastal protection method for all shorelines. This conclusion is supported by 12, suggesting that seagrass meadows' optimal coastal protection function is achieved in shallow waters with low wave energy environments. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1M, N, CM, G, 2024, Mediterranean seagrasses provide essential coastal protection under climate change. Rep 14, 130269. 2M, Bull JC, KW, Kennedy Ha, M, D. Al, 2017, Measuring the Role of Seagrasses in Regulating Sediment Surface Elevation. Rep 7, 111917. 3D, P, TJ, A. Manes C. 2024, On the Wave Attenuation Properties of Seagrass Meadows. Coast, 189, 104472. 4C, V. I. Sierra JP, A. 2022, Beach Profile Changes Induced by Surrogate, Laboratory Experiments. Coast, 175, 104144. 5D, A. Van J. Call R. J. 2009, Modeling Storm Impacts on Beaches, Dunes, and Barrier Islands. Coast 56, 1112, 113352. 6A, Q. 2017, Wind Wave Analysis in Depth Limited Water Using OceanLYZ, a MATLAB Toolbox. 106, 180, 1189. 7K, A. 2020, I. Helsingborg 2020, in Fauna Epifauna Med. UB. 8AB, Kroon A. M. CB. C. 2023, spatial and temporal wave climate variability along the south coast of Sweden during 1959-2021. Stud Marine, 63103011. 9. 2018. Manual on Wave Overtopping of Sea Defenses and Related Structures. An overtopping manual, largely based on European research, but for worldwide application. 2nd edition ed. 10 RJ, 1978. Editor uses for a calculated limit depth to beach erosion. Proc 16th Coastal Conf Hamburg, Germany. 11 T. J. P. 2022. Eelgrass meadows harbor more species but bare sediments can be as functionally diverse. J. X. Mar, 554-151777. 12b IJ JL M C TJ Al 2014. The role of seagrasses in coastal protection in a changing climate. Coast 80 7-158-168. Machine learning identification of pollutants and other debris in Canadian waterways. Abstract. Plastic pollution is a global challenge, necessitating innovative monitoring solutions. This paper explores the use of artificial intelligence, AI-enhanced methods for litter detection by leveraging state-of-the-art convolutional neural network, CNN, architectures. A novel dataset was created, using stationary camera data from Canada. This dataset enabled a comparative analysis of model performance, identifying dense Net 121 and Mobile Net V2 as optimal architectures for large and small model categories, respectively. The study also investigates the impact of training models on specific environments versus unified datasets that encompass varied conditions. Results show that a unified dataset leads to only a minor decrease in predictive performance, while retaining the ability to distinguish between classes unique to specific datasets. This capability may be attributed to the distinct image properties resulting from differences in imaging equipment and techniques, which needs further investigation. To enhance future model performance, the importance of consistent imaging properties is therefore emphasized. The next steps involve integrating the developed models into a hardware setup for long-term monitoring of water sections, as well as exploring advanced AI techniques for identifying individual and sparsely distributed litter items. Keywords. 1. Introduction. Plastic pollution has emerged as one of the most pressing environmental challenges, with far-reaching impacts on ecosystems, marine life, and human communities. 10. 11. Among the diverse strategies being explored that assess this global problem, the integration of artificial intelligence, AI, into litter detection systems presents a promising direction for addressing plastic waste at scale. 8. AI-enhanced litter detection offers the potential to automate and optimize the identification and quantification of plastic waste, enabling more efficient monitoring and intervention, as demonstrated in work conducted in Southeast Asia. 1. 2. However, deploying AI models in diverse and dynamic environmental conditions poses a significant challenge. Models trained on specific datasets often struggle to generalize to new settings, such as varying climates, terrains, and waste compositions, that they have not been previously exposed to. 12. 13. This paper explores the possibility of performance improvement of AI-driven litter detection, as well as addressing the challenges of adapting these systems to unfamiliar environmental conditions. 2. Methodology. This section outlines the methodology for creating a novel dataset to evaluate state-of-the-art CNN architectures. Model performance is compared, followed by an analysis of how training on specific or a combination of different environments affects predictive performance. Lastly, a hardware setup is presented in which the developed AI model can be integrated in order to implement long-term monitoring of relevant water sections. 2.1 Database. The images for the new dataset were provided by the Water Survey of Canada and were captured at 6 hydrometric stations across Alberta, British Columbia, and Nova Scotia. The data spans from November 2017 to May 2023, covering diverse environmental and seasonal conditions. To ensure variety, 80 images were selected from each camera, representing seasonal and environmental diversity. Depending on the site, the cameras were placed at varying heights and angles, resulting in different image resolutions and ground spatial resolutions. To address this, the raw data was scaled to a uniform ground spatial resolution of 0.2 using interpolation, as it showed superior resolution results. The adapted images were then analyzed for areas corresponding to specific classes: ice, water, vegetation, organic debris, sand soil, stones, other, and a grid was applied to divide areas containing these classes into 128 128 3-pixel image tiles. It should be noted that the available images did not contain any litter objects, which is why the class is not included in the resulting Canada dataset. 2.2 AI Enhanced Plastic Litter Detection. Based on the work of Wolf al. 1-2, the study used tile-wise classification, where 128 128 3-pixel image tiles were classified into predefined environmental classes using the PLDCNN model. Due to the rapid development of AI methods and architectures, the first step of this work was to examine how the performance of the classification model improves when state-of-the-art models are used for the previously described dataset. Specifically, the models 3, DenseNet 121.5, MobileNet v24, and SqueezeNet 116 were examined, with models categorized into larger, RaiseNet 50, DenseNet 121, and compact models, MobileNet v2, SqueezeNet 11, which are important for edge devices with limited resources. Additionally, the adaptability of the litter detection model was tested using a second dataset from Southeast Asia 7, which includes two new classes, litter high and litter low, but lacks the ice class. This comparison explored model performance when trained on environment-specific data, Southeast Asia, Canada, or a combination of the two datasets with greater class variance. For the training of the AI models, the dataset was split into 80% for training, 10% for validation, and 10% for testing, with stratified sampling for even class distribution. The following augmentation techniques were applied: horizontal and vertical flipping, random rotation, 30-30, as proposed by Taylor al. 9, both with a probability of 75%. In addition, all images were normalized using z-score normalization to ensure that the pixel values are distributed uniformly. 2.3 Hardware integration. Architecture of the proposed AI enhanced litter assessment system, consisting of an RGB camera for automated litter detection and a dashboard, visualizing the camera live stream and the classification results. The graphical user interface shows the live stream of the camera, as well as the classification results of the litter detection model. The camera integration, as well as the communication between the different components, illustrated in the figure, is implemented using ROS. 3 Results. This section presents the results of the study, beginning with the main features of the dataset. It then outlines the performance of the models on this dataset and concludes with the results of the DenseNet 121 model trained on the 3 dataset variants. 3.1 Canada Dataset. After applying the preprocessing steps to the raw image data from the hydrometric stations, as described in Sect. 2.1 The developed dataset consisted of image tiles for the classes ice 5600, water 5600, vegetation 4000, org. Debris 4000, sand soil 3300, stones 3300, other 3300. 3.2 Litter Detection Model. In the first step, different model architectures were compared to the baseline A-Plastic-Q PLDCNN model, with results shown in Table 1. Model performance for the tested CNN architectures on the Canada dataset. Models. Precision. Recall. F1 score. Accuracy. PLDCNN. 0.724, 0.72, 0.717, 0.72. RaiseNet 50, 0.794, 0.796, 0.794, 0.796. DenseNet 121, 0.812, 0.811, 0.811, 0.811. MobileNet v2, 0.769, 0.768, 0.767, 0.768. SqueezeNet 11, 0.737, 0.726, 0.727, 0.726. Comparing the best performing models of each category in terms of their model size, DenseNet 121 lead to a model size of 27.1 MB with 6,691,031 parameters, while MobileNet v2 resulted in a trained model of 2,232,839 parameters and a size of 8.75 MB. The second study compared the predictive performance between a model trained on a specific environment, Canada, and a model trained on the combined dataset from Canada and Southeast Asia. Using DenseNet 121, the best performing model, the F1 scores for individual and unified models are shown in Fig. 2. F1 score class performance of DenseNet 121 for two environment-specific datasets and the unified dataset. For discussion, DenseNet 121 proved most effective for the large model category, while MobileNet v2 excelled in the category of smaller models, making it ideal for edge devices with limited computational resources. Beyond predictive performance, AL. 14 demonstrated that using well-established models for plastic litter detection can also reduce CO2 emissions. The unified model, trained on a combined dataset, showed only a slight drop in performance, i.e. F1 score, compared to the Southeast Asia dataset, while maintaining similar performance compared to the model trained on the Canada data, highlighting the model's generalization capability. Notably, the model generalized well to classes present in only one dataset, potentially aided by differences in data origins. Drone-captured images in Southeast Asia versus stationary camera images in Canada. These variations in image properties may have provided additional classification cues, underscoring the importance of considering imaging conditions in model training. 5. Conclusion and future work. This study highlights the potential of AI-enhanced models, like DenseNet 121 and MobileNet v2, for detecting and classifying plastic litter in diverse environments. While unified datasets offer promising results, challenges remain due to variations in data collection methods, such as differences in sensors, lighting, and resolution, emphasizing the need for further refinement. Future efforts will focus on gathering datasets with consistent properties to improve class differentiation, such as between litter and ice, and reduce biases from varied image sources. Additionally, advancing the system's capabilities to detect individual and sparsely distributed litter items will require integrating more advanced AI methods. This research was funded by the Government of Canada under the Collaborative Science, Technology and Innovation Program, CSTIP, grant number INT0191. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Wolf M. al., 2020, Machine Learning for Aquatic Plastic Litter Detection, Classification and Quantification, A Plastic Q. EnvironRace 1511-114042. 2 Wolf M. al., 2023. Improved Deep Learning-Based Litter Detection in Aquatic Environments in Indonesia using Drones. OCEANS 2023, Limerick IEEE 17. 3 Hike al., 2016, Deep Residual Learning for Image Recognition. In Proceedings of the 2016 IEEE Conference on Computer Vision and Pattern Recognition, CVPR, 777-78, IEEE. 4 AG al., 2017, MobileNets, Efficient Convolutional Neural Networks for Mobile Vision Applications. 5G al., 2017, Densely Connected Convolutional Networks. In Proceedings of the 2017 IEEE Conference on Computer Vision and Pattern Recognition, CVPR, 2261-2269. IEEE. 6N al., 2016, SqueezeNet, AlexNet level accuracy with 50x fewer parameters and 0.5 MB model size. OrgAbs 160207360. 7 Wolf M. al., 2021, Aquatic Plastic Litter Dataset developed for A Plastic Q publication, V1 Dataset. Org 10 10881748932601. 8 N. al., 2022, Close-Range Remote Sensing-Based Detection and Identification of On-Water Assisted by Artificial Intelligence. A review. Water Race 222, 118902. Org 10 1016J2022 118902. 9 Taylor L. G. 2018, Improving Deep Learning with Generic Data Augmentation. In 2018 IEEE Symposium Series on Computational Intelligence, SSCI, 1542-1547. IEEE. 10 SB al., 2020, Predicted Growth in Plastic Waste Exceeds Efforts to Mitigate Plastic Pollution. Science 369, 1515-1518. Org 10 1126 Science 3656. 11 GB, 2002, The Pollution of the Marine Environment by Plastic Debris. A review. Marine Bull 449. Org 10 1016 S002, 5326 X02002205. 12 DB al., 2024, Artificial Intelligence in Environmental Monitoring. Advancements, Challenges, and Future Directions. Hygiene Environ Health Adv. Org 10 1016J202411001114. 13 J al., 2019, Learning Under Concept Drift. A review. IEEE Trans. Data Org 10 1109, TKDE 20-182876857. 14 Daphne T. al., 2023, Green Auto ML for Plastic Litter Detection. Workshop on Tackling Climate Change with Machine Learning. International Conference on Learning Representations, ICLR. Evaluation of closure depth along the Portuguese coast. Abstract. The concept of depth of closure, DEC, plays a pivotal role in coastal and engineering, serving as a key parameter for estimating sediment budgets, designing beach nourishment projects, and modeling shoreline changes. Despite its significance, field measurements of DEC remain limited due to the logistical, operational, and financial challenges of systematic topobathymetric data collection. This study provides a field-based evaluation of DEC along the mainland Portuguese coast, encompassing diverse wave energy conditions, geomorphological characteristics, and exposure. 64 nearshore beach profile surveys conducted across 14 locations between 2018 and 2021 under the Portuguese Coastal Monitoring Program, COSMO, were analyzed. To define DEC, the study introduces the relative morphological variability, RMV. Criterion: setting a critical threshold of 1.2 local measurement uncertainty. DUC results indicate significant regional variability. On the high-energy western coast, ranges from 7.8 m to 14.1 m MSL. On the lower-energy southern coast, values are shallower, from 4.1 m to 7.2 m MSL, reflecting not only the lower wave energy environment, but also seasonal data acquisition limitations. Empirical estimations using ANS formulas were compared with field data. Whilst method consistently overestimates the DUC, this approach aligns more closely with observed values, particularly along the western coast. These findings highlight formula as the preferred empirical method for estimating DUC along the Portuguese coast when field data is scarce or unavailable. This work underscores the importance of precise field measurements and validated empirical approaches, providing new insights for coastal management and engineering applications. Keywords. 1. Introduction. Depth of closure DUC is a widely used concept within coastal and engineering, being often used to infer a seaward limit to significant cross-shore sediment transport 1, and is applicable, for example, in estimates of coastal sediment budgets, shoreline change models, beach nourishment design, and to set limits to dredging depths. However, field measurements of DUC are relatively scarce, mainly due to operational, logistical, and economical constraints related to systematical collection of topobathymetric data. The main objective of this work is to provide a comprehensive field assessment of DUC along the Portuguese coast that reflects different wave energy conditions, geomorphological constraints, and exposure. The results were compared with the two most used empirical DUC estimators to assess their suitability. Location of beach nearshore profiles and offshore wave data. Significant morphological change was defined using the relative morphological variability, RMV, defined as the ratio between local morphological variability and acquisition method S error, which is estimated by the morphological variability, MV, in the seaward section of the profile. Different morphological variability statistics were compared, standard deviation, amplitude, and interquartile range, but all gave similar results. Based on this, DUC was set to a depth when the value of RMV exceeds the critical limit of 1.2 offshore variability. This was defined in the offshore profile section where vertical morphological changes are known to be negligible, so that variability can be regarded as a proxy of the acquisition method S error, which was found to be slightly different at each location. 2 Results and discussion. Figure 2 shows an example of 3 profile dataset located in the western coast, A2, B6 Costa Nova, and C9 Costa. At each profile, the middle and bottom panels show the morphological variability, MV, and the relative morphological variability, RMV. In all profiles, the DUC represents a distinct transition in profile behavior, characterized by the convergence of the morphological envelope. Offshore DUC, the nearshore is characterized by a regular bottom with a gentle slope and MV, and RMV assumes an almost constant value. Onshore, the profile is characterized by significant morphological changes over time. Table 1 shows that in the western coast, high wave energy, DUC ranges from 7.8 m MSL to 14.1 m MSL, being most of the values between 10 m MSL and 12 m MSL. The lower DUC value found in 2 profiles can be attributed to the existence of a chronic sand deficit and the presence of a rock armor revetment, constraining cross-shore processes and sediment exchanges between the subaerial and submarine beach. In the southern coast, low to medium wave energy, field DUC measurements vary between 4.1 m MSL and 7.2 m MSL. It must be stressed that at the southern coast, field data is limited to 3 profiles at each location, acquired in summer conditions, leading to an underestimation of DUC. Example of measured DUC in 3 beach nearshore profiles at A2, B6 Costa Nova, and C9 Costa. DUC estimates from measured profile surveys and empirical formulas, T 10 years. Location. Profiles. Measured Ducy MSL. Formulas. Empirical Ducy MSL. Wave data. 1 do. 5. 14.1 M2. 5. 7.8 M3. 5. 10 M1. 18.5 MH, 12T8 7 M4. 5. 10.5 M2. 14.2 M14 8. 5. 6. 12.8 M6 Costa Nova. 7. 10.7 M7. 6. 10.7 M1. 17.4 MH, 12T8 2 M8. 5. 10.43 M2. 13.4 M13 9 S9 Costa. 5. 10.2 M10. 3. 6.4 M11. 3. 4.1 M1. 12.7 MH 12T56 M12 Vale do Lobo. 3. 4.5 M2. 9.9 M12 4S13 Praia Ferro. 3. 7.2 M14 Praia. 3. 4.2 M3 Conclusions. Measuring Ducy is a challenging task that depends on high-quality profile data repeated over time. Acquisition methods and oceanographic conditions generally limits the comparability of data and challenges the use of a single criteria to define significant morphological changes. In this work, we have addressed this issue by developing a criterion called relative morphological variability, RMV, to ensure that the detected variations were greater than the acquisition method uncertainty. In this work, we adopted a threshold criterion of 1.2 local measurement uncertainty. On the western coast, the Ducy value was found to reach up to 14 m MSL, with most values ranging between 10 m MSL and 12 m MSL, strongly dependent on geomorphological constraints and wave forcing. On the southern coast, the maximum Ducy values reached 7 m MSL. A comparison between measured data and empirical formulas shows that this approach was found to be the most suitable when calculating the Ducy along mainland Portugal, if beach nearshore profiles are rare, or 1. Assumptions of empirical formulas and formulas are empirical approaches that simplify sediment transport processes by relying on long-term wave statistics and assuming uniform sediment characteristics, both developed and calibrated for specific conditions along the U.S. Atlantic coast. These generalized approaches cannot account for the complex local factors influencing sediment dynamics, leading to deviations from field-measured values. Assumptions of empirical formulas. Since formulas are empirical approaches that simplify sediment transport processes by relying on long-term wave statistics and assuming uniform sediment characteristics, both developed and calibrated for specific conditions along the U.S. Atlantic coast. These generalized approaches cannot account for the complex local factors influencing sediment dynamics, leading to deviations from field-measured values. 2. Local wave climate variability and temporal resolution measured Ducy reflects real-world wave climate variability, including seasonal and storm-induced changes, which are not fully captured by empirical formulas. The formulas rely on wave statistics that may not fully represent site-specific wave climate. Furthermore, measured profiles often have low acquisition frequency and cover limited temporal spans, whereas the formulas predict long-term equilibrium conditions. Survey quality also affects measured values, introducing variability that is absent in formula-based predictions. Local wave climate variability and temporal resolution. Measured Ducy reflects real-world wave climate variability, including seasonal and storm-induced changes, which are not fully captured by empirical formulas. The formulas rely on wave statistics that may not fully represent site-specific wave climate. Furthermore, measured profiles often have low acquisition frequency and cover limited temporal spans, whereas the formulas predict long-term equilibrium conditions. Survey quality also affects measured values, introducing variability that is absent in formula-based predictions. 3. Measurement methodology. The DUC derived from beach nearshore surveys depends on the analytical approach used to define it. For instance, using relative morphological variability, RMV, emphasizes changes that exceed measurement uncertainty. This approach differs conceptually from the wave parameters that form the basis of empirical formulas, highlighting the divergence between measured and predicted values. Measurement methodology. The DUC derived from beach nearshore surveys depends on the analytical approach used to define it. For instance, using relative morphological variability, RMV, emphasizes changes that exceed measurement uncertainty. This approach differs conceptually from the wave parameters that form the basis of empirical formulas, highlighting the divergence between measured and predicted values. 4. Geomorphology. Setting and sediment characteristics. Field measured DUC is influenced by site-specific sediment grain sizes and coastal features like rock outcrops or engineering structures, e.g., rock armor revetments, which may constrain cross-shore sediment transport. Empirical formulas, however, assume homogeneity and ignore geomorphological constraints, causing over- or underestimations of DUC geomorphology setting and sediment characteristics. Field-measured DUC is influenced by site-specific sediment grain sizes and coastal features like rock outcrops or engineering structures, e.g., rock armor revetments, which may constrain cross-shore sediment transport. Empirical formulas, however, assume homogeneity and ignore geomorphological constraints, causing over- or underestimations of DUC open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source. Provide a link to the Creative Commons license and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. R.J. W. R.J. 1996, Application of the Depth of Closure Concept. Coast Proc 12538743887. 2. Pinto C. N. Piers B. 2021, Portuguese Coastal Monitoring Program COSMO, From Conception to Implementation. X. CPGs CPAP. Brazil. P3 in Portuguese. 3. RJ 1981, Seaward Limit of Significant Sand Transport by Waves, an Annual Zonation for Seasonal Profiles. USACA. CERC. 81 P2. 4 WA 1985, Field Data on Seaward Limit of Profile Change. J. Port Coast Ocean, 111 3598 602. 5 and C. M. Wise Ra 1998, Depth of Closure in Beachfill Design. Coastal Engineers Technical Note. U.S. Army Engineer Waterways Experiment Station. Coastal and Hydraulics Laboratory. Vicksburg, Mississippi. 113. 6K R. Y 2020, An Assessment of Measured and Computed Depth of Closure Around Japan. Rep 102987. Hydrodynamics and Morphology on Composite Beaches. Abstract. Composite beaches, by a dissipative sand beach backed by a steep cobble berm, exhibit unique hydro and behaviors due to their bimodal sediment size distribution. This study analyzes morphological variability and wave on a composite beach in Wales, using continuous LiDAR data collected from July 2021 to October 2024. Results indicate that the lower berm face is dynamic due to regular swash inundation, while the primary berm crest remains stable with minimal changes. Secondary berms located seaward of the primary berm can be formed and removed within a single tide. This is in contrast to sand beaches, where they tend to translate landward, controlled by the neap spring tidal cycle. Existing wave equations provide reasonable estimates of total water level, but perform worse than previously observed at other composite beach locations due to a higher dependence of wave on offshore wave height. Keywords. 1. Introduction. Composite beaches were defined by N1 as consisting of a typically dissipative sand beach backed by a steep cobble berm and are common in many countries, e.g. UK, USA, Ireland, NZ. These beaches differ from mixed sand and gravel beaches, primarily due to the bimodal nature of the sediment size distribution and a much higher proportion of sand relative to coarse material. Cross-shore sorting by waves leads to a generally dissipative lower foreshore of sand, 0.01 to 0.05, backed by a steep, permeable and reflective upper foreshore or ridge of cobbles, 0.1 to 0.25. The differences in the slope, roughness, permeability, and groundwater characteristics of the sand and gravel components of composite beaches means that both the hydro and vary with water level, and they behave differently to both pure sand and pure gravel beaches. Effectively, composite beaches represent a combination of the two most stable states at either end of the classification of right and short 2, making them relatively stable in response to changing hydrodynamic conditions. The dissipative sand beach component exhibits lower mobility because the low gradient promotes a wide surf zone, within which wave energy is gradually dissipated, leading to smaller shortwave heights at the shoreline. The steep cobble ridge derives its stability primarily from its porous nature, which promotes swash asymmetry 3. As a result, while strong swash uprush flows can relatively easily transport cobbles up the slope, infiltration of water into the cobble matrix during uprush and flow reversal means that the backwash is weakened, which limits seaward transport of material even during highly energetic conditions and leads to cross-shore sediment sorting and a steep slope. Compared to their pure sand or gravel counterparts, research into morphological change and hydrodynamics on composite beaches is lacking with few dedicated studies. This paper presents initial analysis of the morphological variability and wave on a composite beach at the tide-by-tide timescale over a 3-year period. 2. Methodology. Continuous LiDAR data was collected between July 2021 and October 2024 at a range 51 m, west-facing composite sand-gravel beach in Wales. The cobble berm at Wales provides essential coastal flooding protection to the town, which lies at approximately the elevation of the berm crest. Cross-section of the beach at the LiDAR installation location. The bar indicates the percentage of valid LiDAR returns at each cross-shore location. Note that the surface intersection between sand and gravel was unusually high on the day of installation and is more typically at approximately x40 m, Z25 m3 results. 3.1 Morphology change. Top shows all measured low-tide beach profile data in. Solid black line indicates the median profile, with the dashed lines indicating the 10th and 90th percentile profiles. Horizontal dot dash and dotted lines show the elevation of MHWS and MHW respectively. Bottom, cross-shore variation of standard deviation of bed elevation and probability of. The of morphology change presented in Fig. 3 highlights the different timescales of morphology change with cross-shore position. The lower berm face, x30-45 m, undergoes regular changes because wave reaches these positions on the majority of high tides, Fig. 2. The frequency of measured morphology change decreases moving landward. Between 17 m and 30 m, changes in the berm geometry are more episodic, caused by intermittent high-energy swash conditions coinciding with high tide, after which the berm profile remained approximately constant until the next high-energy event. The primary berm crest geometry is consistent throughout the measurement period, with only minor changes caused by occasional wave overtopping. Contour plot of morphology change relative to the initial measured profile. Green symbols indicate the crest location of local berm features. Top of detected berm volume change. Bottom of predicted high tide TWL. Regions indicate when no valid profile data was available. Vertical magenta lines indicate storms where reaches the 99th percentile and remains above the 95th percentile for at least 2H in the bottom plot. Data is plotted in blue for periods when surge residual data was available, and black where no surge data was available. 3.2 wave. While it was only possible to confidently extract maximum TWL for 463 high tides, this represents a substantial dataset against which to test composite and gravel beach equations. Figure 5 left compares measured and predicted TWL at high tide using the AL. 5 equation for all high tides, where surge residual data was available. Note that the measured TWL takes the maximum observed height, while 5 predicts our 2%, and so might be expected to slightly underestimate. It is observed that equation enables reasonable prediction of TWL with a root mean square error of 0.25 m, as expected. The largest values of TWL occur during spring tides and storm surge when the water depth at the berm toe. Interestingly, however, there is a clear influence of offshore significant wave height on wave fig. 5s. This is in contrast to observations at the 3 field sites used to develop the equation, where it was found that wave elevation was decoupled from the wave height offshore due to the dissipative nature of the surf zone. Comparison of measured and predicted total water level using left AL. 5.025 m, middle AL. 6 using tan 0.25 m and right AL. 6 using tan 0.78 m. Results are according to offshore. 4 conclusions. This paper presents an initial analysis of morphological change and wave over a 3-year period on a composite beach. It was demonstrated that the cobble berm structure itself was very stable at the tidal timescale. The berm volume varied by around an order of magnitude less than on sand beaches with an absence of seasonal. The primary berm crest saw minimal change, 0.09 m, and was only overtopped during 5 high tides. It was also found that secondary berm is very different to that on sand beaches, with berms formed removed in a single tide. Finally, existing wave equations were able to provide reasonable estimates of total water level, but there was a clear influence of offshore wave height, on which is contrary to previous observations on composite beaches. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1R, J. 2002, a field-based classification scheme for gravel beaches. MAR 186-2, 11-228. 2 Wright L., Shorday 1984, Variability of Surf Zones and Beaches, a Synthesis. MAR 5693, 118. 3G, Lee L. 2001, The role of swash infiltration in determining the gradient, a numerical study. Mar 176, 139, 156. 4 Phillips M. C. Splinter K. M. Turner IL 2019. Modes of berm and recovery following storm reset. Observations using a continuously scanning LiDAR. J. Ray's Earth Surface, 124, 720. 5 C. Al. 2022. Wave on composite beaches and dynamic cobble berm revetments. Coast, 176, 104148. 6 T. Call R. G. 2016. Anew for on gravel beaches. Coast, 117, 176, 190. Flow dynamics over sand deposits at the Fire Island Shelf, New York. Abstract. The forecast of water exchange between the continental shelf and the coastline is required in a variety of coastal and ocean applications, such as sediment budget and coastal evolution. This exchange is controlled by physical processes including hydrodynamics, human interventions, and resulting bathymetric evolution. To improve the understanding of this exchange, field observations, process-based modeling of ocean circulation, and sediment processes over the entire shelf and nearshore need to be conducted under varying forcing conditions. Accordingly, circulation over the shore oblique sand deposits at the shelf offshore of Fire Island, New York, USA has been investigated. Keywords. 1. Introduction. Coastal and ocean dynamics, such as the sediment budget and the evolution, are controlled by the water exchange along and across the continental shelf and the coastline. This circulation is regulated by physical processes including hydrodynamics, human interventions, and the resulting evolution of the bathymetry. Most of the circulation modeling efforts have typically been based on idealized forcings and bathymetries, e.g. 1. Such findings improved our understanding of shelf flows, but are applicable to less realistic conditions. To cross-check those findings and enhance the overall understanding of water circulation over the continental shelves in general, and the impacts of overlooked processes such as waves and cross-shelf winds too, it is essential to conduct field observations and develop process-based models on realistic bathymetry and forcing conditions. Accordingly, the goal of this study is to advance the skill to forecast shelf flows on realistic bathymetry and forcing conditions by analyzing high-resolution field observations and applying a hydrodynamics-based numerical model. 2. Method. The study site is the shelf of Fire Island, located on the Atlantic coast of New York, USA, where sand deposits run obliquely to the shoreline. These deposits extend approximately 10 in the cross-shore and are spaced several kilometers apart along the coast, interacting with flow circulation during moderate energy flows, energetic storms, and hurricanes 3, 4. For further details on the geology, atmospheric, and oceanographic processes of the Fire Island Shelf and near shore, reader is referred to Al. 5 is Al. 367, Warner Al. 1-4 and Van Al. 8. Field measurements were collected during an experiment conducted in winter 2014-9, which was the energetic season at the study site. A comprehensive dataset of atmospheric conditions, flow patterns, waves, and sediment processes were collected and analyzed. Hydrodynamic processes were decomposed to tidal and components for analysis. A hydrodynamics-based numerical modeling system coupled ocean atmosphere wave sediment transport, COAWSD. 10. That integrates atmospheric processes, ocean circulation, waves, and sediment transport was configured and applied. The model was validated using the experimental observations of the vertical structures of stratified hydrodynamics, waves, suspended sediment load, and 3. Results. Relation between the observed alongshore, currents near the sea surface, and the seabed. The red and green lines indicate the best linear fit and a 1-to-1 relation, respectively. The alongshore flow was vertically sheared, but the direction was virtually uniform throughout the water column. The alongshore flow velocities near the surface were 35% greater than those near the bed. Fig. 4.1. Relations between the observed alongshore current velocities and the alongshore wind velocities. The two lines indicate the best linear fits. Cross-shelf flow dynamics, on the other hand, had several differences from the along-shelf flow dynamics. First, cross-shelf flow velocities were not strictly following the cross-shelf wind forcing. Fig. 3. Then, cross-shelf flow velocities were about an order of magnitude smaller. Fig. 3b. Also, a two-layer vertical structure was observed in cross-shelf flows, such that flows were dominantly onshore near the seabed and offshore near the sea surface. Fig. 3b. 2-day-long time series of a cross-shelf wind velocity, B observed, and C modeled cross-shelf flow velocities. In the color code of the vertical structures of the flows, red and blue correspond to onshore-directed and offshore-directed currents, respectively. Ongoing work includes the data analysis and modeling of two main aspects: all the processes that affect the along and cross-shelf momentum balances, e.g., wind forcing, wave effects, etc., are being diagnosed. The resulting sediment fluxes over the shelf and the nearshore under varying forcing conditions are being evaluated in order to achieve a better understanding of the sediment exchange between the shelf and the coastline. 11. This study was supported by the U.S. Department of the Interior, United States Geological Survey Grant No. G21 AC10799900. Computing resources used in this work were provided by the National Center for High Performance Computing of UHM under grant number 1,011,240,2021. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Warner J.C., Al. 2014, Inner Shelf Circulation and Sediment Dynamics on Shoreface-Connected Ridges Offshore of Fire Island, NY. Ocean Dynamics, 64. Org 10 1007 S102360 1407881Y. 2 S.J. Mr. 2012, The Wind and Wave-Driven Innershelf Circulation. Revmar 4317343. Org 10 1146 Marine 120 709 142 745. 3 W.C. Al. 2017. Change in Morphology and Modern Sediment Thickness on the Intercontinental Shelf Offshore of Fire Island, New York between 2011 and 2014. Analysis of Hurricane Impact. Mar 391 4864. Org 10 1016 J20 170 7010. 4 Warner J.C., W.C. List J.H. I. M. Baldwin W. 2017. Innershelf Ocean Dynamics and Geophysical Changes During Hurricane Sandy. Shelf Raise 138 118. Org 10 1016 J20 170 2003. 5I. List J.H. Warner J.C. W.C. 2017. Persistent Shoreline Shape, Induced from Offshore Geologic Framework, Effects of Shoreface Connected Ridges. J. Rays Oceans, 122. Org 10 100220 17 JC0 12808. 6 W.C. Al. 2013. Geologic Evidence for Onshore Sediment Transport from the Intercontinental Shelf, Fire Island. New York. J. Coastal, Raise 29 526 544. Org 10-2 112 JCO Estuaries 1200 1601. W.C. Al. 2014. Modification of the Quaternary Stratigraphic Framework of the Intercontinental Shelf by Holocene Marine Transgression. An example offshore of Fire Island. New York, Marine Geology 355, 346, 360. Org 10-1016J20, 1406011. 8 Van M., Nelson Tr., CJ.D. 2020, Modeling of the Wilderness Breach, Fire Island, New York. Part I, Models Setup and Validation. Coastal Engineering, 157 L, 103,621. Org 10-1016J20, 19103621. 9 BN Al. 2015, Coastal Change Processes Project Data Report for Oceanographic Observations near Fire Island. New York, February through May, 2014. U.S. Geological Survey Open File Report, 2015-1033. Org 10-3, 13320, 151033. 10 Warner J.C., B. He R., J.B. 2010, Development of a Coupled Ocean Atmosphere Wave Sediment Transport, COAWSD Modeling System. Ocean Modeling 35. Org 10-1016J20, 100, 7010. 11 MS, BU, Warner J.C., T.S., I 2023, Wave Asymmetry Impacts on Sediment Processes at the Nearshore of Fire Island, New York. Coastal Sediments, 2023, New Orleans, USA. Org 10-11429789, 8112751350, 173. Simulating Storm Impacts on the Southwest Florida Coast, Following Hurricane. Abstract. Hurricane impacted the southwest Florida Barrier Island coast, with devastating storm surge flooding. In its wake, numerous ebb surge channels cut across extensive stretches of shoreline on island, while Lovers Key was and breached. The process-based model, XBeach, was used to predict the formation of these ebb surge channels and breaching events, and model results were compared to post-storm Lidier DEMS. Results show that XBeach accurately predicts the number and locations of ebb surge channels. However, the results were limited by the ability to represent highly varied land cover within the model. Results suggest that non-surfaces such as roads and parking lots prevented the extension of ebb surge channels deep inland during the surge. XBeach predicted substantial deflation of Lovers Key compared to measurements, highlighting the importance of high-resolution land cover data and accurate hydrodynamic boundary conditions. Keywords. 1. Introduction. Over recent years, the Southwest Florida SW coast has been severely impacted by the passage of several hurricanes. In 2017, in 2022, and in 2023, and Debbie and Milton in 2024. Hurricane made landfall on Costa as a strong Category 4 hurricane, with record storm surges in and Fort Beach up to 4 m, resulting in widespread inundation. 1. Surge heights reduced further down the coast toward Naples and Marco Island. However, given the low crest elevation of coastal dunes, and collision regimes too remained widespread. Over 200 ebb surge channels were carved out, cutting across the upper beach profile. Over 92% of these channels corresponded to man-made beach access pathways. 3. These pathways are typically and low-lying compared to the surrounding terrain, which allowed the ebb surge to preferentially flow out at these locations. The impact was different at Lovers Key State Park, which lies between Fort Beach to the north and Naples to the south. Lovers Key suffered primarily from dune and breaching. Breaching occurred in areas that were previously opened during hurricane, which had not yet re-established mature vegetation. The devastating impact underscored the need for increased resilience within coastal communities. In response, many are engaged in adaptation planning, e.g., fortifying and elevating dunes, employing nature-based features, redeveloping urban infrastructure and disaster preparedness plans. In doing so, the use of predictive models such as XBeach4 is important not only for understanding and quantifying storm surge erosion processes, but also for determining the efficacy of coastal interventions in reducing erosion hazards and associated risks. The locations in and Lovers Key represent two different results of storm impact during the flood and ebb phases of the surge. Important lessons can be learned from the impact of the storm in developed areas and undeveloped areas, which are able to react naturally. The primary aim of this work is to better understand storm surge flow processes and the role of natural vegetation and urban development on ebb channel and formations. This will be done using XBeach to simulate hurricane impact on and Lovers Key. The results will allow coastal managers in these jurisdictions to identify locations which may remain vulnerable to future storm impacts and to, ultimately, find solutions that would increase resilience. 2. Location and methodology. 2.1 Locations. Locations of the 3 XBeach model grids in Southwest Florida. 2.2 Publicly available datasets. The 2018 NOAA Continuously Updated Digital Elevation Model, CUDEM-5, is used as the pre for and Lovers Key. The USACE FEMA LIDAR topobathymetry, collected on 16 November 2022, is used as the post dataset 6. Elevations in these datasets are relative to the North American Vertical Datum, NAVD. With these datasets, measured sedimentation erosion patterns at and Lovers Key are able to be generated with high accuracy, as shown in the results. Boundary wave and water level conditions representative of the storm. Significant wave height, Panel A, peak wave period, Panel B, and water level, Panel C. Structures influence the flow of water during flood events and also shield the underlying substrate from erosion. 2022 building footprint data from FEMA 13 were used to identify areas in the model where structures were located. The data was downloaded in vector format and rasterized at a 1M grid level for use in XBeach. Land use and land cover is important when considering flow roughness during a storm surge. Data was obtained from the USGS National Land Cover Database, NLCD, at a 30M spatial resolution for 2023-9. The dataset specifies several classes of land use: developed, wetland, grassland, aquatic, shore, and bare, with sublevel classifications. Several methodologies exist to relate land cover and land use data to Manning's friction factors 10. Here, vegetation is classified as primary or secondary, and are assigned Manning's values of 0.04 and 0.05, respectively 11. In addition, 2 more classes are added, namely sandy bed and non-surfaces with Manning's values of 0.02 and 0.1, respectively. A second NLCD dataset for 2021 tree canopy cover at 30M resolution was used to estimate percent tree canopy 12. Areas with tree canopy cover between 33 and 67% were classified as primary vegetation. Areas with tree canopy cover greater than 67% were classified as secondary vegetation. 2.3 XBeach Model Setup. As part of the FHICS Project 14, XBeach model grids were developed for SWFL to provide real-time forecasts of storm impacts during the active hurricane season. Fig. 1. The model grids cover an area with a total distance of 2.5 alongshore and 4 between the offshore boundary and the estuary. Originally, the computational grid was coarsely spaced, 16 m alongshore, to prioritize speed for forecasting purposes. However, the alongshore grid resolution is reduced to 5 m in this work, while the cross-shore resolution is varied, with a minimum of 2 m in the surf zone and on land. Measured nearshore bathymetry, 2018 pre-dataset, is used out to 6 m depth, beyond which the depth contours are artificially sloped down to 25 m at the offshore model boundary to allow transformation of waves toward the shoreline. Manning's bed friction values were adopted based on land use and land cover classification, as outlined in Sect. 2.2. Buildings were represented in the model by first identifying grid cells lying beneath building footprints. These grid cells were then assigned as being non by setting the sediment thickness at these locations to 0 and increasing the bed elevation by 4 m above the nominal ground level. In this manner, any incoming surge will be slowed by the presence of the structure and will be forced to flow around it. Each simulation was run for a period of 2 days, from 1800 September 27, 2022, until 1800 September 29, 2022, representing the 24H period before and after the peak storm surge Fig. 2. Additionally, a water level gradient was imposed on the front and back model boundaries by keeping the same water level signal, but simply adopting a time lag between these locations. For Lover's Key, a 60 min time lag is applied, corresponding to observed time lags between USGS water level measurement stations around Bay. For a 120 min time lag is applied, given the larger width of the area in Pine Island Sound. A morphological acceleration factor of 5 was used, with all other model settings remaining at default values. 3 results. 3.1. Erosion and sedimentation patterns. Final bed levels, simulated for the 2 locations, are shown in Panel A of Figs. 3 and 4, alongside measured bed levels, USACE FEMA post datasets. In Panel B, the post data matches the alongshore extent of the model domain, but is limited to a cross-shore area approximately 100-200 m wide, just above 0 m elevation. Panel C and D in Figs. 3 and 4 show the simulated and measured erosion and sedimentation pattern, respectively. For Fig. 3, there is significant erosion between 0 and 1 m elevation in both the simulated and measured data. In the simulations, the eroded sediment is deposited further inland and lower on the beach profile. Ebb surge channels can be distinguished as areas with particularly enhanced erosion in both the simulated and measured data. For Lover's Key Fig. 4, in contrast to the simulations, there is relatively no deposition on lower parts of the beach profile, but rather a wholesale landward migration corresponding to severe into the lagoon. A breach is observed in the measured data, occurring around the abutment of an access bridge to the island. However, this feature is not present in the simulation. 3.2. Contour outlines of ebb surge channels and breaches. Comparison of simulated and measured data at the final simulated bed level, Panel A, is compared to LIDAR data, Panel B. Contour lines are drawn with red 0 m, blue 1 m, and black 2 m elevation relative to NAVD. Sedimentation erosion pattern relative to the initial bathymetry shown at the end of the simulation, Panel C, and for the measured data, Panel D. Green polygon in Panels A and C show the outline of the measured data. Comparison of simulated and measured data at Lover's Key. The final simulated bed level, Panel A, is compared to LIDAR data, Panel B. Contour lines are drawn with red 0 m, blue 1 m, and black 2 m elevation relative to NAVD. Sedimentation erosion pattern relative to the initial bathymetry shown at the end of the simulation, Panel C, and for the measured data, Panel D. Green polygon in Panels A and C show the outline of the measured data. Comparison of the final simulated blue and measured red 1 m NAVD contour level at Panel A and Lover's Key, Panel B. The 1 m contour level provides a good representation of the location and extent of ebb surge channels and breaches. Black lines show the outlines of buildings for reference. Very few channels in the model showed this trellis drainage pattern, as most channels were oriented cross-shore. At Lover's Key, the model mainly predicted dune. In Fig. 5b, the final simulated 1 m contour level is barely evident, indicating a dramatic lowering of the dune crest without any breaching. However, the measured data shows that the dune crest ridge was maintained above the 1m contour level, with breaching localized in only a few key areas near the access bridge abutment. For discussion and conclusion. For island, while the simulations successfully generated similar numbers of ebb surge channel features as observed, there were some noticeable differences in their dimensions and orientation. As shown in Figs. 5a, predicted ebb surge channels were cross-shore oriented and often extended further inland compared to those observed. In actuality, the model overestimated channel length in areas where key landscape features, such as roads, driveways, and parking lots, were not accounted for. This suggests that these non-areas, which were not represented in the model, effectively halted the inland propagation of the observed channels. Satellite imagery of impacted areas shows that the inland terminus of ebb surge channels often corresponded to densely vegetated areas, large structures, or roadways. To achieve more realistic simulation results, it is crucial to include these non-surfaces in the model's boundary conditions. This may require refining the model's computational grid, as the average width of roadways is 6.5 m, and obtaining more detailed land cover datasets to account for features like parking lots and driveways. For Lover's Key, the extensive deflation predicted by XBeach occurs in an area lacking non-features. Therefore, the discrepancy with observations can likely be explained by either variables related to the classification of vegetation from land-covered datasets or by hydrodynamic conditions during the storm. Regarding the former, vegetation is sparse on the outer island of Lover's Key. However, tufts of grass and scrub vegetation have grown at higher elevations along the dune ridge, helping to protect underlying sediment. These areas, however, are classified as sandy in current land-covered datasets, placing them in a category with a higher likelihood of erosion compared to primary vegetation. Regarding the latter, hydrodynamic flow around SWFL barrier islands can be complex, especially at Lover's Key, which lies between two tidal inlets, Big Carlos Pass and New Pass. The extent to which these inlets may modify peak surge phase shifts between the estuary and offshore is unknown, but could be better accounted for with more sophisticated surge flow models. In conclusion, XBeach simulated storm surge conditions on island and Lover's Key corresponding to hurricane, making use of several publicly available datasets. XBeach reproduced the locations of observed ebb surge channels on well. However, it was found that additional metadata relating to roads and parking lots would likely further improve results. At Lover's Key, it is necessary to account for small-scale changes in vegetation and local hydrodynamic regimes to create conditions that would allow breaching. The XBeach models will be further fine-tuned for predicting future storm impacts in the SWFL region, incorporating prospective coastal interventions to assess resilience capacity. This work is funded by NOAA Florida Sea Grant under the project, Increasing Resilience Capacity within SW Florida Coastal Communities. The authors acknowledge ongoing partnerships with the USGS. Petersburg. Many thanks to staff and students of the FGCU Coastal Research Group and the Vester Marine Lab and the FGCU Wiser Eagles program. Representatives from the cities of Fort Beach and Naples and the Lover's Key State Park are thanked for their participation. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Florida Dep. 2022, Hurricane and Hurricane, Preliminary Post-Storm Beach Conditions and Coastal Impact Report, Office of Resilience and Coastal Protection, FL Dep. 2A 2000, Storm Impact Scale for Barrier Islands. J. Coast Res 16389895. 3M Al. 2023, Impact of Hurricane Storm Surge Along the Gulf Coast of Southwest Florida, Lessons for Building Resilience Capacity. Geological Society of America, National Meeting, Pittsburgh. 4D, A. Van J. Call R. J. 2009, Modeling Storm Impacts on Beaches, Dunes and Barrier Islands. J. Coast, 5611331152. 5. Cooperative Institute for Research in Environmental Sciences, CIRES, at the University of Colorado, Boulder, 2014, Continuously Updated Digital Elevation Model, CUDEM, 19 arcsecond resolution bathymetric topographic tiles, NOAA National Centers for Environmental Information. Org 10-2-59219V35. Access 10 May 2024. 6. OCM Partners, 2024-2022 USACE FEMA Post, LIDAR, Florida. NOAA National Centers for ENV. Information. Fisheries Item 71695. 7. Climate Change Service, Climate Data Store, 2023, Era 5 Hourly Data on Single Levels from 1940 to present. Climate Change Service, C3S, Climate Data Store, CDS. Org 10243, 81-D47. Accessed 9 Sept. 2024. 8. U.S. Geological Survey, USGS, 2021 Flood Event Viewer, Hurricane. 2022. Access 2. 2024. 9. U.S. Geological Survey, USGS, 2024 Annual NLCD Collection 1 Science Products, U.S. Geological Survey Data Release. Org 105066P94 UXNTS. 10E R Van M, 2023, Uncertainties in Predicting Barrier Island Response to Hurricane Forcing, Influence of Vegetation. In Proceedings of 10th Coastal Sediments, New Orleans, 2599-2603. 11 Cuvas S. 2023, Predicting Erosion of Vegetated Dunes During Hurricanes, Assessing the Representation of Vegetation Effects in X-Beach. AM Thesis, Delft Technical. 12 IW, K. JP, B. Bender S. K. W. Bogle S. 2023, National Land Cover Database Tree Canopy Cover Methods V20214. GTAC 10268 RPT1, 26. U.S. Department of Agriculture, Forest Service, Geospatial Technology and Applications Center, Salt Lake City, UT. 13. Federal Emergency Management Agency, FEMA, Geospatial Response Office, 2024, USA Structures, Geospatial Rays. Center. Disasters USA Structures 14 Van A, J. Van M, K. A. 2023, Forecasting Hurricane Impacts on Coasts Using Sea Storm Modeling System, COSMOS. In Proceedings of 10th Coastal Sediments, New Orleans, 2653-2658. Uncovering Causation of Short-Term Sandy Beach Surface Dynamics, Measured by Permanent Laser Scanning. Abstract. The causal drivers of short-term changes, days to months, in human, wind, and wave-driven sand transport on a sandy beach, are not often considered in an integral and data-driven approach. However, improving current knowledge on urban sandy beach topographical change requires the incorporation of multi-scale, cross-sectional, and human factors. In this research, we process a time series of 21,194 hourly point clouds, obtained in a permanent terrestrial laser scanning setup. From this 3D time series, we extract 5,102 short-term temporary surface dynamics through a method called 4D Objects by Change, 4D OBCs. The causal drivers of two of these 4D OBCs are investigated in detail. One is interpreted as an Aeolian depositional surface dynamic 1, and one as a bulldozer deposit that consecutively eroded under high wave energy conditions 2. The dynamics show clear correlation to a particular combination of wind direction and intensity 1, and wave height and wave period 2, indicating that point cloud time series derived 4D OBCs are useful data to study causality of short-term surface dynamics of different origins. However, to study these surface dynamics systematically and derive statistical proof of causal relations, we must consider multivariate correlations, as well as spatiotemporal dependence between sediment dynamics and larger-scale morphological changes on the beach. Keywords. 1. Introduction. Sandy coasts are dynamic environments, constantly shaped by natural processes and human activities. Rising sea level intensifies coastal squeeze, threatening the livelihoods of coastal communities. 1. Thorough knowledge of the complex interplay between natural forces, human actions, and sand redistribution is thus essential to ensure the effectiveness of management strategies under changing conditions. Traditionally, sandy beach dynamics have been studied by focusing on long-term years, decades, natural behavior of beach dune systems too, or on short-term days, months processes, but often lacking integration. 3. The relationship between human activities, beach dune sand redistribution, and broader coastal dynamics remains poorly understood. 4. Enhancing our understanding of the gaps in our knowledge requires a spatiotemporal holistic approach. We need to consider the impact and conditions of short-term surface dynamics, existing for only hours to months, over the full cross-section of the sandy beach, and place them in the perspective of longer-term change. This requires high frequency, quality, and coverage of observations over long time scales. Only recently, permanent laser scanning, PLS, acquiring hourly 3D elevation measurements at level accuracy over extended periods of time, months, years, offers the data to advance our understanding. 5. The challenge, however, is to automatically extract relevant surface dynamics from these millions of observations and link these to causal parameters. This study presents a framework through which the causal parameters of short-term sandy beach surface dynamics can be studied in large point cloud time series datasets. Our goal is to answer the questions. 1. How can short-term surface dynamics be derived automatically from extensive time series of point clouds? 2. How can causation of short-term surface dynamics be uncovered? The research questions will be answered by, first, extracting short-term surface dynamics from a point cloud time series as 4D objects by change, 4D OBCs 6, and second, assessing the environmental conditions in which two examples of these short-term surface dynamics existed. 2 datasets. 2.1 Permanent laser scanning dataset. In a PLS setup, a terrestrial laser scanner is permanently mounted in a fixed position and acquires elevation data as point clouds over regular intervals for an extended time. For this study, an open-source dataset of 21,780 hourly point clouds Fig. 1 is used, acquired with a VZ2000 at the Netherlands, 52.24 N, 4.42 E between 2019-0706 and 2022-0717. Here, elevation measurements of the dune area top, center, and part of the intertidal area bottom are obtained. The systematic errors between point clouds 8 are corrected using transformation matrices as provided with the dataset at 4TU Research Data 7. Point clouds containing strong noise were also removed. 2.2 Data of candidate causal parameters. Example of a point cloud of the beach at colored, using aerial photography of the Dutch government. The black box indicates the area of the point cloud used for the analysis. Spatial A, B, C, and temporal D, representation of a 4D object by change, 4D OBC. A. Elevation change with respect to first epoch of the dataset, at start of the 4D OBC. The black box indicates the bounding box of the 4D OBC. B. Elevation change at the last epoch of the 4D OBC. C. Spatial outline of the 4D OBC, colored area. The colors indicate the dynamic time warping distance, dTW, to the seed time series, red star. D. Time series of elevation change with respect to the start of the 4D OBC, of the seed, in black, and other points incorporated in the 4D OBC, colored by dTW distance, corresponding to C. The temporal extent of the 4D OBC lies between the two dashed lines. 3. 4D objects by change extraction. The 4D objects by change method is used to extract a dataset of temporary surface dynamics, 4D OBCs, from the 21,780-point clouds, of which the causation and conditions can be studied. A 4D OBC represents the spatial and temporal extent of a temporary deposition or erosion event within a point cloud time series, Fig. 2. They are extracted by, first, detecting in the time series of elevation change. These indicate a change in local elevation dynamics. From each, a temporal region is segmented, which extends in time until the elevation of the first is reached again, thereby representing a temporary surface change, Fig. 2D. These temporal segments are used as seeds for subsequent object segmentation and are sorted based on neighborhood similarity of the time series. Starting with the first seed, a spatial region is grown based on a similarity criterion between the time series, for which the dynamic time warping distance, dTW, is used, Fig. 2C. This is done successively for each seed candidate that is not yet incorporated in another 4D OBC. For a more detailed description, refer to 6. For this study, the workflow is executed in parallel for 9 temporal subsets to allow for faster computing and reduce memory use. After extraction, if the percentage of time series in a 4D OBC with a different sign than the seed is larger than 10%, the 4D OBC is not considered. This can occur if the seed time series shows only little elevation change. Also, 4D OBCs are filtered out with an unrealistic 1m and instant absolute change in height in the intertidal area. 4 results. Active 4D objects by change over the 3-year dataset. Each color represents one of 9 temporal subsets. 4.1 Causal conditions for 2 4D objects by change. Figure 4b and c show the temporal volumetric change and spatial outline of the 4D OBC, also presented in Fig. 2. The cross-shore location is centered around the high tide line. Figure 4a shows the evolution over time of 2 candidate causal parameters of this surface dynamic, namely the hourly mean wind speed and wind direction. The colors in A and B correspond to the slope of the volumetric change at that point in time. We can observe that during the initial phase of the 4D OBC, erosion occurs under a relatively high wind speed, 9 ms, with a slight landward direction. The direction approaches a right angle to the coast before the erosion halts under lower wind speeds, 9 ms. During this stabilization of deformation, the wind alternates intermittently between landward and more seaward directions. At the final depositional part of the surface dynamic, the wind speed increases again, but now the direction stabilizes for a short period into a longshore direction, in contrast to previous oblique directions. In Fig. 2b, at the end of the 4D OBC duration, spatially intermittent elevation increases, sand waves, occur, perpendicular to the coastline, which are signs of sand transport in longshore direction. A2 causal parameters at different points in time, 12h mean, wind speed u, and wind direction during an erosional 4D object by change, 4D OBC on the beach near the dunes. B. Temporal volumetric evolution of the 4D OBC. With the extent of the 4D OBC between the dashed lines. The color scale in A and B represents the slope of the volumetric change WRT. The start of the 4D OBC. C. Spatial outline and height change at center epoch of 4D OBC. D. Wave period and significant wave height 12H mean during a depositional 4D OBC on the in front of a beach pavilion. E and F are alike B, and C5 discussion and conclusions. The results show that 4D objects by change, 4D OBCs, extracted from large point cloud time series, contain information on causal conditions of short-term surface dynamics. These conditions are defined by combinations of multiple variables, and only under certain combination and sequencing does the deformation rate in the surface dynamics alter. For example, the depositional recovery after wind erosion occurs only when wind direction stabilizes parallel to the coast and wind speed decreases compared to prior erosion under a shoreward direction. This possibly relates to fetch length variations, a known driver of sand transport. The other 4D OBC discussed here is driven by combinations of wave period and wave height, which affect total water level and wave energy, variables often used to predict wave-driven sand transport. Both analyses thus show a clear relation to known causal conditions, which implies that dense point cloud time series, in combination with 4D OBC extraction, can be used to study causality of short-term beach dynamics. To statistically prove the causal relations, uncover unknown causal relations, and scale up the causal analysis to all the 5,102 4D OBCs. Future work will consider correlation to multivariate sequences of causal parameters. Additionally, coastal system memory will be considered, encompassing spatial and temporal dependencies. Within a 4D OBC, this memory dependency is already a conditioning factor. A local accumulation is part of a temporary disturbance or trend in an equilibrium, which is partially eroded away again as part of the adjustment. The conditional dependencies should, however, be considered in a multi-scale approach, extending further than the short term represented by the 4D OBCs. For example, the seasonal presence or location of a berm will influence the potential of hydrodynamic forcing and the fetch length on the. Thus, we will investigate the of the beach topography, as well as spatial between presence of 4D OBCs. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Mi Al. 2020, Sandy Coastlines Under Threat of Erosion. Change 10.3.262.63. 2 Jackson NL, KF 2020, Trends in Research on Beaches and Dunes on Sandy Shores, 1969-2019. Geomorphology 366, 106737. 3 Walker IJ Al. 2017, Scale-Dependent Perspectives on the Geomorphology and Evolution of Beach Dune Systems. Earth Rev 171, 2253. 4 Ma Al. 2021, Beach Nourishment Has Complex Implications for the Future of Sandy Shores. Rev Earth Environ 2, 17084. 5 Juh Al. 2016, Beyond 3D, The New Spectrum of LiDAR Applications for Earth and Ecological Sciences. Remote Sens Environ 186, 372, 392. 6K Al. 2021, Fully Automatic Spatiotemporal Segmentation of 3D LiDAR Time Series for the Extraction of Natural Surface Changes. ISBRSJ, Remote Sens, 173-297-308. 7S, a 2023 4D temporal laser scan dataset of the beach dune system in NL. 3D point clouds. 4TU. Research data. 8M Al, 2024, identifying topographic changes at the beach using multiple years of permanent laser scanning. Coast 193, 104594. Coastal dynamics in the Black Sea, observed from optical and SAR satellite images. Abstract. This paper presents an overview of the approach developed to detect coastal dynamics by combining synthetic aperture, SAR, and optical images. The method was developed with Sentinel-1 SAR and Sentinel-2 MSI images with a spatial resolution of 20 m to detect the coastline changes in the Black Sea between 2016 and 2023. When compared within measurements, the results showed that our approach provides reliable results, with the rate of coastline change having a root mean square error of 1.73 m/year. In the Black Sea, around half the coastline changes are a result of natural process, and around 35% associated with coastal engineering. Natural coastline changes were mainly observed in deltaic areas, such as the Danube Delta. 91% of the artificial changes were found in the southern Black Sea coast on the Turkish coastline, and are a result of airport and harbor construction and land reclamation activity. The results of this study can provide information on interventions that support the sustainable coastal zone management. Keywords. 1. Introduction. Coastal zones are among one of the most productive environments and provide essential ecosystem services to society. Turner, Al. 2015. Coastal zones in the Black Sea are impacted by multiple pressures including sea level rise, increasing intensity of storms, changing wind and wave conditions, and also relevant anthropogenic disturbances. And 2017. Monitoring and understanding coastal dynamics are crucial to identifying effective interventions that sustainably maintain the integrity of the coastal zone and the ecosystem services they provide. The exploitation of satellite-based Earth observation provides an efficient way to monitor coastline changes due mainly to its characteristics of large spatial coverage and short revisit period, and the ability to reconstruct past previously unmonitored events. Al. 2018. Two types of remote sensing data can be used to monitor coastline changes: optical imaging platforms and synthetic aperture radar SAR platforms, and 2021. The advantage of optical image is it can clearly distinguish land and water due to the contrast in the reflectance characteristics of bright land surfaces compared to darker water. Su, 2006. However, optical images are impacted by clouds, shadows cast by cliff lines, and very high suspended sediment concentrations in the water. Whilst not being impacted by cloud, SAR images can be used to detect small morphological changes. Al. 2022, but can suffer from noise introduced by waves and vegetation change and boat traffic. Thus, a combined approach builds on the strengths of each sensor type. This study aimed to develop a method for monitoring coastline changes using the combination of optical and SAR satellite images, and detect the coastline changes in the Black Sea between 2016 and 2023, with focusing on the region of most significant changes, i.e. the Turkish coastline. 2. Methodology. 2.1 In data collection. In coastline data were collected from the Romanian and Georgian coasts in the Black Sea between 2016 and 2023. The in-coastline data were used to validate the accuracy of the satellite-extracted coastline, along with the satellite-detected coastline change rate and areas. 2.2 Satellite data processing. Sentinel-1 VH SAR images and Sentinel-2 MSI optical images with a spatial resolution of 20 m in July and August between 2016 and 2023 were downloaded from Google Earth Engine G. For SAR images, We selected a reference image in 2016 and 2023 and subtract the reference from all images in other years to characterize the change taking place. Then the average was calculated from the first step to establish the difference intensity. Accretion and erosion were identified from pixels, where the difference intensity values were higher than 95% and smaller than 5% respectively. The detected changes from SAR images and optical images were compared, and only the locations where both SAR images and optical images showed the same change direction, i.e., erosion or accretion, were treated as real coastline changes and kept for further analysis. 3 results. We compared the extracted coastline from optical images within measured coastlines in Romanian and Georgian coasts. They showed a very good agreement, and the detected coastline change rate from optical images agreed well with the value calculated from in-data with a root mean square error, RMSE, of 1.7 m/year. The detected coastal change areas from SAR images also in line with the changes detected from in-measured coastlines. Al. 2025. Coastline changes in the Turkish coast between 2016 and 2023. Type of change. Direction of change. Area of change 2. Percentage of change in the Turkish coast %. Percentage of change in the Black Sea coast %. Natural change. Accretion. 1.5. 10. 4.3. Erosion. 1.5. 10. 4.3. Artificial change. Advance. 10.5. 69.2. 30. Retreat. 0.5. 3.3. 1.4. Other change. Old. 1.1. 7.5. 3.2. Natural changes appeared mainly where rivers, deltas, estuaries, barrier beaches, pocket beaches, and sandy coasts occur. For example, the Danube Delta in the west, the deltas in the south, the river mouths in the east of the Black Sea, Al. 2025. Artificial changes mainly occurred in the Turkish coast because of constructions of airport, harbors, ports, and so on. Natural and artificial changes in the Turkish coast detected from optical and SAR images between 2016 and 2023. Size of the circle represents the change area. Green and red represent accretion, advance, and erosion, retreat, respectively. Examples of artificial changes in the Turkish coast from 2016 to 2023. A sea port, DF coast, GI coast. Pixel scale represents the difference intensity, DI, from SAR images. Dark blue and pink lines represent the coastlines in 2016 and 2023 respectively. Background images are from Sentinel-2, MSI True Imagery. Examples of natural changes in the Turkish coast from 2016 to 2023. A sea accretion in the river mouth, DF erosions in the coast, GI accretion and erosion in the river mouth. Pixel scale represents the difference intensity, DI, from SAR images. Dark blue and pink lines represent the coastlines in 2016 and 2023 respectively. Background images are from Sentinel-2, MSI True Imagery. For discussion and conclusions. The method proposed in this study provides an efficient and accurate way for coastal dynamic monitoring, which is very useful in large area monitoring and in areas where in-data are not available. The use of optical and SAR data provides not only the rate of coastline change, but also the change in surface extent. In addition, the matching procedure of the detection results from the 2 types of images used in this method serves as a cross-validation, which demonstrates the reliability of the approach. Nevertheless, some limitations in the proposed method remain. The method is not able to detect small changes, e.g., limited only by the spatial resolution of the satellite data, in this case 20 m, The method has only been validated in the Black Sea coast, which has a negligible tidal range and has not been tested in coastlines impacted by large tidal ranges. And vegetation changes on the land adjacent to the coast can influence and lead to overestimation of the change, estimated from SAR imagery. Further studies are still required to refine the approach. Nevertheless, the results demonstrate a good agreement with previous studies of the Black Sea coast. Natural erosion and accretion in the Danube Delta were reported by Al. 2020, occurring mainly in river mouth area. Coastal erosion in the delta were reported by Al. 2011 and Kale Al. 2019, and associated with the change of sediment supply because of dam construction in the river catchment. However, we didn't observe significant coastline changes in the northern Bulgarian coast, as reported by Al. 2018. This is likely because they used very high spatial resolution data from field survey and images. Comparing our results with the shoreline types reported by Al. 2019, we found that natural changes we identified in this study are mainly located in the coast areas, by sand and pebbles. We also found that 91% artificial changes are located in the Turkish coast, indicating significant human activities in the study period. The observable activities from satellite images include the new constructions of airport, harbors, ports, and some land reclamations in the Turkish coast. Those activities may have posed impacts to the coastal habitats and aquatic ecosystem in the Black Sea. In addition, this study demonstrates the level of influence of human activities in the coastal zones. Besides reducing river sediment supply sources by damming and embankment, the direct interventions in the coastal zones and extensive constructions play a major role in some areas of the Black Sea, e.g. the Turkish coastline, on the same order of magnitude with the natural changes. Despite some limitations, the methodology developed provides a systematic synoptic approach to assessing coastal dynamics, and an approach that could help target sustainable interventions to sustain the integrity of the vulnerable coastal areas and the ecosystem services they support. This study was supported by the European Union Horizon 2020 DOORS project, developing optimal and open research support for the Black Sea, No 101,518. We thank the European Space Agency, ESA, and Google Earth Engine platform for accessing the Sentinel-1 SAR and Sentinel-2 MSI images. The collaboration for this research is part of the international scientific collaboration of the Observation Node of DANUBUSRI, the International Center for Advanced Studies on Riversea Systems, ESFRI project DANUBUSIP. Implementation phase for the Pan-European Research Infrastructure DANUBUSRI, the International Center for Advanced Studies on RSS, No 101,079,778. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: D.K. 2021, A Review and Meta-Analysis of Remote Sensing Data, GIS Methods, Materials and Indices Used for Monitoring the Coastline Evolution Over the Last 20 Years. J. Remote Sens, 54 1242 65. EA, VI, TV, YI, SV, TV, 2020. Using of Landsat space images to study the dynamic of coastline changes in the Black Sea northwestern part in 1983-2013. In Theoretical and Applied Aspects 2020. European Association of Geoscientists and Engineers, 2020, No. 115. D. Al. 2025. Combining optical and SAR satellite data to monitor coastline changes in the Black Sea. ISBRS J Photogram Remote Sends. Kale M. Is 2019. Assessment of shoreline alterations using a digital shoreline analysis system. A case study of changes in the delta in northern Turkey from 1953 to 2017. Environ Assess 191-113. TAF M 2011. Automatic detection of shoreline change on coastal wetlands of Turkey. Ocean 3810-114-11149. AGRFG S 2018 The State of the World's Beaches. Rep 81111. N 1975. A threshold selection method from gray-level histograms. 11-285-296-23-27. H. M. Young R. A 2018. Analysis of shoreline changes and cliff retreat to support marine spatial planning in municipality, northern Bulgaria. Ocean Coast, 156-127-140. F. Al. 2019. The Black Sea Coastline Erosion, Index-Based Sensitivity Assessment and Management-Related Issues. Ocean Coast, 182-104-949. A. M. PM, K. 2022, SAR Data Applications in Earth Observation, an Overview. Expert, 205-117-342. Turner R.K., M. 2015, Coastal Zones Ecosystem Services. Serve 959-75. E. M. 2017, The Black Sea, Physical, Environmental and Historical Perspectives. Springer Cam. Sue H. 2006, Modification of Normalized Difference Water Index, NDWI, to enhance open water features in remotely sensed imagery. J. Remote Sends, 27-14-302-53033. Headland Sand Bypassing in New South Wales, Australia Classification of Headland Morphology. Abstract. Australia's National Sediment Compartment Framework underpins coastal management in Australia, delineating sediment sharing systems based on geological and geomorphological transitions. Along the 2000 coastline of New South Wales, NSW, the numerous headlands often present some form of barrier to northward alongshore sediment transport driven by the modal southeast swell, with sand bypassing an important factor in sediment budget calculation. Despite its noted importance, there has been no systematic investigation of headland morphology or sand bypassing potential in NSW. In this study, we use high-resolution topographic bathymetric data and spatial analysis to classify the morphology of headlands in NSW, which will enable an investigation of bypassing sensitivity to headland morphology in the region. Individual and compound headlands are defined through automated methods, and parameters are calculated to evaluate sediment connectivity. The results reveal spatial variations in headland distribution and morphology along the coastline, highlighting the influence of both subaerial and subaqueous geomorphology on sediment transport. This analysis will enable the evaluation of sediment compartment boundaries, e.g., open, leaky, closed, providing new insights into headland morphology and sediment bypassing dynamics to inform coastal management practices in NSW and elsewhere. Keywords. 1. Introduction. Australia's National Sediment Compartment Framework was developed to support coastal management in Australia by providing a nested template for sediment-sharing coastal systems, in which compartment boundaries were defined by major changes in geology, geomorphology, orientation of the coastline, and prominent headlands. 1. Along the southeastern coast, in New South Wales, NSW, 9 primary compartments are divided into 47 secondary compartments, primarily at coastal headlands. Fig. 1. The NSW coastline includes over 2,000 of Australia's ocean-facing shorelines, with around 50% formed of potentially sandy shorelines. Sediment on Australia's southeast coast is moved northward in a major alongshore sediment transport pathway driven by the predominantly southeast swell direction too. Headlands and engineered structures, such as river and estuary entrance training walls, can act as barriers to alongshore sediment transport pathways in the Region 3. Headland bypassing is a primarily wave-driven process that connects adjacent beaches and sediment compartments by the migration of sediment around a natural headland and is an important component of sediment budget calculations. Studies of headland bypassing around the globe have increased in recent years including along the southeast Australian coastline 5/8. However, there has been no systematic investigation of coastal headland morphology along the NSW coastline, and the regional scale significance of headland bypassing remains unknown. This study presents new insights on headland bypassing potential and alongshore sediment connectivity from an analysis of subaerial and submerged headland morphology. The results will inform a deeper evaluation and classification of sediment compartment boundaries in the region. 2 methods. High-resolution topographic bathymetric morphology data, spatial analysis, and previously published, were used to classify NSW headlands and assess bypassing potential. The National Dataset 9, containing GIS mapping of shore geomorphology along Australia's coastline, was used with Surface Geology Mapping 10 to identify rocky shore geomorphology that headlands. A threshold filtering process removed very short pocket beaches that are often embedded in headlands using a cutoff percentile of beach length tailored to the geology of each sediment compartment, and ephemeral beaches with rocky and zones that were classified in as not a sandy shore. When headland polygons were delineated, if one or more of the removed beaches were part of the headland polygon, the headland was classified as a compound headland. This filtering process allows, for the first time, all headlands along with other natural and artificial obstructing features, Fig. 1, to be objectively defined and numbered. Individual headlands were also identified and numbered within compound headlands for a multi-scale classification. An analysis following methods described by George Al. 11 was then undertaken and expanded on to classify each headland. Additional exploratory parameters were developed to encapsulate the complexity of the seabed morphology observed in detailed mapping along the NSW coastline. To explore how seabed type may influence bypassing sensitivity, the seabed area around each headland was divided into 3 segments, and the proportions of sedimentary and rocky seabed in each segment was identified. The exploratory seabed parameters seek to investigate the influence of seabed type around headlands on headland bypassing potential, which is the focus of fieldwork currently in progress. The results are compared with sediment compartment boundaries along the NSW coast, providing an evaluation of existing boundaries and preliminary identification of tertiary compartments. 3 results and discussion. Results from the first pass classification revealed that the number of individual and compound headlands was highest in the 2 southernmost NSW sediment compartments, Table 1, reflecting that region's rugged and steep coastal geology and smaller embayments. Although NSW-08 and NSW-07 have relatively short coastline lengths, they were found to have the second and third highest headland counts respectively. In these regions, sediment transport is dominated by onshore-offshore exchanges during and following storm events, rather than alongshore sediment migration 1. While NSW-06 is nearly triple the coastline length of NSW-05, it has only twice as many headlands and 2 more compound headlands. NSW-06 has the shortest average beach length of the sediment compartments and includes Sydney's drowned river valley estuaries, marking the transition to a more embayed coastline to the south. Despite the short coastline of NSW-05, it has the second highest count of other obstructions, suggesting that sediment transport may be influenced by rocky outcrops in the beach and near shore rather than just headland features. Numbers of headlands, compound headlands, and obstructing features in each primary compartment. Fig. 1. Other includes tombolos, salients, and nearshore rocky outcrops. Headlands bordering compartment boundaries were counted using a majority area rule. NSW. Primary. Sediment compartment. Coastline length. Sediment obstruction category. Headland. Compound headland. Artificial. Obstruction trained river entrance. Others. NSW01. NSW02. NSW03. NSW04. NSW05. NSW06. NSW07. NSW08. NSW09. 167. 201. 192. 169. 96. 288. 158. 180. 328. 12. 28. 22. 19. 14. 28. 32. 36. 77. 5. 13. 10. 5. 7. 9. 10. 17. 35. 6. 4. 4. 1. 2. 5. 1. 4. 2. 7. 3. 2. 6. 1. 2. 5. 4. Examples of sediment obstruction categories in the first pass classification. A. Location of NSW, Australia. B. Division points of primary sediment compartments in NSW, locations of panels C, and location of Fig. 2. See example of a compound headland, Cape, with two beaches within the compound headland. D. Example of a sediment obstruction, Back Beach, Point, and E. Example of a headland. Green lines in panels C, D, and E show beach shorelines. Red lines indicate the polygon extent of the relevant sediment obstruction. To investigate the potential influence that different seabed geomorphology may have on headland bypassing, the seabed area surrounding headlands were partitioned into 3 zones: 1, 2 apex, and 3, Fig. 2. Within these zones, the high-resolution seabed mapping data was investigated. Analysis transects across each zone allows for distance depth-based calculations of seabed type between the zones, which may influence bypassing sensitivity. Depth contour-based seabed analysis was also pursued to determine the primary seabed character at different water depths around headlands, with focus on limiting depths of sand transport potential. Example of sediment transport zones around Crowdy Head, NSW, location indicated in Fig. 1. Seabed classifications data is presented to display how the seabed may transition through these zones and may act as a control on sediment transport across this headland, which is a secondary compartment boundary. For conclusion, this study makes an initial step towards understanding the morphological complexity of coastal headlands and their influence on sediment transport along Australia's New South Wales coastline. Using newly available high-resolution topographic bathymetric data and seabed classification data, this research offers the first systematic classification of headlands along this coastline, identifying individual and compound headlands and other sediment-obstructing features. Key findings reveal that headland occurrence and complexity is both regionally and locally variable, with southern sediment compartments exhibiting the highest concentration of headlands and obstructions, correlating with the rugged coastal geology and constricted embayments. Additionally, the study highlights that compound headlands are often chosen to define primary and secondary sediment compartment boundaries, suggesting a potential scale bias around perceived obstructions to a longshore sediment transport that is worthy of further investigation. The analysis presented here is part of a broader investigation of headland bypassing in settings with complex coastal and seabed geomorphology. Further spatial analysis and field experiments currently in progress will offer additional insights on bypassing sensitivity to nearshore seabed geomorphology, with the goal to inform compartment-based coastal management strategies and support coastal resilience in a changing climate. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1B IG MND short AD CD 2018 National Sediment Compartment Framework for Australian Coastal Management, Faculty of Science, Medicine and Health Papers, Part A 5215. 2 short AD CD 2009 The Coast of Australia. Cambridge University Press, Cambridge. 3 short AD 1999 Handbook of Beach and Shoreface. 4 AHF de G R APD short AD 2020 Headland Bypassing and Overpassing, Form, Processes and Applications. In Sandy Beach. Org 101016B9780008 10292 750000230. 5 ID Stables MA JM 2006 Wave Climate, Sand Budget and Shoreline Alignment Evolution of the Woody Bay Sand Barrier, Northern New South Wales, Australia, since 3000 BP. MAR 226, 12127, 144. Org 101016J200 509013. 6 ID Freeman R. K. 2013. An Insight into Headland Sand Bypassing and Wave Climate Variability from Shoreface Bathymetric Change at Bay, New South Wales, Australia. MAR 340 12945. Org 101016J20 1305005. 7 APD AL 2021 Headland Bypassing Timescales, Processes and Driving Forces. Total Environs 793 148591. Org 101016J202 11488591. 8 APD 2022 Climate Control on Natural Headland Bypassing. D. Thesis, Griffith University. 9M, 2024 Geomorphology. ECAT GA Records 2B970, 7F3B, 49C0, 830, 1FA9659 AD. Accessed 31 June 2024. 10GP, AL 2023, New South Wales Seamless Geology Dataset, version 2.2. Geological Survey of New South Wales DURN. Search Geoscience Product 9232 81216993. 11 George D.A., J.L., C.D., Barnard P.L. 2015. Classification of Rocky Headlands in California with Relevance to Littoral Cell Boundary Delineation. MAR 369, 137, 152. Org 101016J20 1508010. Nearshore circulation dynamics, revealed by combining optical observations with numerical modeling. Abstract. Wave-driven currents are a primary driver of sediment transport and morphological change along sandy coastlines. Along-shore currents can be estimated by applying optical retrieval algorithms to remotely sensed imagery. In the present study, the recently updated optical current meter algorithm, OCM V20, is applied to optical data from a sandy beach in Duck, NC during a moderate wave energy event. Optically derived current estimates are validated with field sensors throughout the surf zone. A numerical model vertically resolves the wave-driven currents to enhance our understanding of the nearshore circulation. When compared to the surface layer of the modeled alongshore current, the OCM V20 estimates yield low mean averaged errors for mean current speeds up to 1 ms, with the best results yielded in regions of moderate braking and low vertical current gradient. The algorithm is available in the updated Open Access Coastal Imaging Research Network, CIRN, Video Currents Toolbox. Keywords. 1. Introduction. When surface waves break in shallow water, they transfer momentum to the mean flow, causing morphological changes to sandy beaches. The alongshore component of this wave-driven current transports sediments, nutrients, and pollutants along the coast. Accurate and continuous current measurements are vital to build on our understanding of sediment transport and morphological change in the nearshore environment. While field sensors can monitor temporal changes in wave energy and current velocity, they are seldom deployed in sufficient numbers to capture the detailed spatial variability with which alongshore velocity can change. Stationary cameras, 1, can collect detailed observations of nearshore surface circulation over large nearshore areas. Numerical models can be used to provide larger and more complete data sets to inform image processing algorithms too. The optical current meter, OCM3, efficiently uses optical data at shore parallel pixel arrays Fig. 1 to calculate alongshore currents, enabling long-term remote monitoring of the coastal environment. In the present study, the non-hydrostatic swash numerical model 4 is run during moderately energetic wave conditions to provide continuous nearshore surface velocity estimates at the U.S. Army Corps of Engineers Field Research Facility, FRF, in Duck, North Carolina. Model results are compared with remotely sensed estimates from the updated OCM2 Algorithm 5 that is available in the new open-source Coastal Imaging Research Network, CIRN, Video Currents Toolbox 6. 2 methods. Observations from field sensors provide wave, pressure, and current data with which to initiate and validate the model. This includes an array of bottom-mounted acoustic velocimeters, ADVs, with locations indicated in Fig. 1B is used to validate the simulated near-bottom currents. An Argus camera station on a 43m high tower with the location shown in Fig. 1B collects video imagery over the nearshore domain. The surf zone edge can be easily delineating using the variance of pixel intensity following the methods described in 7. Fig. 1 as high-resolution alongshore data arrays collecting pixel intensity at 5 cross-shore locations. These V-bar pixel arrays were designed to be used as inputs to the OCM Algorithm 3, referred to here as OCM V10. The OCM algorithm is a 4-step process that uses a Fourier transform to analyze the frequency spectrum, estimate the average foam drift velocity, and fit a spectral model to determine alongshore currents with associated confidence intervals. The recently updated algorithm, OCM V20, increases estimate accuracy as far as 500 m away from the camera source. One of the key updates is the application of a radon transform to constrain the search for orthogonal wave signatures. The radon transform was successfully applied in the work of Al. 2016 to identify angles of foam drift in one-dimensional pixel array data 8. OCM estimates are calculated every 10 m using 20 m wide analysis windows, which are then smoothed using a moving mean filter with a width of 50 m, a bathymetric survey of the nearshore region, collected on 11 October 2017, Fig. 1b, defines the bottom boundary condition for the swash model. The boundary is prescribed using directional wave observations at the offshore acoustic wave and current AWAC, located at x1300 m. The model generates current speeds at 3 terrain-following vertical layers, and bottom-mounted ADVs are used to validate the results at simulated near-bottom current speeds. Fig. 2. Maps indicating a 10 min time averaged pixel intensity on 13 October 2017 at 14H00 GMT, with the solid white line delineating the surf zone edge, and B. Bathymetric survey conducted at the Field Research Facility on 11 October 2017, including the locations of field sensors and camera pixel arrays. The 5 VBAR pixel arrays at X125, 150, 175, 200, and 225 m are shown by blue dashed lines. ADV's acoustic velocimeter are shown by inverted triangles, with the magenta indicating those used to compare with optically derived alongshore current estimates. Orange circles indicate the locations of the wave and current profilers. 3 results. Comparison of numerical model results, contours and field observations, triangles and circles, for 13 October 2017 at 14H00 GMT including a locations of maximum red and minimum white vertically averaged current, B. the near bottom velocity, and C. the near surface. The simulated currents are represented by black vectors, and the observed currents by the white and vectors at each observation site. When compared with modeled currents, the optical data shows that cross-shore locations of vertically averaged local minima align with the shoreward edge of the bar break Fig. 1a, with the most energetic currents at the shoreward edge of the shore break. Optically derived currents exhibit more spatial variability along the cross-shore transects. OCM-derived near-surface currents are well aligned with modeled and measured alongshore currents, particularly at the offshore transects, where vertical current gradients are insignificant. Fig. 3. Using SWASH as a synthetic dataset that provides the complete picture of nearshore conditions, the relative mean absolute error, MAE, of optically derived estimates reaches a maximum at the shoreward, 43%, but reduced to between 12–18% in X175, 200, and 225 m alongshore current speed at the 5 alongshore VBAR transects, X125, 150, 175, 200, and 225 m. The OCM V20 weighted method, blue line, and modeled results from simulating waves till shore swash, red dotted and solid lines indicated the near surface K1 and near bottom K3 layers, respectively. Near bottom current speeds measured using acoustic ADV sensors are indicated by triangles. 4 conclusions. In this study, the updated OCM V20 algorithm is applied to estimate wave-driven alongshore currents from optical imagery at a sandy beach in Duck, NC. A numerical model, SWASH, with 3 vertical layers was applied to simulate nearshore circulation under moderate wave conditions, providing a continuous synthetic dataset against which optical and field sensor measurements are compared. From these analyses, OCM V20 current estimates align well with both the surface layer model outputs and field observations, particularly along offshore VBAR transects. In the inner surf zone, persistent wave breaking may contribute to higher discrepancies, yet the relative mean absolute errors remain below 20% for most alongshore transects. Combining OCM V20 with numerical models provides a deeper picture of nearshore dynamics and improves our understanding of wave-driven currents. We thank Meg USGS for her continued mentorship and support through this project, Steve, and a Woods Hole Oceanographic Institution for sharing field observations, U.S. Naval Research Laboratory for helpful discussions, and FRF staff for continuous efforts to provide coastal observations. Thanks to Rob for providing the Argus imagery, and USGS for assisting with software development. This research is funded by an Office of Naval Research, ONR, Global, Naval International Cooperative Opportunities in Science and Technology Program, Grant N6290917-12169, with support from the U.S. Geological Survey Coastal Marine Hazards and Resources Program. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1R. Stanley J. 2007, The History and Technical Capabilities of Argus. Coast 54-674-77-491. 2 M.E. Mulligan R.P., M.L. 2023. Evaluation of Nearshore Bathymetric Inversion Algorithm using camera observations and synthetic numerical input of surface waves during storms. Coast 184-104338. 3C. R. M. 2003. An Optical Technique for the Measurement of Longshore Currents. J. Rays Oceans C. 11108. 4M. Stelling G. Smith P. 2011 SWASH. An Operational Public Domain Code for Simulating Wave Fields and Rapidly Varied Flows in Coastal Waters. Coast 5810-992-1012. 5 E.M. Mulligan R.P. M.L. Video Currents Toolbox. Coastal Imaging Research Network Video Currents Toolbox. Access 12 2025. 6 ML, KL 2022, The Coastal Imaging Research Network CIRN. Remote Sensing 14353. 7 AS, KL, TJ, Smith JM, 2019. Applying dynamically updated nearshore bathymetry estimates to operational nearshore wave modeling. Coast 1455364. 8R, S, B, T, F 2017, on the use of the radon transform to estimate longshore currents from video imagery. Coast 114.3.01308. Observing temporal beach sediment composition using remote imagery and deep learning. Abstract. Sediment is highly mobile under the combined effects of waves, currents, tides, and winds in coastal systems. This frequent sediment movement, reconfiguration, and sorting can lead to high spatial and temporal variability in the surfacemost sediment layer. To advance the ability to better map these complex patterns in surface sediment composition over broad temporal scales, we develop a 4-year observational record of spatially extensive grain size variability at the U.S. Army Engineer Research and Development Center, ERDC, Field Research Facility, FRF, in Duck, NC, USA by leveraging Argus camera observations to train a deep learning model on visual differences between quartz sand and coarse shell gravel. Tests of model performance against both labeled imagery and 3 years of weekly grain size sampling demonstrates that machine learning approaches have skill in mapping out complex observed patterns in coastal bed sediments. Keywords. 1. Introduction. Grain size is a first-order control on sediment transport rates and thus morphological change in coastal environments. In many coastal settings, bed sediment properties, including both their size and composition, can be highly variable over space and time scales. Quantify temporal patterns in grain size properties is typically time-consuming and requires extensive sampling. This leads to the common assumptions in models and analyses of a single unimodal grain size that does not vary in space or time. In this paper, we demonstrate a technique to develop an observational record of spatial and temporal grain size variability using Argus imagery 1. In a setting where there are visual differences between quartz sand and coarser shell gravel. 2. Study site. Orange-hued shell gravel lag atop the quartz-rich sands near Duck, NC, USA. 3. Methods. To investigate changes in surficial beach sediment, we use 4418 snapshot Argus images from 2016 to 2020 from a 43m high tower at the FRF taken at 11:30 UTC. We focus here on the north-facing camera, C1. Each pixel of Argus imagery is classified into one of 4 classes: background, water, buildings, people, vehicles, beach sand, vegetation, and coarse sediment lag, shell gravel. These classes are easily discernible in imagery, notably because of the observed color difference in shell gravel lag deposits relative to the background quartz beach sand. We select 107 images to label using an active learning methodology, e.g. 5 and images were labeled by a single person using Doodler 6, a human-in-the-loop annotation tool. We use a single labeler for consistency, both between and within classes, but note that a single labeler prohibits us from understanding inter-agreement, e.g. 7. Metrics from similar tasks, e.g. 6, 8, suggest that inter-agreement would likely be high for labeling tasks of this nature. Label image pairs are used to train a deep learning-based semantic segmentation model with segmentation GIM 9. We use a Ray's UNet model, adding residual connections to the convolutional blocks of the UNet fully convolutional model architecture 10 to improve model performance, e.g. 9. We train the model with a 50-50 training validation split for 200 epochs, with early stopping, using mean dice as the loss function, Atom as a batch size of 14, a learning rate scheduler, image augmentations, and calculating the mean intersection over union, MIOU, as a performance metric. A holdout test set of 10 images from C1 north-facing camera and 10 images from C6 south-facing camera were labeled to quantitatively assess model performance. We include a camera with an entirely different vantage, south-facing C6, to test the generalizability of the segmentation model. 4 results. Example results of segmentation model for north-facing C1 camera using holdout test set. The original image is shown in the left column. The image with human-generated labels is shown in middle column, considered ground truth, and the ML model predicted results are shown in the right column. Dark blue is background, water, buildings, people, vehicles. Light blue is quartz sediment, yellow is vegetation, and red is coarse sediment lag, shell gravel. Example results of segmentation model for south-facing C6 camera using holdout test set. The original image is shown in the left column. The image with human-generated labels is shown in middle column, considered ground truth, and the ML model predicted results are shown in the right column. Dark blue is background, water, buildings, people, vehicles. Light blue is quartz sediment, yellow is vegetation, and red is coarse sediment lag, shell gravel. As a third test, we combine segmentation model results with a catalog of physical grain size samples from the FRF that were taken at known locations and times. We first find matchups between images run through our segmentation model and 720 physical sediment samples. These samples come from 69 different days and 12 different cross-shore locations. Each of the 720 physical samples is matched to a pixel classified using the segmentation model as either beach sand or coarse lag. Samples have a corresponding grain size distribution, and here we specifically look at values for D10, D25, D50, D75, and D90. The physical samples from pixels classified as coarse material are then compared to physical samples that correspond to pixels classified as quartz-rich beach sand. We find that physical samples from pixels classified as coarse lag are coarser than physical samples classified as quartz-rich beach sand. This difference in grain size is true for all 5 measured values of the grain size distribution: D10, D25, D50, D75 and D90. A two-sample test with this matchup dataset suggests coarse and fine pixels are distinct populations at all grain size values, that physical samples from pixels classified as coarse are different from physical samples matched with pixels classified as quartz-rich beach sand. This analysis using physical data gives further confidence that our segmentation model is successfully capturing existing superficial grain size variability. 5. Discussion. The segmentation model developed here was trained using images from a single north-facing camera. We test the model with a holdout test set of 10 images from the north-facing camera, as well as 10 images from a second, south-facing camera at the same site. Results indicate the model was able to segment the south-facing images, but with slightly degraded performance, MIOU of 0.75 versus 0.6, mean dice of 0.8 versus 0.69. All imagery used in this study is from the FRF, from 2016 to 2020, and all taken at 11:30 UTC. If the model developed here was given images from different locations, or even the same location but different years and/or times of day, the performance would likely degrade because of light conditions, different camera hardware, and different camera settings, e.g. color, white balance, gain, etc. Adding more labeled data to the training set would mitigate any drop in performance and would help the model generalize further under a range of different conditions. Future work to develop segmentation routines at different sites or different camera vantages could use the labeled data presented here as a foundation to develop models, potentially needing fewer newly labeled images to train a performant model. Our existing model and observational record of surface beach sediment could also be coupled with environmental time series to uncover the controls on coarse deposit presence-absence, e.g. 2.3. 6. Open research statement. All environmental and morphology data used in this work can be accessed through the FRF THREDDS server at MIL. All imagery, labeled training data, and ML models used in this study can be found in 11. Code to analyze ML model output can be found online, //.com//FRF grain size. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License, org licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S. and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Ra, Stanley J. 2007, The History and Technical Capabilities of Argus. Coast, 54.67477-491. 2. CJ, 1972, Bimodal Composition and Cyclic Characteristics of Beach Sediment in Continuously Changing Profiles. J. Sedimentary, Res 4248-25857. 3. Richmond B.M., A.H. 1985, Cross-Shore Transport of Bimodal Sands. In Coastal Engineering 1984, 1997-2-008. 4. E. H. J. A. M. 2016, A Conceptual Model for Spatial Grain Size Variability on the Surface of and Within Beaches. J. Mar 4238. 5. E.B. S.D. S.N. Valentine J. 2020, An Active Learning Pipeline to Detect Hurricane in Post-Storm Aerial Images. In AI for Earth Sciences Workshop at IPS 2020. Org 10.3.1223 X5 JW23. 6D, AL 2022, human-in-the-loop segmentation of Earth surface imagery. Earth space 93E2 021EA002085. 7EB, AL 2021, Labeling Coastal Imagery for Machine Learning, Measurement of Agreement. Earth space 89E2 021EA001896. 8D, P, S, Favela J, EB, NM 2023, a 1.2 billion pixel human-labeled dataset for data-driven classification of coastal environments. Data 10-146. 9D, EB, 2022, a reproducible and reusable pipeline for segmentation of imagery. Earth space 99E2 022EA002332. 10O, P, T, 2015, UNET, Convolutional Networks for Biomedical Image Segmentation. In Medical Image Computing and Computer-Assisted Intervention, MICCAI 2015, 18th International Conference, Munich, Germany, October 5-9, 2015, Proceedings, Part III 18. Springer, Heidelberg, 234-241. 11E 2023, Detecting Coarse Beach Sediment Using Remotely Sensed Imagery at the FRF, DUC, NC, USA. Labeled Images, Deep Learning Model, Testing Data and Predictions. 0.1. Org 1052-8170-75342. Coupling satellite-derived coastal change metrics with data-driven modeling for near-future predictions. Abstract. Modeling short-term coastal change and ongoing resilience pre- and post-storm events can help coastal managers make better-informed decisions. Hazards exacerbated by climate change often affect coasts differently, so approaches to predicting physical responses need to be broadly applicable. When compared to traditional process-based approaches, data-driven models require less information and can be simpler and more efficient in construction. However, these models rely on regular measurements of coastal metrics to form a statistical understanding of past trends and make robust predictions. Gathering observations via ground-based techniques is costly and logistically difficult, leading to spatiotemporal record gaps. Public satellites offer a solution with regular, scalable, moderate, high-resolution data, giving greater insights into coastal change. Seizing upon this opportunity for integration, we present a framework for satellite data-driven, short-term coastal change predictions in near real time. A variety of satellite-derived observations of coastal change are obtained automatically for a site in northeast Scotland, using the toolkits CoastSat and SAT. These include the waterline and vegetation edge derived from Sentinel-2 imagery and wave-related metrics from Marine Service. A deep learning model is trained with these regular observations, stored as on cross-shore transects, over the 10-year of Earth observation data. The trained model is then forced with near-future wave conditions from and predicts 10-day cross-shore waterline and vegetation edge positions. With validation, neural networks trained on satellite-derived observations could offer a revolution in automated, scalable, efficient solutions for coastal management in a changing climate. Keywords. 1. Introduction. As sea levels rise and storm events worsen and occur more frequently with climate change, soft coastal assets and communities are increasingly under threat of damage and destruction. 1. The shoreface state can change rapidly under extreme events such as storms and tropical cyclones, which shift sediment, sometimes rapidly and catastrophically. Coastal communities need to be prepared for the beach response to these events in the short term, but also understand their ongoing levels of coastal resilience over longer timescales too. One approach to aiding coastal adaptation and resilience efforts is to model future coastal morphology and the hazards that influence it. There now exists a significant collection of model approaches and applications to abstract coastal processes and predict future geomorphic responses to hydrodynamic forcings. 3. The right model for effectively predicting coastal response to short-term hazards should account for short-term cross-shore processes, but also include longer-term influences in the alongshore direction 4. Data-driven models can offer this flexibility in terms of spatial and temporal constraints, as they rely entirely on statistical patterns in whatever past data is provided to make future predictions. Simple forms of data-driven modeling, such as multivariate regression, fit a single relationship to a of coastal observations and use that relationship for future projections 5. More sophisticated approaches are now being applied to coastal change and risk modeling, with deep learning (DL) techniques being used to reasonably predict coastal evolution in the short and long-term 6-8. Recent studies have generally agreed that while DL models are more computationally efficient and able to handle nonlinearity well, leading to robust predictions, the amount of training data required is the main restriction on this robustness. 9. Coastal DL studies have therefore validation on data-rich locations, where long-term in monitoring exist. 10. As a solution, large training datasets of coastal change indicators have recently been sourced instead from publicly available satellite data, which offer near-global spatial coverage at a moderate resolution and daily, weekly rate 11, 12. These studies focus on using the instantaneous waterline WL as a proxy for topographic change across the shoreface. While this indicator is relatively simplistic and easily interpretable by stakeholders, its accuracy relies on correction to remove the effects of hydrodynamics. The tidal range and dynamism of the studied system can also introduce errors into the WL positions. 13. Furthermore, using a model driven only on past WL change can ignore other complex forcings present across the upper and lower shoreface, which haven't been captured in that proxy. There now exists a variety of techniques to obtain a broader variety of coastal change indicators from satellite data. 14, 15. We seize on the opportunity to couple techniques for obtaining repeatable, varied, dense, and analysis-ready coastal information from freely available satellite data with an efficient and scalable DL framework. Our goal is to generate short and medium-term coastal risk predictions that can be repeatedly updated with new satellite-derived observations. 2 methods. 2.1 Satellite-derived observations for training. Variables used to train the data-driven coastal change model. Variable name. Symbol. Unit. Use in model. Mean wave direction from. Training. Wave. R2. M training. Number wave breaking index for sloped beach. 0. 1. Training. Instantaneous waterline cross-shore position along. WL. M target. Coastal vegetation edge cross-shore position along. VA. M target. Data from the entire Sentinel-2 was used to define the period of investigation, with 2015-2023 equating to 291 test site images. That was split into a 75-15-10 split of training, validation, and test data. The training and validation data was then sequenced into 10-day portions to help the model learn temporal patterns and to match the 10-day forecast of wave conditions used in forcing. 2.2 Model infrastructure. The model is constructed and trained using the DL library TensorFlow. We decided to use a long short-term memory LSTM network as it is well suited to sequential data with complex patterns such as environmental, because of its capability to pass on information through and evolve iteratively. 20. The LSTM was constructed with 144 hidden layers, a dense layer with 64 units, 150 epochs, a batch size of 32, and a dropout layer with a rate of 0.2, as well as an atom with a learning rate of 0.001. The model type and were chosen based on an analysis of the highest accuracy and lowest loss using the test portion of data. 3 results. Example result from the Scottish test site. A shows the satellite-derived vegetation edges, VEs, and waterlines, WLs, extracted automatically, the of interest that coastal are stored on, and the derived offshore wave conditions at the of interest. B shows of the past target features, with the last portion separated for testing the model. As suspected, the noisier and less rhythmic WL results in a less accurate prediction than the VE under the current model construction. It was found during testing that reduced dimensionality in the number of training features, i.e., using training features, which are a combination of wave or coastal conditions, improved the accuracy of the model, as the model can better generalize over the data with less. For discussion and conclusion. The coastal change indicators used to train the model have been gathered from satellite observations with much higher frequency than ground surveys. Unfortunately, the observation on each cross-shore are still only semi-regular, resulting in noisy due to cloud cover, poor image quality, and particularly for the WLs, hydrodynamic effects not captured by the tidal correction process. To smooth these gaps, linear interpolation of the was performed to obtain daily observations for model training. Therefore, the gaps themselves, as well as the interpolation method, are likely to have introduced uncertainty into the model. One solution to this may be to include coastal observations from higher resolution satellite products, such as PlanetScope, which have a much higher revisit time than Landsat or Sentinel-2, and only train the model over the period that platform has been active for. While the primary goal of this framework is to produce future coastal predictions upon which to inform risk responses, it may also be helpful to present these predictions in a more intuitive format. Presenting the one-line coastal change predictions made on a spectrum of seriousness or impact